Right now, every atom in your body was forged in cosmic violence that began 13.8 billion years ago. Scientists confirmed this timeline through decades of observation, and the implications reshape everything we understand about existence. Before Earth formed, before the sun ignited, before any planet or star existed anywhere, the entire universe erupted from a point smaller than an atom. This moment was not an explosion into space. It was the explosion of space itself, carrying with it the seeds of everything that would ever exist. The Big Bang gave birth to time, matter, energy, and the physical laws governing reality. Understanding this cosmic beginning reveals why Earth would eventually form exactly as it did, in exactly the location it occupies, with exactly the conditions necessary for life. The first fraction of a second. The universe began in a state beyond human comprehension. At approximately 10 to the power of negative 37 seconds into existence, something extraordinary happened. A phase transition triggered cosmic inflation, a period when the universe expanded faster than the speed of light. This statement defies the popular understanding that nothing can exceed light speed, yet inflation bypassed this limitation because space itself was expanding, not matter moving through space. During this inflationary epoch, the universe grew exponentially, doubling in size repeatedly within fractions of a second. The expansion was unconstrained by light speed invariance, and temperatures dropped by a factor of 100,000. Scientists remain uncertain what powered this inflation. The energy driving this expansion may have been inherent to the fabric of space-time itself. This mysterious force resolved several fundamental problems in cosmology. Before inflation was proposed, physicists struggled to explain why the universe appears so uniform in all directions. Regions of space, currently separated by billions of light years, should never have been in contact with each other, yet they display nearly identical properties. Inflation solved this horizon problem by revealing that these distant regions were once close together before inflation stretched them apart. The universe underwent exponential expansion, and the particle horizon expanded far more rapidly than previously calculated. Regions presently on opposite sides of the observable universe were well inside each other's particle horizon before inflation began. The flatness problem also found resolution through inflation. The density of matter and energy in our universe sits remarkably close to the critical density needed to produce a flat universe rather than a curved one. Without inflation, this balance would require fine-tuning to an absurd degree. Inflation naturally drove the universe toward flatness regardless of initial conditions. The uniformity we observe in cosmic microwave background radiation follows directly from this larger region being in causal contact before inflation commenced. The particle soup emerges. As inflation ended and the universe continued expanding at more conventional rates, temperatures remained extraordinarily high. The cosmos existed as a seething plasma too hot for atoms to form. Fundamental particles emerged from the energy density, including quarks, electrons, and photons. These particles collided constantly in the extreme heat, unable to bind together into stable structures. The universe was opaque during this period because photons could not travel freely. They scattered off charged particles continuously, creating a luminous fog that filled all of space. Within the first few minutes after the Big Bang, the universe cooled enough for protons and neutrons to form from quarks. These nuclear particles represented the first composite structures in existence. Shortly afterward, primordial nucleosynthesis began. Protons and neutrons combined to create the nuclei of the lightest elements. Hydrogen nuclei, consisting of single protons, formed most abundantly. Helium nuclei, containing 2 protons and 2 neutrons, emerged as the second most common product. Trace amounts of lithium and beryllium also appeared during this brief window of conditions suitable for nuclear fusion. The proportions created during primordial nucleosynthesis would determine the chemical composition of the universe for hundreds of millions of years. Roughly 75% of normal matter became hydrogen, while approximately 25% became helium. These ratios persist to the present day, observable in the oldest stars and in the overall composition of galaxies. No heavier elements formed during this early period because the universe expanded and cooled too rapidly for fusion reactions to proceed beyond lithium. Creating elements like carbon, oxygen, and iron would require the intense conditions inside stars that would not exist for tens of millions of years. The cosmic dark age begins. For 380,000 years after the Big Bang, the universe remained opaque. Photons could not travel far before interacting with free electrons. Then, as expansion continued and temperatures dropped below approximately 3000 Kelvin, a critical transition occurred. Electrons became trapped in orbits around atomic nuclei for the first time, forming the first complete atoms. This process, called recombination, transformed the universe fundamentally. With electrons bound to nuclei rather than floating freely, photons could suddenly travel unimpeded through space. The universe became transparent. The light released during recombination still fills the cosmos. We detect it today as the cosmic microwave background radiation, stretched to longer wavelengths by the expansion of space. This radiation provides a snapshot of the universe at age 380,000 years, revealing its structure and composition at that early epoch. The cosmic microwave background is remarkably uniform, showing temperature variations of only a few millionths of a degree across the entire sky. This uniformity confirms the smoothness of the early universe, while also revealing tiny density fluctuations that would eventually grow into galaxies and galaxy clusters. After recombination, the universe entered what cosmologists call the Dark Ages. No stars yet existed to emit light. The hydrogen and helium gas filling space was transparent but dark. Gravity began pulling matter together, working slowly against the expansion of space. Dense regions became slightly denser as their gravity attracted more material. Underdense regions became emptier as matter flowed away toward denser areas. These density fluctuations, originally created by quantum processes during inflation, were amplified by gravitational attraction over millions of years. Dark matter scaffolding. Most of the gravitational attraction driving structure formation came not from normal matter, but from dark matter. This mysterious substance comprises approximately 85% of all matter in the universe, yet it interacts only through gravity. Dark matter does not emit, absorb, or reflect light, making it invisible to telescopes. Its existence was inferred from gravitational effects on visible matter and from the patterns observed in cosmic microwave background radiation. After the Big Bang, dark matter clumped into blobs along narrow filaments, forming a cosmic web across space. This invisible scaffolding determined where galaxies would eventually form. Normal matter fell into the gravitational wells created by dark matter concentrations, collecting in the densest regions. While radiation pressure kept normal matter dispersed during the early universe, dark matter was immune to such pressure and began clustering immediately after the Big Bang. By the time recombination occurred, dark matter had already established the framework upon which visible structures would build. Dark energy represents an even deeper mystery. This unknown form of energy appears to drive the accelerating expansion of the universe, though its nature remains unexplained. Unlike dark matter, which clumps together gravitationally, dark energy seems spread uniformly throughout space. In the early universe, dark energy had less influence because matter and radiation were denser. As expansion continued and the universe became less dense, dark energy's repulsive effect grew more significant. This shift would eventually cause the expansion rate to accelerate rather than decelerate. The first stars ignite. Between 100 and 200 million years after the Big Bang, the first stars ignited. These population 3 stars formed from pristine hydrogen and helium gas, untainted by heavier elements. Theoretical models suggest they were enormous, perhaps 100 to 300 solar masses, far larger than typical stars today. Their immense size resulted from the chemistry of primordial gas. Without heavier elements to facilitate cooling, gas clouds had to accumulate much more mass before gravitational collapse could overcome thermal pressure. Population 3 stars burned intensely hot and bright, with surface temperatures exceeding 100,000 Kelvin. They consumed their hydrogen fuel at prodigious rates, living only a few million years before exhausting their cores. Despite their brief lives, these first stars transformed the universe. Nuclear fusion in their cores created the first heavy elements. Helium fused into carbon and oxygen. Further reactions built neon, magnesium, silicon, and eventually iron. This process, called stellar nucleosynthesis, manufactured elements that had not existed since the Big Bang. When these massive stars exhausted their nuclear fuel, they died catastrophically. Their cores collapsed, triggering supernova explosions that outshone entire galaxies. The shock waves from these explosions heated the outer layers of the stars to billions of degrees, creating conditions where elements heavier than iron could form. Neutron capture processes during the explosion built elements like gold, platinum, and uranium. These heavy elements were blasted into the surrounding space at speeds reaching 10% of light speed. The supernova ejector enriched the interstellar medium with metals, the astronomical term for all elements heavier than helium. Subsequent generations of stars formed from gas clouds containing these metals, incorporating them from birth. Population 2 stars contained small amounts of heavy elements, typically less than 5% of the metal content seen in the Sun. Population 1 stars, including our Sun, contain even higher metallicity, having formed from gas enriched by multiple generations of stellar death. Cosmic structure emerges. As more stars formed and died, the universe brightened. Star clusters coalesced into the first small galaxies. These early galaxies were much smaller than modern galaxies, containing only millions of stars rather than hundreds of billions. They merged frequently, gradually building larger structures. Dark matter halos surrounding these galaxies determined their gravitational potential, influencing how fast they rotated and how easily they could capture additional gas. Observations from the James Webb Space Telescope revealed surprising numbers of bright galaxies in the first 500 million years after the Big Bang. These galaxies appear as large and luminous as the Milky Way despite forming when the universe was only 3% of its current age. Standard models predicted galaxy formation would proceed more slowly, taking about 1 billion years to produce such massive structures. The unexpected abundance of early bright galaxies suggests that structure formation was more efficient than previously thought, possibly due to early dark energy or enhanced dark matter clustering. The first billion years established patterns that persist today. Gravity pulled matter into a cosmic web of filaments and walls surrounding vast voids. Galaxies formed preferentially along these dense filaments. The largest galaxies grew at the intersections where multiple filaments met. This hierarchical structure building, where small structures merge to form larger ones, continues throughout cosmic history. By 1 billion years after the Big Bang, the universe had transformed from a nearly uniform fog of hydrogen and helium into a complex tapestry of galaxies, stars, and enriched gas. Supernovae had seeded space with heavy elements. Black holes had formed from the most massive stars. The stage was set for the formation of solar systems containing rocky planets. Among the countless star-forming regions scattered across the universe, one particular molecular cloud would eventually collapse to form our Sun and Earth. But that transformation required the death of multiple stellar generations to provide the necessary ingredients. The atoms making up Earth originated in stellar furnaces and supernova explosions that occurred billions of years before our solar system existed. Understanding this cosmic ancestry reveals that Earth represents not an isolated world, but a product of universal processes connecting us to the deepest reaches of space and time. Chapter 2: Stellar Nurseries and the Death of Ancient Stars. The first generation of stars burned with fury the universe would never see again. These population 3 giants, forged from pristine primordial gas, lived fast and died explosively, fundamentally altering the chemistry of the cosmos. Their death seeded the space between galaxies with elements that would become mountains, oceans, and eventually living organisms. Every atom heavier than helium in your body passed through at least one stellar furnace before Earth existed. The iron in your blood, the calcium in your bones, the oxygen you breathe all originated in nuclear reactions deep inside ancient stars or in the violent seconds of supernova explosions. Understanding stellar nucleosynthesis and the multi-generational enrichment of the universe explains not just where Earth's elements came from, but why certain elements are abundant while others are rare, and how the raw materials for planets and life gradually accumulated across cosmic history. Population: 3 giants. The first stars faced unique challenges. They formed in an environment containing only hydrogen, helium, and trace amounts of lithium. This simple chemistry profoundly affected how stars could form. In modern star-forming regions, heavier elements act as crucial coolants. Carbon and oxygen atoms radiate energy efficiently, allowing gas clouds to cool and collapse under gravity. Without these cooling agents, primordial gas clouds had to accumulate far more mass before they could overcome thermal pressure and collapse. Theoretical models indicate population 3 stars typically ranged from 100 to 300 solar masses, though some may have been even larger. These behemoths dwarfed typical modern stars. Our Sun, by comparison, contains only 1 solar mass. The largest stars forming today rarely exceed 100 solar masses. The immense size of population 3 stars had dramatic consequences. Larger stars burn hotter and brighter, consuming their nuclear fuel at vastly accelerated rates. While the Sun will shine for approximately 10 billion years, a 200 solar mass star exhausts its core hydrogen in only 2 to 3 million years. The life cycle of these giants proceeded through distinct phases. Hydrogen fusion dominated initially, converting hydrogen into helium through the proton-proton chain and CNO cycle. Without carbon, nitrogen, and oxygen already present, the CNO cycle could not function initially. Instead, hydrogen fused directly through proton-proton reactions. As helium accumulated in the core, the star's structure adjusted. The core contracted and heated up while the outer layers expanded. When core temperatures exceeded 100 million Kelvin, helium fusion began through the triple alpha process. 3 helium nuclei combined to form carbon, releasing energy and temporarily stabilizing the star. This carbon represented the first heavy element created in the universe. Its formation opened pathways to building even heavier elements. Carbon nuclei could capture additional helium to form oxygen. At higher temperatures, carbon and oxygen could fuse together, creating neon, magnesium, and sodium. As the star aged, it developed an onion-like structure with different elements burning in concentric shells. Hydrogen fusion occurred in the outermost shell. Beneath that, helium fused into carbon. Deeper still, carbon burned to form neon and magnesium. The pattern continued with oxygen burning to produce silicon and sulfur, and finally silicon burning to create iron peak elements. The silicon catastrophe. Iron represents the end of the line for fusion energy production. All fusion reactions up to iron release energy because the resulting nucleus is more tightly bound than its components. Fusing elements lighter than iron liberates energy that supports the star against gravitational collapse. Iron occupies a special position as the most stable nucleus. Fusing iron into heavier elements requires energy input rather than releasing energy. Once a massive star builds an iron core, no further fusion can generate outward pressure to counteract gravity. The iron core grows as silicon burning continues in the shell above it. When the core mass exceeds approximately 1.4 solar masses, electron degeneracy pressure can no longer support it against gravity. The core collapses catastrophically in less than 1 second. Electrons are forced into protons, creating neutrons and neutrinos in a process called neutronization. The core density skyrockets to nuclear densities comparable to the density of atomic nuclei themselves. At these extreme densities, the nuclear force becomes repulsive, halting the collapse. The infalling material rebounds off the incompressible neutron core, generating an outward-moving shock wave. This shock wave transforms the star. As it propagates outward through the stellar layers, it heats material to billions of degrees. Explosive nucleosynthesis occurs in the intense conditions behind the shock front. Elements that require energy input to form, such as iron, nickel, cobalt, and heavier elements, are synthesized in these seconds. The shock wave reaches the star's surface hours to days after core collapse, depending on the star's radius. When the shock breaks through the surface, the star explodes as a supernova, briefly outshining all other stars in its galaxy combined. Forging heavy elements. Supernova explosions create elements through multiple processes. Explosive burning in the oxygen and silicon shells produces substantial amounts of silicon, sulfur, argon, calcium, titanium, chromium, manganese, iron, cobalt, and nickel. The exact mix depends on the temperature and density of each layer as the shock passes through. The innermost regions experience the most extreme conditions, producing primarily iron peak elements. Outer regions undergo explosive oxygen and neon burning, generating intermediate mass elements. Elements heavier than iron form primarily through neutron capture. When neutrons encounter atomic nuclei, they can be absorbed, increasing the nucleus's mass. If the resulting nucleus is unstable, it undergoes beta decay, converting a neutron into a proton and increasing the atomic number by 1. This process builds progressively heavier elements. Two distinct neutron capture processes occur in stellar environments, each producing different elements. The slow neutron capture process, called the S process, operates in stars that have not yet exploded. During late-stage stellar evolution, neutrons are produced by reactions involving carbon-13 and helium. These neutrons are captured by iron peak nuclei over thousands of years. After each capture, there is time for beta decay to occur before another neutron is captured. The S process follows a specific pathway through the chart of nuclides, creating elements like strontium, yttrium, barium, and lead. Roughly half of elements heavier than iron are produced by the S process. The rapid neutron capture process, called the R process, occurs in environments with extremely high neutron densities. Supernova explosions create such conditions, as does the merger of neutron stars. In the R process, nuclei capture neutrons so rapidly that many neutrons are absorbed before beta decay occurs. This produces extremely neutron-rich isotopes that subsequently undergo multiple beta decays, walking up the chart of nuclides to create heavy elements. The R process is responsible for roughly half of elements heavier than iron, including gold, platinum, thorium, and uranium. Recent research suggests the earliest stars may have produced elements heavier than any found naturally on Earth. Analysis of 42 ancient stars in the Milky Way revealed chemical abundances requiring the prior production of elements with atomic masses greater than 260. These superheavy elements would have been unstable, undergoing fission to produce lighter, more stable elements like ruthenium, rhodium, palladium, and silver. The abundance ratios observed in these old stars do not match predictions from the R process alone, suggesting fission products from even heavier elements contributed significantly. Population 2 stars emerged. As the first supernovae enriched their surroundings, the next generation of stars formed from chemically altered gas. These population 2 stars contained small amounts of heavy elements, typically 0.1% to 3% of the metal content in the Sun. This seemingly tiny amount made an enormous difference. Metals provided cooling mechanisms that allowed gas clouds to fragment more easily and form smaller stars. Population 2 stars ranged from less than 1 solar mass to perhaps 100 solar masses, rather than the 100 to 300 solar mass range typical of population 3. The presence of metals also affected stellar evolution. Carbon, nitrogen, and oxygen enabled the CNO cycle, an alternative hydrogen fusion pathway that dominates in stars more massive than about 1.2 solar masses. The CNO cycle produces energy more rapidly than the proton-proton chain, causing higher mass stars to burn brighter and hotter. Metal-containing stars develop different internal structures compared to metal-free stars of the same mass. They have larger convective cores and different opacity profiles, affecting how energy is transporting from core to surface. Population 2 stars formed in the first billion years after the Big Bang. Many still exist today in the Milky Way's halo and in globular clusters. These ancient stars provide windows into early cosmic chemistry. By analyzing their spectra, Astronomers determine which elements were present when they formed and in what proportions. This forensic astronomy reveals the nucleosynthesis yields of population 3 supernovae. Different elements appear in characteristic ratios, depending on whether they originated in core-collapse supernovae, pair instability supernovae, or other exotic events. Some population 2 stars exhibit unusual abundance patterns that challenge standard models. Ultra-metal-poor stars with iron content less than 0.001% of solar contain odd proportions of heavy elements. Some are enriched in carbon but deficient in iron. Others show enormous overabundances of neutron capture elements like europium. These peculiar compositions suggest they formed from gas enriched by single supernova explosions rather than well-mixed material from many supernovae. Each population 3 star that exploded had a unique mass and explosion energy, producing a distinct elemental fingerprint. The first population 2 stars inherited these individual signatures. Pair instability supernovae. The most massive population 3 stars, those with helium core masses between 64 and 133 solar masses, died in a particularly spectacular way. In these behemoths, core temperatures exceeded 100 billion Kelvin. At such temperatures, photons carry enough energy to spontaneously convert into electron-positron pairs. This pair production removes energy from the photon field, reducing radiation pressure that helped support the star against gravity. The core contracts in response, heating up and accelerating fusion reactions. The increased fusion releases enormous energy, driving an expansion that cools the core. Pair production then decreases, radiation pressure recovers, and the core contracts again. This instability causes violent pulsations. In some mass ranges, the pulsations grow strong enough to eject the star's outer layers in supernova-like explosions without collapsing the core. The star survives but loses significant mass with each pulse. Eventually, it either stabilizes as a smaller star or accumulates a large iron core that collapses to a black hole. In a narrow mass range, however, the pair instability completely disrupts the star. The entire star explodes, leaving no remnant neutron star or black hole behind. These pair instability supernovae release even more energy than typical core-collapse supernovae and produce distinct abundance patterns with unusual amounts of odd-numbered elements. For population 3 stars with helium cores more massive than 133 solar masses, corresponding to main sequence masses above 260 solar masses, the outcome was different. These ultramassive stars collapsed directly to black holes without producing supernovae. The entire star fell into the forming black hole, ejecting no material and contributing no metals to the interstellar medium. If such stars were common, they represented a sink for baryonic matter, removing it from the chemical enrichment cycle. Current evidence suggests most population 3 stars fell in the mass range that did produce supernovae, but the possibility of frequent direct black hole formation remains debated. Chemical evolution of the universe. With each stellar generation, the metal content of the universe increased. Population 3 stars converted primordial hydrogen and helium into heavy elements. Their supernovae dispersed these elements across thousands of light years. The enriched gas mixed with pristine gas, diluting the metal concentration but spreading elements across vast volumes. New stars formed from this mixture, synthesizing additional metals during their lifetimes and releasing them in their own death throes. This chemical evolution proceeded at different rates in different locations. Regions of intense star formation, where massive stars formed and exploded frequently, became enriched faster. Quiet regions with little star formation remained metal-poor longer. Gas flowing between regions through galactic winds and intergalactic streams transporting metals across space, gradually homogenizing composition but never achieving perfect uniformity. The metallicity of star-forming gas increased logarithmically over cosmic time. After the first generation of population 3 stars exploded, the gas metallicity jumped from essentially zero to perhaps 0.001% solar. Subsequent generations doubled this metallicity every few hundred million years. By 1 billion years after the Big Bang, typical star-forming gas contained approximately 1% solar metallicity. By 4 billion years, it reached 10% solar. When our solar system formed 4.6 billion years ago, the gas from which it condensed had nearly solar metallicity, enriched by billions of years of stellar processing. Different elements increased at different rates depending on their sources. Oxygen, produced copiously by massive stars with short lifetimes, increased rapidly in the early universe. Iron, produced by both massive stars and type Ia supernovae from white dwarfs with longer delay times, increased more gradually. The oxygen-to-iron ratio in ancient stars is higher than in young stars, reflecting the different timescales of enrichment. Elements produced by the S process in low-mass stars became abundant only after the first low-mass stars evolved to their asymptotic giant branch phase and released these elements, typically 1 to 10 billion years after formation. Setting the stage for planets. The accumulation of heavy elements made planet formation possible. Rocky planets require silicon, magnesium, iron, aluminum, calcium, and other metals to form their solid structures. Water requires oxygen, a product of stellar nucleosynthesis. Organic molecules require carbon and nitrogen, also stellar products. Without multiple generations of stars living and dying, Earth could never have formed. The primordial universe lacked the chemical diversity necessary for terrestrial planets. By the time the molecular cloud that would become our solar system collapsed, it contained all the elements needed for Earth. Oxygen represented about 1% of atoms, carbon about 0.3%, neon 0.1%, iron 0.03%, and other heavy elements smaller fractions. These percentages sound tiny, but they translated into enormous absolute amounts in a cloud containing thousands of solar masses. The heavy elements would condense into dust grains, planetesimals, and eventually planets. Recent discoveries of planets around metal-poor stars demonstrate that some planet formation occurs even at low metallicity. However, these planets tend to be gas giants rather than rocky terrestrial planets. The correlation between stellar metallicity and planet occurrence is strong. Stars with higher metal content are far more likely to host planets, especially massive planets. This metallicity requirement explains why planet formation accelerated over cosmic time as the universe became more metal-rich. Isolated galaxies in underdense regions of the universe may have formed stars from relatively pristine gas billions of years after the Big Bang. One such galaxy, called CR7, appears to contain population 3-like stars forming only 2 billion years after the Big Bang. By this time, most of the universe had been enriched with metals. CR7 existed in such an empty region that no metals from surrounding areas had reached it. This isolation allowed it to form its own first generation of stars separately from the rest of the universe. Such examples are rare, highlighting how the normal course of cosmic evolution involved continuous mixing and enrichment. The deaths of ancient stars across billions of years gradually transformed the universe from a simple, metal-free hydrogen and helium cosmos into a chemically rich environment capable of producing planets, moons, asteroids, and comets. The supernova explosions that seemed destructive were actually creative acts, forging the periodic table and distributing its elements. These processes established the necessary conditions for Earth to form with the composition it has. The next phase of our story examines how one particular region of enriched gas, floating in the disk of the Milky Way galaxy, began to collapse under its own gravity, setting in motion the events that would create the Sun, Earth, and the entire solar system. The atoms were ready. The stage was set. The birth of our world could begin. Chapter 3: Birth of the Solar Nebula. In a spiral arm of the Milky Way galaxy, 26,000 light-years from the galactic center, a cloud of gas and dust floated through space. This giant molecular cloud stretched across hundreds of light-years, containing enough material to form thousands of stars. The cloud drifted for millions of years in relative stability, held together by its own gravity, yet prevented from collapsing by internal pressure and magnetic fields. Most molecular clouds persist in this balance indefinitely, slowly evaporating under ultraviolet radiation from nearby stars. this particular cloud faced a different fate. Something disturbed it, triggering a cascade of events that would ultimately produce Earth and every world in our solar system. The trigger came from violence. A massive star in the cloud's vicinity exhausted its nuclear fuel and exploded as a supernova approximately 4.6 billion years ago. The shock wave from this explosion raced through space at thousands of kilometers per second, slamming into the molecular cloud with tremendous force. The collapse begins. The supernova shock wave compressed portions of the molecular cloud, pushing gas and dust together. This compression increased density in certain regions beyond the critical threshold where gravity could overcome internal pressure. Parts of the cloud began to collapse under their own weight. The collapse was not uniform. Dense regions within the cloud, called cores, contracted independently. Our solar system formed from one such core, perhaps 1 light-year across, initially, and containing slightly more than 1 solar mass of material. Evidence for this supernova trigger exists in meteorites. Prosolar grains, microscopic silicon carbide crystals smaller than 1 micrometer, are found in primitive meteorites. These grains formed in the outflows of dying stars and were incorporated into our solar nebula. Their isotopic compositions do not match any processes occurring within our solar system, but reveal they originated elsewhere. Specific isotopes like aluminum-26 and iron-60 appear in these grains in abundances that can only be explained by recent supernova nucleosynthesis. The radioactive decay timescales of these isotopes indicate the supernova occurred within a few million years before our solar system formed, close enough in time and space to deliver freshly synthesized material into the collapsing cloud. As the core contracted, gravitational potential energy converted to kinetic energy and heat. Particles falling inward accelerated, colliding with other particles and generating friction. The center of the collapsing core heated up rapidly. The outer regions remained cold, shielded from the growing warmth at the center by the sheer volume of intervening material. This temperature gradient would prove crucial for determining what types of worlds could form at different distances from the eventual star. The initial collapse proceeded quickly. Basic physics determines the timescale. For a cloud with initial density around 10 to the power of -18 grams per cubic centimeter, gravitational collapse occurs in approximately 50,000 to 100,000 years. The densest central regions collapsed first, while the lower density outer envelope took millions of years to accrete onto the growing protostar. This difference in timescales created the layered structure typical of forming stellar systems. The disk takes shape. The molecular cloud from which our solar system formed was rotating slowly. All clouds possess some angular momentum acquired from galactic rotation and turbulent motions within the interstellar medium. As the cloud collapsed, conservation of angular momentum became critically important. When material moves closer to the rotation axis, it must spin faster to conserve angular momentum, just as an ice skater spins faster when pulling their arms inward. Material falling directly along the rotation axis could accrete onto the central protostar relatively easily. Material with significant angular momentum perpendicular to the rotation axis could not fall straight down. Instead, it spiraled inward, forming a rotating disk around the growing protostar. This protoplanetary disk represented the birthplace of planets. Everything orbiting the Sun today, including Earth, condensed from material in this disk. The disk geometry emerged naturally from physics. Material with high angular momentum settled into the disk's plane, where centrifugal force balanced the inward pull of gravity. Material with insufficient angular momentum to remain in stable orbit accreted onto the protostar. The disk acted as a temporary storage reservoir, holding material until mechanisms could transport angular momentum outward, allowing mass to spiral inward to the star. Several processes transporting angular momentum within the disk. Gravitational instabilities created spiral density waves that transferred angular momentum outward through gravitational torques. These spiral arms transporting mass inward while carrying angular momentum outward. Turbulence generated by magnetorotational instability also contributed to angular momentum transport. Magnetic fields threading the disk coupled to charged particles, creating turbulent eddies that mixed material radially. This turbulence allowed mass to accrete onto the star while expanding the disk's outer regions. The disk was massive initially. Observations of young stellar objects suggest protoplanetary disks typically contain between 1% and 10% of the central star's mass. For the forming Sun, this translates to 10 to 100 Jupiter masses of material in the disk. This abundance of material provided ample raw ingredients for building planets. The disk extended from very close to the protostar, perhaps 0.1 astronomical units, to potentially 100 astronomical units or more in its early stages. Material was not distributed evenly throughout this expanse. The disk was denser near the star and more tenuous at greater distances. Temperature zones emerged. Temperature varied dramatically with distance from the forming Sun. Near the protostar, where gravitational potential energy converted to heat most intensely, temperatures exceeded 1,500 Kelvin. At these extreme temperatures, even refractory materials like metals and silicates existed as vapor. Moving outward, temperatures declined steadily. By 0.5 astronomical units, approximately where Mercury would eventually orbit, temperatures had dropped to perhaps 1,000 Kelvin, cool enough for iron and nickel to condense into solid particles. The composition of condensed material changed with temperature. In the hottest regions, only the most refractory substances could solidify. Calcium-aluminum-rich inclusions, the oldest known solids in the solar system with ages of 4.567 billion years, formed in these inner zones. These millimeter-sized objects crystallized from vapor at temperatures above 1,300 Kelvin. Slightly cooler regions allowed iron-nickel alloys to condense, followed by magnesium-silicate minerals like forsterite and enstatite at temperatures around 1,000 Kelvin. At approximately 2.7 to 3.2 astronomical units from the forming Sun, a critical boundary emerged. Here, temperatures dropped below approximately 150 to 170 Kelvin, cold enough for water ice to condense. This boundary, called the frost line or snow line, separated the inner solar system where only rock and metal could solidify from the outer regions where volatile ices could accumulate. The frost line's location was not fixed. As the protostar's luminosity evolved and the disk's properties changed, the frost line migrated inward and outward, potentially reaching as far as 17.4 astronomical units during certain phases. Beyond the water frost line, the amount of solid material available for planet building increased dramatically. Water ice was far more abundant than rock and metal in the solar nebula, reflecting the overall cosmic abundances of elements. Inside the frost line, planetesimals could form only from scarce heavy elements, producing relatively small terrestrial planets. Outside the frost line, the addition of water ice increased the available solid mass by a factor of 3 to 4, enabling formation of much larger planetary cores. These massive cores could then gravitationally capture hydrogen and helium gas from the surrounding nebula, growing into gas giant planets. Further outward, additional frost lines existed for other volatile compounds. Carbon monoxide, nitrogen, methane, and ammonia each had characteristic temperatures below which they transitioned from gas to solid ice. These successive frost lines created compositional zones in the outer solar system. The locations of these boundaries influenced which materials accreted into the forming giant planets, affecting their eventual compositions. The chemical inventory. The solar nebula inherited its composition from the interstellar medium. Hydrogen dominated overwhelmingly, comprising roughly 71% of mass. Helium accounted for approximately 27%. All heavier elements together made up only about 2% of the total mass. Within this 2%, oxygen was most abundant, followed by carbon, nitrogen, neon, magnesium, silicon, iron, and sulfur. Every other element appeared in smaller quantities. This composition reflected billions of years of stellar nucleosynthesis. The hydrogen and most helium dated to the Big Bang. Carbon, oxygen, magnesium, silicon, and iron came primarily from massive stars that lived and died before our solar system formed. Elements like gold, platinum, and uranium originated in neutron star mergers and supernova explosions. The recent supernova that triggered the clouds collapse added freshly synthesized material, including radioactive isotopes like aluminum-26. The chemical composition varied between gas and dust phases. Volatile elements like hydrogen, helium, carbon, nitrogen, and oxygen remained mostly in gaseous form throughout the disk. Refractory elements like calcium, aluminum, titanium, magnesium, silicon, and iron condensed into solid dust grains when temperatures dropped below their condensation points. This separation between gas and dust had profound implications for planet formation. Terrestrial planets would build from dust particles, inheriting only the refractory elements that could condense in the hot inner solar system. Gas giant planets would capture both dust and gas, acquiring compositions closer to the overall solar nebula composition. Dust grains in the solar nebula were typically submicrometer to micrometer in size initially. They consisted of various minerals depending on temperature. Silicate minerals like olivine and pyroxene formed common dust components. Carbon appeared as amorphous carbon or graphite. In colder regions beyond the frost line, icy mantles coated silicate cores, creating composite grains. These tiny particles represented the seeds from which planets would grow. Disk dynamics and evolution. The protoplanetary disk was not static. It evolved constantly through multiple physical processes. Material from the remnant cloud envelope continued falling onto the disk for the first million years or so, adding mass and stirring the disk. This infall created strong vertical shear because material above and below the disk midplane rotated at subkeplerian velocities. The shear excited low-order spiral modes that transporting angular momentum very efficiently. Mass accretion rates during this infall phase could reach 10 to the power of -5 solar masses per year, far exceeding the steady-state rates in isolated disks. Gas in the disk did not orbit at perfect Keplerian velocities. Pressure gradients caused gas to orbit slightly slower than the Keplerian rate. This sub-Keplerian rotation created a headwind that dust particles experienced. Aerodynamic drag from this headwind caused dust particles to spiral inward toward the star. The drag strength depended on particle size. Millimeter to centimeter-sized particles experienced the strongest drag and spiraled inward fastest, potentially reaching the star in only thousands of years. This rapid inward drift posed a problem for planet formation. If dust particles spiraled into the star before they could grow large enough to resist drag, planet formation would fail. Several mechanisms counteracted this inward drift. Turbulence in the disk suspended small particles, preventing them from settling completely to the midplane where drag was strongest. Pressure bumps, regions where pressure increased with radius rather than decreased, acted as dust traps. Particles drifting inward accumulated at these pressure bumps, creating zones of enhanced dust density. Such accumulations may have formed at the edges of gaps carved by forming planets or at the boundaries between different disk regions. The streaming instability, discussed later, also helped overcome the drift barrier by enabling rapid collapse of concentrated dust layers. Magnetic fields influenced disk evolution significantly. The magnetorotational instability generated turbulence that transporting angular momentum, driving accretion. However, this instability required sufficient ionization for magnetic fields to couple to the gas. The inner disk, heated by the protostar and bombarded by X-rays, maintained enough ionization for strong coupling. The outer disk, heated by cosmic rays penetrating from outside, also had decent ionization. A dead zone existed in the middle regions of the disk, where ionization was too low for magnetorotational instability to operate. This dead zone had different dynamics, potentially accumulating material until gravitational instabilities took over. Setting the stage. Within a few 100,000 years, the solar nebula had established the basic architecture that would determine the solar system's structure. A massive disk of gas and dust surrounded the growing protostar. Temperature gradients separated the disk into distinct zones, each capable of forming different types of worlds. The frost line divided rocky planet territory from giant planet territory. Material was slowly spiraling inward, while mechanisms worked to overcome the rapid inward drift of dust. The molecular cloud's collapse had concentrated enough mass at the center to form the Sun. Nuclear fusion would soon begin, fundamentally changing the environment. The disk contained sufficient material to build the planets we observe today. Jupiter alone accounts for about 300 Earth masses, Saturn another 95 Earth masses, Uranus and Neptune together about 30 Earth masses, and the terrestrial planets plus asteroid belt represent roughly 2 Earth masses. The gas in the disk contributed far more mass than the solids, but it would eventually be dispersed, leaving behind only the solid cores and whatever gas the giant planets managed to capture before dispersal occurred. The protoplanetary disk existed in a dynamic, evolving state. Processes operating within the disk over the next few million years would transform microscopic dust grains into planets. Understanding the disk's initial conditions and evolution provides the foundation for understanding how Earth and the other planets formed. The stage was set. The raw materials were present. The temperature zones that would determine planetary compositions were established. The next phase of solar system formation could begin with the ignition of the Sun and the growth of solid bodies from dust. Chapter 4: The Sun ignites. At the center of the swirling disk, the mass kept accumulating. Gravity pulled material from the surrounding nebula onto the growing protostar, increasing its mass steadily over hundreds of thousands of years. The protostar was already large, perhaps several times the current radius of Mercury's orbit, and luminous from gravitational contraction. Material falling onto the protostar released tremendous energy, heating the surface to thousands of degrees. The protostar glowed brightly, visible across the disk as a red or orange beacon. Yet this light came from gravitational collapse, not nuclear fusion. The protostar was not yet truly a star. That transformation awaited sufficient mass accumulation and core heating to trigger the thermonuclear reactions that would power the Sun for billions of years. Approach to fusion. The core temperature rose relentlessly as material piled on. When the protostar's mass reached approximately 0.08 solar masses, the core temperature climbed above 10 million Kelvin. This temperature marked a critical threshold. Hydrogen nuclei, stripped of their electrons by the intense heat, moved fast enough to overcome the electromagnetic repulsion between positively charged protons. Quantum tunneling allowed protons to fuse despite not having quite enough energy to surmount the repulsive barrier classically. The first fusion reactions began tentatively, converting hydrogen to deuterium and then helium. Initially, fusion contributed little to the protostar's energy output. Gravitational contraction still provided most of the luminosity. The fusion reactions occurred sporadically in the small, hottest regions of the core. As more mass accreted and the core compressed further, temperature and density increased. More fusion reactions occurred. The energy generation rate from fusion climbed exponentially with temperature. Core temperature followed a scaling relationship with total mass. More massive protostars achieved higher core temperatures. The protosun passed through several intermediate stages as its mass approached 1 solar mass. The fusion process involved multiple steps. The proton-proton chain dominated energy production in solar mass stars. In the first step, 2 protons fused to create a deuterium nucleus, releasing a positron and a neutrino. This step was extremely slow because it required a weak nuclear force interaction. On average, a proton in the Sun's core waits billions of years before successfully fusing with another proton. The second step proceeded much faster. The deuterium nucleus captured another proton, forming helium-3 and releasing a gamma ray. The third step involved 2 helium-3 nuclei fusing to create helium-4 plus 2 protons. The net result of the complete chain converted 4 hydrogen nuclei into 1 helium nucleus, 2 positrons, 2 neutrinos, and multiple gamma rays. Mass was converted to energy according to Einstein's famous equation, E equals mc squared. When the protosun's mass reached approximately 1 solar mass and core temperature exceeded 15 million Kelvin, hydrogen fusion became self-sustaining. The energy released by fusion reactions generated enough pressure to halt further gravitational contraction. The protostar achieved hydrostatic equilibrium, where inward gravitational force balanced outward pressure force. This moment, occurring roughly 1 million years after the initial collapse began, marked the birth of the Sun as a main sequence star. Nuclear fusion would now power the Sun for the next 10 billion years, maintaining this equilibrium with only slow evolution. The T-Tauri phase. Before reaching the main sequence, the protosun passed through a tumultuous period called the T-Tauri phase, named after the prototype star T-Tauri. This phase lasted several million years and was characterized by intense stellar activity. The protosun exhibited strong magnetic fields, large star spots covering significant fractions of its surface, and powerful stellar winds. These winds were far stronger than the current solar wind, carrying mass away from the star at rates reaching 10 to the power of -7 solar masses per year. The T-Tauri wind had profound effects on the surrounding disk. The wind originated from the star's entire surface, but was channeled by magnetic fields and collimated by the disk into two oppositely directed beams, creating a bipolar outflow. These jets extended perpendicular to the disk plane, carrying energy and momentum outward. The jets cleared material from the polar regions, creating cavities above and below the disk. Material caught in these outflows was accelerated to velocities of 100 to 300 kilometers per second and ejected from the system entirely. During the T-Tauri phase, the protosun could lose up to 0.4 solar masses through these winds and outflows. This mass loss was significant, removing nearly 1/3 of the protostar's mass and disrupting the inner portions of the disk. The winds also transporting angular momentum away from the star, helping solve the angular momentum problem. Young stars rotate rapidly due to conservation of angular momentum during contraction. Without angular momentum loss mechanisms, the protosun would have been spinning so fast it would tear itself apart. The T-Tauri wind, coupled with magnetic braking, removed angular momentum efficiently, allowing the protosun to contract to its main sequence radius without overspinning. The composition of the T-Tauri jets evolved over time. Early in the T-Tauri phase, when the circumstellar disk was still thick and dense, the jets were primarily molecular, containing molecules like carbon monoxide and water vapor. As the disk thinned and the protosun's temperature increased, the jets transitioned to atomic composition, dominated by hydrogen, helium, and ionized heavier elements. This evolution reflected both the changing disk properties and the increasing ionization caused by the protosun's ultraviolet radiation and stellar wind. Observations of modern T-Tauri stars reveal complex interactions between the star and its disk. Many T-Tauri stars show signs of ongoing accretion, with material from the disk flowing along magnetic field lines onto the stellar surface. These accretion columns create hot spots on the star where infalling material impacts at high velocity. The hot spots rotate with the star, producing periodic variations in brightness and spectral features. Magnetic fields connect the star to the disk at a radius called the corotation radius, where the disk's orbital period matches the star's rotation period. Inside this radius, magnetic fields can disrupt the disk and control accretion flow, clearing the inner system. As the Sun approached the main sequence, its luminosity and wind strength increased dramatically. The combination of stellar radiation, stellar wind, and persistent accretion heating created intense conditions in the inner solar system. The innermost regions of the disk, within about 0.1 astronomical units, experienced temperatures exceeding 1,500 Kelvin. Material this close to the protosun was either accreted onto the star or driven outward by radiation pressure and wind. The stellar wind became particularly effective at removing gas from the disk. Hydrogen and helium, being the lightest elements, were most easily pushed outward and ejected. The wind interacted with the disk's surface, creating a boundary layer where disk material was heated and accelerated. Photoevaporation, where ultraviolet radiation from the protosun heated gas to escape velocity, also contributed to disk dispersal. High-energy photons ionized hydrogen atoms, giving them enough thermal energy to escape the Sun's gravity. This process was most effective at intermediate distances, perhaps 5 to 20 astronomical units, where radiation could penetrate the disk efficiently, but gravity was weak enough that heated gas could escape. The timescale for gas dispersal varied with location. The inner disk, exposed to the most intense radiation and wind, cleared within 1 to 3 million years. The outer disk persisted longer, typically 5 to 10 million years, though some systems retained gas disks for as long as 20 million years. Dust particles, being more massive than gas molecules, resisted wind pressure more effectively. Dust disks persisted after gas disks disappeared, sometimes for 100 million years or more. However, without gas drag to damp their velocities, dust particles in gas-free disks experienced destructive collisions that ground them down, eventually clearing the remaining dust as well. The sun's radiation also altered the chemistry of disk material. Ultraviolet photons broke apart complex molecules, creating radicals and ions that underwent different chemical reactions than neutral molecules. Ionization created a plasma in the upper layers of the disk, enabling magnetic field coupling and magnetorotational instability. X-rays from the active young sun penetrated deeper into the disk, ionizing material near the midplane and affecting the dead zone's extent. These energetic processes altered the composition of solids that would eventually be incorporated into planets. Reaching the main sequence. When hydrogen fusion in the core became fully self-sustaining, the sun settled onto the main sequence, where it would spend the vast majority of its lifetime. The main sequence sun had a mass of 1 solar mass, a radius of approximately 0.9 times its current radius, and a luminosity of only 70% of its present luminosity. This lower luminosity resulted from the sun's early composition and structure. As hydrogen fused to helium in the core over billions of years, the mean molecular weight of the core would increase, requiring higher core temperature to maintain pressure support. This higher temperature would drive increased fusion rates, gradually raising the sun's luminosity throughout its main sequence lifetime. The sun's surface temperature at this stage was approximately 5,500 Kelvin, slightly cooler than today's 5,778 Kelvin. The sun emitted primarily visible and near-infrared radiation, with peak emission in the yellow-green portion of the spectrum. This radiation illuminated the disk, heating its surface and driving temperature gradients. The disk temperature at any given radius depended on the balance between absorbed stellar radiation and re-radiated infrared emission. Closer to the sun, absorbed stellar radiation dominated, creating high temperatures. Further out, internal heating from viscous dissipation contributed, while radiative cooling to space kept temperatures low. The newly formed main sequence sun rotated much faster than it does today. Estimates suggest a rotation period of perhaps a few days, compared to the current 25-day period at the equator. This rapid rotation, combined with convection in the outer layers, generated strong magnetic fields through dynamo action. These fields produced large star spots, intense flares, and a vigorous stellar wind. The sun's early high rotation rate and magnetic activity created a harsh environment for the inner solar system, bombarding the region with energetic particles and radiation. Lifetime of the disk. The protoplanetary disk did not disappear instantly when the sun reached the main sequence. Observations of young stellar systems reveal that disks typically persist for several million years after the central star begins fusion. During this window, planets must form from the available material. The disk lifetime imposed a strict constraint on planetary formation timescales. Giant planets had to form rapidly within the first few million years to capture substantial amounts of hydrogen and helium before the gas dispersed. Rocky planets could take longer since they built from solid material, but even they had to assemble while enough planetesimals remained. The disk lifetime varied between systems. Some circumstellar disks dispersed within 1 million years of the star reaching the main sequence. Others persisted for 10 million years or longer. The variation depended on multiple factors. Stellar mass influenced disk lifetime, with more massive stars producing stronger winds and radiation that cleared disks faster. Disk mass and structure also mattered. More massive disks took longer to disperse. Disks with low turbulence retained gas longer than highly turbulent disks. External environmental factors played roles as well. Stars forming in dense clusters experienced disk photoevaporation from nearby massive stars, shortening disk lifetimes significantly. For the solar system, evidence suggests the gas disk persisted for approximately 3 to 4 million years after the Sun formed. By this time, Jupiter and Saturn had likely formed, capturing vast amounts of hydrogen and helium. Uranus and Neptune may have been forming or had recently formed, capturing smaller amounts of gas before the supply ran out. The terrestrial planets were still in early assembly stages, building from planetesimals. The gas dispersal marked a major transition in solar system evolution, ending the era when giant planets could grow and beginning the era when rocky planets assembled through collisions. The early sun's influence. The young sun profoundly shaped the environment where planets formed. Its luminosity determined temperature gradients, controlling where different materials could condense and where ice could exist. The frost line migrated inward as the sun's luminosity increased, altering the boundary between rocky and icy planet-forming regions. This migration may have influenced planet compositions if planets formed while the frost line moved. The sun's magnetic field extended throughout the inner solar system, interacting with ionized gas in the disk. Magnetic field lines threaded through the disk, creating channels along which material could flow toward or away from the sun. These fields may have generated dead zones where turbulence was suppressed, allowing material to accumulate. Magnetic braking removed angular momentum from the sun, but it also affected disk dynamics, potentially driving jets and winds from the disk itself. High-energy radiation from the young sun created isotopic anomalies preserved in meteorites. Short-lived radioactive isotopes like beryllium-10 and aluminum-26 were produced when cosmic rays and solar energetic particles bombarded dust grains. The decay products of these isotopes appear in primitive meteorites, providing evidence for intense particle bombardment in the early solar system. This irradiation altered the chemistry of solids, creating isotopic heterogeneities that persisted into the planets. The sun's influence extended even to the disk's outer reaches. Solar wind pressure and magnetic fields affected material at tens of astronomical units. The transition from the sun-dominated inner region to the interstellar medium-dominated outer region occurred somewhere between 100 and 200 astronomical units, defining the extent of the sun's sphere of influence. Material beyond this boundary was more influenced by galactic dynamics than solar processes. A star is born. Within 1 million years, the protosun had transformed from a collapsing cloud core into a stable main sequence star powered by nuclear fusion. This transformation was remarkably rapid on cosmic timescales. The sun would now shine steadily for billions of years with only gradual evolution. The violent T-Tauri phase had ended, though the young sun remained more active than it is today. The disk had been processed by intense radiation and winds, with much of its gas driven away. Yet sufficient material remained to build all the planets we see today. The sun's formation was not unique. Millions of stars formed similarly throughout the galaxy during the same epoch. Many of those stars have planetary systems of their own, built from their own protoplanetary disks. The processes that formed the sun were universal, operating wherever molecular clouds collapsed to form stars. Understanding the sun's birth provides insight into how all stars form and how common planetary systems might be throughout the universe. The sun had ignited. Its light and heat now warmed the surrounding disk. Its wind and radiation cleared material and drove chemical reactions. The stage was set for the next phase of solar system formation, where solid material would begin accumulating into progressively larger bodies. Dust grains would collide and stick together. Pebbles would form, then boulders, then planetesimals kilometers across. Eventually, these planetesimals would collide and merge, building the planetary embryos that would become Earth and the other rocky worlds. The sun's role was established. Now the process of planet assembly could proceed in earnest. Chapter 5. Planetary embryos form. The disk was alive with collisions. Trillions upon trillions of dust particles drifted through the protoplanetary disk, each one following its own orbit around the young sun. These microscopic grains, typically less than 1 micrometer across, represented the starting point for planet formation. They were the raw materials, the fundamental building blocks from which worlds would grow. The transformation from dust to planets required overcoming multiple barriers, each presenting challenges that threatened to halt the process entirely. The dust grains had to stick together despite collision velocities that could shatter them. They had to grow large enough to resist being swept into the sun by gas drag. They had to accumulate into planetesimals kilometers across before the disk gas dispersed. Understanding how this accumulation occurred reveals the remarkable physics that built Earth from countless tiny particles floating in space. From dust to pebbles. The smallest dust grains collided constantly due to Brownian motion, the random thermal jostling of molecules. At the low collision speeds produced by Brownian motion, typically only centimeters per second, grains always stuck together. Surface forces dominated at these scales. Van der Waals forces, arising from quantum fluctuations in electron clouds, created attraction between nearby surfaces. When two dust grains touched, these intermolecular forces bound them together. The contact area was small, but the forces were strong enough to hold micrometer-sized particles in loose aggregates. As grains stuck together, they formed fluffy structures resembling dust bunnies. These aggregates had extremely low densities, often only a few % of solid material, with the rest being empty space. The porous structure resulted from the random nature of collisions. Grains stuck wherever they touched, creating branching, fractal-like structures rather than compact spheres. These fluffy aggregates grew by sweeping up smaller particles, incorporating anything they collided with. Growth through Brownian motion worked well for particles up to about 1 micrometer in size. Larger particles experienced weaker Brownian motion and collided less frequently with other small grains. Different growth mechanisms had to take over. Turbulence in the gas disk stirred particles of different sizes, creating relative velocities between them. Larger particles, being more strongly coupled to the gas, moved with the bulk flow. Smaller particles followed turbulent eddies more closely, creating collision opportunities. This turbulent growth allowed particles to reach millimeter and centimeter sizes. Differential settling provided another growth mechanism. Larger particles settled toward the disk midplane faster than smaller particles due to their higher mass-to-surface area ratio. As large particles fell through a layer of smaller particles suspended higher in the disk, they collided and swept up material. This mechanism was particularly effective for growing centimeter to decimeter-sized objects. Growth barriers. Beyond centimeter sizes, planet formation encountered serious obstacles. The bouncing barrier emerged when collision velocities increased enough that particles bounced apart rather than sticking. The threshold velocity for sticking depended on particle composition, size, and structure. For compact silicate particles, the threshold was approximately 1 meter per second. Irregular-shaped particles had higher sticking probabilities, showing some sticking even at higher velocities due to their rough surfaces providing more contact points. When collision velocities exceeded the sticking threshold, particles simply bounced off each other without growing. In the inner solar system, turbulence and differential orbital velocities created collision speeds exceeding 1 meter per second for centimeter-sized particles. Growth stalled at this size, with particles repeatedly colliding but never sticking. This bouncing barrier prevented direct growth from centimeters to meters through pairwise collisions. The fragmentation barrier posed an even more severe threat. At collision velocities above approximately 10 meters per second, particles shattered instead of bouncing. High-energy impacts destroyed aggregates, breaking them into smaller fragments. In the inner disk, where orbital velocities were high, fragmentation limited particle sizes. As soon as particles grew large enough to achieve destructive collision velocities, they broke apart. The process of growth and fragmentation reached an equilibrium, maintaining particles at a characteristic size determined by the balance between growth and destruction. The drift barrier represented perhaps the most dangerous obstacle. Particles larger than millimeters experienced significant aerodynamic drag from the subkeplerian gas. This drag caused them to lose angular momentum and spiral inward toward the Sun. Meter-sized objects spiraled inward fastest, potentially reaching the Sun in only a few hundred orbits, corresponding to mere thousands of years at distances of several astronomical units. This rapid inward drift could sweep all the solid material into the Sun before planets could form, erasing the raw materials needed for terrestrial worlds. Streaming instability solution. The streaming instability provided a mechanism to bypass the growth barriers and form planetesimals rapidly. This process operated when the local ratio of solid particles to gas exceeded approximately 1, meaning solids were at least as abundant as gas by mass in certain regions. Such high solid-to-gas ratios could develop in zones where particles piled up due to pressure bumps or where inward drifting particles accumulated. The streaming instability arose from a feedback loop between particles and gas. Particles drifting inward due to drag created a slight headwind for the gas, causing the gas to lose angular momentum and drift inward as well. This modified the gas velocity structure, which affected the drag on particles. Where particle concentrations were slightly higher, the feedback was stronger, causing even more particles to concentrate there. The instability grew exponentially, creating dense filaments of particles embedded in the gas disk. Within these filaments, particle densities reached values far exceeding the average disk density, sometimes by factors of 100 or more. At such high densities, self-gravity became important. The filaments began to gravitationally contract, pulling even more particles into their cores. This runaway process led to the rapid formation of gravitationally bound clumps. These clumps collapsed over timescales of years to decades, forming solid planetesimals ranging from 1 to hundreds of kilometers in diameter. The streaming instability formed planetesimals with characteristic properties. They were pebble piles, porous structures composed of loosely bound smaller particles. Their low densities reflected their formation through gravitational collapse rather than compaction through high-velocity collisions. Impact speeds during collapse were limited to a few tens of meters per second, insufficient to fragment particles significantly. The planetesimals retained porosity from their parent filaments. Numerical simulations revealed that streaming instability operated most effectively beyond the snow line, where ice increased the solid-to-gas ratio. Inside the snow line, achieving the necessary solid enrichment was more challenging, possibly requiring special conditions like a pressure bump at roughly 1 astronomical unit. This pressure bump could arise from a change in disk structure or from the inner edge of a dead zone where turbulence dropped. Particles drifting inward would pile up at such locations, increasing local solid density enough to trigger streaming. Pebble accretion. Once planetesimals formed, they grew further through pebble accretion, a highly efficient mechanism for adding mass. Pebble accretion operated when large solid bodies encountered a flux of smaller particles drifting through the gas. The gravitational field of the planetesimal pulled in pebbles from a large cross-section, far exceeding the planetesimal's geometric size. Gas drag helped by reducing the orbital energy of captured pebbles, causing them to spiral onto the planetesimal's surface. The accretion efficiency depended on the planetesimal's size and the properties of the gas and pebbles. Small planetesimals with weak gravity captured pebbles inefficiently. Only pebbles passing very close were accreted. As planetesimals grew larger, their gravitational reach extended, and accretion became more efficient. A critical transition occurred when the planetesimal's gravitational influence exceeded the gas disk's scale height. At this point, the planetesimal could perturb the gas flow, creating pressure patterns that funneled pebbles toward it. Pebble accretion allowed rapid growth. A planetesimal could grow from 100 kilometers to 1,000 kilometers in only 10,000 to 100,000 years, given sufficient pebble flux. This timescale was much shorter than growth through planetesimal collisions, which required millions of years. The rapid growth through pebble accretion helped explain how giant planet cores formed before the gas disk dispersed. Jupiter's core needed to reach approximately 10 Earth masses to trigger runaway gas accretion. Achieving this mass within the disk lifetime of a few million years required efficient accretion mechanisms like pebble accretion. Runaway growths. Once some planetesimals grew larger than their neighbors, they entered a phase called runaway growth. In this regime, the largest bodies grew faster than smaller bodies, causing the size gap between them to increase exponentially over time. The physics behind runaway growth was straightforward. Larger planetesimals had stronger gravity, giving them larger gravitational cross-sections for capturing other objects. They swept up material from wider feeding zones than smaller planetesimals. The growth rate was proportional to mass squared for gravitational focusing, meaning that doubling mass quadrupled the growth rate. Runaway growth was remarkably rapid. Simulations showed that within 100,000 years, a few lucky planetesimals could grow from 10 kilometers to over 1,000 kilometers, while most remained small. These large bodies were planetary embryos, Moon-to-Mars-sized objects that dominated their local regions. The size distribution during runaway growth became bimodal, with a few giants and many leftover small planetesimals. Runaway growth eventually slowed as planetary embryos cleared their feeding zones of material. Each embryo stirred up the orbits of nearby planetesimals through gravitational interactions, increasing random velocities. Higher velocities meant more energetic collisions, reducing accretion efficiency. The embryo's feeding zones began to overlap, and interactions between embryos became important. Growth transitioned from runaway to oligarchic growth. Oligarchic growth. In oligarchic growth, multiple similar-sized planetary embryos grew at comparable rates. The term oligarchic referred to rule by a few, reflecting the dominance of several large embryos rather than one runaway winner. Each embryo controlled a distinct feeding zone, an annular region around its orbit where it was the largest object and accreted most efficiently. The feeding zone width increased with distance from the Sun because orbital velocities were lower and gravitational focusing was stronger. The embryos grew by accreting leftover planetesimals within their feeding zones. Growth rates were slower than during runaway growth because the embryos' masses were similar and they did not have the same competitive advantage. The time to grow to Mars size was typically less than 10 million years in the inner solar system. In the outer solar system, oligarchic growth produced even larger embryos due to wider feeding zones and greater solid mass availability beyond the snow line. Oligarchic growth created a specific architecture. Embryos were spaced regularly, separated by several mutual Hill radii. The Hill radius defined the region where an object's gravity dominated over the Sun's tidal forces. Spacing at several Hill radii ensured orbital stability, preventing close encounters that would lead to collisions or ejections. This spacing meant that perhaps 50 to 100 embryos formed in the terrestrial planet region, each with masses between the Moon and Mars. Building blocks of rocky planets. The terrestrial planets formed primarily through collisions among these inner solar system embryos. Isotopic evidence from Earth and Mars indicates they accreted mainly from material originating in the inner solar system rather than from outer solar system pebbles drifting inward. The contribution of outer solar system material to Earth was limited to only a few % by mass. This finding refutes models where terrestrial planets formed by accreting large amounts of inward drifting pebbles from beyond the snow line. Instead, terrestrial planets grew through a protracted period of giant impacts among planetary embryos. After the gas disk dispersed, removing the damping effect of gas drag, embryo orbits became unstable. Close encounters led to collisions and mergers. This chaotic phase lasted tens of millions of years, gradually reducing the number of embryos while increasing the size of survivors. Earth likely accreted from collisions involving 10 to 20 embryos of various sizes. The isotopic composition of Earth reveals mixing among distinct populations of material. Molybdenum isotopes, which vary between carbonaceous and non-carbonaceous meteorite groups, show that Earth contains mostly non-carbonaceous material from the inner solar system, with a small carbonaceous component likely added late in accretion. Mars shows a similar pattern, but with different mixing proportions, indicating it accreted from a somewhat different population of embryos. The presence of a dust drift barrier in the disk may have separated inner and outer solar system materials. This barrier prevented most outer solar system pebbles from drifting inward to the terrestrial planet region, explaining why Earth and Mars contain limited outer solar system material. Pressure bumps, gaps carved by Jupiter, or other disk structures could have created this barrier, highlighting that planet formation was influenced by disk dynamics and architecture established early in solar system history. Giant planet cores. Beyond the snow line, planetary embryos grew larger due to abundant ice and wider feeding zones. Jupiter and Saturn formed through core accretion, where solid cores reaching 10 to 25 Earth masses triggered runaway gas accretion from the surrounding nebula. The cores formed first through planetesimal and pebble accretion, accumulating ice and rock over perhaps 1 to 3 million years. Pebble accretion was particularly important for giant planet core formation. The rapid growth rates achievable through pebble accretion allowed cores to reach critical mass before the gas disk dispersed. Once the core exceeded approximately 10 Earth masses, its gravity became strong enough to hold onto a significant gaseous envelope. Gas accretion accelerated as the envelope mass increased, eventually becoming nearly free fall. Jupiter captured about 300 Earth masses of hydrogen and helium, forming its massive atmosphere. Saturn formed similarly, but captured less gas, possibly because it formed later when the disk was already dispersing, or because Jupiter's gravity perturbed the disk in Saturn's region. Recent measurements from the Juno and Cassini missions revealed that Jupiter's core is diffuse, with heavy elements mixed into the envelope rather than concentrated in a compact central core. This distribution suggests continued solid accretion during gas accretion, with planetesimals dissolving into the growing envelope. Uranus and Neptune formed farther out, where solid material was scarcer and orbital periods were longer. They likely formed cores of a few Earth masses, but captured only modest gas envelopes before the nebula dispersed. Their compositions are dominated by ices rather than gas, classifying them as ice giants rather than gas giants. The lower gas content resulted from slower core growth at larger distances, causing their cores to reach critical mass after much of the gas had already been removed by photoevaporation and stellar winds. A solar system takes shape. Within roughly 10 million years, the solar system's basic architecture was established. Dozens of planetary embryos populated the inner solar system, each one a potential building block for the terrestrial planets. Jupiter and Saturn had formed in the outer regions, their massive gravity dominating their neighborhoods. Uranus and Neptune were forming or had recently formed farther out. The asteroid belt region between Mars and Jupiter contained additional embryos and planetesimals, though Jupiter's gravity prevented them from accreting into a single planet. The stage was set for the final assembly of the terrestrial planets through giant impacts. One of these impacts would be the most consequential event in Earth's history, fundamentally reshaping the planet and creating the Moon. But before that dramatic collision, a proto-Earth had to form, growing from one of the planetary embryos through accretion of surrounding material. This proto-Earth would be Earth's immediate precursor, the version of our planet that existed before the moon-forming impact transformed it forever. Chapter 6. Proto Earth takes form. One planetary embryo in the inner solar system grew larger than the others. Its location was favorable, roughly 1 astronomical unit from the Sun, in a region where temperatures allowed rock and some volatile compounds to condense. This embryo, which would eventually become Earth, began as one among many similar-sized objects. Through a combination of fortunate positioning, gravitational focusing, and time, it accreted more material than its neighbors. Within approximately 30 to 50 million years after the solar system began forming, this embryo had grown to roughly 90% of Earth's current mass. This object was Proto-Earth, the primordial version of our planet before the giant impact that would create the Moon and complete Earth's formation. Rapid accretion. Proto-Earth grew through continuous bombardment of smaller bodies. Planetesimals and smaller embryos crashed into its surface at velocities of several kilometers per second, releasing enormous energy. Each impact delivered mass while converting kinetic energy to heat. The larger proto-Earth grew, the faster it attracted additional material through gravitational focusing. The gravitational cross-section for capture exceeded the geometric size by factors of 10 or more, allowing proto-Earth to sweep up material from a wide region around its orbit. The accretion timescale was surprisingly short. For proto-Earth to reach 90% of its current mass required no more than 50 million years from the start of solar system formation. Some models suggest even faster growth, with most mass accumulating within 10 to 30 million years. This rapid timescale was necessary to explain the state of early Earth. If accretion had proceeded more slowly, the heat generated by impacts would have had time to radiate away, potentially preventing the global melting that characterized early Earth's state. Evidence for rapid accretion comes from isotopic systems, particularly hafnium-tungsten dating. Hafnium-182 decays to tungsten-182 with a half-life of 9 million years. This short-lived isotope was present when the solar system formed, but decayed away within the first 50 million years. The hafnium-tungsten system records the timing of core formation, when metallic ions separated from silicate rock and sank to Earth's center. The tungsten isotopic composition of Earth's mantle indicates that core formation occurred while hafnium-182 was still decaying, constraining it to within roughly 30 to 50 million years of solar system formation. A molten surface. Proto-Earth was not the cool, solid world we inhabit today. The surface was molten, covered by an ocean of liquid rock extending hundreds of kilometers deep. This magma ocean resulted from the continuous energy input from impacts. Every planetesimal impact released energy proportional to the square of the impact velocity. At Earth's orbital distance, typical impact velocities reached 10 kilometers per second or more. At these speeds, the kinetic energy per unit mass exceeded the energy needed to vaporize rock by factors of several. The impacts occurred so frequently that heat accumulated faster than it could radiate away. Surface temperatures reached 1,500 to 2,000 degrees Celsius, well above the melting points of most silicate minerals. The entire surface layer melted, creating a global magma ocean. The depth of this ocean varied over time, deepening during periods of intense bombardment and partially solidifying during quieter intervals. Models suggest the magma ocean extended at least several hundred kilometers deep, possibly encompassing the entire mantle in the most energetic scenarios. The magma ocean was not a placid body of molten rock. It was violently turbulent, stirred by convection and by the constant input of impactor energy. Convection cells transporting hot magma from depth to the surface, where it cooled by radiating heat to space. The cooled surface layer sank back down, completing the convection cycle. This convective motion homogenized the magma ocean's composition, mixing material from different impactors throughout the molten region. Recent research revealed that proto-Earth's rapid rotation influenced how the magma ocean crystallized. The early Earth rotated much faster than it does today, with a day lasting perhaps 5 to 6 hours. This rapid rotation created strong Coriolis forces that affected convection patterns. The rotation caused minerals crystallizing from the magma ocean to settle unevenly, potentially accumulating more at certain latitudes. This uneven crystallization may have influenced the early development of Earth's internal structure and possibly contributed to initiating plate tectonics billions of years later. Building the layers. Even while molten, proto-Earth began differentiating into distinct layers. Dense materials sank toward the center, while lighter materials rose to the surface, driven by gravity. The most important differentiation was the separation of metallic iron from silicate rock. Iron delivered by impactors melted and formed droplets in the magma ocean. These iron droplets were denser than the surrounding silicate melt and sank through it, descending toward Earth's center. The sinking iron formed an increasingly large metallic core. This process, sometimes called the iron catastrophe, released gravitational potential energy as dense material fell through thousands of kilometers of lighter material. The energy released heated proto-Earth even further, potentially contributing to maintaining the magma ocean. The sinking iron reached the center within thousands to tens of thousands of years once it began, a geologically instantaneous process. The core formation had profound chemical consequences. Iron is a siderophile element, meaning it preferentially enters metallic phases rather than silicate phases. When iron separated from silicates, it took with it other siderophile elements like nickel, cobalt, platinum, gold, and iridium. These elements were extracted from the mantle into the core, depleting the mantle in siderophiles. The degree of depletion provides information about the conditions during core formation, including the pressure, temperature, and oxygen content of the differentiating material. The mantle that formed above the core consisted primarily of silicate minerals. Magnesium-rich minerals like olivine and pyroxene dominated. These minerals had crystallization temperatures around 1,400 to 1,700 degrees Celsius, determining the temperature at which the magma ocean could solidify. As the magma ocean cooled, crystals formed and either sank or floated, depending on their density. Most silicate minerals were denser than the melt and sank, accumulating in the lower mantle. Some minerals, particularly plagioclase feldspar, were less dense than the melt and floated, potentially forming a primitive crust. Atmospheric outgassing. Proto-Earth had an atmosphere, though it bore little resemblance to the nitrogen-oxygen atmosphere we breathe today. The primordial atmosphere was initially captured hydrogen and helium from the solar nebula. This hydrogen-rich envelope surrounded Proto-Earth during its formation, dissolved into the magma ocean, and was held by gravity. However, this primordial atmosphere was lost. The intense ultraviolet radiation from the young sun, combined with Earth's relatively modest gravity and high surface temperature, allowed hydrogen and helium to escape to space. Within a few million years, the primordial atmosphere was largely stripped away. A secondary atmosphere replaced it, generated through outgassing from the interior. Impactors delivered volatile compounds, including water, carbon dioxide, nitrogen, and sulfur compounds. These volatiles dissolved in the magma ocean and were later released as gases. Volcanic activity, driven by internal heating, brought volatiles from depth to the surface where they degassed into the atmosphere. The composition of this secondary atmosphere was dominated by water vapor, carbon dioxide, and nitrogen, with smaller amounts of methane, ammonia, hydrogen, and sulfur gases. The atmospheric pressure was much higher than today. Some estimates suggest pressures reaching 10 to 100 times the current atmospheric pressure due to the large amounts of outgassed volatiles. The thick atmosphere was opaque, trapping heat through a powerful greenhouse effect. Surface temperatures remained high not only from impacts and internal heat, but also from the insulating effect of the atmosphere. The sky glowed red from the incandescent magma below and from the thermal radiation of the hot atmosphere itself. Water vapor dominated the atmosphere initially, but the surface was too hot for liquid water to exist. Water remained as a supercritical fluid or gas, unable to condense and form oceans. Only when surface temperatures dropped below water's critical point of 374 degrees Celsius, or the lower boiling point corresponding to atmospheric pressure, could liquid water condense. This cooling would not occur until the bombardment intensity decreased and heat could radiate away. Proto-Earth composition. Recent discoveries have provided direct evidence of Proto-Earth's composition preserved in modern rocks. In 2025, scientists reported finding isotopic anomalies in ancient rocks that represent material from Proto-Earth that survived the moon-forming impact. These samples show a subtle deficit in potassium-40 compared to typical Earth rocks, suggesting they preserve a chemical signature from before the giant impact. The isotopic composition revealed that Proto-Earth accreted materials with distinct characteristics from those added after the giant impact. This finding indicates that the building blocks of Proto-Earth came from a specific population of planetesimals with isotopic signatures different from later additions. The Proto-Earth mantle had particular isotopic ratios that survived in some deep mantle reservoirs, isolated from mixing by the giant impact and subsequent geological processes. Proto-Earth's composition reflected its accretion from inner solar system materials. The planetary embryos and planetesimals from which it formed originated mostly from the region inside approximately 2 astronomical units. These bodies contained primarily non-carbonaceous material, meaning they were isotopically distinct from the carbonaceous meteorites originating from the outer asteroid belt and beyond. The limited contribution from outer solar system materials meant proto-Earth was relatively depleted in volatile elements and water compared to what it would later acquire. The bulk composition was dominated by iron, oxygen, silicon, and magnesium, the most abundant rock-forming elements. Iron comprised about 30% of proto-Earth's mass, mostly in the core. Oxygen, silicon, and magnesium together made up most of the mantle. Calcium, aluminum, sodium, potassium, and other elements appeared in smaller but significant quantities. Carbon, nitrogen, and water were present but scarce, delivered primarily by the fraction of impactors originating from farther out in the solar system where volatiles were more abundant. Constant bombardment. The environment was unimaginably violent. Proto-Earth experienced continuous impacts ranging from small meteorites to moon-sized bodies. The impact rate during peak accretion was thousands of times higher than in the modern solar system. Large impacts, those capable of excavating craters hundreds of kilometers across, occurred every few thousand years. Truly giant impacts with bodies comparable to Mars in size were rarer but catastrophic when they did occur. Each large impact delivered a massive energy pulse. A Mars-sized impactor carries kinetic energy equivalent to trillions of nuclear weapons. This energy was deposited in seconds to minutes, heating and vaporizing rock at the impact site. The impact created a fireball that expanded through the atmosphere, delivering radiative heat that could vaporize surface material on the opposite side of the planet. Ejector thrown into ballistic trajectories re-entered the atmosphere at high speed, heating up and raining back down as molten droplets. The impacts also affected proto-Earth's spin and orbital properties. Each impact delivered momentum, altering the planet's rotation rate and axis orientation. The cumulative effect of many impacts stirred proto-Earth's rotation in somewhat random ways. Large impacts could significantly change the rotation period and obliquity. The net angular momentum increased over time as impacts preferentially added angular momentum due to the geometry of accretion in a rotating disk. Growth toward a critical mass. Proto-Earth grew steadily toward its current mass. By the time it reached approximately 90% of present mass, it had swept up most of the large embryos in its feeding zone. However, significant material remained. Smaller planetary embryos survived in nearby orbits, some with masses comparable to Mars. Countless planetesimals littered the inner solar system, leftovers from the oligarchic growth phase. These bodies represented the remaining material from which Earth would accrete its final 10% of mass. One of these remaining embryos would deliver that final mass increment in spectacular fashion. This body, which scientists call Theia, orbited near proto-Earth. Theia had grown to approximately Mars size, roughly 10% of Earth's mass. For millions of years, it followed a stable orbit, possibly trapped in a Lagrange point of proto-Earth's orbit where gravitational forces created a stable configuration. Gravitational perturbations from other bodies or its own growth beyond a critical mass eventually destabilized this orbit. Theia began experiencing closer approaches to proto-Earth. Its orbit evolved chaotically, perturbed by repeated encounters. The orbital evolution proceeded over hundreds of thousands of years, gradually bringing Theia closer. Collision became inevitable. The two bodies were on a collision course that would fundamentally transform both, creating the Earth-Moon system and determining the final characteristics of the planet we inhabit. Proto-Earth had reached its peak, a nearly complete world awaiting its final transformation. The surface glowed with the heat of accretion. The interior had differentiated into a metallic core and silicate mantle. The atmosphere was thick with outgassed volatiles. The bombardment continued relentlessly, delivering material and energy. Everything that proto-Earth had become through 50 million years of accretion was about to be undone and remade in a single catastrophic event. The stage was set for the most important impact in Earth's history, the collision that would birth the Moon and create the world we recognize as Earth. Chapter 7: The Thia Impact, Birth of the Moon. The collision was not head-on, which proved fortunate for everything that would follow. Theia approached Proteus at an oblique angle, approximately 45 degrees from a direct strike. The Mars-sized body, containing roughly 10% of Earth's mass, slammed into Proteus at a velocity between 4 and 15 kilometers per second. This range of velocities represents different modeling scenarios, but all produce catastrophic results. The kinetic energy involved was incomprehensible, equivalent to roughly 100 million billion megatons of TNT. In an instant, approximately 4.51 billion years ago, both worlds were transformed beyond recognition. The impact vaporized rock, melted both bodies, ejected enormous amounts of material into orbit, and fundamentally reshaped what would become Earth. This was not merely a collision. It was a merger, a violent fusion of two planetary bodies that created the Earth-Moon system we know today. The moment of impact. Theia struck Proteus's surface at a grazing angle. The geometry of the impact determined everything that followed. A head-on collision would have resulted in complete mixing and likely prevented the formation of a large moon. A glancing blow at too shallow an angle would have caused Theia to rebound rather than merge. The actual impact represented a middle ground, energetic enough to thoroughly disrupt both bodies yet oblique enough to produce optimal conditions for moon formation. Impact sequence unfolded over several hours, but the most violent phases occurred within minutes. The initial contact point experienced pressures exceeding millions of atmospheres. Rock at the contact zone was instantly compressed, heated to temperatures above 10,000 Kelvin, and converted to plasma. This superheated vapor expanded explosively in all directions. A shock wave propagated through both bodies at speeds of tens of kilometers per second, heating and melting everything in its path. Theia did not survive as an intact body. The smaller impactor was completely destroyed, its core and mantle disrupted and merged with Proteus's mass. Theia's iron core, comprising perhaps 20% of its total mass, sank through the molten Proteus to merge with Earth's existing core. The process took hours to days as dense iron descended through lighter silicate material. Theia's mantle material, heated to incandescence by the impact, mixed with Proteus's outer layers and was ejected into space as part of the debris cloud. Proteus fared somewhat better structurally, but was fundamentally transformed. The impact excavated approximately 10 to 20% of Proteus's mantle, blasting enormous quantities of molten rock into orbit. The energy delivered by the collision remelted much of Proteus that had begun solidifying. The entire planet became a molten body once again, with surface temperatures reaching 4,000 to 7,000 Kelvin in the immediate aftermath. The solid Proteus that had existed for millions of years was erased, replaced by a roiling sphere of liquid rock. The debris disk forms. The impact ejected a massive amount of material into space. Computer simulations suggest that approximately 20% of Theia's mass ended up as an orbiting ring of debris around the post-impact Earth. This translates to roughly 2% of Earth's current mass, or about 2 lunar masses worth of material. The debris consisted of vaporized rock, molten droplets, and solid fragments ranging from dust-sized particles to kilometer-scale chunks. The debris did not escape into space entirely. Most of it remained gravitationally bound to Earth, forming a disk in orbit around the planet's equator. This circumterrestrial debris disk extended from just above Earth's surface, possibly as close as 2 to 3 Earth radii, out to perhaps 10 to 20 Earth radii or more. The disk was incredibly hot, glowing with thermal radiation from the vaporized and molten material. It formed rapidly within hours of the impact, as ejected material followed ballistic trajectories that intersected at various distances from Earth. The debris disk was not initially uniform or stable. Material ejected at different angles and velocities ended up in orbits with varying eccentricities and inclinations. The disk was clumpy and irregular, with concentrations of material in certain regions and gaps in others. Particles in the disk collided constantly, exchanging momentum and energy. These collisions caused some material to spiral inward and re-impact Earth, while other material moved outward. The narrowest point in the disk where debris was most concentrated, initially lay near the original collision point in Earth's orbit. However, precession of the debris particle orbits gradually shifted this concentration zone. Over time, the disk became more axisymmetric as collisions and gravitational interactions circularized orbits and damped eccentricities. The transition from a highly asymmetric, clumpy disk to a more uniform circular disk occurred over months to years. The Moon accretes. Within the hot debris disk, the Moon began to form. The process was remarkably rapid compared to planet formation timescales. Approximately 50% of the material that would eventually become the Moon accreted within the first few months after the impact. The remainder accumulated over the following years to decades. The entire Moon formation process, from impact to a fully formed Moon, probably took less than 100 years, possibly as little as a few years in the most rapid scenarios. The accretion mechanism combined several processes. In the inner portions of the disk, close to Earth, material spiraled inward and was reaccreted by Earth. Farther out, beyond approximately 3 to 4 Earth radii, material had sufficient angular momentum to remain in orbit. Here, gravitational instabilities caused the disk to clump. Dense regions attracted more material, growing through accretion while also clearing gaps in the disk. One clump grew faster than the others, sweeping up a disproportionate share of available material. This became the proto-moon. Its position in the disk, likely between 3 and 6 Earth radii initially, placed it in the optimal location to accrete efficiently while avoiding immediate re-impact with Earth. The proto-moon's growth was self-reinforcing. Larger size meant stronger gravity, which captured material from a wider region, causing even faster growth. The Moon did not accrete as a cold body. The debris disk was extraordinarily hot, with temperatures in the inner regions exceeding 4,000 Kelvin. Material accreting onto the proto-moon was molten or vaporized. Each collision released additional energy, heating the growing Moon further. The early Moon was completely molten, covered by a magma ocean hundreds of kilometers deep. This magma ocean would persist for millions of years, slowly cooling and crystallizing to form the lunar crust and mantle we see today. Angular momentum transfer. The giant impact had profound effects on Earth's rotation. Before the collision, proto-Earth likely rotated with a period of perhaps 5 to 10 hours, though the exact pre-impact rotation remains uncertain. The impact delivered enormous angular momentum. Thea's orbital angular momentum and its own rotation contributed to the system's total angular momentum budget. When Thea merged with proto-Earth, much of this angular momentum transferred to Earth's spin. After the collision, Earth rotated much faster than before. Models indicate a post-impact rotation period of approximately 2 to 5 hours. This means an Earth day lasted only a few hours immediately after the giant impact. The planet was spinning so rapidly that it became noticeably oblate, bulging significantly at the equator due to centrifugal forces. The rapid rotation contributed to the flattened shape of the debris disk, which formed in Earth's equatorial plane. The impact also established Earth's obliquity, the tilt of its rotation axis relative to its orbital plane. The angle and geometry of Thea's strike determined both the magnitude of Earth's rotation and the orientation of its spin axis. Computer simulations suggest that after the impact, Earth's equator and the Moon's orbit were coplanar, meaning the Moon initially orbited in Earth's equatorial plane. The current obliquity of 23.5 degrees developed later through subsequent gravitational perturbations. The Moon initially orbited much closer to Earth than it does today. Formation models place the early Moon at approximately 15,000 to 25,000 kilometers from Earth's center, corresponding to about 3 to 4 Earth radii. At this distance, Earth would have appeared enormous in the lunar sky, subtending an angle of 30 to 50 degrees. The tidal forces between Earth and Moon were tremendously strong due to the close proximity, causing significant tidal heating in both bodies. Tidal evolution. Immediately after formation, tidal interactions began transferring angular momentum from Earth's rotation to the Moon's orbit. The mechanism involves tidal bulges raised on Earth by the Moon's gravity. Because Earth rotates faster than the Moon orbits, the tidal bulge is carried slightly ahead of the Earth-Moon line. The offset bulge gravitationally pulls on the Moon, accelerating it in its orbit. This acceleration causes the Moon to gradually move to a higher, more distant orbit. Meanwhile, the gravitational pull of the offset bulge on Earth acts as a brake, slowing Earth's rotation. This tidal energy transfer has been operating continuously since the Moon formed. The early rate of transfer was much higher than today because tidal forces scale inversely with the sixth power of distance. When the Moon was half its current distance, tidal forces were 64 times stronger. The Moon migrated outward rapidly at first, perhaps moving from 20,000 kilometers to 40,000 kilometers in only the first 10 million years. As the Moon receded, Earth's rotation slowed correspondingly. The angular momentum lost by Earth's rotation was gained by the Moon's orbital motion. The total angular momentum of the Earth-Moon system has remained nearly constant, conserved except for small losses to solar tides and internal friction. The day length increased from the initial 2 to 5 hours to approximately 6 hours within the first billion years, and has continued lengthening at a decreasing rate ever since. Today, the day length increases by approximately 2 milliseconds per century due to ongoing tidal friction. Chemical implications. The giant impact had important consequences for Earth's chemistry. The extreme temperatures generated during the collision vaporized a significant fraction of both Proteus and Theia. Volatile elements, those with low boiling points, were preferentially lost to space during and after the impact. Elements like hydrogen, helium, carbon, and nitrogen were depleted, while refractory elements like calcium, aluminum, and titanium remained. The Moon inherited a composition reflecting the vaporization process. Compared to Earth, the Moon is depleted in volatile elements and enriched in refractory elements. This depletion signature has been observed in lunar samples returned by Apollo missions and is considered strong evidence for the giant impact hypothesis. The Moon also has a very small iron core, comprising only about 2% of its mass compared to Earth's 32%. This difference arises because the Moon formed primarily from the mantles of Proteus and Theia, with most iron having already segregated into cores before the impact. Isotopic evidence supports the impact hypothesis while also revealing complexities. Oxygen isotopes in lunar rocks are nearly identical to Earth's, suggesting the Moon formed from material isotopically similar to Proteus. This similarity was initially puzzling because models predicted the Moon should form mainly from Theia's mantle, which likely had a different isotopic signature. Recent models propose that the extreme energy of the impact caused thorough mixing and isotopic equilibration between Proteus and Theia material, explaining the similarity. Some isotopic systems do show differences between Earth and Moon. Potassium isotopes are slightly heavier in the Moon, consistent with volatile loss during the impact. Titanium and tungsten isotopes show subtle variations that may preserve information about Theia's composition and the impact dynamics. These isotopic clues help constrain the impact geometry, velocities, and mixing processes that occurred during the collision. A new world emerges. The Earth that emerged from the giant impact was fundamentally different from Proteus. It was larger, having incorporated Theia's mass. The merged planet contained approximately 1 Earth masses compared to Proteus' 0.9 Earth masses. It rotated much faster, completing 1 rotation every few hours. It was entirely molten from surface to core, with temperatures high enough to melt the most refractory minerals. It had a moon, a large satellite that would influence Earth's rotation, stabilize its obliquity, and drive tidal forces for billions of years. The impact reset many aspects of Earth's evolution. The geological record of Proteus was largely erased, with any primitive crust that had formed before the impact destroyed and remelted. The atmosphere was blown away or vaporized, requiring reconstruction through renewed outgassing. Water present on Proteus before the impact may have been lost, though some fraction likely survived in the deep interior and was later released through volcanism. Despite the violence, the giant impact was ultimately constructive. It gave Earth its rapid rotation, which would later slow to the 24-hour day that drives weather patterns and biological rhythms. It created the Moon, whose tidal forces have shaped Earth's oceans and whose gravitational stabilization of Earth's obliquity has maintained relatively stable climate conditions favorable for life. It thoroughly mixed and homogenized the material that would become Earth's mantle, establishing chemical reservoirs that persist to the present. The moon formed from this catastrophe stands as permanent evidence of Earth's violent birth. Every time we look up and see the moon in the sky, we are witnessing the result of the most significant impact event in our planet's history, a collision that determined much of what Earth would become. Chapter 8: Hell on Earth, the Molten Beginning. The newly formed Earth was incompatible with any form of life. Surface temperatures exceeded 1,200 degrees Celsius across the entire planet. The sky glowed red from thermal radiation, illuminated further by the incandescent magma ocean that stretched to every horizon. No solid ground existed anywhere on Earth. The surface was a roiling sea of molten rock, convecting violently as heat transporting from the interior to the thin radiative boundary layer at the top. This was the Hadean Aeon, named after Hades, the Greek underworld. The name was fitting. Earth resembled the mythological conception of hell more than anything recognizable as a planet capable of harboring life. This period, extending from Earth's formation at 4.54 billion years ago until approximately 4 billion years ago, represented the most extreme conditions Earth has ever experienced. Multiple heat sources. Several mechanisms heated early Earth to molten temperatures. Gravitational compression provided the first heat source. As material fell inward during Earth's accretion, gravitational potential energy converted to kinetic energy and then to heat upon impact. This process continued during the giant impact and its aftermath as Thea's core merged with Proto-Earth's core. The energy released by material falling through thousands of kilometers of gravity well was substantial, contributing significantly to early heating. Radioactive decay provided a persistent heat source that continues today, though much diminished. The early Earth contained higher concentrations of radioactive isotopes than it does now. Short-lived isotopes like aluminum-26, with a half-life of only 720,000 years, contributed intense heating during the first few million years, but decayed away rapidly. Long-lived isotopes like uranium-238, uranium-235, thorium-232, and potassium-40 provided sustained heating over billions of years. Current measurements indicate that approximately 20 terawatts of Earth's heat output comes from radioactive decay, about half of the total heat escaping from Earth's interior. The uranium-238 decay chain contributes roughly 8 terawatts, the thorium-232 decay chain another 8 terawatts, and potassium-40 decay approximately 4 terawatts. In the Hadean, these isotopes were approximately twice as abundant due to less time having passed for decay, meaning radioactive heating was roughly twice as intense as today. Combined with the additional contribution from short-lived isotopes, radioactive heating in the Hadean was substantial, perhaps 50 to 100 terawatts or more. The giant impact delivered the most concentrated burst of heat. The energy deposited during the collision between Proto-Earth and Theia instantly remelted much of Earth's outer layers. Models suggest that the impact energy was sufficient to vaporize portions of both bodies and completely melt Earth to depths of thousands of kilometers. This impact-generated heat was not immediately lost. It took millions of years for the heat to conduct outward and radiate into space, maintaining elevated temperatures long after the collision. The magma ocean depths. The exact depth of the magma ocean remains debated, but evidence suggests it was extensive. Traditional models proposed that the magma ocean extended through the entire mantle, reaching down to the core mantle boundary at approximately 2,900 kilometers depth. Such a whole mantle magma ocean would have contained about 5 times 10 to the power of 24 kilograms of molten rock, representing roughly 70% of Earth's total mass. Recent research suggests a more complex structure. The upper mantle was completely molten, forming a magma ocean extending to depths of perhaps 1,000 kilometers. Below this, increasing pressure raised melting points while temperature increases with depth were more gradual. This pressure-temperature relationship meant that at some depth, the rock's melting point exceeded the actual temperature, allowing partially solidified or fully solid rock to exist even in the Hadean. However, a basal magma ocean may have existed at the base of the mantle, just above the core mantle boundary. This basal magma ocean formed through different physics than the surface magma ocean. As the upper mantle cooled and crystallized, iron-rich minerals formed and sank due to their high density. These iron-rich solids accumulated in the lower mantle, where pressure and core heat caused them to remelt, forming a dense layer of iron-rich magma. Because this melt was denser than the surrounding solid mantle, even in liquid form, it did not rise. It remained trapped at the bottom, forming a basal magma ocean that may have persisted for hundreds of millions of years or longer. The surface magma ocean was vigorously convective. Temperature differences between the hot interior and the relatively cooler surface drove convection currents. Hot magma rose from depth, cooled at the surface by radiating heat to space, and sank again. The convection was turbulent, with velocities potentially reaching meters per second. The timescale for magma to cycle from surface to depth and back was perhaps thousands of years, ensuring relatively efficient heat transport despite the magma ocean's enormous volume. Differentiation continues. The iron catastrophe, the separation of metallic iron from silicate rock, continued after the giant impact. While much of Earth's core had already formed during Proto-Earth's development, Thea's core needed to merge with it. The iron from Thea's core descended through the molten silicate mantle as droplets and diapias, accumulating at Earth's center over timescales of thousands to tens of thousands of years. This process released additional gravitational energy. The rainout model describes how dense iron droplets fell through lighter silicate magma, converting potential energy to kinetic energy and then to heat through viscous dissipation. The heat release helped maintain the molten state of the mantle, creating a positive feedback where iron separation generated heat that kept the silicates molten, which allowed more efficient ion separation. Core formation was essentially complete by approximately 4.5 billion years ago, within 30 to 50 million years of solar system formation. The hafnium-tungsten chronometer constrains this timing. Hafnium-182 decays to tungsten-182 with a half-life of 9 million years. Hafnium is lithophile, preferring silicate phases, while tungsten is moderately siderophile, entering iron metal. When core formation occurred, tungsten was extracted from the mantle into the core. The tungsten isotopic composition of Earth's mantle preserves a record of when this extraction occurred, indicating core formation during the first 50 million years. The differentiated core consisted primarily of iron and nickel, with iron comprising about 85% and nickel about 10% by mass. The remaining 5% consisted of lighter elements that could dissolve in molten iron under core conditions. These light elements, possibly including sulfur, oxygen, silicon, carbon, and hydrogen, were necessary to explain the core's observed density, which is slightly lower than pure iron-nickel alloy would be. The exact identity and abundance of light elements in the core remain uncertain, but their presence affects core dynamics and the generation of Earth's magnetic field. Birth of the magnetic field. Earth's magnetic field likely began forming once the core achieved sufficient differentiation and convection. The field is generated by a dynamo process in the liquid outer core. Convection of electrically conducting molten iron, combined with Earth's rotation, creates electric currents that generate and sustain the magnetic field. The convection in the outer core was driven initially by thermal buoyancy. Heat flowing from the hot core into the overlying mantle created temperature gradients that drove fluid motion. As iron near the bottom of the outer core heated, it became less dense and rose. Cooler iron from above sank to replace it, creating convection cells. Earth's rotation deflected these flows through the Coriolis effect, organizing them into columnar structures aligned roughly parallel to the rotation axis. Later in Earth's history, compositional convection augmented thermal convection. As the inner core began crystallizing from the liquid outer core, pure iron preferentially solidified, leaving the remaining liquid enriched in light elements. This light element-enriched fluid was buoyed upward, driving compositional convection. However, in the Hadean, the core was likely entirely liquid and too hot for inner core crystallization to begin. The early dynamo probably operated purely through thermal convection. The strength and geometry of the Hadean magnetic field remain uncertain. Some models suggest a weaker field than today's, perhaps 10 to 50% of the current intensity. Others propose a stronger field due to more vigorous convection driven by higher heat flow. The field geometry may have been multipolar rather than dipolar in the earliest times, with multiple north and south poles rather than the simple two-pole structure we see today. As the dynamo matured and convection patterns organized, the field likely transitioned to a more stable dipolar configuration. Evidence for the timing of magnetic field onset is limited. The oldest preserved magnetic minerals are zircon crystals dated to 4.2 billion years ago that contain tiny magnetite inclusions, potentially recording an ancient magnetic field. However, interpreting these signals is challenging because the magnetite could have formed long after the host zircon crystallized. Direct evidence for the magnetic field strength and geometry in the Hadean remains scarce, requiring inference from models and extrapolation from later geological evidence. Atmospheric conditions. The post-impact atmosphere was thick and opaque. Outgassing from the magma ocean released enormous quantities of volatiles. Water vapor dominated, possibly comprising 50% or more of the atmospheric mass. Carbon dioxide was the second most abundant component, with nitrogen, methane, ammonia, hydrogen, and sulfur gases present in smaller amounts. The exact composition depended on the oxidation state of the magma, which controlled which chemical forms of carbon, nitrogen, and sulfur were stable. Atmospheric pressure may have been 10 to 100 times higher than today's 1 bar at the surface. This thick atmosphere had profound effects. The greenhouse effect was intense, with water vapor and carbon dioxide absorbing outgoing infrared radiation and trapping heat. Surface temperatures remained above 200 degrees Celsius even after the magma ocean began solidifying. The atmosphere was opaque to visible light, shrouded in a permanent haze of dust and vapor. Water could not exist as liquid on the surface. Temperatures exceeded water's critical point of 374 degrees Celsius throughout much of the Hadean. Above the critical point, water exists as a supercritical fluid with properties between liquid and gas. Only as temperatures declined below the critical point could water vapor condense into liquid droplets. The timing of this transition determined when oceans could first form. The atmosphere was continuously eroded by solar wind and ultraviolet radiation from the young sun. Hydrogen, the lightest element, escaped to space most readily. Ultraviolet photons dissociated water vapor into hydrogen and oxygen. The hydrogen escaped, while the oxygen reacted with reduced materials in the crust and atmosphere or was incorporated back into magma. This process gradually depleted the atmospheric water content, though outgassing from the interior replenished losses. Late heavy bombardment. The violence of the Hadean extended beyond internal heat. The solar system remained a chaotic shooting gallery, with countless asteroids and comets on unstable orbits. The late heavy bombardment, occurring approximately 4.1 to 3.8 billion years ago, represented a spike in impact rates near the end of the Hadean. During this period, the impact rate increased by perhaps 10 to 100 times above the background level, delivering enormous numbers of asteroids to the inner solar system. The cause of the late heavy bombardment is debated. One hypothesis involves the orbital migration of the giant planets, particularly Jupiter and Saturn. As these planets moved, their gravitational influence destabilized the asteroid belt, scattering countless asteroids onto Earth-crossing orbits. Another hypothesis proposes the collisional breakup of a large main belt asteroid, producing a family of fragments that subsequently impacted the terrestrial planets. A third model invokes a now-lost fifth giant planet, Planet V, whose encounters with other bodies scattered asteroids before the planet itself was ejected from the solar system. Regardless of the cause, the effects were dramatic. Large impacts, those producing craters exceeding 1,000 kilometers in diameter, occurred on Earth several times during the late heavy bombardment period. Some of the largest impacts may have been energetic enough to evaporate portions of any early oceans that had formed, sterilizing the surface and forcing life, if it had emerged, to retreat to underground refugia. The late heavy bombardment was not entirely destructive. Impactors delivered volatiles including water, organic compounds, and atmospheric gases. Carbonaceous asteroids and comets were particularly rich in these materials. The delivered water may have constituted a significant fraction of Earth's eventual ocean mass, supplementing outgassed water from the interior. Organic compounds, including amino acids and other prebiotic molecules, were delivered intact or synthesized in impact plumes, providing raw materials that would later enable life's origin. The Hadean landscape. Despite the hellish name, the Hadean was not uniformly violent throughout its 500-million-year duration. Conditions moderated with time as radioactive isotopes decayed, impact rates declined, and heat radiated to space. The magma ocean began solidifying from the bottom up as pressure-induced increases in melting point exceeded cooling rates in the deep interior. Simultaneously, it crystallized from the top down as surface cooling proceeded through efficient radiation. The first solid crust that formed was likely mafic, rich in iron and magnesium, compositionally similar to basalt. This primitive crust was thin and unstable, constantly disrupted by impacts and volcanic activity. It fractured and foundered back into the magma ocean, recycling repeatedly. No Hadean crust survives today. The oldest preserved crustal rocks date to about 4 billion years ago, marking the end of the Hadean and the transition to the Archean eon. Despite the lack of preserved rocks, tiny zircon crystals provide windows into Hadean conditions. Zircons are extremely resistant to weathering and melting, allowing them to survive when their host rocks do not. The oldest known zircons, from the Jack Hills region of Western Australia, crystallized 4.4 billion years ago. Oxygen isotope ratios in these ancient zircons suggest they formed from magma that had interacted with liquid water. This finding implies that surface temperatures had dropped below water's boiling point by at least 4.4 billion years ago, allowing liquid water to exist and potentially forming the first oceans only 150 million years after Earth formed. The Hadean Earth was transforming from a molten ball into a world with solid crust, liquid oceans, and an atmosphere capable of supporting the chemical reactions that would eventually lead to life. The worst extremes had passed. The stage was being set for the next phase of Earth's evolution, when the planet would cool enough to maintain permanent oceans and continents, establishing stable surface conditions for the first time. Chapter 9. The First Crust Solidifies. The magma ocean could not last forever. Heat radiated into the cold vacuum of space at a rate determined by the Stefan-Boltzmann law, which dictates that energy loss increases with the fourth power of temperature. The hotter Earth became, the more efficiently it shed heat to space. This fundamental physics principle ensured that even the most intense heating eventually gave way to cooling. The magma ocean that had dominated Earth's surface for millions of years gradually solidified as the cooling process won out over heat inputs from impacts, radioactive decay, and core formation. Solid crust appeared for the first time, creating islands of stability in an otherwise molten world. The oldest surviving evidence of this crust comes from microscopic zircon crystals found in Western Australia, dated to 4.4 billion years ago. These tiny time capsules reveal that Earth cooled far faster than previously thought, forming a solid crust only 160 million years after the solar system began. Crystallization begins. The magma ocean did not solidify uniformly. Crystallization proceeded from multiple directions simultaneously based on the temperature and pressure profiles within Earth. At the surface, efficient radiative cooling lowered temperatures below the melting points of the most refractory minerals. Olivine, a magnesium ion silicate with formula Mg2CO4 to Fe2CO4, crystallized first at temperatures around 1,700 degrees Celsius. These olivine crystals were denser than the surrounding melt and sank, removing magnesium and iron from the upper magma ocean while enriching it in aluminum, calcium, and sodium. As olivine sank and accumulated in the lower mantle, the remaining melt became progressively enriched in incompatible elements, those that preferentially stay in the liquid phase rather than entering crystalline structures. This process, called fractional crystallization, changed the magma ocean's composition over time. The evolving melt produced different minerals as crystallization continued. Pyroxene, another magnesium iron silicate, followed olivine. Plagioclase feldspar, a calcium-sodium-aluminum silicate, crystallized at lower temperatures. Unlike the dense mafic minerals that sank, plagioclase was less dense than the melt and floated upward. The floating plagioclase accumulated at the magma ocean's surface, forming a primitive anorthositic crust. This crust was composed primarily of the mineral anorthite, a calcium-rich member of the plagioclase family. The lunar highlands preserve this type of crust beautifully, having formed through an identical process on the Moon's smaller magma ocean. On Earth, however, this primitive anorthositic crust was continuously disrupted by ongoing impacts and volcanic activity, preventing large-scale preservation. The timescale for magma ocean solidification depended on its depth and the cooling rate. Models suggest that a magma ocean several hundred kilometers deep would solidify in approximately 10 to 100 million years. This relatively rapid cooling was possible because of the efficient heat loss at the surface. The solid crust that formed acted as an insulating layer, slowing subsequent cooling of the mantle below. This created a negative feedback where crust formation reduced cooling rates, extending the time needed for complete solidification of the deeper mantle. The Jack Hills zircons. The oldest evidence for solid crust comes from zircon crystals extracted from the Jack Hills region of Western Australia. These crystals, embedded within much younger sedimentary rocks, date to 4.4 billion years ago, confirmed through uranium-lead radiometric dating. Zircon incorporates uranium into its crystal structure when it forms, but excludes lead. The uranium radioactively decays to lead over time with known half-lives. By measuring the ratio of uranium isotopes to lead isotopes, scientists determine how much time has elapsed since the zircon crystallized. The Jack Hills zircons survived when their host rocks did not, because zircon is extraordinarily durable. It resists chemical weathering, mechanical abrasion, and even high-temperature metamorphism that would destroy most minerals. When the granite or granodiorite rocks that originally contained these zircons eroded away billions of years ago, the resistant zircons remained. They were transporting by rivers, deposited in sedimentary basins, and eventually incorporated into younger rocks. Multiple cycles of erosion, transport, and deposition could not destroy them, allowing them to survive for 4.4 billion years to deliver their message to modern scientists. The oxygen isotope composition of these ancient zircons provides critical information about formation conditions. Oxygen has 3 stable isotopes with atomic masses 16, 17, and 18. The ratio of oxygen 18 to oxygen 16, expressed as delta 18O, varies depending on temperature and the presence of water. Zircons that crystallize from dry, mantle-derived magmas have delta 18O values around 5 to 6 per mil. The Jack Hills zircons, however, show delta 18O values around 6 to 7 per mil, indicating they formed from magma that had interacted with water at Earth's surface. This finding has profound implications. For the parent magma to interact with surface water, 2 conditions must have been met. First, liquid water had to exist on Earth's surface, meaning temperatures had dropped below water's boiling point. Second, crustal rocks had to exist to be weathered by water, then melted and recrystallized to form the zircons. The oxygen isotope evidence suggests that by 4.4 billion years ago, Earth possessed both a solid crust and liquid water oceans. The hellish conditions of the early Hadean had already moderated to something approaching habitability only 160 million years after the solar system formed. Continental crust formation. The primitive basaltic crust that formed first was not like modern continental crust. Basalt is rich in iron and magnesium, dark-colored, and relatively dense with specific gravity around 3. Continental crust, in contrast, is rich in silicon and aluminum, light-colored and less dense with specific gravity around 2.7. This density difference is crucial because it allows continental crust to float higher on the mantle, forming elevated landmasses above sea level. Recent research suggests that extensive felsic continental crust formed surprisingly early, potentially accounting for up to 50% of present-day continental mass by 4.4 to 4.5 billion years ago. This discovery challenges the traditional view that continents grew slowly over billions of years through gradual accumulation. The mechanism for producing this early continental crust involved interactions between water and primitive crustal rocks. When seawater infiltrated the hot primitive crust, chemical reactions occurred that hydrated the ultramafic and mafic minerals. The process of serpentinization converted olivine and pyroxene into serpentine minerals by incorporating water into the crystal structure. These hydrated rocks, when subsequently heated through burial or proximity to magma chambers, underwent partial melting at lower temperatures than dry rocks. The melts produced were enriched in silica, aluminum, and alkali elements, creating felsic magmas similar in composition to granite. This water-rock interaction at shallow depths, less than 20 kilometers, allowed for efficient production of felsic crust in the Hadean. The process required a hydrosphere to provide water and a heat source to drive melting. Volcanism associated with early tectonic processes supplied the heat. The abundant water delivered by carbonaceous asteroids and outgassed from the interior provided the aqueous component. The combination allowed for rapid generation of continental-type crust far earlier than previously considered possible. The hafnium isotope evolution of Hadean zircons worldwide supports this scenario. Hafnium isotopes trace the age of the crustal material from which the zircon's parent magmas derived. The isotopic signatures indicate that by 4.4 billion years ago, a substantial volume of evolved continental crust already existed. This crust formed the substrate from which later granitic magmas were extracted, recorded in the zircons that survived to the present. Crustal instability. The early crust was not stable like modern continental crust. It was thin, perhaps only a few kilometers thick in most places. It was constantly disrupted by impacts that punctured it, creating pathways for magma to erupt onto the surface. Volcanic activity was far more intense than today because the mantle was hotter and heat production from radioactive decay was approximately double current levels. Mantle plumes, rising columns of hot rock, frequently broke through the weak crust, resurfacing areas with fresh lava flows. The crust also underwent continuous recycling. The intense impact bombardment of the Hadean fragmented crustal rocks, mixing them with impact melt and ejecta. Subsequent volcanism melted and reprocessed this material. Any given piece of crust likely cycled between solid rock, molten magma, and fragmented debris multiple times over millions of years. This recycling explains why no intact Hadean crustal rocks survive. Only the most durable mineral grains, especially zircons, persisted through multiple cycles of destruction and reformation. Tectonic processes may have begun operating in primitive form during the Hadean. The hot mantle convected vigorously, and the thin crust responded by fracturing and deforming. Whether true plate tectonics with subduction and seafloor spreading operated this early remains debated. The hot mantle would have produced weak, easily deformable crust that might have behaved differently than the cold, rigid plates that characterize modern plate tectonics. Some models propose a stagnant lid regime where the crust formed a single global shell that occasionally overturned or foundered rather than breaking into distinct plates. Other evidence suggests protocontinents may have begun forming scattered island chains that rose above the global ocean. These islands would have been volcanic in origin, similar to modern oceanic island chains like Hawaii. Where volcanic activity was particularly intense or long-lived, sufficient magma accumulated to build substantial landmasses. These embryonic continents were likely small, perhaps the size of Greenland or Madagascar, rather than modern continents. They would have been unstable, subject to erosion, subsidence, and destruction by impacts. Zircon insights into habitability. Some Jack Hill's zircons show evidence of forming in the presence of fresh water rather than seawater. The distinction comes from oxygen isotope analysis. Seawater contains heavier oxygen isotopes because lighter isotopes preferentially evaporate. Rainwater and fresh water on land have lighter isotopic compositions. Zircons with particularly light oxygen isotope signatures suggest their parent magmas interacted with fresh water. This finding indicates that by 4 billion years ago, and possibly as early as 4.4 billion years ago, Earth had not only oceans, but also land exposed above sea level and a hydrological cycle with evaporation and precipitation. Water evaporated from the oceans, formed clouds, and rained onto land, creating freshwater rivers and lakes. These freshwater systems would have provided the light oxygen isotope signature recorded in some zircons. The existence of exposed land and fresh water has important implications for the origin of life. Many prebiotic chemistry scenarios require concentration mechanisms, where dilute organic compounds in the ocean become concentrated enough to react and form more complex molecules. Evaporative ponds on land surfaces, where water evaporates and leaves dissolved compounds behind, provide ideal concentration environments. Tidal pools, volcanic hot springs, and impact crater lakes could have served as chemical reactors where the building blocks of life assembled. The rapid appearance of habitable conditions challenges the perception of the Hadean as uniformly hellish. While the first 100 to 200 million years after Earth's formation were indeed extreme, conditions moderated surprisingly quickly. By 4.4 billion years ago, Earth had cooled enough to support liquid water, solid crust, and possibly even the chemical precursors to life. The window for life's origin opened much earlier than once thought, potentially beginning in the late Hadean rather than waiting for the more benign conditions of the Archean. Surface conditions. The landscape of the late Hadean was alien yet strangely familiar in some respects. The sky was different, likely orange or reddish from a thick atmosphere rich in carbon dioxide and water vapor. Atmospheric pressure was higher than today, perhaps several times current levels. The greenhouse effect maintained relatively warm surface temperatures despite the sun being about 25% fainter than it is now, a puzzle known as the faint young sun paradox. Volcanic activity dominated the scenery. Thousands of active volcanoes dotted the landscape, erupting frequently to build volcanic islands and replenish the atmosphere with gases from the interior. Lava flows created vast basaltic plains. Volcanic ash fell continuously in some regions, accumulating in layers that would eventually become sedimentary rocks. The air smelled of sulfur from volcanic emissions. Lightning was common, both from volcanic plumes and from weather systems in the thick, humid atmosphere. The ocean was global but shallow, covering most of Earth's surface to depths of perhaps a few kilometers on average. Isolated volcanic islands and small protocontinents broke the monotonous water surface. The water was likely warm, heated from below by the hot crust and from above by the greenhouse atmosphere. Ocean chemistry was different from today, probably more acidic due to dissolved carbon dioxide and enriched in dissolved iron, giving the water a greenish tint. The moon loomed enormous in the sky, still much closer than today. It appeared perhaps 3 to 5 times larger than we see it now, dominating the sky as it orbited Earth every few hours. Tides were extreme, with water levels rising and falling by hundreds of meters twice per day. These megatides stirred the oceans vigorously, mixing nutrients and preventing stratification. Coastal regions alternated between being underwater and exposed to air on timescales of hours, creating harsh environments where only the most resilient prebiotic chemistry could operate. Setting the stage. The formation of the first solid crust marked a crucial transition in Earth's evolution. The molten planet of the early Hadean was transforming into a world with distinct surface features, environments, and chemical gradients. Solid crust provided stable substrates where materials could accumulate rather than immediately sinking into magma. Water could pool in depressions, creating isolated chemical environments. Temperature gradients between hot volcanic regions and cooler ocean floors created diverse niches where different reactions could proceed. The zircon evidence demonstrates that these habitable conditions appeared far earlier than previously thought, only 150 to 200 million years after the solar system formed. This rapid transition from molten ball to potentially habitable planet compressed the timeline for life's origin. Rather than waiting billions of years for conditions to improve, the stage for life was set surprisingly quickly. The next question becomes not when Earth became habitable, but when did water accumulate into oceans, and what were those early oceans like? Chapter 10. Water arrives on Earth. Every drop of water on Earth came from somewhere else. The hydrogen and oxygen atoms making up water molecules originated in different places and times across cosmic history. Hydrogen nuclei formed in the Big Bang 13.8 billion years ago, representing the most ancient atoms in existence. Oxygen atoms were forged in the cores of massive stars that lived and died billions of years before our solar system formed, released into space through supernova explosions. These atoms eventually found each other in the cold molecular clouds where stars and planets form, bonding into water molecules through chemical reactions on the surfaces of dust grains. Understanding how this water reached Earth, when it arrived, and in what quantities reveals fundamental aspects of our planet's development and its capacity to host life. Multiple sources. Water arrived on Earth through multiple delivery mechanisms operating at different times. The first delivery occurred during Earth's initial accretion. The planetesimals that collided to build proto-Earth were not completely dry. Even bodies forming in the hot inner solar system contained water molecules bound within mineral structures or absorbed onto grain surfaces. This accretion stage water was incorporated directly into Earth's mass as the planet grew. Carbonaceous chondrites represent the most likely primary source of Earth's water. These primitive meteorites, which formed in the outer asteroid belt beyond approximately 2.5 astronomical units, contain up to 10% water by mass locked in hydrated minerals like clays and serpentine. The hydrogen isotope ratio in carbonaceous chondrites, measured as the deuterium to hydrogen ratio or DH ratio, matches ocean water remarkably well. This isotopic similarity provides strong evidence that bodies similar to carbonaceous chondrites delivered most of Earth's water. The asteroid Vesta, one of the largest bodies in the main belt, shows the same hydrogen isotopic composition as carbonaceous chondrites and Earth. This finding indicates that water-bearing asteroids were common in the asteroid belt region. As the giant planets formed and migrated, their gravity scattered asteroids throughout the inner solar system. Many of these asteroids collided with Earth, delivering their water cargo. The continuous bombardment during Earth's first 500 million years brought substantial water to the growing planet. Comets, once considered the primary water source, actually contributed relatively little to Earth's oceans. Comets form in the cold outer solar system beyond the orbit of Neptune. They contain abundant water ice, up to 50% or more by mass. However, measurements of comet DH ratios show they are significantly higher than Earth's ocean water, typically by factors of 2 or more. Using these DH ratios, models predict that less than 10% of Earth's water came from comets. The bulk arrived via asteroidal material from the inner regions of the asteroid belt, where DH ratios match Earth's composition. Volcanic outgassing. Not all of Earth's water came from external sources. Significant amounts were outgassed from the interior through volcanic activity. When planetesimals accreted to form Earth, any water they contained was incorporated into the growing planet. Much of this water dissolved in the magma ocean, held in solution by high pressure. As the magma ocean cooled and began to crystallize, water became increasingly incompatible with the forming minerals and concentrated in the remaining liquid. Volcanic eruptions brought this interior water to the surface. Magma rising from depth depressurizes as it ascends, causing dissolved volatiles, including water vapor, to exsolve and form bubbles. These bubbles expand violently, driving explosive eruptions that inject water vapor directly into the atmosphere. The process continues today, though at much lower rates than in the Hadean. Modern volcanism releases approximately 0.2 cubic kilometers of water per year, an amount that seems small but accumulates significantly over geological time. In the Hadean, volcanic outgassing rates were much higher due to more intense mantle convection and higher internal heat production. Estimates suggest that volcanic activity could have outgassed an ocean's worth of water, roughly 1.4 billion cubic kilometers, within the first few 100 million years. This internally sourced water combined with water delivered by impactors to build Earth's total water inventory, currently estimated at approximately 1.4 billion cubic kilometers in the oceans, plus additional water in the crust, mantle, and atmosphere. The atmosphere immediately after the giant impact was dominated by water vapor and carbon dioxide released from the vaporized and molten rock. This rock vapor atmosphere contained silicate species like CO and O2 along with sodium vapor. As it cooled over approximately 1,000 years, the silicates rained out according to their condensation temperatures, eventually leaving an atmosphere composed primarily of H2O, CO2, and smaller amounts of nitrogen, methane, and ammonia. This secondary atmosphere formed from outgassed volatiles and delivered materials replaced the primordial hydrogen-helium atmosphere that had escaped to space. The timing question. Determining exactly when water arrived on Earth remains challenging because multiple delivery mechanisms operated simultaneously. The distinction between water arriving and oceans forming is important. Water molecules were present from the beginning of Earth's accretion, incorporated into the planetesimals that built the planet. However, this water could not exist as liquid on the surface until temperatures dropped sufficiently and enough water had accumulated. Recent studies suggest Earth formed as a wet planet with water incorporated from the start, rather than as a dry planet that later acquired water. This conclusion comes from comparing hydrogen and nitrogen isotope ratios between Earth and potential source materials. The isotopic signatures indicate that water and other volatiles were present in the materials that accreted to form Earth rather than being added later through a late veneer of cometary or asteroidal impacts. The Vesta measurements support this scenario. Vesta, which formed very early in solar system history within the first few million years, already contained water with Earth-like isotopic composition. This indicates that water was present in the planet-forming region from the beginning, available to be incorporated into growing planets. Earth accreted this water continuously throughout its formation rather than remaining dry until some later delivery event. However, the surface conditions did not allow liquid water to persist until temperatures declined below water's critical point. The zircon evidence places this transition at approximately 4.4 billion years ago, suggesting that liquid water appeared on the surface within 150 million years of Earth's formation. This represents a remarkably rapid cooling, transitioning from a molten magma ocean to a planet with liquid water in less time than it takes modern continents to drift a few thousand kilometers. The first rains. As Earth's surface cooled below water's critical temperature, the water vapor-dominated atmosphere began to condense. The transition from a thick steam atmosphere to one where water could exist as liquid marked one of Earth's most important thresholds. Rain fell for the first time, probably as a torrential downpour that lasted for millions of years as the atmosphere surrendered its water vapor burden to form surface oceans. The rainfall was unlike anything occurring on modern Earth. The atmospheric pressure was much higher, perhaps 10 to 100 times current levels. The high pressure raised water's boiling point, allowing liquid water to exist at temperatures well above 100 degrees Celsius. The rain fell as hot, high-pressure droplets that would have been scalding by modern standards, yet represented a dramatic cooling from the earlier superheated steam atmosphere. The rain carved channels into the newly solidified crust, creating the first river systems. Water collected in topographic lows, forming the first lakes and ponds. As rainfall continued over millions of years, these isolated bodies of water expanded and merged, gradually filling the planet's basins to create a global ocean. The process was not smooth or steady. Large impacts periodically vaporized portions of the forming ocean, sending water back into the atmosphere as steam. The water subsequently recondensed and fell again as rain, cycling between ocean and atmosphere repeatedly. Ocean formation. By approximately 4.4 billion years ago, enough water had accumulated on Earth's surface to form substantial oceans. The zircon evidence indicates liquid water existed at this time, though the extent and depth of oceans remain uncertain. Initially, the ocean was likely shallow, covering most of Earth's surface to depths of perhaps a few kilometers. The crust had not yet differentiated into deep ocean basins and high continental platforms. Instead, Earth resembled a water world with a relatively uniform ocean covering almost the entire surface, except for scattered volcanic islands. The ocean's chemistry was radically different from modern seawater. Dissolved iron was abundant, giving the water a greenish color. The iron came from volcanic emissions and from dissolution of iron-rich basaltic crust. In the modern ocean, iron immediately oxidizes and precipitates because oxygen is abundant. In the Hadean Ocean, oxygen was absent, allowing ferrous iron to remain dissolved in high concentrations. The ocean was acidic, with pH probably around 5 to 6, compared to today's slightly alkaline pH of 8.1. The acidity resulted from dissolved carbon dioxide from volcanic outgassing and from reactions between water and sulfur gases producing sulfuric acid. The high CO2 concentration also meant the ocean contained abundant carbonic acid. This acidic condition enhanced weathering of crustal rocks, extracting calcium, magnesium, sodium, and potassium that accumulated in the ocean as dissolved ions. Salinity was probably lower than modern seawater initially because insufficient time had passed for salts to accumulate through weathering. The ocean started relatively fresh, gaining its salt content gradually as rivers delivered weathering products from land and as hydrothermal vents at seafloor spreading centers leached ions from crustal rocks. The process of salinity increase continued throughout the Archean, eventually reaching concentrations similar to modern seawater by approximately 3 billion years ago. Late heavy bombardment impacts. The formation of stable oceans faced a severe challenge from the late heavy bombardment between 4.1 and 3.8 billion years ago. During this period, the impact rate spiked dramatically, with numerous large asteroids striking Earth. Some impacts were energetic enough to evaporate significant fractions of the ocean, temporarily sterilizing the surface. Computer models show that impacts by bodies 200 to 500 kilometers in diameter would have vaporized the upper several hundred meters of ocean, creating a steam atmosphere. Smaller impacts would have excavated massive craters and heated surrounding water to boiling. The largest impacts might have evaporated a substantial portion of the total ocean volume, forcing any emerging life to survive in deeper water or in subsurface hydrothermal systems. However, recent three-dimensional computer models suggest that much of Earth's deep crust and the microbes potentially living in it could have survived the bombardment. While the surface would have been repeatedly sterilized by ocean vaporizing impacts, hydrothermal vent systems below the seafloor could have provided refugia for thermophilic microbes. These deep subsurface environments, heated by volcanic activity and shielded by kilometers of rock, maintained relatively stable conditions even when the surface was being devastated. The bombardment, paradoxically, may have aided the origin of life even while threatening to extinguish it. Impact craters created ideal environments for prebiotic chemistry. The impacts fractured the crust, creating pathways for water to circulate deeply and become heated by contact with hot rocks. These impact-induced hydrothermal systems contain diverse minerals, including clays, zeolites, and metal sulfides, that could catalyze organic synthesis reactions. The crater depressions collected water, creating isolated chemical reactors where compounds could concentrate through evaporation. Impact events also delivered organic compounds directly to Earth. Carbonaceous asteroids contain amino acids, nucleobases, sugars, and other prebiotic molecules synthesized in the interstellar medium or on the asteroid parent bodies. These compounds survived impact delivery in some cases, particularly in smaller, lower-velocity impacts. The continuous rain of organic-rich material provided raw materials for the chemical evolution leading to life. Water volume and distribution. The total amount of water on Earth today is approximately 1.4 billion cubic kilometers, with about 97% in the oceans and the remainder in ice, groundwater, lakes, rivers, atmosphere, and biosphere. How much water Earth possessed in the Hadean remains uncertain. The planet may have had more water than today, with subsequent loss to space through hydrogen escape. Alternatively, water may have continued accumulating throughout the Hadean and Archean through ongoing impacts and outgassing, reaching current levels only after 1 billion years or more. Evidence suggests that by the start of the Archean eon at 4 billion years ago, oceans already covered much of Earth. These early oceans were extensive enough to leave evidence in the oldest preserved sedimentary rocks. Pillow basalts, which form when lava erupts underwater, appear in 3.8 billion-year-old rocks in Greenland, demonstrating that deep water existed at that time. Stromatolites, layered structures formed by microbial mats in shallow water, appear in 3.5 billion-year-old rocks in Australia, indicating that shallow marine environments already existed. The distribution of water between surface reservoirs and interior reservoirs also remains debated. Current estimates suggest the mantle contains one to several ocean masses of water dissolved in high-pressure minerals. This interior water cycles between the mantle and surface through volcanic outgassing and subduction. In the Hadean, when volcanic activity was more intense and crust was being continuously created and destroyed, water cycling rates were higher. The balance between water stored in the mantle versus water present in surface oceans may have fluctuated over time, complicating attempts to determine total water abundance from surface observations alone. Life's essential ingredient. The arrival and accumulation of water fundamentally enabled Earth to become a living world. Water possesses unique properties that make it essential for life as we know it. It is an excellent solvent, dissolving a wide range of compounds and allowing them to move and react. It has a high heat capacity, moderating temperature fluctuations. It is less dense as a solid than as a liquid, causing ice to float, which prevents oceans from freezing solid from the bottom up. Water molecules are polar, allowing them to form hydrogen bonds that stabilize biological molecules like proteins and nucleic acids. Without water, the chemistry needed for life could not proceed. Organic synthesis reactions, the assembly of small molecules into larger biological polymers, typically require aqueous environments. Metabolism, the extraction of energy from chemical reactions, depends on water as a medium for transporting reactants and products. Reproduction and evolution require aqueous environments for molecules to interact and for genetic information to be copied and transmitted. The early appearance of liquid water on Earth, by 4.4 billion years ago according to zircon evidence, opened the possibility for life to emerge much earlier than once thought. Instead of waiting until the end of the late heavy bombardment at 3.8 billion years ago, life could potentially have begun forming even before 4 billion years ago. The earliest life would have faced harsh conditions and periodic extinction from large impacts, but the fundamental requirements of water, organic compounds, and energy were present from very early in Earth's history. The stage was set for the origin of life. Chapter 11: Late Heavy Bombardment. Between 4.1 and 3.8 billion years ago, the inner solar system transformed into a cosmic shooting gallery. The impact rate, which had been steadily declining since the planets finished forming, suddenly spiked to levels hundreds of times higher than before. This period, called the Late Heavy Bombardment, delivered approximately 22,000 impacts, creating craters larger than 20 kilometers across Earth's surface. Around 40 impacts produced basins roughly 1,000 kilometers in diameter. Several catastrophic collisions excavated basins approaching 5,000 kilometers across, large enough to span from New York to Los Angeles. These were not gentle encounters. Each major impact released energy equivalent to billions of nuclear weapons, vaporizing rock, boiling oceans, and potentially sterilizing vast regions of Earth's surface. The Late Heavy Bombardment represented the final major episode of planetary violence before Earth could settle into more stable conditions that would eventually allow life to establish a permanent foothold. Evidence from the Moon. The primary evidence for the late heavy bombardment comes from lunar samples returned by Apollo astronauts. These rock samples, collected from various locations on the Moon's surface, underwent isotopic dating using uranium lead and argon-argon techniques. The results revealed something unexpected. Rather than showing a smooth distribution of ages spanning billions of years, the impact-melted rocks clustered tightly around 3.9 to 3.8 billion years ago. This narrow time window suggested that a disproportionate number of large impacts occurred during this brief 100 million year period. The Moon preserves impact history better than Earth because it lacks plate tectonics, erosion, and active volcanism that would erase or obscure craters. The lunar highlands, covering roughly 83% of the Moon's surface, are saturated with craters from this bombardment. The maria, the dark smooth plains visible from Earth, formed when massive impacts fractured the lunar crust deeply enough to allow mantle basalts to erupt and flood the newly formed basins. The largest of these impact basins, like Mare Imbrium, Serenitatis, and Crisium, all date to the late heavy bombardment period. Extrapolating the lunar cratering rate to Earth, which has a surface area 13 times larger and gravitational cross-section about 20 times greater than the Moon, indicates Earth experienced far more impacts during this period. The bombardment would have completely covered Earth's surface with craters. Every square kilometer would have been struck multiple times by projectiles large enough to excavate significant craters. The largest impacts would have been felt globally, with seismic waves traveling through the entire planet and ejecta raining down worldwide. Causes of the bombardment. Several hypotheses attempt to explain why the impact rate suddenly increased 600 million years after the solar system formed. The Nice model, named after the French city where it was developed, remains the most widely accepted explanation. This model proposes that the giant planets, Jupiter, Saturn, Uranus, and Neptune, formed in different orbits than they currently occupy and underwent orbital migration that destabilized the asteroid belt and scattered countless bodies into the inner solar system. According to the Nice model, Jupiter and Saturn began in a resonant configuration where their orbital periods had a simple integer ratio. For hundreds of millions of years, they remained in this stable resonance. However, gravitational interactions with the remaining planetesimals beyond Neptune's orbit gradually perturbed the giant planets' orbits. Eventually, Jupiter and Saturn crossed a critical resonance threshold, triggering a period of rapid orbital migration. Jupiter moved slightly inward, while Saturn, Uranus, and Neptune moved outward. This migration had catastrophic consequences for the asteroid belt. As the planets' orbits shifted, their gravitational resonances swept through different regions of space. The new 6 secular resonance, in particular, crossed the asteroid belt, destabilizing countless asteroids. These asteroids were kicked into eccentric, highly elliptical orbits that crossed the paths of the terrestrial planets. Over the next few million years, these displaced asteroids bombarded Mercury, Venus, Earth, and Mars, creating the spike in impact rate observed in the lunar rock record. The planetary migration also disrupted the Kuiper belt beyond Neptune. As Neptune migrated outward, it scattered icy bodies throughout the outer solar system. Some were ejected from the solar system entirely. Others were thrown onto highly elliptical orbits that brought them into the inner solar system as long-period comets. Evidence suggests that comets contributed significantly to the late heavy bombardment, possibly delivering more total mass than asteroids. Alternative hypotheses. Other explanations for the late heavy bombardment have been proposed, though none has gained the same level of acceptance as the Nice model. The Planet V hypothesis suggests that a fifth terrestrial planet once existed between Mars and the asteroid belt. This hypothetical world, dubbed Planet V, had a mass between the Moon and Mars. For hundreds of millions of years, it maintained a stable orbit. Eventually, gravitational perturbations from the other terrestrial planets destabilized Planet V's orbit, causing it to plunge into the asteroid belt. According to this scenario, Planet V scattered asteroids throughout the inner solar system before ultimately crashing into the Sun or being ejected from the solar system. Computer simulations show that such an event could produce the observed spike in impact rate, provided the asteroid belt was heavily concentrated toward its inner edge at the time. The hypothesis remains speculative because Planet V left no surviving trace, making it difficult to test directly. Another hypothesis proposes that the late heavy bombardment resulted from the collisional breakup of a large Mars-crossing asteroid. A vesticized body, one of the remnants from the initial period of planet formation, orbited on a path that crossed Mars' orbit. Eventually, this body experienced a catastrophic collision that shattered it into thousands of fragments. These fragments, now on slightly different orbits, continued crossing the terrestrial planet's paths, creating an enhanced bombardment lasting tens of millions of years. Some researchers question whether a true spike in impact rate occurred at all. They argue that the apparent clustering of lunar impact ages might represent a statistical artifact caused by biased sampling. The Apollo missions collected rocks primarily from regions near large impact basins. These basins ejected material across vast distances, scattering impact melt far from the source craters. When astronauts collected samples, they unknowingly gathered multiple pieces of ejecta from the same few large impacts rather than sampling independent events from across billions of years. If this interpretation is correct, the late heavy bombardment might not have been a discrete event, but rather the tail end of a gradual decline in impact rate that began when planet formation ended. Recent dating of asteroid samples supports this view, showing a range of impact ages from 3.4 to 4.1 billion years ago rather than a tight cluster around 3.9 billion years ago. The debate continues as scientists analyze additional samples and refine dating techniques. Comets versus asteroids. Determining whether the late heavy bombardment impactors were primarily asteroids or comets has important implications for understanding their effects on Earth. Asteroids approach from relatively low-velocity orbits within the inner solar system, striking Earth at velocities around 10 to 20 kilometers per second. Comets, originating from the distant reaches beyond Neptune, approach on highly elliptical orbits and collide with Earth at much higher velocities, often 30 to 70 kilometers per second. The impact energy scales with the square of velocity, meaning comets deliver far more energy per unit mass than asteroids. A 1-kilometer comet striking at 50 kilometers per second releases approximately 6 times more energy than a 1-kilometer asteroid striking at 20 kilometers per second. This difference affects the environmental consequences. Comet impacts vaporize a larger fraction of the projectile and target rock, injecting more material into the atmosphere and potentially having more severe global effects. Chemical evidence from Earth's oldest preserved rocks provides clues about impactor composition. Sedimentary rocks from the Isua Greenstone Belt in Greenland, dated to 3.8 billion years ago, contain elevated levels of iridium, an element rare in Earth's crust but common in asteroids and comets. The iridium concentration in these rocks is approximately 7 times higher than expected from normal crustal processes, indicating an extraterrestrial source. The amount of iridium enrichment matches predictions for a cometary source better than an asteroidal source. Asteroids would need to have struck Earth at implausibly high velocities to deposit the observed iridium levels while remaining consistent with the lunar cratering rate. Comets, with their inherently higher impact velocities and lower iridium concentrations compared to chondritic asteroids, fit the observations more naturally. This suggests that comets dominated the late heavy bombardment, at least in terms of the mass delivered to Earth. If comets were the primary impactors, they would have delivered substantial amounts of water and organic compounds. A cometary bombardment equivalent to the inferred impact rate would have added roughly 1 kilometer depth of water across Earth's entire surface. This represents a significant fraction of Earth's current ocean volume, possibly doubling the amount of water present before the bombardment. The delivered water would have had isotopic compositions different from asteroidal water, potentially explaining some of the isotopic variations observed in Earth's hydrosphere. Effects on Earth's surface. The environmental consequences of the late heavy bombardment were severe. The largest impacts, those creating 1,000 kilometer diameter basins, released energies equivalent to 100 million billion tons of TNT. The initial explosion vaporized thousands of cubic kilometers of rock, creating a fireball that expanded through the atmosphere at supersonic velocities. Thermal radiation from the fireball ignited global wildfires. Rock vapor and fine ejecta launched on ballistic trajectories re-entered the atmosphere across the entire planet, heating the upper atmosphere to incandescence. Ocean vaporizing impacts represented the most extreme threat to any emerging life. Computer models indicate that impacts by bodies 200 to 500 kilometers in diameter would have vaporized the upper several hundred meters of ocean. The resulting steam atmosphere would have had surface temperatures exceeding 500 degrees Celsius, sterilizing the surface environment for thousands of years until the steam condensed and rained back down. The frequency of such catastrophic impacts remains uncertain, but even a handful during the 100 million year bombardment would have repeatedly reset surface conditions. Smaller but still massive impacts, those creating 100-kilometer craters, occurred far more frequently. Each such impact excavated billions of tons of rock, launching it on suborbital trajectories. Ejecta fell back to Earth across areas the size of continents, reheating the surface where it landed. Impact generated seismic waves propagated through Earth's crust, triggering volcanic eruptions at weakened zones. Tsunamis thousands of meters high swept across ocean basins, eroding coastlines and depositing chaotic sediment layers. Despite the violence, recent three-dimensional hydrodynamic simulations suggest that habitable niches could have persisted throughout the bombardment. The deep ocean, below several hundred meters depth, remained relatively shielded from surface sterilization events. Even the largest ocean vaporizing impacts would have left deep ocean refugia where thermophilic organisms could survive. Subsurface environments, particularly hydrothermal systems kilometers below the seafloor, maintained stable temperatures and chemistry regardless of surface conditions. Delivery of organics. The late heavy bombardment paradoxically may have aided the origin and evolution of life even while threatening to extinguish it. Impact craters created diverse environments favorable for prebiotic chemistry and early life. Craters fractured the crust, allowing seawater to penetrate deeply and become heated by contact with hot subsurface rocks. These impact-generated hydrothermal systems persisted for thousands to hundreds of thousands of years, providing stable conditions where organic synthesis reactions could proceed. The impactors themselves delivered organic compounds. Carbonaceous asteroids and comets contain amino acids, nucleobases, sugars, and other prebiotic molecules synthesized in the interstellar medium or on the parent bodies. Some of these compounds survived impact delivery, particularly in smaller, low-velocity collisions. Laboratory experiments show that organic molecules can survive shock pressures up to approximately 20 gigapascals, sufficient to endure many smaller impacts. Impact plumes also synthesized organic molecules through shock chemistry. The intense heat and pressure during impact drove reactions between atmospheric gases like carbon dioxide, nitrogen, methane, and water vapor, producing amino acids, hydrogen cyanide, and other compounds. These impact-synthesized organics rained down across large areas, enriching the environment with prebiotic molecules. The repeated delivery and synthesis of organics throughout the bombardment continuously supplied raw materials for chemical evolution. The bombardment ends. By approximately 3.8 billion years ago, the impact rate declined to much lower levels. The asteroids and comets destabilized by planetary migration had either collided with planets, been ejected from the solar system, or settled into stable orbits where they no longer threatened the inner planets. Earth transitioned from a world suffering frequent catastrophic impacts to one where large collisions became rare, occurring perhaps once every 100 million years rather than several times per million years. This transition allowed stable surface environments to persist long enough for life to establish itself permanently. Before 3.8 billion years ago, any life that emerged faced repeated extinction from sterilizing impacts. After 3.8 billion years ago, life could expand across the surface without facing global catastrophes every few million years. The oldest undisputed fossils, stromatolites from Western Australia, date to 3.5 billion years ago, suggesting life had indeed established itself by this time. The late heavy bombardment marked the final chapter in Earth's prolonged period of accretion and heavy cratering. The planet had survived the violence of formation, the moon-forming impact, and hundreds of millions of years of bombardment. Earth was now ready to enter a period of relative stability where geological processes could shape the surface without constant disruption from space. Continental crust could accumulate and survive. Oceans could persist without repeated evaporation. The stage was set for life to not just emerge, but to flourish and evolve into the complex biosphere that would eventually give rise to intelligence. Chapter 12: The First Continents Emerge. Scattered across the ancient ocean, islands of solid rock rose above the waves. These were not continents in the modern sense, but proto-continents, the embryonic landmasses that would eventually coalesce into the vast continental platforms we know today. They formed through processes operating in Earth's hot Archean mantle, which convected far more vigorously than today's mantle due to higher internal temperatures and greater heat production from radioactive decay. By approximately 4 billion years ago, enough felsic crust had accumulated to create stable cratonic cores that could resist destruction and recycling into the mantle. These ancient cratons represent the longest-lived physical structures on Earth, surviving through 4 billion years of geological upheaval while continents assembled, fragmented, and reassembled around them. Understanding how these first continents formed reveals the tectonic processes that operated on the early Earth and established the foundation for all subsequent continental growth. Cratons, ancient cores. Cratons are the stable, ancient cores of continents composed of rocks older than 2.5 billion years. They represent the nuclei around which younger continental material accreted over geological time. Modern continents all contain cratonic regions, typically located in their interiors. North America's cratons include the Superior, Wyoming, Slave, and Nain cratons. Africa hosts the Karpfel and Zimbabwe cratons. Australia contains the Pilbara and Yilgarn cratons. These cratons share common characteristics that distinguish them from younger continental crust. They are composed primarily of tonalite-tronjamite granodiorite suites, collectively known as TTG. These rocks are silica-rich, with silicon dioxide contents between 63% and 75%. They are sodium-rich rather than potassium-rich, distinguishing them from typical granites. They contain high concentrations of rare earth elements, with specific patterns indicating formation through melting of basaltic source rocks under high pressure. Cratons possess thick lithospheric roots extending 200 to 300 kilometers deep into the mantle, far deeper than typical continental lithosphere. These deep roots are composed of depleted peridotite mantle rock from which partial melts have been extracted. The depletion makes the roots buoyant and mechanically strong, helping cratons resist destruction. Seismic imaging reveals that craton roots have remained attached to the overlying crust for billions of years, moving with the continents as they drift across Earth's surface. The Pilbara craton in Western Australia and the Karpfel craton in South Africa represent two of the best-preserved Archean crustal sections on Earth. Both contain rocks ranging from 3.8 to 2.7 billion years old, providing windows into early Earth processes. Remarkably, geological and paleomagnetic evidence suggests these two cratons, now separated by thousands of kilometers, were once joined as a single landmass called Volbara. TTG formation mechanisms. The formation of TTG crust requires specific conditions not common in modern Earth, but evidently widespread in the Archean. TTGs form through partial melting of hydrated basaltic crust at high pressure, typically 15 to 25 kilobars, corresponding to depths of 50 to 80 kilometers. At these pressures, garnet remains stable in the residue after melting, giving the resulting melt its characteristic rare earth element pattern. The melting requires water to lower the melting temperature sufficiently and requires a heat source to drive melting. Modern analogues to TTG formation exist at subduction zones, where oceanic crust subducts beneath continental or oceanic lithosphere. As the slab descends, water released from hydrous minerals lowers the melting point of the basaltic crust. If the slab is young and hot, it can partially melt, producing magmas with TTG-like compositions called adacites. However, adacites are rare in the modern world because most subducting slabs are old and cold, preventing them from reaching melting temperatures before water is driven off. In the Archean, the situation was different. The mantle was hotter by approximately 200 to 300 degrees Celsius, producing hotter oceanic crust through higher degrees of partial melting at mid-ocean ridges. This hotter oceanic crust, when subducted, remained hot enough to undergo partial melting at shallower depths and lower pressures than in modern subduction zones. The result was voluminous production of TTG magmas at convergent margins. Recent research suggests that Archean plate tectonics operated similarly to modern plate tectonics despite the hotter mantle. Evidence from the North Atlantic craton in Greenland shows thrust faulting, fold structures, and intercalation of volcanic arc rocks with TTG plutons, all consistent with convergent margin tectonics. The structural style indicates subhorizontal thrusting and crustal shortening rather than vertical diapirism, supporting plate tectonic models for Archean crustal growth. Alternative models propose that TTG formation occurred through melting of overthickened basaltic crust in intraplate settings. In this scenario, basaltic volcanism produced extremely thick piles of basalt, perhaps 30 to 50 kilometers thick. Hydration of the lower portions of this thick crust through interaction with seawater lowered melting temperatures. The weight of the overlying basalt provided the pressure needed to stabilize garnet. Heating from radioactive decay or underlying mantle plumes drove partial melting, producing TTG magmas that rose to form the first felsic crust. Both mechanisms may have operated simultaneously on the early Earth. Convergent margin TTG production through slab melting likely dominated, given the structural and geochemical evidence from preserved Archean terrains. However, over-thickened intraplate basaltic plateaus may have contributed to early continental growth, particularly in the Hadean before well-organized plate tectonics began operating. Continental emergence. The formation of felsic crust alone did not guarantee that land would rise above sea level. For continents to emerge, the crust needed to become thick and buoyant enough to float higher on the underlying mantle than the surrounding oceanic crust. Recent research indicates that much of the cratonic crust became exposed above sea level between 3.3 and 3.2 billion years ago, earlier than previously thought. The mechanism for craton emergence involved thickening and chemical differentiation. Mantle plumes, rising columns of hot rock from deep in the mantle, impinged on the base of the lithosphere beneath cratons. The thermal anomaly caused partial melting of the lower crust and uppermost mantle. The melts were enriched in silica and alkali elements, further differentiating the crust toward granitic compositions. Intrusion of these granitic magmas thickened the crust and reduced its density. Simultaneously, mafic and ultramafic residues from melting accumulated at the base of the lithosphere, forming the dense, depleted mantle roots characteristic of cratons. These roots extended deep into the mantle, providing buoyancy through their low density despite their great depth. The combination of thick, light crust and deep, depleted roots caused cratons to float higher on the mantle than surrounding regions, raising them above sea level. Evidence for emergence comes from sedimentary rocks deposited on the cratons. Sandstones and conglomerates formed in river and beach environments indicate that substantial land area existed above water. Paleosols, ancient soils formed through weathering of exposed rock, appear in the geological record by 3.2 billion years ago. Chemical signatures in sediments indicate weathering under subaerial conditions rather than submarine weathering. Collectively, these lines of evidence demonstrate that by 3.3 billion years ago, significant portions of cratonic crust stood above sea level as islands or small continents. Volbara, the first supercontinent. The Pilbara Craton in Western Australia and the Karpfel Craton in South Africa show striking geological similarities that suggest they were once joined. Both cratons preserve rock sequences including ancient volcanic flows, banded iron formations, and sedimentary layers with matching ages and compositions. The Fortescue group in Pilbara correlates with the Venterstorp supergroup in Karpfel, both deposited around 2.7 billion years ago. Paleomagnetic data provide the strongest evidence for their connection. When volcanic rocks cool, iron-bearing minerals align with Earth's magnetic field, preserving a record of the field direction at that time. By analyzing magnetic signatures in rocks of the same age from Pilbara and Karpfel, scientists determined that their ancient magnetic poles were aligned, indicating the cratons were positioned adjacent to each other rather than separated as they are today. This ancient landmass, dubbed Volbara, may have existed from approximately 3.6 to 2.7 billion years ago. During this time, Volbara was likely the dominant continental mass on Earth, though probably smaller than modern Australia. The supercontinent drifted across Earth's surface, driven by mantle convection beneath the lithospheric plates. Around 2.7 billion years ago, tectonic forces began pulling Volbara apart. Rifting created deep fractures through the crust. Molten magma surged upward, forming new oceanic crust in the widening rift. By approximately 2.1 billion years ago, Volbara had completely fragmented, with its pieces drifting apart as independent cratons. Other cratonic fragments existed during Volbara's reign, but do not show direct connections to the Karpfel-Pilbara assembly. The Slave Craton in northern Canada contains rocks dating back 4 billion years, including the Acasta gneiss, one of Earth's oldest rock formations. The Superior Craton stabilized around 3.0 billion years ago and later became a major component of the supercontinent Kenorland. These cratons likely existed as separate microcontinents or island chains during the Volbara era. The Archean atmosphere. The atmosphere surrounding these emerging continents was radically different from today's. Oxygen was absent or present only in trace amounts. The atmosphere was anoxygenic, lacking free molecular oxygen. Instead, it was dominated by nitrogen, carbon dioxide, methane, and water vapor. Methane concentrations may have exceeded 5,000 parts per million, more than 2,000 times higher than pre-industrial levels. The high methane concentration was maintained by methanogens, microorganisms that produce methane as a metabolic byproduct. These organisms appeared early in Earth's history, with phylogenetic analyses suggesting their origin before 3.5 billion years ago. In the absence of oxygen, methane accumulated in the atmosphere rather than being rapidly destroyed by oxidation. The methane created a greenhouse effect, warming Earth's surface, despite the sun being approximately 20 to 25% dimmer than today. This methane greenhouse was critical for maintaining liquid water on Earth's surface. Without it, the faint young sun would have provided insufficient energy to prevent global glaciation. Calculations show that atmospheric methane concentrations of a few thousand parts per million were necessary to keep surface temperatures above freezing. The methane acted as a thermostat, with biological methane production responding to temperature changes. If Earth cooled, weathering rates declined, reducing the consumption of atmospheric carbon dioxide. The buildup of carbon dioxide enhanced the greenhouse effect, warming the planet again. The anoxygenic atmosphere had important implications for surface chemistry. Iron dissolved in seawater remained in its reduced ferrous form rather than oxidizing to insoluble ferric oxides. This gave the ocean a greenish color and allowed iron to accumulate to high concentrations. When photosynthetic organisms began producing oxygen locally in surface waters, the oxygen immediately reacted with dissolved iron, precipitating it as iron oxides. These precipitates accumulated as banded iron formations, distinctive rocks consisting of alternating layers of iron-rich and iron-poor material. Ultraviolet radiation from the sun reached Earth's surface at much higher intensities than today because there was no ozone layer to absorb it. Ozone forms when oxygen molecules are split by ultraviolet light and the resulting atoms combine with other oxygen molecules. Without molecular oxygen, ozone could not form. The intense ultraviolet flux would have been lethal to surface organisms lacking protective mechanisms. Early life likely remained in the oceans, shielded by meters of water that absorbed most ultraviolet radiation. Tectonic regime. Whether plate tectonics operated in the Archean as it does today remains debated, but evidence increasingly supports some form of plate-like behavior. The hotter mantle produced more buoyant oceanic lithosphere that resisted subduction. However, hydration of oceanic crust through reactions with seawater increased its density when metamorphosed to eclogite, facilitating subduction. Numerical models suggest that a mix of mobile lid plate tectonics and stagnant lid regimes may have operated simultaneously, with plate tectonics becoming increasingly dominant as Earth cooled. Geological evidence from Archean terrains supports convergent margin processes. Thrust faults indicate horizontal compression consistent with plate collisions. Calcaline volcanic rocks with geochemical signatures of subduction zones appear in greenstone belts. Blueschist and eclogite metamorphic rocks, which form under high pressure and relatively low temperature conditions characteristic of subduction zones, have been identified in rocks as old as 3 billion years, though they are rare. The Wilson cycle, the opening and closing of ocean basins through continental breakup and reassembly, likely operated in modified form during the Archean. Continents rifted apart, creating new ocean basins. The oceanic crust cooled and eventually became dense enough to subduct. Subduction consumed the ocean basin, bringing continents together in collision. The cycle repeated, driving continental drift and the assembly of supercontinents. This process built continents incrementally, adding new material at convergent margins, while older cratonic cores remained relatively intact. Foundation for life. The emergence of continents profoundly influenced Earth's habitability and the evolution of life. Exposed land provided diverse environments absent in the purely oceanic world that preceded it. River systems transporting nutrients from land to sea, fertilizing coastal waters. Tidal zones created environments where organisms experienced alternating wet and dry conditions, potentially driving evolutionary innovations. Subaerial weathering of silicate rocks consumed atmospheric carbon dioxide, providing a long-term climate regulation mechanism. Continental crust also influenced ocean chemistry. Weathering released calcium, magnesium, potassium, and phosphorus into rivers, which carried these elements to the ocean. Phosphorus, a limiting nutrient for life, became more available as weathering rates increased. The delivery of nutrients from continents may have enhanced biological productivity, allowing microbial communities to expand and diversify. By the end of the Archean, at 2.5 billion years ago, continents covered perhaps 20 to 30% of Earth's surface, substantially less than today's 29%, but far more than the tiny volcanic islands that existed in the Hadean. These continents provided the foundation for all subsequent geological and biological evolution. The cratons formed in the Archean still exist in modern continents, having survived through 2.5 billion years of supercontinent cycles. They represent Earth's most durable features, monuments to the tectonic processes that built the first landmasses rising above the primordial ocean. Chapter 13: The Origin of Life. Somewhere in the ancient ocean, chemistry became biology. The transition was not sudden, not a single moment when non-living matter abruptly became alive. Instead, life emerged gradually through countless incremental steps, each small change building upon the last, as simple chemical reactions evolved into self-replicating molecular systems capable of evolution. The exact location remains unknown. It might have been a shallow tidal pool where organic molecules concentrated through evaporation. It could have been a deep-sea hydrothermal vent where superheated water mixed with cold seawater, creating chemical gradients that powered synthesis reactions. Perhaps life began in multiple locations simultaneously, with only one lineage surviving to become the ancestor of all modern organisms. What we know with certainty is that by 3.5 billion years ago, life had established itself on Earth, leaving fossil evidence in the form of stromatolites preserved in Western Australia. Understanding how life originated requires examining the chemical pathways that could have assembled the building blocks of biology from simple inorganic starting materials. The chemical building blocks. Life as we know it requires specific molecules. Proteins perform most cellular functions, catalyzing reactions, providing structure, and transporting materials. Nucleic acids, including DNA and RNA, store and transmit genetic information. Lipids form cell membranes that separate the interior of cells from the external environment. Carbohydrates provide energy and structural support. All these molecules are organic compounds, containing carbon atoms linked together in chains and rings. The question facing origin of life researchers is how these complex organic molecules could have formed on the early Earth. The atmosphere of the Archean Earth contained no free oxygen, but was rich in carbon dioxide, nitrogen, methane, water vapor, and smaller amounts of hydrogen sulfide and ammonia. These simple gases provided the raw materials. Energy sources were abundant. Lightning strikes discharged electrical energy through the atmosphere. Ultraviolet radiation from the sun bathed the surface with high-energy photons. Volcanic eruptions released heat and shock waves. Meteorite impacts generated intense heat and pressure. Each of these energy sources could drive chemical reactions that would not occur spontaneously. Early experiments demonstrated that organic molecules form readily under simulated early Earth conditions. The Miller-Urey experiment, conducted at the University of Chicago in 1953, recreated the presumed early atmosphere by mixing water, methane, ammonia, and hydrogen in a closed system. Electric sparks simulating lightning provided energy. Within days, the experiment produced amino acids, the building blocks of proteins. Subsequent experiments, using different atmospheric compositions and energy sources, generated nucleobases, sugars, and lipid precursors. These results showed that the fundamental building blocks of life could form through ordinary chemistry given the right conditions. Delivery from space contributed additional organic compounds. Carbonaceous chondrites, primitive meteorites that have remained largely unchanged since the solar system formed, contain over 80 different amino acids, including many found in living organisms. Analysis of the Murchison meteorite, which fell in Australia in 1969, revealed complex organic molecules, including purines and pyrimidines, components of nucleic acids. Comets contain even more diverse organic chemistry, with spectroscopy revealing the presence of formaldehyde, methanol, and other compounds. The continuous rain of meteorites and cometary dust throughout the Hadean and Archean delivered these preformed organic molecules directly to Earth's surface. The RNA world hypothesis. Among the various proposals for how life originated, the RNA world hypothesis has gained substantial support. This hypothesis proposes that RNA, rather than DNA or proteins, was the first biological molecule. RNA possesses unique properties that make it suitable as a primordial biomolecule. Unlike DNA, RNA is single-stranded and can fold into complex three-dimensional shapes. These shapes allow RNA to act as an enzyme, catalyzing chemical reactions. Some RNA molecules can even catalyze their own synthesis, copying themselves without requiring protein enzymes. The discovery of ribosomes, RNA molecules with catalytic activity, provided strong support for the RNA world hypothesis. Naturally occurring ribosomes catalyze various reactions, including cutting and joining RNA strands. Laboratory experiments have created artificial ribosomes capable of catalyzing increasingly complex reactions, including polymerizing new RNA strands and synthesizing amino acids. These findings demonstrate that an RNA-based metabolism is chemically feasible. The RNA world hypothesis faces challenges. RNA synthesis requires specific conditions, particularly regarding pH. Early proposals suggested RNA arose in alkaline hydrothermal vents, but recent research indicates RNA is unstable at high pH instead. RNA likely evolved in acidic environments, possibly in the acidic Hadean Ocean itself or in volcanic crater lakes. The acidic conditions would have stabilized RNA against hydrolysis, while allowing the chemical reactions needed to synthesize nucleotides and polymerize them into RNA chains. Forming RNA from scratch requires overcoming significant hurdles. Nucleotides, the building blocks of RNA, are complex molecules consisting of a sugar, a phosphate group, and a nitrogenous base. Each component must form separately before they can be joined together. The sugar ribose is particularly problematic because it forms in low yields from simple starting materials and degrades rapidly. Researchers have proposed alternative pathways that bypass free ribose, instead building nucleotides through reactions that join all components simultaneously. These reactions work under plausible prebiotic conditions, suggesting RNA could have formed on the early Earth. Hydrothermal vent hypothesis. Deep-sea hydrothermal vents provide attractive environments for life's origin. These vents form where seawater percolates through cracks in the oceanic crust, becomes heated by proximity to magma chambers, and erupts back into the ocean as superheated fluids rich in dissolved minerals. Two types of vents exist with different chemistries. Black smokers emit acidic, high-temperature water exceeding 300 degrees Celsius, laden with metal sulfides that precipitate as black particles. White smokers or alkaline vents emit cooler, alkaline water around 100 degrees Celsius, rich in hydrogen, methane, and calcium. Alkaline vents create natural chemical gradients between the alkaline vent fluid and the acidic, iron-rich ocean water. These gradients span porous mineral structures that form at the interface, creating countless microscopic compartments separated by thin mineral walls. The walls contain iron-sulfur minerals similar to those used in modern metabolism as electron transfer agents. Proton gradients across these walls could drive synthesis reactions, providing energy for building complex molecules. LUCA, the last universal common ancestor of all life on Earth, appears to have been adapted to hydrothermal vent environments. Genetic analysis comparing the genomes of living organisms across all three domains of life reveals that LUCA lived in hot, anaerobic conditions rich in iron, sulfur, hydrogen, and carbon dioxide. Its metabolism depended on hydrogen oxidation and carbon dioxide reduction, producing methane or acetate as waste products. It synthesized amino acids from ammonia and fixed nitrogen from nitrogen gas. All these metabolic capabilities are consistent with life in a hydrothermal vent system. Recent research using molecular clock analysis dates LUCA to approximately 4.2 billion years ago, only 400 million years after Earth formed. This surprisingly early date places LUCA near the end of the late heavy bombardment period, suggesting life arose quickly once conditions permitted. The rapid emergence of life on Earth has implications for the prevalence of life in the universe. If life appears readily when conditions are favorable, then life might be common throughout the cosmos. The primordial soup. An alternative to hydrothermal vents as the location for life's origin is the primordial soup model. This hypothesis, dating to the 1920s, proposes that life originated in surface water bodies where organic molecules accumulated to high concentrations. Darwin himself speculated about a warm little pond where the right combination of chemicals and energy could spark life. The primordial soup concept builds on this idea, envisioning the early ocean as a dilute solution of organic compounds continuously enriched by atmospheric synthesis, meteorite delivery, and chemical reactions in the water itself. Concentration mechanisms are crucial for the primordial soup scenario. Organic molecules in the vast ocean would be too dilute to react efficiently. Tidal pools and evaporative ponds could concentrate dissolved compounds by factors of 10,000 or more. Minerals like clays and zeolites could absorb organic molecules onto their surfaces, bringing reactants into close proximity and catalyzing their reactions. Cycles of wetting and drying, as tidal pools filled and evaporated, could drive polymerization reactions that join monomers into polymers. The primordial soup model faces criticisms regarding energy supply. RNA polymerization requires energy input, typically provided by activated nucleotides containing high-energy bonds. In modern cells, these activated nucleotides are produced through metabolic pathways powered by ATP. In a primordial soup, no metabolic machinery existed yet, so alternative energy sources were needed. Candidates include cycling between wet and dry states, which can drive condensation reactions and chemical energy from redox reactions between minerals and organic compounds. Recent thinking suggests that primordial soup and hydrothermal vents need not be mutually exclusive. Organic molecules synthesized in the atmosphere or delivered by meteorites would have accumulated in the ocean, creating a dilute soup. Concentration of these molecules in specialized microenvironments, whether tidal pools, volcanic crater lakes, impact crater ponds, or hydrothermal vent systems, could have provided favorable conditions for the next steps toward life. Different stages of chemical evolution may have occurred in different settings, with molecules formed in one environment transporting to another where subsequent reactions took place. Self-replication and evolution. The defining characteristic of life is the ability to reproduce, creating copies that inherit information from their predecessors. For chemical systems to evolve into life, they needed to develop self-replication. The first replicators were probably simple molecules, perhaps short RNA sequences or even simpler polymer chains. These molecules needed to catalyze their own synthesis, using themselves as templates to direct the formation of complementary copies. Errors in copying provided variation. Most copying errors would have been neutral or harmful, producing non-functional molecules. Occasionally, a copying error would improve the molecule's ability to replicate, making it more successful at spreading through the environment. Over generations, better replicators outcompeted poorer ones, driving chemical evolution toward increasingly efficient and complex replicating systems. Compartmentalization represented a crucial innovation. Free-floating replicators in solution competed with all others, but there was no direct link between a molecule's success and the benefits it created. If one molecule evolved a function that improved replication, other nearby molecules reaped the benefits without paying the costs of maintaining that function. This freeloading problem prevented the accumulation of complex functionality. Enclosing replicators within membrane compartments solved this issue. Lipid molecules spontaneously form closed vesicles in water, creating natural compartments. Replicators inside a vesicle were isolated from freeloaders, allowing beneficial functions to be retained. Protocells, simple membrane-bound compartments containing replicating molecules, represented an intermediate stage between chemistry and biology. These protocells could grow by incorporating lipids from the environment and divide when they became too large, distributing their contents between daughter vesicles. Natural selection acted on protocells as units. Those containing more efficient replicators or beneficial catalysts grew faster and produced more offspring. Over time, protocells evolved increasingly sophisticated internal chemistry, eventually developing the complex metabolic networks characteristic of living cells. The path to LUCA. The transition from protocells to LUCA involved numerous innovations. The genetic code, which translates nucleotide sequences into amino acid sequences, had to be established. Transfer RNAs, which carry amino acids to ribosomes during protein synthesis, evolved. Ribosomes, the molecular machines that synthesize proteins, developed through the association of multiple RNA molecules and proteins. Metabolic pathways for extracting energy from chemical reactions and synthesizing necessary building blocks assembled step by step. LUCA already possessed remarkable complexity. Its genome encoded hundreds of genes for metabolism, replication, and cellular maintenance. It had a lipid membrane, though the membrane chemistry would later diverge between bacteria and archaea. It used the universal genetic code, with minor variations that arose later in some lineages. LUCA was truly the last universal common ancestor because all subsequent evolution proceeded from this single ancestral organism. The environment LUCA inhabited shaped its characteristics. Living in hot, anaerobic, iron-sulfur-rich conditions meant LUCA did not need defenses against oxygen, which was still absent from Earth's environment. It could not photosynthesize, instead relying on chemical energy from hydrogen oxidation. The metabolic pathways LUCA possessed reflect adaptations to hydrothermal vent chemistry, supporting the hypothesis that life originated in such environments. After LUCA, the tree of life split into three major branches: bacteria, archaea, and eventually eukaryotes. Bacteria and archaea are both prokaryotes, lacking nuclear and membrane-bound organelles, but they differ fundamentally in membrane chemistry, cell wall composition, and genetic machinery. The divergence between these domains occurred early, within a few 100 million years of LUCA. Each domain radiated into countless lineages adapted to diverse environments across Earth. Life takes hold. By 3.8 to 3.5 billion years ago, life had spread throughout the ocean. Microfossils, microscopic structures preserved in ancient rocks, show bacterial cell shapes from this period. Stromatolites, layered rock structures built by microbial mats, appear in the geological record 3.5 billion years ago. These stromatolites formed in shallow marine environments where photosynthetic bacteria trapped and bound sediment, layer by layer, building mounds that eventually fossilized. The early biosphere was entirely prokaryotic. No eukaryotic cells existed yet. All organisms were single-celled bacteria or archaea following simple metabolic strategies. Anaerobic metabolism dominated because oxygen remained absent from the atmosphere and ocean. Organisms extracted energy from fermentation, methanogenesis, sulfate reduction, and other anaerobic pathways. Primary production was limited, probably an order of magnitude less than modern rates, because photosynthesis was still primitive or absent. Despite its simplicity, this early biosphere had begun transforming Earth. Biological weathering enhanced the breakdown of rocks, altering ocean chemistry. Methanogens produced methane that accumulated in the atmosphere, contributing to the greenhouse effect that kept Earth warm. Carbon fixation by autotrophic organisms removed carbon dioxide from the atmosphere, though volcanic outgassing continuously replenished it. Life had established itself as a permanent feature of Earth, surviving the tail end of the late heavy bombardment and beginning its long process of reshaping the planet's surface and atmosphere. The origin of life, occurring at an unknown time and place during the Hadean or early Archean, represents the most profound transition in Earth's history, the moment when our planet became a living world. Chapter 14: The First Living Cells. The earliest cells were nothing like the complex eukaryotic cells that make up animals, plants, and fungi today. They were prokaryotes, simple single-celled organisms lacking nuclei, mitochondria, chloroplasts, and other membrane-bound organelles. Their genetic material floated freely in the cytoplasm rather than being sequestered within a nuclear envelope. Their ribosomes, the protein-making factories, were smaller and simpler than those in eukaryotic cells. Despite their simplicity, these prokaryotic cells possessed all the essential features of life. They metabolized nutrients for energy, grew and divided to reproduce, responded to environmental stimuli, and evolved through natural selection. The two great prokaryotic domains, bacteria and archaea, diverged from LUCA early in Earth's history and radiated into countless lineages that colonized every available habitat. Understanding these first living cells reveals how life adapted to the harsh conditions of the Archean Earth and began the long process of transforming the planet's chemistry. Prokaryotic cell structure. Prokaryotic cells are typically small, measuring 1 to 5 micrometers in diameter, roughly 1/10 the size of typical eukaryotic cells. This small size reflects the lack of internal compartmentalization. Without organelles, all cellular chemistry occurs in a single compartment, and diffusion alone suffices to transport molecules within the cell. The small volume also provides a favorable surface area to volume ratio, allowing efficient exchange of nutrients and wastes with the environment through the cell membrane. The cell membrane forms the outer boundary, separating the cell interior from the external environment. This membrane consists of a phospholipid bilayer, two layers of lipid molecules arranged with their hydrophobic tails facing inward and their hydrophilic heads facing outward. Proteins embedded in the membrane perform various functions, transporting specific molecules across the membrane, detecting environmental signals, and anchoring structural components. The membrane is selectively permeable, allowing water and small molecules to pass freely while blocking larger molecules and charged ions, unless specific transport proteins facilitate their passage. Most prokaryotes possess a cell wall outside the membrane, providing structural support and protection. In bacteria, the cell wall consists primarily of peptidoglycan, a polymer of sugars cross-linked by short peptides forming a mesh-like structure. This wall prevents the cell from bursting due to osmotic pressure when internal solute concentrations exceed external concentrations. Archaea also have cell walls, but they are made of different materials than bacterial cell walls, reflecting the fundamental differences between these domains. The cytoplasm fills the interior of the cell, consisting of water, dissolved nutrients, enzymes, ribosomes, and the genetic material. Ribosomes are abundant, sometimes numbering tens of thousands per cell, reflecting the constant need for protein synthesis. The nucleoid region contains the cell's DNA, typically a single circular chromosome, though some prokaryotes have multiple chromosomes or supplementary small circular DNA molecules called plasmids. The nucleoid is not separated from the rest of the cytoplasm by a membrane, distinguishing it from the membrane-bound nucleus of eukaryotic cells. Many prokaryotes possess external structures aiding movement or attachment. Flagella are long, whip-like structures that rotate like propellers, driving the cell through liquid environments. Pili are shorter hair-like projections used for attachment to surfaces or for exchanging genetic material with other cells. Some bacteria form spores, dormant structures resistant to heat, desiccation, and chemical stress, allowing survival through extended periods of unfavorable conditions. Bacteria and archaea, fundamental differences. Bacteria and archaea, while both prokaryotic, differ in fundamental ways that reflect their early divergence from LUCA. The most striking difference lies in membrane chemistry. Bacterial membranes contain lipids with ester bonds linking fatty acids to glycerol backbones, the same type of linkage found in eukaryotic membranes. Archaeal membranes contain lipids with ether bonds linking isoprene chains to glycerol, a completely different chemistry. Some archaea even have monolayer membranes rather than bilayers, with lipids spanning the entire membrane as single molecules with hydrophilic groups at both ends. The genetic machinery also differs between domains. Bacterial RNA polymerase, the enzyme that synthesizes RNA from DNA templates, is relatively simple with 4 to 5 subunits. Archaeal RNA polymerase is more complex with 8 to 12 subunits, more similar to eukaryotic RNA polymerase than to bacterial versions. The DNA replication machinery, ribosomal proteins, and various metabolic enzymes show similar patterns, with archaea often resembling eukaryotes more than bacteria despite being prokaryotic. These differences suggest that bacteria and archaea separated very early, perhaps within a few 100 million years of LUCA. The archaea first hypothesis proposes that archaea diverged first from the stem lineage, with bacteria and eventually eukaryotes branching off later. This hypothesis finds support in molecular features like transfer RNA structures and 5S ribosomal RNA sequences that show archaea as the most ancient branch. The unusual ether-linked membrane lipids in archaea may represent a primitive feature retained from LUCA or an early adaptation to extreme environments where archaea thrived. Archaean metabolic diversity. The first living cells could not use oxygen for respiration because oxygen did not exist in the atmosphere or ocean. Instead, they relied on anaerobic metabolisms, chemical pathways that extract energy without requiring molecular oxygen. These anaerobic pathways remain widespread among modern prokaryotes, particularly in oxygen-depleted environments like deep sediments, waterlogged soils, and animal digestive systems. Fermentation represents the simplest anaerobic metabolism. In fermentation, organic molecules like sugars are partially broken down, releasing a small amount of energy while producing waste products such as ethanol, lactate, or acetate. Fermentation is inefficient, extracting only about 5% of the energy available in glucose, but it requires no external electron acceptor and operates in virtually any environment containing organic compounds. Methanogenesis, the production of methane as a metabolic waste product, was likely one of the earliest metabolic innovations. Methanogens are archaea that reduce carbon dioxide with hydrogen to produce methane and water. This metabolism is chemically simple, requiring only a few enzymes, and exploits the hydrogen produced by fermentation or geological processes. Methanogens played a crucial role in the Archean atmosphere, producing the high methane concentrations necessary for the methane greenhouse that kept early Earth warm despite the faint young sun. Sulfate reduction uses sulfate ions as electron acceptors, reducing them to hydrogen sulfide. This metabolism requires sulfate availability, which was limited in the Archean Ocean because sulfate is produced through oxidation of sulfide minerals, a process requiring oxygen. Nevertheless, sulfate reducers existed, exploiting whatever sulfate was available from photochemical reactions in the atmosphere or from rare oxygenated microenvironments. Ion reduction uses ferric iron as an electron acceptor, reducing it to ferrous iron. The Archean Ocean was rich in dissolved ferrous iron, providing abundant electron donors, but ferric iron as an electron acceptor was scarce because it required prior oxidation. Some organisms coupled ion oxidation to photosynthesis, using light energy to transfer electrons from ferrous iron to carbon dioxide, fixing carbon while oxidizing iron. This anaxigenic photosynthesis did not produce oxygen as waste, but was an important step toward oxygenic photosynthesis. The first photosynthesizers. Photosynthesis, the use of light energy to drive chemical synthesis, evolved relatively early. The earliest photosynthesis was anaxigenic, meaning it did not produce oxygen. Anaxigenic photosynthetic bacteria use electron donors like hydrogen sulfide, hydrogen gas, or ferrous iron rather than water. Light energy excites electrons in photosynthetic pigments, and these excited electrons drive carbon dioxide reduction to organic compounds. The spent electrons are replaced from the external electron donor rather than from water splitting. Cyanobacteria evolved oxygenic photosynthesis, a revolutionary innovation that would eventually transform Earth's atmosphere. Oxygenic photosynthesis uses water as the electron donor, splitting water molecules to extract electrons and releasing molecular oxygen as waste. This process requires more energy than anaxigenic photosynthesis because water is more difficult to oxidize than hydrogen sulfide or ferrous iron. Cyanobacteria solved this challenge by linking two photosystems in series, providing sufficient energy to split water. The evolution of oxygenic photosynthesis is dated to between 3.4 and 2.9 billion years ago, based on molecular clock analysis and biomarker evidence. This places the origin of oxygen-producing life 500 million years before the Great Oxidation Event, when oxygen first accumulated in the atmosphere to significant levels. For at least 500 million years, cyanobacteria produced oxygen that was immediately consumed by reaction with reduced species in the ocean and atmosphere, never accumulating to detectable levels in the environment. The evolution of photosynthesis involved horizontal gene transfer, the exchange of genes between organisms. The modern photosynthetic system apparently arose through lateral transfer and fusion of genes from two different photosynthetic systems, possibly from different bacterial lineages. This finding indicates that early evolution was not strictly tree-like, but involved gene sharing across lineages, accelerating the development of complex metabolic capabilities. Stromatolites, fossilized microbial communities. The oldest undisputed fossils are stromatolites from Western Australia and South Africa, dated to 3.5 billion years ago. Stromatolites are layered rock structures built by microbial mats, communities of bacteria that grow in shallow water. The microbes trap and bind sediment particles, cementing them together with secreted organic material. As the mat grows upward, new layers form on top of old ones, creating the distinctive laminated structure visible in cross-section. Modern stromatolites still grow in a few locations, most famously at Shark Bay in Western Australia. These modern examples are dominated by cyanobacteria, photosynthetic bacteria that form dense mats on the seafloor in shallow, warm, hypersaline water. The high salinity excludes most grazing animals that would otherwise consume the bacterial mat faster than it could grow. By studying modern stromatolites, scientists gain insights into how their ancient counterparts formed and what environments supported them. Ancient stromatolites indicate that by 3.5 billion years ago, photosynthetic microbial communities thrived in shallow marine environments. The stromatolites occur in rocks interpreted as ancient reef and tidal flat deposits, indicating that life had colonized coastal environments where light was abundant. The presence of stromatolites implies complex microbial ecosystems with multiple species cooperating to build and maintain the structures. Some stromatolites show evidence of cyanobacterial metabolism through isotopic signatures and molecular fossils. Carbon isotope ratios in stromatolite organic matter indicate carbon fixation through photosynthesis. Certain lipid molecules called hopanes, produced primarily by cyanobacteria, appear in rocks as old as 2.7 billion years, providing chemical evidence for cyanobacteria's presence. Collectively, these findings demonstrate that cyanobacteria and likely oxygenic photosynthesis existed by the mid-Archean, setting the stage for the eventual oxygenation of the atmosphere. The iron-rich ocean. The Archean Ocean differed dramatically from modern seawater in its chemistry. Dissolved ferrous iron reached concentrations 1,000 times higher than today, giving the water a greenish color. The high iron content resulted from volcanic and hydrothermal input, combined with the absence of oxygen to oxidize and precipitate the iron. This ferruginous condition persisted throughout most of the Archean, maintaining an iron-rich ocean until oxygen finally accumulated 2.4 billion years ago. Banded iron formations represent the signature rock type of the Archean and Proterozoic. These distinctive rocks consist of alternating layers of iron-rich and iron-poor material, typically red or black iron oxides alternating with gray silica-rich layers. Each band ranges from millimeters to centimeters thick, and the banded pattern continues vertically for hundreds of meters, representing millions of years of deposition. Banded iron formations record the interaction between iron and oxygen. Oxygen produced by cyanobacteria in surface waters oxidized dissolved ferrous iron to ferric iron, which immediately precipitated as iron oxides. These precipitates sank to the seafloor, forming iron-rich layers. When oxygen production temporarily declined or iron input increased, silica-rich layers formed instead. The alternation between iron-rich and iron-poor layers may reflect seasonal or longer-term cycles in biological productivity, ocean circulation patterns, or volcanic activity. The peak of banded iron formation deposition occurred around 2.5 billion years ago, coinciding with increasing atmospheric oxygen. As oxygen levels rose, the deep ocean gradually oxidized, consuming the reservoir of dissolved ferrous iron. By 1.85 billion years ago, banded iron formation deposition largely ceased, indicating that the deep ocean had become oxygenated and could no longer transport significant dissolved iron into depositional basins. The end of widespread banded iron formation marks the completion of ocean oxygenation, one of Earth's most profound environmental transitions, setting the stage for complexity. By the end of the Archean, prokaryotic life had become firmly established across Earth's surface. Bacteria and archaea occupied every available habitat, from hot springs to frozen lakes, from deep ocean trenches to rocky outcrops on emerging continents. Metabolic diversity had expanded to include fermentation, methanogenesis, sulfate reduction, ion oxidation, and both anoxygenic and oxygenic photosynthesis. Microbial mats built stromatolites in shallow waters, while planktonic cells drifted in the open ocean. The stage was set for the next great evolutionary transition, the oxygenation of the atmosphere. Cyanobacteria had been producing oxygen for perhaps 1 billion years, but reducing substances in the ocean and atmosphere consumed this oxygen as fast as it formed. Eventually, the reduced materials would be exhausted, tipping Earth into an oxygen-rich state. This great oxidation event would occur around 2.4 billion years ago, fundamentally transforming Earth's surface chemistry and opening the door to the evolution of eukaryotic cells and eventually complex multicellular life. But that transformation still lay hundreds of millions of years in the future as Archean prokaryotes continued their reign over an anoxic world. Chapter 15: The Oxygen Catastrophe. For hundreds of millions of years, cyanobacteria quietly poisoned the world. The oxygen they released as waste from photosynthesis accumulated slowly at first, immediately consumed by reactions with iron dissolved in the ocean and reduced gases in the atmosphere. These oxygen sinks absorbed every molecule of oxygen as quickly as it formed, preventing any buildup in the environment. But sinks have finite capacity. The dissolved iron could only oxidize until it was exhausted. The volcanic gases could only consume oxygen until their supply diminished. Around 2.4 billion years ago, the balance tipped. Oxygen began accumulating in the atmosphere for the first time, rising from essentially zero to perhaps 1% of current atmospheric levels within a few tens of millions of years. This great oxidation event transformed Earth more profoundly than any event since the moon-forming impact, fundamentally altering the chemistry of the atmosphere, ocean, and crust, while triggering a mass extinction that wiped out much of the anaerobic life that had dominated Earth for over 1 billion years. Cyanobacteria proliferate. Cyanobacteria evolved oxygenic photosynthesis at least 500 million years before oxygen accumulated in the atmosphere. Molecular clock studies place the origin of oxygen-producing photosynthesis between 3.4 and 2.9 billion years ago, while the Great Oxidation Event did not occur until 2.4 billion years ago. This delay of 500 million years or more requires explanation. If cyanobacteria were producing oxygen for so long, why did atmospheric oxygen remain negligible until the Paleoproterozoic? The answer lies in oxygen sinks, chemical processes that consume oxygen as fast as it forms. The Archean Ocean contained dissolved ferrous iron at concentrations roughly 1,000 times higher than today. When oxygen produced by cyanobacteria diffused into iron-rich water, it immediately reacted, oxidizing ferrous iron to ferric iron. The ferric iron precipitated as iron oxide minerals, settling to the seafloor and forming banded iron formations. This process consumed enormous quantities of oxygen over hundreds of millions of years, preventing any accumulation in the atmosphere. Volcanic gases provided additional oxygen sinks. Volcanoes emit hydrogen, methane, and sulfur dioxide, all of which react with oxygen. Hydrogen oxidizes to water. Methane oxidizes to carbon dioxide and water. Sulfur dioxide oxidizes to sulfate. The continuous supply of volcanic gases from the mantle maintained these sinks throughout the Archean. As long as volcanism remained vigorous, these gases consumed photosynthetic oxygen before it could escape to the atmosphere. Around 2.4 billion years ago, something changed. One possibility is that cyanobacteria experienced a burst of diversification, rapidly expanding their population and geographic range. Genetic analysis reveals that shortly before the Great Oxidation Event, cyanobacterial lineages underwent accelerated speciation, branching into multiple new species adapted to different environments. This diversification may have increased oxygen production beyond the capacity of existing sinks to consume it, tipping the balance toward accumulation. Another possibility is that the sinks themselves diminished. The deep ocean's reservoir of dissolved iron was finite. After hundreds of millions of years of oxidation, most of the iron had been converted to oxides and deposited as banded iron formations. With less dissolved iron available to consume oxygen, more oxygen could escape to the atmosphere. Similarly, declining volcanic activity would have reduced the flux of reduced gases, lowering the atmospheric oxygen consumption rate. The most likely scenario involves both factors working together. Increasing cyanobacterial productivity raised oxygen production, while simultaneously the major oxygen sinks approached saturation. The system reached a tipping point where oxygen production exceeded consumption. Once this threshold was crossed, oxygen began accumulating rapidly, transforming Earth's surface chemistry within tens of millions of years. Atmospheric transformation. The rise of atmospheric oxygen was not smooth or monotonic. Evidence from sulfur isotopes preserved in ancient sediments reveals complex oxygen dynamics. Before 2.45 billion years ago, sulfur isotopes show mass-independent fractionation, a signature that only forms when sulfur dioxide in the atmosphere is photochemically processed under essentially oxygen-free conditions. This mass-independent fractionation disappeared between 2.41 and 2.35 billion years ago, marking the permanent appearance of oxygen in the atmosphere. The initial oxygen rise brought atmospheric oxygen to perhaps 1 to 10% of present atmospheric levels, roughly 0.01% to 1% by volume. This represents a dramatic increase from effectively zero, but oxygen remained far below modern levels. The atmosphere was still predominantly nitrogen, carbon dioxide, and methane, with oxygen as a minor but chemically significant component. Oxygen accumulation had cascading effects on atmospheric chemistry. Methane, which had been a major atmospheric constituent maintaining the greenhouse effect that kept Archean Earth warm, reacted with oxygen to form carbon dioxide and water. The reaction is rapid once oxygen concentrations exceed trace levels. As methane concentrations declined, so did the greenhouse warming it provided. Methane absorbs infrared radiation roughly 30 times more effectively per molecule than carbon dioxide, making it a potent greenhouse gas. Its removal from the atmosphere represented a massive reduction in greenhouse forcing. The destruction of the methane greenhouse created a climate crisis. The sun during the Paleoproterozoic was still about 20 to 25% dimmer than today, providing insufficient energy to keep Earth's surface above freezing without greenhouse enhancement. With methane largely removed and carbon dioxide alone unable to compensate, Earth's climate cooled dramatically. The planet plunged into the most severe glaciation it had yet experienced, the Huronian glaciation, which would last for hundreds of millions of years. Mass extinction of anaerobes. For the anaerobic organisms that dominated the Archean biosphere, oxygen was poison. Molecular oxygen is highly reactive, oxidizing biological molecules and disrupting cellular processes. Anaerobic organisms lack defenses against oxidative damage. They have no enzymes to neutralize reactive oxygen species, no mechanisms to repair oxidative damage to DNA and proteins, no strategies to prevent oxygen from entering their cells. As oxygen concentrations rose, anaerobic ecosystems collapsed. Species after species went extinct as their habitats became oxygenated. The extinction was selective, targeting strict anaerobes while sparing facultative organisms that could tolerate some oxygen exposure or organisms living in oxygen-poor refugia. The scale of extinction remains difficult to quantify because microbial fossils are scarce and many anaerobic lineages left no fossil record. However, genetic evidence suggests that numerous ancient bacterial and archaeal lineages disappeared during or shortly after the Great Oxidation event. The survivors retreated to anoxic environments where oxygen could not reach. Deep sediments, waterlogged soils, the digestive tracts of animals that would evolve billions of years later all became refuges for anaerobic life. These environments remain oxygen-free today, and the descendants of Archean anaerobes still thrive there, unchanged in their fundamental biochemistry. Modern methanogens, sulfate reducers, and fermenters in anoxic sediments are living fossils, metabolically similar to their ancestors that survived the oxygen catastrophe by hiding from the toxic atmosphere. The extinction opened ecological niches for organisms that could tolerate or utilize oxygen. Aerobic respiration, the use of oxygen to extract energy from organic molecules, evolved relatively quickly once oxygen became available. Aerobic respiration is far more efficient than fermentation, extracting roughly 20 times more energy from glucose. Organisms that evolved aerobic metabolism gained enormous advantages, allowing them to grow faster and compete more effectively. This drove the diversification of aerobic bacteria and set the stage for the evolution of eukaryotic cells, which would internalize aerobic bacteria as mitochondria. Snowball Earth, the Huronian glaciation. The collapse of the methane greenhouse triggered the Huronian glaciation, Earth's first snowball Earth event. Between approximately 2.4 and 2.1 billion years ago, ice sheets expanded from the poles toward the equator, eventually covering much of the planet in ice. Glacial deposits from this period appear at low latitudes, indicating that ice reached tropical regions. Some researchers interpret this as evidence that Earth froze almost entirely, with ice covering the oceans from pole to pole. The Huronian glaciation may have consisted of multiple distinct glacial episodes separated by warmer interglacial periods. Sedimentary rocks from the Huronian supergroup in Canada preserve evidence of at least 3 separate glaciations during this time interval. Each glaciation lasted millions to tens of millions of years. The temperature fluctuations reflect feedback mechanisms in the climate system, with ice albedo feedback driving cooling, while carbon dioxide accumulation from volcanism eventually drove warming. During the most severe phases, global average temperatures may have dropped below -50 degrees Celsius. Ice thickness at mid-latitudes reached hundreds of meters to possibly several kilometers. Ocean surfaces froze over, except perhaps for some open water near the equator or near volcanic hotspots. The frozen ocean surface reflected most incoming sunlight back to space, making it extremely difficult for the planet to warm up even as volcanic carbon dioxide slowly accumulated in the atmosphere. Life survived the Huronian glaciation, though likely in reduced numbers and diversity. Refugia near volcanic hotspots, in the deep ocean near hydrothermal vents, and under the ice in meltwater pockets provided habitable environments. Cyanobacteria continued photosynthesizing in these refugia, possibly beneath thin ice where some sunlight could penetrate. The survival of photosynthetic life through the glaciation ensured that oxygen production would continue, preventing a return to the anoxic conditions of the Archean. The glaciation ended when volcanic carbon dioxide accumulated to sufficient levels to overwhelm the ice albedo feedback. Volcanic outgassing continued throughout the glaciation, adding carbon dioxide to the atmosphere, while the frozen ocean prevented weathering of silicate rocks. The main sink for atmospheric carbon dioxide. Over tens of millions of years, carbon dioxide concentrations rose to perhaps 100 to 300 times current levels, creating a greenhouse effect powerful enough to begin melting the ice. Once melting started, the ice albedo feedback reversed. Darker ocean water, exposed by melting ice, absorbed more sunlight, accelerating further warming in a runaway deglaciation. The planet transitioned from snowball to hothouse within perhaps only 10,000 years once the warming threshold was crossed. Ocean chemistry changes. The Great Oxidation Event fundamentally altered ocean chemistry. The Archean Ocean had been anoxic and iron-rich, with dissolved ferrous iron giving the water a greenish tint. As oxygen produced by cyanobacteria spread through the ocean, it reacted with this dissolved iron, precipitating it as iron oxides. The precipitation formed banded iron formations, the last great deposits of this distinctive rock. Banded iron formation deposition peaked around 2.5 billion years ago and ended by approximately 1.85 billion years ago. The cessation of banded iron formation marks the completion of ocean oxygenation. With dissolved iron removed, oxygen could accumulate in seawater. The deep ocean took longer to oxygenate than surface waters because of limited mixing and continued consumption of oxygen by organic matter sinking from the surface. A stratified ocean developed with oxygenated surface waters overlying anoxic deep waters. This stratification persisted throughout much of the Proterozoic. Surface waters, in contact with the oxygenated atmosphere, maintained oxygen concentrations sufficient for aerobic organisms. The deep ocean remained anoxic, with sulfate reduction producing hydrogen sulfide that accumulated in deep waters. The boundary between oxygenated surface waters and anoxic deep waters was sharp, creating a chemocline where chemical conditions changed abruptly over a few meters' depth. Organisms living near this chemocline experienced extreme chemical gradients, driving evolutionary innovations in metabolism. Sulfate concentrations increased in the ocean as sulfide minerals on continents oxidized and weathered, delivering sulfate to rivers and eventually to the ocean. Sulfate-reducing bacteria, previously limited by low sulfate availability, expanded into new habitats. The sulfur cycle became more complex, with oxidation and reduction reactions cycling sulfur between different oxidation states. This increased cycling enhanced the biological productivity of the ocean by making nutrients more. The ozone layer forms. One beneficial consequence of atmospheric oxygenation was the formation of the ozone layer. Ozone forms in the stratosphere when ultraviolet radiation from the sun splits oxygen molecules into individual oxygen atoms. These atoms then combine with other oxygen molecules to form ozone, a molecule consisting of 3 oxygen atoms. Ozone absorbs ultraviolet radiation particularly effectively, preventing most ultraviolet photons from reaching Earth's surface. Before the ozone layer formed, intense ultraviolet radiation bathed Earth's surface. This radiation was lethal to most organisms, limiting life to underwater environments where several meters of water absorbed the ultraviolet before it could harm cells. The appearance of stratospheric ozone between 2.4 and 2.1 billion years ago reduced surface ultraviolet intensity by roughly 90%, making the land surface habitable for the first time. However, life would not colonize land for another 1.5 billion years. The Paleoproterozoic atmosphere, while containing oxygen and ozone, still had oxygen levels far too low to support complex aerobic organisms. Plants and animals require oxygen concentrations approaching modern levels, roughly 20% of the atmosphere by volume. The Paleoproterozoic atmosphere contained perhaps 1% of current levels, sufficient for ozone formation but inadequate for large aerobic organisms. Colonization of land would await further oxygen accumulation during the Neoproterozoic and Paleozoic. A transformed world. By 2.1 billion years ago, Earth had been fundamentally transformed. The atmosphere contained oxygen, though at modest levels compared to today. The ocean was stratified, with oxygenated surface waters and anoxic deep waters. Banded iron formations no longer accumulated because dissolved iron had been exhausted. The methane greenhouse had collapsed, replaced by a carbon dioxide-dominated greenhouse supplemented by rising oxygen. The planet had survived its first snowball Earth event, emerging into warmer conditions. Life had been reshaped by the oxygen catastrophe. Anaerobic organisms survived only in oxygen-poor refugia. Aerobic organisms diversified rapidly, exploiting the high-energy yields available from aerobic respiration. Cyanobacteria, the organisms whose waste product triggered the transformation, continued thriving in oxygenated surface waters. The stage was set for the next major evolutionary transition: the origin of eukaryotic cells, complex organisms that would internalize aerobic bacteria as mitochondria and eventually give rise to all multicellular life, including plants, animals, and fungi. But that transition required stable oxygenated conditions and would not occur for several 100 million years as Earth's oxygen levels fluctuated and gradually stabilized. Chapter 16: The Rise of Eukaryotic Cells. Somewhere between 2.1 and 1.6 billion years ago, a momentous event occurred that would change the course of evolution forever. An archaeal cell engulfed a bacterium, perhaps intending to digest it for food. The bacterium, an aerobic organism capable of using oxygen to generate energy, was not digested. Instead, it survived inside its host, establishing a permanent residence within the archaeal cell's interior. This relationship, initially perhaps parasitic or merely tolerated, evolved into mutualism. The bacterium processed oxygen and generated energy-rich molecules that the host could use. The host provided protection and raw materials. Over time, the bacterium transferred most of its genes to the host nucleus, becoming an organelle completely dependent on the host cell, the mitochondrion. This endosymbiotic event was so successful that all modern eukaryotes, from single-celled amoebas to humans, descend from that single ancestral merger. The evolution of eukaryotic cells opened possibilities that prokaryotes could never achieve. Large size, complex internal organization, and eventually multicellularity, with specialized cell types cooperating within a single organism. The endosymbiotic theory. The idea that mitochondria originated as free-living bacteria seems radical, but is supported by overwhelming evidence. Mitochondria retain their own DNA, a small circular chromosome similar to bacterial chromosomes, and unlike the linear chromosomes in the eukaryotic nucleus. Mitochondrial DNA encodes only a few dozen genes, far fewer than the thousands present in free-living bacteria, but these genes are clearly bacterial in origin. Their sequences match those of alpha protobacteria, a group of bacteria that includes many aerobic species living today. Mitochondria replicate through division, splitting into two daughter mitochondria just as bacteria divide. This division proceeds independently of the host cell's division cycle, though it must be coordinated to ensure that daughter cells receive mitochondria. The replication machinery mitochondria use resembles bacterial replication machinery more than eukaryotic replication machinery. Mitochondria have their own ribosomes, smaller than eukaryotic ribosomes, and more similar to bacterial ribosomes in size and structure. The mitochondrial membrane also tells a story of bacterial ancestry. The inner mitochondrial membrane contains cardiolipin, a phospholipid common in bacteria but rare elsewhere in eukaryotic cells. The protein import machinery in the outer mitochondrial membrane resembles systems bacteria use to secrete proteins, repurposed to import nuclein-coded proteins into the mitochondrion. These molecular fossils preserve evidence of the mitochondrion's bacterial past, despite billions of years of evolution. The timing of mitochondrial acquisition was critical for eukaryotic evolution. Current evidence suggests that the mitochondrial endosymbiont was acquired early, possibly before the host had evolved many characteristic eukaryotic features like a nucleus. The endosymbiont may have driven the evolution of these features by creating selective pressures for better management of the host-endosymbiont relationship. An alternative hypothesis suggests that some eukaryotic features evolved first, creating conditions favorable for hosting an endosymbiont. The debate continues, but most researchers agree that mitochondria were present in the last eukaryotic common ancestor, meaning all modern eukaryotes inherited mitochondria from this. Energy and complexity. The acquisition of mitochondria solved a fundamental problem that limited prokaryotic complexity. Generating cellular energy requires membrane-bound proteins that pump protons across membranes, creating electrochemical gradients. The energy stored in these gradients drives ATP synthesis, the universal energy currency of cells. Prokaryotes generate these gradients across their outer cell membrane. This works well for small cells, but energy production scales with membrane area while cell volume scales with the cube of radius. As cells grow larger, the membrane area per unit volume decreases, limiting energy production per unit biomass. Eukaryotic cells solved this scaling problem by internalizing energy production within mitochondria. A large eukaryotic cell can contain hundreds or thousands of mitochondria, each with extensive internal membrane area for energy production. The total membrane area available for ATP synthesis scales with cell volume rather than just with cell surface area. This allows eukaryotic cells to grow much larger than prokaryotes while maintaining sufficient energy production. The energy advantage provided by mitochondria was enormous. A typical eukaryotic cell generates approximately 100,000 times more energy per gene than a prokaryotic cell. This energy surplus funded the evolution of complex features: an elaborate cytoskeleton for transporting materials within the cell, a nucleus for protecting and organizing DNA, an endomembrane system for processing proteins and lipids, and mechanisms for engulfing other cells through phagocytosis. These features require energy to build and maintain, energy that only mitochondria could provide in sufficient quantities. Evolution of the nucleus. The nucleus represents one of the defining features of eukaryotic cells, yet its evolutionary origin remains debated. The nucleus is a membrane-bound compartment that sequesters chromosomes, separating transcription from translation. In prokaryotes, transcription and translation occur simultaneously in the same cellular compartment. In eukaryotes, DNA is transcribed into RNA in the nucleus. Then the RNA is transporting through nuclear pores to the cytoplasm, where ribosomes translate it into protein. This separation allows for regulatory complexity impossible in prokaryotes. The RNA produced by transcription can be edited, spliced, and modified before translation. Alternative splicing creates multiple different proteins from a single gene by including or excluding different combinations of exons. Regulatory proteins can control which RNAs are exported from the nucleus and when. The delay between transcription and translation provides additional checkpoints where gene expression can be controlled. The nuclear envelope evolved from the endoplasmic reticulum, part of the endomembrane system. The double membrane surrounding the nucleus is continuous with the endoplasmic reticulum, reflecting its evolutionary origin. Nuclear pore complexes, large protein structures that control transport between nucleus and cytoplasm, likely evolved from proteins originally involved in membrane fusion. Over evolutionary time, these proteins specialized for controlled transport while maintaining their ability to allow membrane continuity. One hypothesis links nuclear evolution to the mitochondrial endosymbiosis. The presence of an endosymbiont created selective pressure for protecting the host genome from foreign DNA. Mitochondria initially contained thousands of genes, many of which transferred to the host nucleus over time. Managing these gene transfers and preventing mitochondrial DNA from disrupting host gene expression may have favored the evolution of a nuclear envelope. The nucleus provided a protected environment where host DNA could be carefully regulated, while genetic material from the endosymbiont was gradually integrated and domesticated. The first eukaryotes. Dating the origin of eukaryotes proves challenging because early eukaryotes were microscopically small and left limited fossil evidence. Molecular clock analyses, which estimate divergence times by counting genetic differences between organisms and assuming mutation, occurs at relatively constant rates, suggest eukaryotes arose between 2.3 and 1.6 billion years ago. This wide range reflects uncertainties in molecular clock calibration and different assumptions about mutation rates. The earliest putative eukaryotic fossils date to approximately 2.1 billion years ago. These microfossils show cell sizes and shapes consistent with eukaryotic cells, though morphology alone cannot definitively prove eukaryotic identity. More convincing evidence comes from biomarkers, molecular fossils of lipids that are diagnostic of eukaryotic metabolism. Stearanes, breakdown products of sterols like cholesterol that only eukaryotes synthesize, appear in rocks dating to 1.6 billion years ago, providing strong evidence that eukaryotes existed by this time. The early eukaryotes were likely simple single-celled organisms living in marine environments. They would have been larger than typical bacteria, but smaller than modern protists like amoebas or paramecia. They possessed mitochondria, a nucleus, and probably a rudimentary endomembrane system. They could perform phagocytosis, engulfing food particles by wrapping their cell membrane around them and bringing them inside. This ability was crucial because it was the mechanism through which they acquired the bacterial endosymbiont that became mitochondria. Early eukaryotes diversified slowly at first. For hundreds of millions of years, they remained relatively rare compared to the dominant prokaryotes. Only when atmospheric oxygen levels rose during the later Proterozoic did eukaryotes begin radiating into the diversity of forms we see today. Higher oxygen levels allowed aerobic respiration to become more efficient, providing eukaryotes with more energy to fuel their complex cellular machinery. Chloroplasts, a second endosymbiosis. Some eukaryotes acquired photosynthetic capability through a second endosymbiotic event. A eukaryotic cell that already possessed mitochondria engulfed a cyanobacterium, the same group of bacteria that had oxygenated Earth's atmosphere hundreds of millions of years earlier. Like the mitochondrial endosymbiont, the cyanobacterium was not digested, but instead established permanent residence inside the host cell, eventually becoming the chloroplast. Chloroplasts, like mitochondria, retain remnants of their bacterial heritage. They have circular DNA encoding genes clearly derived from cyanobacteria. They replicate through division. They have double membranes, reflecting the engulfment process that brought them into the cell. The inner membrane corresponds to the original cyanobacterial membrane, while the outer membrane came from the host cell's engulfing vesicle. Chloroplast ribosomes resemble bacterial ribosomes in structure and antibiotic sensitivity. The chloroplast endosymbiosis occurred later than the mitochondrial endosymbiosis and happened independently in different eukaryotic lineages. The primary endosymbiosis that gave rise to plant chloroplasts occurred approximately 1.5 billion years ago. Additional secondary and tertiary endosymbioses occurred when eukaryotes that already had chloroplasts were themselves engulfed by other eukaryotes, creating complex nested endosymbiotic relationships visible today in various algal groups. The acquisition of chloroplasts transformed the eukaryotes that received them. These photosynthetic eukaryotes could generate their own food from sunlight, water, and carbon dioxide, making them independent of external organic carbon sources. They diversified into numerous algal lineages that became the base of aquatic food chains. One lineage eventually colonized land, giving rise to land plants that would transform terrestrial environments during the Paleozoic and later eras. Increased genetic complexity. Eukaryotic genomes are vastly larger and more complex than prokaryotic genomes. While a typical bacterium has 3 to 5 million base pairs of DNA encoding several thousand genes, eukaryotic genomes range from 10 million to over 100 billion base pairs. The human genome contains over 3 billion base pairs, encoding approximately 20,000 protein-coding genes, plus vast amounts of non-coding DNA, including regulatory sequences, introns, and repetitive elements. Much of this increased complexity arose from gene duplication events. When genes duplicate, one copy can retain the original function, while the other is free to evolve new functions. Over evolutionary time, repeated duplication events built gene families with related but distinct functions. Whole genome duplications occurred multiple times in eukaryotic evolution, instantly doubling the entire genetic repertoire and providing raw material for evolutionary innovation. Introns, non-coding sequences within genes that are removed from RNA during splicing, proliferated in eukaryotic genomes. Most prokaryotic genes lack introns, but eukaryotic genes often contain numerous introns interrupting coding sequences. Introns provide flexibility through alternative splicing and may facilitate evolution by allowing new functional domains to be mixed and matched through recombination. The origin of introns remains debated, with some evidence suggesting they existed in the earliest life forms but were lost in prokaryotes while being retained in eukaryotes. Sexual reproduction evolved in early eukaryotes, fundamentally changing how genetic variation is generated and distributed. Sexual reproduction involves meiosis, specialized cell divisions that create gametes with half the normal chromosome number, and fertilization, the fusion of gametes to restore the full chromosome number. This process shuffles genetic variation through recombination, creating offspring with novel gene combinations. Sexual reproduction accelerated evolution by more efficiently spreading beneficial mutations through populations, and by creating genetic diversity that selection could act upon, setting the stage for complexity. By 1.6 billion years ago, eukaryotic cells had established themselves in marine environments. They possessed all the fundamental features that would allow them to evolve into the spectacular diversity of eukaryotic life we see today. Mitochondria for energy production, nuclei for genetic control, endomembranes for processing and transport, cytoskeletons for structure and movement, and sexual reproduction for generating variation. Some lineages had acquired chloroplasts, making them photosynthetic. The rise of eukaryotes represented a transition as significant as the origin of life itself. Prokaryotes had dominated Earth for over 2 billion years, achieving remarkable metabolic diversity but remaining limited to relatively simple single-celled forms. Eukaryotes broke through these limitations, achieving sizes and complexities impossible for prokaryotes. Path was now open for the next major transition, the evolution of multicellularity, where individual cells would cooperate within unified organisms, specializing and coordinating their activities to build bodies of astonishing complexity. That transition would occur during the Neoproterozoic, still hundreds of millions of years in the future, as Proterozoic eukaryotes continued diversifying in an ocean that was gradually becoming more oxygenated and more hospitable to complex life. Chapter 17: Suppositions and Stasis. The dance of continents never stopped. Throughout Earth's history, continents drifted across the planet's surface, driven by convection currents in the underlying mantle. They collided, forming mountain ranges where their edges crumpled together. They rifted apart, creating new ocean basins where magma welled up to fill the gap. On timescales of hundreds of millions of years, these movements followed a cycle. Continents assembled into supercontinents, remained together briefly by geological standards, then fragmented and dispersed before eventually reassembling into new supercontinents. The Proterozoic eon witnessed several iterations of this supercontinent cycle. Kennorland assembled around 2.7 billion years ago from Archean cratons and broke apart by 2.5 billion years ago. Columbia, also called Nuna, formed between 2.1 and 1.8 billion years ago and persisted until approximately 1.5 billion years ago. These continental assemblies profoundly influenced Earth's climate, ocean chemistry, and biological evolution, setting the stage for transformations that would follow. Kennorland, the first supercontinent. Kennorland represents one of Earth's earliest supercontinents, assembling near the end of the Archean eon, around 2.72 billion years ago. The supercontinent formed through accretion events where separate cratons collided and fused together. The Yilgarn Craton in Western Australia records these accretion events in its greenstone belts. Metamorphosed basaltic sequences that were squeezed and heated during collisions. The craton's core contains metamorphic rocks as old as 3.2 billion years, with younger material accreted around this ancient nucleus over hundreds of millions of years. Other cratons that likely formed part of Kennorland include the Superior Craton in North America, portions of the Baltic Shield in Scandinavia, and possibly the Wyoming Craton. Reconstructing Kennorland's exact configuration remains challenging because subsequent tectonic activity has obscured the evidence. The continents that once comprised Kennorland have been reworked, split apart, and reassembled multiple times over the past 2.5 billion years, erasing many geological clues about their original arrangement. The breakup of Kennorland began around 2.5 billion years ago, coinciding with the transition from the Archean to the Proterozoic eon. Rifting split the supercontinent into separate fragments that drifted apart. Evidence for this rifting comes from sedimentary sequences typical of continental rifts, and from ophiolites, fragments of oceanic crust thrust onto continental margins that indicate ocean basins opened between the separating continents. By 2.45 billion years ago, an ocean existed between what are now the Kola and Karelia cratons, demonstrating that Kennorland had fragmented. The timing of Kenorland's breakup coincides with major geological transitions. The shift from Archean to Proterozoic marks changes in tectonic style, with plate tectonics becoming more organized and resembling modern patterns. Some researchers propose that Kenorland's breakup represents the transition from deep mantle plume-dominated tectonics to the two-layer core mantle convection system that drives modern plate tectonics. The Earth's inner core may have solidified around this time, changing the pattern of mantle convection and influencing how continents moved. Columbia, assembly and configuration. Columbia, also known as Nuna, assembled between approximately 2.1 and 1.8 billion years ago during the Paleoproterozoic. The supercontinent formed through massive collisions between cratons that had separated when Kenorland broke apart. These collisions generated enormous mountain ranges comparable to the modern Himalayas, but extending for thousands of kilometers. The collision zones underwent metamorphism under high pressure and temperature, creating distinctive rock assemblages that geologists use to reconstruct Columbia's configuration. The assembly of Columbia proceeded in two main stages. The first stage, between 2.0 and 1.8 billion years ago, created a megacontinent called Nuna through collisions characterized by bimodal metamorphism. Some collision zones produced high-pressure, low-temperature rocks typical of subduction zones, while others generated high-temperature, low-pressure rocks characteristic of continental collision. These contrasting metamorphic signatures appear in major mobile belts that sutured together the megacontinent's center. The second stage, between 1.8 and 1.6 billion years ago, involved the final assembly of Columbia through soft collisional origins that recorded intermediate to high temperature-to-pressure metamorphism. This second stage produced different metamorphic signatures than the first, suggesting changes in tectonic style or collision geometry. The completed Columbia supercontinent persisted for several hundred million years before beginning to fragment. Columbia's configuration placed multiple modern continents in contact. Laurentia, the core of North America, likely occupied a central position. Baltica, which includes Scandinavia and parts of Eastern Europe, adjoined Laurentia's northeastern margin. Siberia, Australia, and portions of Antarctica were also part of Columbia, though their exact positions remain debated. China may have comprised multiple separate blocks during this time, some attached to Columbia and others independent. Evidence for Columbia's configuration comes from matching geological features across continents that are now separated by oceans. Sedimentary sequences of the same age and composition on different continents suggest they were deposited in the same basin before the continents rifted apart. Ophiolites of approximately the same age indicate when rifting produced oceanic crust. Volcanic rocks, typical of island arcs, mark where continental margins became subduction zones, signaling the beginning of ocean closure and eventual collision. The boring billions. Between approximately 1.8 and 0.8 billion years ago, Earth entered a period of remarkable stability that geologists informally call the boring billion. This billion-year interval, encompassing much of the Mesoproterozoic era, was characterized by minimal changes in climate, ocean chemistry, atmospheric composition, and biological evolution. Some researchers refer to it as Earth's Middle Ages due to the apparent lack of tectonic activity and evolutionary innovation. The boring billion exhibited geological stasis with little evidence of major mountain-building events or continental collisions. The supercontinent Columbia persisted for much of the early boring billion before breaking apart around 1.5 billion years ago. After Columbia's fragmentation, continents drifted but did not immediately reassemble into a new supercontinent. This prolonged dispersed configuration may have contributed to the stability characteristic of the period. Ocean chemistry remained remarkably constant throughout the boring billion. The deep ocean was anoxic but not sulfidic, a condition called ferruginous. Dissolved iron accumulated in deep waters because insufficient oxygen was available to oxidize it. However, sulfate levels were low enough that sulfate-reducing bacteria could not produce large amounts of hydrogen sulfide. This stable ferruginous condition persisted for hundreds of millions of years with minimal fluctuation. The atmosphere contained oxygen, but at levels far below modern concentrations. Atmospheric oxygen during the boring billion remained at roughly 1 to 10% of present atmospheric levels. This was sufficient to maintain an ozone layer that shielded the surface from ultraviolet radiation, but insufficient to support large, energetically demanding organisms. Oxygen concentrations showed little change throughout the period, neither increasing nor decreasing significantly. Carbon isotope ratios in sedimentary rocks show remarkably flat trends during the boring billion. Normally, carbon isotopes fluctuate as the balance between organic carbon burial and carbonate precipitation changes. These fluctuations reflect variations in biological productivity, ocean circulation, and climate. The flat isotope trend during the boring billion suggests that these factors remained extremely stable for hundreds of millions of years, an unprecedented interval of stasis. Environmental conditions. The boring billion was not truly boring, despite its name. Significant processes operated during this time, but they proceeded slowly and steadily without dramatic fluctuations. The stable environmental conditions actually set the stage for later evolutionary innovations, creating a prolonged period where organisms could gradually adapt and diversify without facing repeated environmental catastrophes. Nutrient availability limited biological productivity. Phosphorus, the key limiting nutrient in most marine environments, was scarce because weathering rates on land were low. With oxygen levels modest, chemical weathering of phosphorus-bearing rocks proceeded slowly. Rivers delivered limited phosphorus to the oceans, constraining the growth of photosynthetic organisms. Low productivity meant limited organic matter production, which in turn limited the oxygen demand from respiration and decomposition. The stratified ocean created distinct chemical environments at different depths. Surface waters were oxygenated through contact with the atmosphere and photosynthesis by cyanobacteria and early eukaryotic algae. These oxygenated surface waters extended to depths of perhaps 100 to several hundred meters. Below this lay anoxic deep waters where oxygen was absent. The boundary between oxygenated and anoxic waters, called the chemocline, was relatively stable, but could shift vertically in response to changes in productivity or ocean circulation. Within the anoxic deep waters, conditions were predominantly ferruginous rather than sulfidic. At least 30 to 40% of the seafloor was covered by anoxic waters, a far greater extent than in the modern ocean where anoxia is largely restricted to a few isolated basins. However, sulfidic conditions covered less than 1 to 10% of the seafloor, much less than the extent of anoxia. This unusual chemistry reflects the balance between sulfate availability, organic matter supply, and ion input from hydrothermal vents and continental weathering. Temperature was relatively warm despite moderate greenhouse gas concentrations. The methane greenhouse that warmed the Archean Earth had collapsed during the Great Oxidation event. Carbon dioxide concentrations were probably higher than today, but not dramatically so. The warm climate resulted partly from the continental configuration, with dispersed continents creating less land area at high latitudes where ice sheets could form. The warm conditions persisted throughout the boring billion, maintaining ice-free poles for hundreds of millions of years. Life during stasis. Biological evolution did not stop during the boring billion, but it proceeded slowly compared to the periods before and after. The stable environmental conditions provided few selective pressures, driving rapid evolutionary change. Organisms adapted to the low oxygen, nutrient-poor conditions, and continued existing in those conditions for hundreds of millions of years with relatively little modification. Eukaryotes underwent their major diversification near the end of the boring billion rather than during it. Molecular clock analyses suggest that the basal radiation of extant eukaryotes occurred around 1.1 billion years ago, near the Mesoproterozoic-Neoproterozoic boundary. This timing places the major diversification of eukaryotic lineages at the end of the boring billion rather than during its middle. Earlier Proterozoic fossils of possible eukaryotic origin mostly cannot be confidently assigned to modern lineages, suggesting they represent extinct stem groups rather than ancestors of living eukaryotes. The delayed diversification of complex eukaryotes resulted from environmental constraints, particularly low oxygen and nutrient limitation. Eukaryotic cells require more energy than prokaryotic cells because of their larger size and complex internal organization. In low oxygen conditions, aerobic respiration is less efficient, reducing the energy available for growth and reproduction. Nutrient limitation further constrained eukaryotic productivity, preventing population expansion and ecological diversification. Prokaryotic life remained dominant throughout the boring billion. Cyanobacteria continued photosynthesizing in surface waters, producing oxygen that was largely consumed by reactions with reduced minerals and organic matter. Anoxygenic photosynthetic bacteria thrived in low-oxygen environments, using light energy without producing oxygen as waste. These bacteria may have consumed substantial amounts of oxygen through their metabolism, contributing to the stable low-oxygen conditions. Heterotrophic bacteria decomposed organic matter, releasing nutrients back into solution. Geological quiet. Tectonic activity continued during the boring billion, but at reduced intensity compared to earlier and later periods. Mountain building events were uncommon, with few orogenies recorded in the geological record. This tectonic quiet may reflect the dispersed continental configuration following Columbia's breakup. When continents are scattered, collision events become less frequent, reducing mountain building and the associated crustal deformation, metamorphism, and magmatism. The reduced tectonic activity had consequences for ocean chemistry and atmospheric composition. Mountain building exposes fresh rock to weathering, which consumes atmospheric carbon dioxide and releases nutrients to the ocean. With minimal mountain building during the boring billion, weathering rates were low, limiting carbon dioxide consumption and nutrient release. This contributed to the stable atmospheric composition and low biological productivity characteristic of the period. Continental rifting began late in the boring billion as continents started moving toward a new assembly that would form the supercontinent Rodinia. The first signs of rifting appeared around 1.3 billion years ago with intrusions of basaltic dikes in several locations. These dikes formed when magma rose from the mantle through cracks in the crust, a common precursor to continental rifting. The rifting intensified between 1.0 and 0.9 billion years ago as continents moved toward collision, eventually assembling into Rodinia. The boring billion ended around 800 to 700 million years ago as Earth entered a period of dramatic environmental change. Atmospheric oxygen began rising during the Neoproterozoic oxygenation event, reaching levels several times higher than during the boring billion. The supercontinent Rodinia began breaking apart, triggering climate instability that led to severe glaciations. Eukaryotes diversified rapidly, evolving into most of the major lineages we recognize today. The long period of stasis gave way to an era of transformation that would culminate in the appearance of complex multicellular life in the Ediacaran period. Chapter 18, Rodinia and Rifting. Around 1.3 billion years ago, continents began converging toward a new assembly. Over the next several hundred million years, these moving landmasses collided in a series of mountain-building events, welding together into the supercontinent Rodinia. The name comes from the Russian word for homeland, reflecting the hypothesis that Rodinia served as the ancestral configuration from which later continents descended. Rodinia incorporated almost all of Earth's continental crust into a single massive landmass that persisted for approximately 450 million years. The assembly of Rodinia through continental collisions built mountain ranges that rivaled or exceeded modern examples in scale. The subsequent breakup of Rodinia beginning around 750 million years ago initiated a cascade of environmental changes that would transform Earth's climate, ocean chemistry, and biological evolution. setting the stage for the emergence of animals in the Ediacaran period. Assembly through collision. Rhydinia formed through the convergence of continental fragments left over from Columbia's breakup. These fragments, having drifted apart over hundreds of millions of years, began moving back together around 1.3 billion years ago. The collisions occurred over an extended period, with different continental blocks joining at different times. Evidence for these collisions appears in orogenic belts, zones of intense deformation. Metamorphism and magmatism that formed where continents collided. The most extensively studied orogeny associated with Rhydinia's assembly is the Grenville orogeny, which affected what is now eastern North America. This mountain-building event occurred between approximately 1.3 and 1.0 billion years ago as Laurentia, the core of North America, collided with another large continent, possibly Amazonia, or a composite of several smaller blocks. The collision created mountains that may have rivaled the modern Himalayas in height, extending for thousands of kilometers along Laurentia's southeastern margin. The Grenville orogeny left a prominent orogenic belt that spans from Labrador to Mexico and extends across the Atlantic to Scotland. This belt consists of highly metamorphosed and deformed rocks that were buried deep in the crust during collision, then later uplifted and exposed by erosion. The metamorphic conditions recorded in these rocks indicate pressures and temperatures equivalent to depths of 20 to 40 kilometers, demonstrating the enormous forces involved in continental collision. Similar-aged orogenies occurred on other continents, indicating that Rhydinia's assembly involved multiple collision events scattered across the globe. Australia experienced collisions between 1.3 and 1.0 billion years ago. Parts of Antarctica, India, and South America preserve metamorphic rocks of the same age range. Correlating these orogenic belts across continents helps geologists reconstruct which continents were adjacent in Rhydinia and how they fit together. The assembly process was not instantaneous. Rhydinia came together over hundreds of millions of years as different continental blocks collided at different times. The process likely began around 1.3 billion years ago and concluded by approximately 1.0 billion years ago. During the intervening 300 million years, the configuration gradually evolved as new collisions added blocks to the growing supercontinent, while rifting may have separated other blocks. Rhydinia's configuration. Reconstructing Rhydinia's exact configuration remains challenging and controversial. Unlike more recent supercontinents such as Pangaea, for which abundant paleomagnetic and geological data constrain reconstructions, Rhydinia's ancient age means that much evidence has been obscured by subsequent geological activity. Different research groups have proposed different configurations, and debate continues about which continents were adjacent and how they were oriented. Most reconstructions place Laurentia at or near Rhydinia's center. This positioning is relatively well constrained by geological and paleomagnetic evidence. Australia and East Antarctica were likely positioned along Laurentia's western margin, though their exact orientations remain debated. Baltica, which includes Scandinavia and parts of Eastern Europe, probably lay adjacent to Laurentia's northern or northeastern margin. Amazonia, the core of South America, may have been positioned along Laurentia's southeastern margin based on evidence from the Grenville orogeny. Other continental blocks whose positions are less certain include Siberia, South China, North China, and several smaller cratons. Some reconstructions place these blocks within Rhydinia, while others suggest they remained independent during Rhydinia's existence, forming separate smaller continents that only later collided with fragments of broken-up Rhydinia. The Congo and São Francisco cratons may have either detached from Rhydinia during its breakup or never been part of the supercontinent at all. The paleomagnetic record shows a significant gap between about 1.075 billion and 900 million years ago, limiting understanding of Rhydinia's configuration during this interval. Recent work collecting samples from the Freda Formation near Lake Superior helps fill this gap, providing data from approximately 1.045 billion years ago. These data, combined with stratigraphic age modeling, help constrain paleopole positions, improving reconstructions of how continents moved during Rodinia's assembly. Mountains and weathering. The assembly of Rodinia through continent-continent collisions built enormous mountain ranges. These mountains underwent weathering and erosion, breaking down the rocks and transporting the debris to lowland basins and eventually to the ocean. The weathering of silicate rocks consumes atmospheric carbon dioxide through reactions that convert carbon dioxide and minerals into bicarbonate ions and new mineral phases. Enhanced weathering during periods of active mountain building can draw down atmospheric carbon dioxide, potentially cooling the climate. The massive mountains created during Rodinia's assembly likely increased weathering rates significantly compared to periods when continents were dispersed and topography was subdued. This enhanced weathering would have consumed carbon dioxide, gradually lowering atmospheric concentrations over millions of years. However, during Rodinia's assembly in the Mesoproterozoic, the climate remained relatively stable and warm. The expected cooling from enhanced weathering did not materialize or was compensated by other factors such as changes in volcanic outgassing rates or ocean circulation patterns. The boring billion's climatic stability persisted through much of Rodinia's assembly, suggesting that weathering feedbacks were either weaker than expected or balanced by opposing processes. The mountains also influenced ocean chemistry by delivering nutrients from weathering to the sea. Phosphorus, released from weathering of continental rocks, provided the key limiting nutrient for photosynthetic organisms. Enhanced weathering during mountain building should have increased phosphorus delivery, potentially stimulating biological productivity. However, productivity appears to have remained low during much of the boring billion, suggesting that phosphorus delivery was limited even with enhanced weathering, or that other factors constrained productivity. The breakup begins. Rodinia remained intact for approximately 450 million years, from roughly 1.1 billion to 750 million years ago. During this time, the supercontinent drifted across Earth's surface, driven by mantle convection beneath it. Internally, Rodinia experienced relatively little tectonic activity once assembly was complete. The stable continental configuration created the conditions characteristic of the late boring billion, with minimal mountain building and subdued tectonic activity. The first signs of Rodinia's breakup appeared around 1 billion years ago with the intrusion of basaltic dikes in several locations. These dikes formed when mantle-derived magma exploited cracks in the continental crust, rising to shallow levels and solidifying as narrow vertical sheets of basalt. Dike swarms, clusters of parallel or radiating dikes, often precede continental rifting by tens of millions of years, reflecting the initial stages of lithospheric extension. Major rifting began around 850 to 800 million years ago. A mantle plume, a rising column of hot rock from deep in the mantle, may have triggered the breakup by impinging on the base of the lithosphere beneath Rodinia. The plume's heat caused partial melting, generating basaltic magma that intruded into the overlying crust. The thermal expansion from heating caused the lithosphere to dome upward and fracture, initiating rifting. Rifting did not start everywhere simultaneously, but propagated through Rodinia over hundreds of millions of years. Some margins began rifting around 800 million years ago, while others remained intact until 700 million years ago or later. The differential timing reflects the complex pattern of stresses within the supercontinent and the locations where mantle plumes or other processes initiated extension. Around 750 to 700 million years ago, rifting accelerated dramatically. Extensive lava flows erupted across multiple continents, evidence for large-scale rifting and magmatism. These flood basalts, enormous volumes of lava that covered hundreds of thousands of square kilometers, formed when mantle plumes delivered massive amounts of magma to the surface. The flood basalts marked the transition from incipient rifting to active seafloor spreading, where new oceanic crust formed between the separating continental fragments. Ocean basins open. As Rodinia rifted apart, new ocean basins opened between the separating continental fragments. The Adamastor Ocean formed between what would become South America, Africa on one side and Australia, East Antarctica, India on the other. This ocean opened during the Ediacaran period as rifting progressed. Other oceans opened between different continental blocks as Rodinia disintegrated into multiple fragments. The opening of new ocean basins had profound effects on ocean circulation and chemistry. When continents are assembled into a supercontinent, ocean circulation is restricted. A single large landmass blocks east-west flow, forcing currents to flow around the supercontinent's margins. When the supercontinent breaks apart, new seaways open that allow more complex circulation patterns. These new circulation patterns can transport more oxygen to deep waters, gradually oxygenating the ocean. The breakup of Rodinia also increased the length of continental margins. Continental margins are sites of high biological productivity because upwelling brings nutrient-rich deep water to the surface where photosynthetic organisms can use it. Longer continental margins mean more total upwelling and higher global productivity. The increased productivity during Rodinia's breakup may have contributed to the rise in atmospheric oxygen that occurred during the Neoproterozoic. Seafloor spreading at mid-ocean ridges increased as new ocean basins opened. Young oceanic crust near spreading centers is hot and thermally expanded, displacing seawater and causing sea level to rise. The proliferation of new spreading centers during Rodinia's breakup may have caused a long-term sea level rise, flooding low-lying continental areas and creating extensive shallow seas. These shallow marine environments became sites of carbonate deposition and provided habitats for early animals evolving in the Ediacaran. Environmental consequences. Rodinia's breakup initiated a cascade of environmental changes that ended the boring billion's stability. Atmospheric oxygen began rising during the Neoproterozoic oxygenation event, increasing from roughly 1 to 10% of present levels during the boring billion to perhaps 50 to 70% of modern levels by 600 million years ago. This oxygen rise resulted from multiple factors, including enhanced organic carbon burial during rifting, increased nutrient delivery from weathering, and changes in ocean circulation that allowed oxygen to penetrate to greater depths. Climate became dramatically unstable during Rodinia's breakup. Earth experienced two severe glaciations around 710 and 650 million years ago, the Sturtian and Marinan glaciations. These glaciations were so intense that ice may have covered the entire planet from poles to equator, creating a snowball Earth. The glaciations alternated with hothouse conditions as carbon dioxide accumulated during glaciation, then drove rapid warming once ice began melting. The instability resulted from Rodinia's configuration and breakup. As the supercontinent drifted toward equatorial latitudes, weathering of the extensive tropical landmass consumed carbon dioxide, cooling the climate. The breakup increased the efficiency of this weathering by creating more coastline and fragmenting the landmass into pieces separated by shallow seas. The enhanced weathering drew down carbon dioxide to levels low enough to trigger runaway glaciation. Only after tens of millions of years of volcanic outgassing during the glaciation could carbon dioxide accumulate enough to melt the ice. Eukaryotic evolution accelerated during and after Rodinia's breakup. The major radiation of eukaryotic lineages occurred near the Mesoproterozoic-Neoproterozoic boundary around 1.1 billion years ago, coinciding with the end of the boring billion and the beginning of Rodinia's breakup. Higher oxygen levels, increased nutrient availability, and greater habitat diversity during the breakup period provided conditions favorable for eukaryotic diversification. By the Ediacaran period, following Rodinia's breakup, the first macroscopic multicellular organisms appeared, marking the beginning of a new era in Earth's biological history. The long period of stability during Rodinia's tenure had ended, replaced by environmental dynamism that would drive rapid evolutionary innovation. Chapter 19: Snowball Earth. Around 720 million years ago, Earth froze almost completely. Ice sheets advanced from the poles toward the equator, thickening as they grew, reflecting more and more sunlight back into space. This triggered a runaway feedback where cooling caused more ice formation, which reflected more sunlight, causing further cooling in an unstoppable cascade. Within years or decades, the ice reached tropical latitudes, transforming Earth into a frozen world with ice covering most or all of the ocean surface. This was the Sturtian glaciation, the first of two extreme ice ages during the Cryogenian period that geologists call snowball Earth events. The Sturtian lasted from approximately 717 to 661 million years ago. An almost inconceivable 56 million years of nearly complete glaciation. A second snowball event, the Marinon glaciation, occurred between approximately 651 and 635 million years ago, lasting perhaps 4 million years. These frozen intervals represent the most extreme climate states Earth has ever experienced, pushing life to the brink of extinction, yet ultimately creating conditions that would allow complex animals to evolve. The path to freezing. The initiation of snowball Earth required atmospheric carbon dioxide to drop below a critical threshold. Climate models indicate this threshold lies somewhere between 10 and 250 parts per million, depending on continental configuration, orbital parameters, and volcanic activity. Below this threshold, the ice albedo feedback becomes unstoppable. Ice reflects approximately 70 to 90% of incoming sunlight, compared to only 5 to 20% reflected by ocean water. As ice coverage increases, the planet's overall reflectivity, or albedo, rises, causing more cooling and further ice expansion. The breakup of Rodinia set the stage for this catastrophic cooling. As the supercontinent fragmented, weathering rates increased dramatically. The creation of new coastlines and shallow seas enhanced exposure of fresh rock to chemical weathering. Weathering of silicate minerals consumes carbon dioxide through reactions that combine atmospheric carbon dioxide with calcium and magnesium from rocks, eventually producing carbonate minerals that are buried in sediments. Enhanced weathering during Rodinia's breakup drew down atmospheric carbon dioxide over millions of years. The continental configuration itself contributed to glaciation susceptibility. Computer simulations show that carbon dioxide thresholds for glaciation vary dramatically depending on where continents are positioned. When large landmasses lie at low latitudes in tropical regions, weathering is most efficient because warm, wet conditions accelerate chemical reactions. As Rodinia drifted into low latitudes during its breakup, tropical weathering intensified, consuming carbon dioxide faster than volcanic outgassing could replenish it. Volcanic eruptions occasionally perturbed the climate system, pushing it closer to the glaciation threshold. Large volcanic eruptions inject sulfur dioxide into the stratosphere, where it forms sulfate aerosols that reflect sunlight and cool the planet. A particularly large eruption near the equator could temporarily reduce incoming solar radiation by 20 to 40 watts per square meter, sufficient to trigger glaciation if carbon dioxide levels were already near the critical threshold. The effects of volcanic cooling, combined with low carbon dioxide, created perfect conditions for runaway glaciation. Once initiated, the freeze proceeded rapidly. Climate models indicate that the transition from partially ice-covered to completely ice-covered occurred within years to decades. The ice albedo feedback operated so strongly at the critical threshold that no intermediate stable state existed. The climate system had two stable configurations, partially ice-covered like modern Earth or nearly completely ice-covered like snowball Earth. The transition between these states was abrupt and catastrophic. Life under ice. The snowball Earth glaciations posed an existential threat to life. With ice covering the ocean surface, sunlight could not penetrate to deeper waters where photosynthetic organisms lived. Primary productivity collapsed to near zero. Temperatures plunged far below freezing everywhere except possibly near the equator or near volcanic hotspots. The frozen ocean surface prevented gas exchange between ocean and atmosphere, causing dissolved oxygen to become depleted as aerobic organisms consumed it. Yet life survived. Photosynthetic cyanobacteria and algae persisted in refugia where conditions remained marginally habitable. Thin ice near the equator may have transmitted enough light to support photosynthesis underneath. Leads or cracks in the ice created by tidal flexing or thermal stress would have exposed water to sunlight intermittently. Volcanic islands poking through the ice provided local heat sources that maintained ice-free zones in their immediate vicinity. Psychrophilic microorganisms, species adapted to extremely cold conditions, colonized the ice itself. These organisms lived in brine pockets within the ice, tiny liquid inclusions where salts concentrated as pure ice froze around them. The high salt concentration depressed the freezing point, keeping water liquid even at temperatures far below 0 degrees Celsius. Similar communities inhabit ice in modern polar regions and provide analogues for understanding how life persisted during snowball Earth. Hydrothermal vents on the seafloor continued operating throughout the glaciations, providing oases of warmth and chemical energy. Communities of thermophilic bacteria and archaea thrived in the hot vent fluids, independent of sunlight. These deep-sea ecosystems were completely isolated from the frozen surface, protected from the catastrophic conditions above. The survival of hydrothermal vent communities ensured that at least some lineages of life persisted through even the most severe phases of glaciation. The duration of the glaciations tested life's resilience. The Sturtian lasted 56 million years, longer than the time separating modern humans from the extinction of the dinosaurs. Over such vast time spans, evolutionary processes continued operating even in refugia. Organisms adapted to the extreme conditions, evolving mechanisms to survive low temperatures, darkness, and isolation. These adaptations would prove crucial for surviving subsequent environmental challenges. Volcanic carbon dioxide accumulation. While Earth froze, volcanic activity continued unabated. Volcanoes erupted through the ice, releasing carbon dioxide and other gases into the atmosphere. In normal times, weathering of continental rocks consumes volcanic carbon dioxide at approximately the same rate that volcanoes emit it, maintaining atmospheric carbon dioxide at relatively stable levels. During snowball Earth, however, weathering virtually ceased because rocks were buried under ice and temperatures were far too cold for efficient chemical reactions. With weathering shut down but volcanism continuing, atmospheric carbon dioxide accumulated. Over millions of years, concentrations rose to levels hundreds or thousands of times higher than before glaciation. Estimates suggest carbon dioxide may have reached 35,000 to 90,000 parts per million, compared to modern levels around 400 parts per million. These extreme concentrations created a powerful greenhouse effect despite the high albedo from ice coverage. The accumulation of carbon dioxide was not instantaneous. Volcanic outgassing rates are relatively low, adding perhaps 500 billion to 1 trillion moles of carbon dioxide annually to the atmosphere. At these rates, millions to tens of millions of years were required to accumulate sufficient carbon dioxide to trigger deglaciation. This explains why the Sturtian glaciation lasted so extraordinarily long, 56 million years. Only after such prolonged accumulation did greenhouse warming become strong enough to begin melting the ice. The Marinon glaciation, lasting only about 4 million years, ended much faster than the Sturtian. This shorter duration suggests that carbon dioxide accumulated more rapidly during the Marinon, possibly because volcanic outgassing rates were higher or because the glaciation was less complete, allowing some weathering to continue and requiring less carbon dioxide to trigger deglaciation. The difference in duration between the two snowball events demonstrates the sensitivity of deglaciation timing to relatively small variations in volcanic activity and glaciation completeness. Deglaciation. When atmospheric carbon dioxide finally reached levels sufficient to overcome the ice albedo feedback, deglaciation began. The process was as abrupt as the initial freezing. Rising carbon dioxide increased greenhouse warming, melting ice and exposing darker ocean water that absorbed more sunlight. This reversed the ice albedo feedback. Warming caused ice melting, which reduced albedo, causing more warming in a runaway cascade toward an ice-free state. The deglaciation may have proceeded even faster than the initial glaciation, potentially completing within a few hundred to a few thousand years once initiated. Evidence from the geological record suggests extraordinarily rapid environmental changes at the glaciation terminations. The extreme carbon dioxide levels created a super greenhouse climate where temperatures soared far above pre-glacial levels. The planet transitioned from frozen wasteland to scorching hothouse almost instantaneously by geological standards. Enhanced volcanism during deglaciation accelerated warming. As ice sheets melted, the removal of weight from the crust caused depressurization of magma chambers beneath volcanic centers. This depressurization triggered enhanced eruptions, releasing additional carbon dioxide and heat. Mercury anomalies in sediments deposited immediately after the Sturtian glaciation provide evidence for this enhanced volcanic activity. The feedback between deglaciation and volcanism amplified warming, ensuring that once deglaciation started, it proceeded rapidly and irreversibly. The melting of continental ice sheets released enormous quantities of meltwater carrying dissolved minerals and sediments. This meltwater formed a freshwater layer on top of the denser seawater, stratifying the ocean. The freshwater layer equilibrated with the high carbon dioxide atmosphere, becoming highly acidic initially. Continental weathering in the hot, humid post-glacial climate delivered massive amounts of alkalinity, cations like calcium and magnesium that neutralized the acidity and allowed carbonate precipitation. Cap carbonates. One of the most distinctive features of snowball Earth glaciations is the presence of cap carbonates, thick layers of limestone or dolostone that directly overlie glacial deposits. These carbonates formed during and immediately after deglaciation, precipitating rapidly from supersaturated waters. The formation of cap carbonates proceeded in 3 stages according to recent modeling. During the first stage, while glaciation was still ongoing, seafloor weathering at low temperatures generated alkalinity in the deep ocean. Reactions between seawater and basaltic oceanic crust proceeded slowly but continuously throughout the millions of years of glaciation, gradually building up alkalinity in deep waters isolated from the atmosphere by the ice cover. The second stage occurred immediately after deglaciation, when vigorous continental weathering in the hot, high carbon dioxide climate supplied enormous amounts of alkalinity to the surface freshwater layer. This alkalinity, combined with calcium from weathering, caused the carbonate saturation state to reach values exceeding 70, far higher than modern ocean values around 4 to 5. Such extreme supersaturation drove rapid carbonate precipitation, forming thick deposits of cap carbonate within perhaps hundreds to thousands of years. The third stage involved the mixing of the surface freshwater layer with the deep ocean alkalinity reservoir. As ocean circulation gradually mixed these water masses, the deep alkalinity was brought to the surface, where it sustained continued carbonate precipitation for an extended period. This 3-stage process explains the observed characteristics of cap carbonates, including their rapid deposition, distinctive geochemistry, and global distribution. Cap carbonates serve as markers for snowball Earth events in the geological record. Their presence indicates not only that glaciation occurred, but that it was sufficiently severe to shut down weathering almost completely, allowing carbon dioxide to accumulate to extreme levels. The intensity of weathering immediately after deglaciation, recorded in cap carbonate geochemistry, demonstrates the extraordinary environmental perturbations associated with snowball hothouse transitions. Environmental reset. The snowball Earth glaciations fundamentally reset Earth's surface environments. The prolonged anoxia during glaciation, followed by rapid reoxygenation during deglaciation, created conditions of extreme environmental stress. Species that could not tolerate these fluctuations went extinct. Those that survived in refugia or possessed metabolic versatility capable of handling both anoxic and oxic conditions inherited a transformed world. Ocean chemistry was reorganized. The stratified ferruginous ocean that characterized much of the boring billion gave way to more complex redox structures. The deep ocean began oxygenating after the Marinone glaciation around 635 million years ago, becoming fully oxic by approximately 580 million years ago. This deep ocean oxygenation created new habitats where aerobic organisms could thrive at all depths, no longer restricted to the thin, oxygenated surface layer. Nutrient availability increased dramatically following deglaciation. The intense weathering released phosphorus and other limiting nutrients that stimulated biological productivity. Cyanobacteria populations exploded, rapidly consuming dissolved carbon dioxide and producing oxygen. This biological response contributed to the rise in atmospheric oxygen during the Neoproterozoic oxygenation event, increasing oxygen from perhaps 10% of modern levels before glaciation to 40 to 50% of modern levels by the end of the Ediacaran. The combination of rising oxygen and available nutrients created conditions favorable for the evolution of large, complex, multicellular organisms. Simple animals require oxygen concentrations of at least 10 to 15% of present atmospheric levels. More active animals with higher metabolic demands require higher oxygen levels. The post-Marinone rise in oxygen crossed thresholds that had previously constrained animal body sizes and activity levels, allowing animals to increase in size and complexity for the first time. The snowball Earth glaciations, despite their severity, may have been necessary prerequisites for animal evolution. The environmental perturbations eliminated many established ecosystems, creating ecological vacuums that new innovations could fill. The metabolic versatility required to survive the fluctuating conditions may have driven innovations in cellular physiology that became foundations for animal biochemistry. The oxygenation triggered by deglaciation provided the energy resources that animals needed. Earth emerged from the cryogenian ice ages, transformed and ready to host the first animal. Chapter 20: The Ediacaran World. Following the Marinone glaciation around 635 million years ago, Earth entered the Ediacaran period. This final period of the Proterozoic eon lasted from 635 to 541 million years ago, spanning 94 million years of transformation. The Ediacaran witnessed the appearance of Earth's first macroscopic multicellular animals, organisms large enough to see with the naked eye that left fossils preserving their body forms. These were not the familiar animals with shells and skeletons that would dominate the later Cambrian period, but strange, soft-bodied creatures unlike anything living today. Some may have been early relatives of modern animal groups, ancestors or close cousins of jellyfish, worms, or mollusks. Others represented evolutionary experiments that left no descendants. Extinct lineages that explored body plans never repeated in later evolution. Understanding the Ediacaran biota reveals how animals first emerged and began diversifying, setting the stage for the explosive radiation that would follow in the Cambrian. 3 assemblages. The Ediacaran biota is divided into 3 successive assemblages, each characterized by distinct organisms and ecological patterns. These assemblages represent stages in the evolution and diversification of early animals, showing progressive increases in complexity, ecological diversity, and resemblance to modern animal. Avalon assemblage appeared first, spanning from approximately 575 to 560 million years ago. This assemblage emerged almost immediately after the Gasquias glaciation, a relatively minor glaciation that occurred around 584 to 582 million years ago. The close temporal association between this glaciation, deep ocean oxygenation that followed it, and the appearance of the first Ediacaran organisms suggests a causal connection. The newly oxygenated deep ocean provided habitats where complex life could survive at all depths. Avalon organisms were dominated by rangiomorphs, fractal branching forms that grew attached to the seafloor in deep, quiet waters. These organisms reached sizes up to 2 meters in height, far larger than any previous life forms except certain algae. their fractal architecture, where each branch resembled the whole organism in miniature maximized surface area for absorbing nutrients or oxygen from the surrounding water. Most rangiomorphs probably fed through osmosis, absorbing dissolved organic matter rather than actively capturing food particles. The White Sea assemblage followed, spanning from approximately 560 to 550 million years ago. This assemblage showed dramatic increases in morphological and ecological diversity compared to the Avalon assemblage. New body plans appeared, including forms that could move across the seafloor leaving trails, organisms that grazed on microbial mats, and possible predators or scavengers. The White Sea assemblage represented a major radiation, an explosive increase in the variety of body forms and ecological strategies. Many iconic Ediacaran fossils belong to the White Sea assemblage. Dickinsonia, an oval quilted organism reaching up to nearly 1.5 meters in length, could move slowly across the seafloor. Chemical analysis of Dickinsonia fossils has revealed cholesterol-like molecules that only animals produce, providing strong evidence that Dickinsonia was indeed an animal rather than some alternative form of life. Kimberella, a slug-like creature with a shell-like structure, left scratch marks on seafloors indicating it fed by scraping microbial mats. The Nama assemblage came last, spanning from approximately 550 to 539 million years ago. This assemblage marked further increases in biologic and ecologic complexity. Animals became more mobile and active. Hard parts began appearing, with some organisms secreting mineralized skeletons made of calcium carbonate. Burrowing organisms excavated tunnels into sediments, bioturbating the seafloor and changing geochemical conditions. The Nama assemblage directly preceded the Cambrian explosion, representing the final stages of animal evolution before the appearance of most modern phyla. Body plans and ecology. Ediacaran organisms exhibited body forms that seem alien to modern eyes. Many were flat, mattress-like creatures that lay on the seafloor absorbing nutrients. Others resembled fronds attached to stalks, swaying in currents while filtering food particles from water. Some had radial symmetry like jellyfish. A few showed bilateral symmetry, the body plan characteristic of most modern animals, including all vertebrates, arthropods, and mollusks. The quilted appearance of many Ediacaran fossils, with their bodies divided into repeated segments or chambers, has led to various interpretations. Some researchers suggest these organisms were pneumatic, fluid-filled structures that maintained their shape through internal pressure, similar to modern sea pens. The quilted chambers may have provided structural support without requiring rigid skeletal elements. Other interpretations suggest the chambers represented repeating body segments like in modern annelid worms, though the arrangements were often different from any living animals. Ediacaran ecosystems were structured differently from modern marine ecosystems. There were no swimming animals, no shells or skeletons in the early Ediacaran, no evidence of predation or defensive structures until near the end of the period. Instead, organisms fed primarily on microbial mats covering the seafloor or on dissolved organic matter in the water. The absence of predation allowed organisms to grow large and adopt body forms that would have been vulnerable to predators. Flat, immobile creatures could spread across the seafloor without fear of being consumed. Mobility appeared and increased throughout the Ediacaran. The earliest Avalon organisms were entirely sessile, attached to the seafloor and unable to move. By the White Sea assemblage, traces preserved in rocks show organisms crawling across sediments, leaving trails and scratch marks. By the Nama assemblage, more complex trace fossils indicate diverse locomotion strategies and behaviors. Some traces show systematic search patterns suggesting organisms were actively seeking food rather than moving randomly. Reproduction in Ediacaran organisms remains poorly understood. Some rangiomorphs from the Avalon assemblage appear to have reproduced through vegetative propagation, with new individuals growing from stolons extending along the seafloor. This asexual reproduction would have produced clones clustered near parent organisms, explaining the patchy distributions seen in some fossil assemblages. Evidence for sexual reproduction appears later, with fossils suggesting some organisms released gametes into the water for external fertilization. Affinities and controversies. The evolutionary relationships of Ediacaran organisms remain hotly debated. Some researchers argue that many Ediacaran forms were stem group animals, early evolutionary experiments that branched off before the main animal phyla diversified. Others suggest that some Ediacaran organisms were crown group members of modern phyla, actual ancestors, or close relatives of living animal groups. A minority proposes that some Ediacaran forms represented entirely different kingdoms of life, extinct alternatives to animals that superficially resembled them but were fundamentally different in their biology. Evidence supporting animal affinities has strengthened in recent years. Chemical analysis finding cholesterol signatures in Dickinsonia provides molecular evidence for animal identity. The discovery of possible muscle tissue and gut structures in some specimens suggests animal-like organ systems. Trace fossils showing coordinated movement and feeding behavior indicate nervous systems capable of controlling complex behaviors. Collectively, these findings demonstrate that at least some Ediacaran organisms were definitely animals, even if others remain ambiguous. Certain Ediacaran forms can be assigned with reasonable confidence to modern phyla. Kimberella shows features characteristic of mollusks, including a possible foot for locomotion and a radula for feeding. Cloudina and Namacalathus, late Ediacaran organisms with mineralized tube-shaped skeletons, may represent early cnidarians or stem group animals near the cnidarian lineage. Trace fossils from the late Ediacaran show complexity, suggesting the presence of bilaterians, animals with bilateral symmetry, including probable worms and arthropod-like organisms. Rangiomorphs and ernietomorphs, two distinctive groups abundant in the Avalon assemblage, probably have no modern descendants. Their body plans are too different from any living organisms to assign them confidently to extant phyla. They may represent stem group animals that diverged before major features like bilateral symmetry and through guts evolved. Alternatively, they might represent entirely separate experiments in multicellularity that went extinct at the end of the Ediacaran, replaced by more successful animal lineages during the Cambrian. Environmental conditions. The Ediacaran Ocean was still quite different from modern oceans. Oxygen levels had risen substantially compared to the Proterozoic, but remained lower than today, perhaps 40 to 70% of present atmospheric levels. The deep ocean had become oxygenated after the Marinone glaciation, but oxygen concentrations remained modest and may have fluctuated. Some regions experienced episodic anoxia, where oxygen was temporarily depleted, creating patchy distributions of habitable and uninhabitable environments. This intermediate oxygen state may have been crucial for early animal evolution. Oxygen concentrations were high enough to support aerobic metabolism and the energetic demands of multicellular body plans, but low enough that metabolic versatility remained advantageous. Animals capable of tolerating variable oxygen conditions could exploit a wider range of habitats than specialists requiring consistently high oxygen. This metabolic flexibility may have been a key factor in the successful diversification of early animals. Nutrient levels were higher than during the Boring Billion, but probably lower than in modern productive coastal waters. Phosphorus released by weathering following Rhydynia's breakup and the snowball Earth glaciations fertilized the oceans, supporting higher primary productivity. Cyanobacteria and eukaryotic algae flourished, producing extensive microbial mats in shallow waters. These mats provided food for grazers and sediment stabilization that allowed delicate organisms to preserve as fossils. Sea level fluctuated throughout the Ediacaran, creating and destroying shallow marine environments. These shallow seas, flooded continental margins, provided ideal habitats for early animals. Water depths of only a few meters to a few tens of meters allowed sunlight to reach the seafloor, supporting photosynthetic communities. Gentle currents brought nutrients and oxygen while preventing excessive sediment accumulation that could bury organisms. The extensive shallow seas created by high sea levels gave animals room to diversify geographically and ecologically. The end. Ediacaran extinction. The Ediacaran period ended with a major extinction event around 539 million years ago. Many characteristic Ediacaran organisms disappeared from the fossil record, never to reappear. This end. Ediacaran extinction cleared the way for the Cambrian explosion, the rapid diversification of animal phyla that began almost immediately afterward. The causes of the extinction remain debated. Ocean chemistry changes may have played a role, with increasing sulfate levels creating more widespread euxinic conditions, waters containing both no oxygen and abundant hydrogen sulfide. These toxic conditions would have been lethal to animals adapted to low but non-zero oxygen. The rise of mobile bilaterians capable of burrowing may have disrupted microbial mat ecosystems, eliminating the food source for many Ediacaran organisms that fed on these mats. Predation probably contributed to extinction. The late Ediacaran saw the first appearance of potential predators with hard mouthparts capable of consuming other animals. Once predation evolved, the flat, soft-bodied, immobile organisms that characterized earlier Ediacaran assemblages became easy targets. Selection favored animals that could move quickly, burrow into sediment for protection, or evolve hard shells to resist predators. The Ediacaran body forms, adapted to a world without predation, became obsolete. The extinction was selective rather than catastrophic. Some Ediacaran lineages survived into the Cambrian, including probable ancestors of modern animal phyla. Trace fossils show continuity in behaviors across the Proterozoic-Phanerozoic boundary. What disappeared were the distinctive Ediacaran-type organisms, the fronds and quilted forms that looked nothing like modern animals. The extinction represented an ecological replacement rather than a mass die-off, with emerging Cambrian animals outcompeting or consuming Ediacaran. Legacy and significance. The Ediacaran period represents a crucial chapter in the history of life. During this 94-million-year interval, animals evolved from microscopic ancestors into macroscopic organisms visible without magnification. Body plans diversified from simple blob-like forms to complex structures with differentiated tissues and organs. Ecology became more complex as organisms developed new feeding strategies, locomotion abilities, and interactions with each other and their environments. The Ediacaran biota demonstrated that large, complex multicellular animals were biologically possible given adequate environmental conditions. Sufficient oxygen, available nutrients, and stable ocean chemistry allowed organisms to invest energy in growing large bodies and developing complex organ systems. Once these conditions were met following the cryogenian glaciations, animal evolution proceeded rapidly, exploring diverse body plans and ecological strategies within tens of millions of years. The innovations that appeared in the Ediacaran laid foundations for later animal evolution. Bilateral symmetry, the body plan of most modern animals, evolved during this time. Mobility and burrowing behaviors developed. The first predators appeared near the end of the period. Sexual reproduction became widespread if it had not already. These fundamental features, once established, were retained and elaborated in subsequent eons as animals radiated into the extraordinary diversity characterizing the Phanerozoic. By the end of the Ediacaran at 541 million years ago, the stage was set for the Cambrian explosion. Animals had established themselves as permanent features of Earth's ecosystems. The basic toolkit of animal body plans, developmental mechanisms, and ecological strategies had been assembled. Environmental conditions, including oxygen levels, nutrient availability, and ocean chemistry, continued improving. The next chapter in Earth's history would see the appearance of most modern animal phyla within a geologically brief interval, transforming life on Earth forever. But that explosive diversification built on foundations laid during the Ediacaran, when animals first learned to be animals. Chapter 21: The Cambrian explosion. The Cambrian period began 541 million years ago with an evolutionary event, unlike anything before or since. Within a geologically brief interval of approximately 13 to 25 million years, virtually all major animal phyla appeared in the fossil record. Trilobites with their compound eyes and segmented bodies scurried across seafloors. Anomalocaris, a meter-long predator with grasping appendages and sophisticated vision, hunted smaller creatures. Brachiopods with their hinged shells filtered food from water. Mollusks, echinoderms, chordates, and dozens of other groups left their first clear fossils during this explosive radiation. The Cambrian explosion did not create the animal phyla, which had originated earlier during the Ediacaran, but it filled them out with diverse body plans and ecological strategies. Molecular evidence suggests the major phyla diverged far earlier than their first fossil appearances, perhaps as early as 876 million years ago for the split between echinoderms and hemichordates. However, these early animals remained microscopic or left no fossils until environmental conditions improved during the Cambrian, allowing them to grow larger, develop hard parts, and preserve as fossils. Understanding the Cambrian explosion requires examining both the evolutionary innovations that animals developed and the environmental changes that permitted those innovations to succeed. The arms race begins. One of the most significant developments during the Cambrian was the evolution of predation as a dominant ecological force. The Ediacaran had been largely predator-free, allowing organisms to adopt vulnerable body forms. The Cambrian shattered this peaceful existence. Predators evolved the ability to actively hunt, capture, and consume other animals. This triggered an evolutionary arms race where prey developed defenses while predators evolved methods to overcome those defenses. Vision played a crucial role in this arms race. Anomalocaris, one of the apex predators of the Cambrian seas, possessed compound eyes with approximately 16,000 separate lenses. These eyes provided acute vision capable of detecting movement and identifying prey from considerable distances. The evolution of such sophisticated visual systems represented a major innovation. Prior organisms either lacked eyes entirely or possessed simple light-sensing organs incapable of forming detailed images. The appearance of large predators with superior vision forced prey animals to evolve protective adaptations. Hard shells made from calcium carbonate or calcium phosphate appeared during the early Cambrian. These mineralized skeletons provided physical barriers that predators had to overcome. The small shelly fauna, diverse assemblages of tiny mineralized structures found in earliest Cambrian rocks, represents early experiments in biomineralization. Many of these structures were probably defensive, protecting soft-bodied animals from predators. Armor evolved in various forms across different lineages. Trilobites developed hard exoskeletons covering their dorsal surfaces. When threatened, they could roll into defensive balls like modern pill bugs, protecting their vulnerable undersides. Brachiopods enclosed themselves within two hinged shells that could snap shut when danger approached. Early mollusks secreted shells covering their bodies. These defensive innovations spread rapidly as natural selection favored individuals that could resist predation. Mobility increased as both predators and prey evolved more efficient locomotion. Jointed appendages allowed precise control of movement. Muscles attached to rigid skeletons provided leverage for powerful swimming or crawling. Streamlined body shapes reduced drag. The fossil record shows trace fossils becoming more complex during the Cambrian, indicating increasingly sophisticated behaviors. Animals no longer simply moved randomly, but showed evidence of hunting behaviors, escape responses, and systematic foraging patterns. Oxygen and animal size. Atmospheric oxygen levels during the Cambrian may have ranged from 10 to 40% of present atmospheric levels, considerably higher than the Ediacaran, but potentially lower than modern conditions. This intermediate oxygen state was sufficient to support active, mobile animals, but may have constrained maximum body sizes and activity levels. The relationship between oxygen and animal evolution remains debated, with some researchers emphasizing oxygen as a primary control, while others argue that ecological factors were more important. Enhanced continental weathering during the early Cambrian delivered nutrients to the ocean while consuming atmospheric carbon dioxide. The weathering intensity increased suddenly at the Ediacaran-Cambrian boundary, indicated by changes in rare earth element patterns and concentrations of water-insoluble elements in marine carbonates. This enhanced weathering may have triggered a rise in atmospheric oxygen concentrations by increasing photosynthetic productivity, which removed carbon dioxide from the atmosphere and released oxygen. The supply of nutrients from weathering fertilized photosynthetic organisms, increasing primary productivity at the base of marine food chains. Higher productivity meant more energy available for consumers, supporting the evolution of larger, more active animals. The appearance of large metazoans in the early Cambrian correlates with both nutrient delivery from weathering and increasing atmospheric oxygen, suggesting both factors contributed to enabling animal diversification. However, Cambrian oceans were not uniformly oxygenated. Evidence indicates that ocean oxygen levels oscillated, with episodes of widespread anoxia interrupting more oxygenated intervals. These oxygen fluctuations promoted evolutionary innovation as animals adapted to variable conditions, but they also drove extinction events when anoxia became too widespread. Life during the Cambrian existed on the edge, inhabiting a marine realm that was progressively oxygenating but still experiencing frequent oxygen crises. Trilobite diversity. Trilobites became the dominant visible animals of Cambrian seas, diversifying into thousands of species adapted to different ecological niches. These arthropods possessed segmented bodies divided into 3 lobes, hence their name. A mineralized exoskeleton provided protection, while jointed limbs underneath allowed walking, swimming, and prey manipulation. Compound eyes gave many species excellent vision. The ability to molt their exoskeletons enabled trilobites to grow throughout their lives. Early Cambrian trilobite faunas show remarkable diversity. The Cranbrook Lagistet in British Columbia preserves at least 8 trilobite species from Cambrian Stage 4, including 4 ulnaloid species, 2 dorypigids, and 2 tichiparioids. The ulnaloids were by far the most abundant, suggesting they dominated these ecosystems. The preservation quality sometimes captures exquisite detail, revealing not just hard parts, but occasionally soft tissues and internal organs. Different trilobite groups exploited different habitats and feeding strategies. Some were benthic crawlers that scoured seafloors for detritus. Others were pelagic swimmers that pursued prey in the water column. Filter feeders strained microscopic organisms from water. Predatory species hunted smaller animals. The diversity of trilobite morphologies reflects this ecological diversification, with body shapes optimized for particular lifestyles. Trilobites underwent rapid evolutionary turnover during the Cambrian. Species appeared, diversified, and went extinct within geologically brief intervals as environmental conditions fluctuated and ecosystems reorganized. This high turnover generated the extraordinary species diversity characteristic of Cambrian trilobite assemblages. By the Middle Cambrian, trilobites had reached their peak diversity, with hundreds of genera distributed globally. The Burgess Shale window. The Burgess Shale in British Columbia provides an exceptional window into Cambrian life. This Middle Cambrian deposit, approximately 508 million years old, preserves soft-bodied organisms that normally would not fossilize. Whereas typical fossil deposits preserve only hard parts like shells and skeletons, the Burgess Shale captures complete organisms including muscles, guts, eyes, and other soft tissues. This extraordinary preservation reveals the true diversity of Cambrian life. The Burgess Shale fauna includes both familiar and bizarre organisms. Anomalocaris, the apex predator, reached lengths over 1 meter. Its circular mouth with radiating plates could crush prey. Grasping appendages captured victims and brought them to the mouth. The animal swam using lateral lobes that undulated along its body. Wiwaxia, a slug-like creature covered in protective spines, scraped microbial films from surfaces. Opabinia possessed 5 eyes and a long, flexible proboscis with a grasping claw at the end. Many Burgess Shale organisms defy easy classification. Hallucigenia, originally reconstructed upside down, walked on paired spines while defensive spikes protected its back. Its affinity remains debated, though it may represent an early relative of modern velvet worms. Anomalocaridids like Anomalocaris belong to the arthropod lineage, but possess features not seen in later groups. These strange body plans represent evolutionary experiments, some successful and others that left no descendants. Preservation of soft tissues allows reconstruction of complete ecosystems. The Burgess Shale captures a slice of Cambrian ocean life at approximately 200 meters depth on a muddy slope. Periodic turbidity currents swept down the slope, burying organisms in fine mud before decay could destroy soft tissues. The rapid burial in anoxic sediments prevented bacterial decomposition, allowing soft tissues to be replaced by minerals that preserved their three-dimensional structure. Cambrian extinctions. Despite its explosive beginnings, the Cambrian was marked by several extinction events that periodically reduced diversity. Around 500 million years ago, oxygen levels fell dramatically in the oceans while hydrogen sulfide concentrations increased, creating euxinic conditions lethal to most animals. This anoxic event drove extinctions across multiple groups. Reef-building sponges called archaeocyathidds, which had replaced stromatolites as the dominant reef builders, went extinct. Stromatolites returned briefly as competition decreased. The speciation rate decreased to between 1/5 and 1/3 of earlier levels during the late Cambrian. This declining trend represented a contraction following the initial explosive radiation. Many of the experimental body plans that flourished in the early Cambrian disappeared as ecosystems matured and competition intensified. The survivors tended to be more specialized, occupying well-defined ecological niches rather than experimenting with diverse strategies. Marine habitat loss contributed to extinctions. Sea level fluctuations, driven by climate changes and tectonic processes, alternately flooded and exposed continental shelves. Shallow marine environments, which hosted the highest diversity, expanded and contracted with these sea level changes. When sea level fell, vast areas of productive shallow habitat disappeared, eliminating the species that depended on them. Subsequent sea level rises recolonized these areas, but with impoverished faunas, lacking many lineages present before. The Cambrian ended around 485 million years ago, with biodiversity substantially reduced from its middle Cambrian peak. The initial explosive radiation had given way to a period of consolidation, where surviving lineages diversified within established ecological frameworks rather than creating fundamentally new body plans. This declining trend would not reverse until the Great Ordovician biodiversification event filled out the Cambrian phyla with extraordinary species-level diversity. Legacy of the explosion. The Cambrian explosion established the basic architecture of animal life that persists today. Between 20 and 35 major phyla appeared during this interval, representing the fundamental body plans around which all subsequent animal evolution has been organized. New phyla have not appeared since the Cambrian. Instead, evolution has worked variations on existing themes, elaborating and modifying the basic plans established during this creative interval. The innovations that evolved during the Cambrian became permanent features of animal biology. Biomineralization, the production of hard parts from calcium carbonate or calcium phosphate, transformed ecology by enabling new defensive and structural adaptations. Vision revolutionized how animals interacted with their environment and each other. Complex nervous systems allowed sophisticated behaviors. Specialized organ systems for digestion, excretion, circulation, and reproduction increased physiological efficiency. The ecological structure established during the Cambrian persisted for hundreds of millions of years. Tiered ecosystems with primary producers, herbivores, carnivores, and decomposers became the standard organization. Food chains extended from microscopic bacteria to meat-along predators. Ecosystem engineering, where organisms modify their environment in ways that affect other species, appeared as burrowers mixed sediments and filter feeders cleared water. These ecological patterns, once established, constrained and channeled subsequent evolution. The Cambrian explosion demonstrated that evolution can proceed extremely rapidly when conditions permit. The appearance of most animal phyla within 13 to 25 million years, a blink of geological time, shows that the pace of evolution is not constant, but accelerates during intervals when ecological opportunity, environmental permissiveness, and evolutionary innovation align. The explosion also showed that chance plays a role. Many viable body plans went extinct for no apparent reason except bad luck, while others survived to become ancestors of all later animals. The particular suite of phyla that survived determined the future course of animal evolution, establishing constraints that persist to the present day. Chapter 22: Ordovician Diversification. The Ordovician period began 486.9 million years ago, following the relatively subdued Late Cambrian. This period, lasting approximately 44 million years until 443.1 million years ago, witnessed the second great explosion of biodiversity in Earth's history. While the Cambrian explosion established the major animal phyla, the Great Ordovician Biodiversification event filled out those phyla with extraordinary diversity at lower taxonomic levels. Marine family diversity tripled during the Ordovician. Ordinal level diversity doubled. Within clade diversity at genus and species levels increased dramatically. The Ordovician radiation established the Paleozoic evolutionary fauna, those taxa which would dominate marine ecosystems for the next 250 million years. Community structure became dramatically more complex, with new communities forming and fundamental shifts in dominance patterns. By the end of the Ordovician, marine ecosystems had achieved diversity levels not seen in the Cambrian, and in some measures exceeding any later time in the Paleozoic. Understanding this diversification requires examining both the evolutionary innovations that drove it and the environmental conditions that permitted such explosive diversification. The biodiversification event. The Great Ordovician Biodiversification event was not a single explosive radiation, but rather many sequential diversification pulses occurring diachronously across different groups and regions. Different fossil groups showed rapid increases during different intervals of the Ordovician. Some lineages diversified early in the period, while others radiated later. Geographic patterns varied, with diversification occurring at different times in different ocean basins and paleocontinents. The GOBE included several biotic immigration events where taxa dispersed on large scales from one biogeographical area to another. The Richmondian invasion saw numerous taxa spreading into new regions during the late Ordovician. The Boda event recorded another major dispersal episode. These immigration events redistributed biodiversity globally, reducing provinciality as formerly isolated faunas mixed and competed. Ordovician biodiversification pulses were closely linked to terminations of positive carbon isotope excursions. These excursions are characteristic of anoxic conditions. When they terminated, oxygen levels presumably increased. The temporal correlation suggests that diversification occurred in concert with increasing oxygen content in seawater. Higher oxygen levels expanded habitable environments and provided the energy needed for more active, diverse communities. After the Steptoean positive carbon isotope excursion around 500 million years ago, extinction in the ocean opened niches for photosynthetic plankton. These organisms absorbed carbon dioxide from the atmosphere and released large amounts of oxygen. More oxygen and more diversified photosynthetic plankton at the base of food chains affected diversity in higher marine organisms and their ecosystems. The feedback between oxygen production, plankton diversity, and animal diversity drove the progressive increase in overall biodiversity throughout the Ordovician. Taxonomic increases. The increase in diversity during the Ordovician occurred primarily at genus and species levels rather than at higher taxonomic ranks. All major phyla were already present from the Cambrian. What changed was the number of orders, families, genera, and species within those phyla. This represents a filling out of the tree of life, adding branches and twigs to trunks that were already established. Brachiopods experienced spectacular diversification, becoming the dominant shelled invertebrates of Ordovician seas. Dozens of new families appeared, each characterized by distinctive shell morphologies and ecological adaptations. Some brachiopods lived attached to hard substrates. Others anchored themselves in soft sediments using pedicles. Filter feeding strategies diversified, with different groups processing water in distinctive ways to extract food particles. Trilobites continued diversifying despite having peaked during the Cambrian. New orders appeared with novel morphological adaptations. Some trilobites became specialized for particular depth zones. Others adapted to specific sediment types. Visual systems became increasingly sophisticated in some lineages, while other lineages lost eyes entirely, adapted to living in deep, dark waters where vision provided no advantage. Mollusks radiated extensively. Bivalves diversified into numerous families. Gastropods evolved varied shell forms and ecological strategies. Cephalopods appeared and quickly became important predators. Nautiloids with their chambered shells and tentacles hunted throughout the water column. Some straight-shelled nautiloids reached lengths of several meters, becoming apex predators rivaling the largest arthropods. Echinoderms underwent remarkable diversification. Crinoids, the sea lilies, appeared and quickly became abundant. These attached filter feeders extended feathery arms into currents to capture food. Blastoids, cystoids, and other extinct groups flourished. Many Ordovician echinoderms possessed bizarre morphologies never repeated in later evolution, representing evolutionary experiments that ultimately failed but were successful for millions of years during the Ordovician. Community complexity. Ordovician communities were far more complex than Cambrian communities. The number of species coexisting in individual communities increased. Trophic structure became more elaborate with multiple tiers of producers, consumers, and decomposers. Ecological interactions diversified, with specialized predator-prey relationships, parasitism, commensalism, and mutualism all appearing. Reef ecosystems became more diverse and structurally complex. Ordovician reefs were built by multiple groups including tabulate corals, rugose corals, bryozoans, sponges, and calcified algae. These framework builders created three-dimensional structures that provided habitat for hundreds of other species. Cryptic spaces within reefs hosted specialized communities that lived in permanent darkness, fed by organic matter filtering through the reef structure. Tiering in benthic communities increased. Rather than all organisms living at the sediment-water interface, communities became vertically structured. Some organisms burrowed deep into sediments. Others lived at the surface. Still others extended upward on stalks or occupied positions in the water column just above the bottom. This vertical partitioning allowed more species to coexist in the same area by exploiting different microhabitats. Ecological guilds became more clearly defined. Within any trophic level, species specialized for particular resources or methods of resource exploitation. Among filter feeders, some species filtered fine particles while others captured larger items. Among predators, some were pursuit specialists while others were ambush predators. This guild structure reduced competition and allowed higher diversity to be maintained. Life invades land. The Ordovician witnessed the first tentative colonization of land by plants and fungi. For billions of years, land surfaces had been essentially barren except for microbial films. During the Ordovician, this began changing as organisms adapted to terrestrial conditions, established permanent populations on land. Arbuscular mycorrhizal fungi may have been among the earliest land colonizers. Fossilized fungal hyphae and spores from Ordovician sediments in Wisconsin, dated to approximately 460 million years ago, represent some of the oldest evidence of terrestrial fungi. These fungi likely played crucial roles in facilitating plant colonization through mycorrhizal symbiosis, making mineral nutrients available to plant cells by breaking down rocks and transporting nutrients to plant roots. The earliest land plants were probably similar to modern bryophytes, lacking vascular tissue for water transport. Molecular clock analyses, combined with fossil evidence, suggest land plants were present by the Middle Cambrian to early Ordovician interval, though definitive fossils are rare before the Silurian. By the early Silurian, the four major lineages of land plants had already diverged and were forming cryptogamic ground covers on land. These early land plants faced enormous challenges. They needed to prevent water loss in the dry atmosphere while still exchanging gases for photosynthesis. Cuticles, waxy coatings covering plant surfaces, evolved to waterproof tissues. Stomata, controllable pores in the cuticle, allowed gas exchange while minimizing water loss. Spores encased in sporopollenin, a resistant organic polymer, could survive desiccation during dispersal. The colonization of land transformed terrestrial environments. Plant roots, even primitive ones, began breaking down rocks and stabilizing soils. Photosynthesis by land plants contributed to atmospheric oxygen production. Organic matter from dead plants accumulated on land rather than washing immediately into the sea, beginning the formation of terrestrial carbon pools. Though early land plants were small and formed sparse ground covers rather than forests, they initiated processes that would eventually transform Earth's surface completely. The late Ordovician extinction. The Ordovician ended with the first of the big five mass extinctions of the Phanerozoic. This extinction occurred in two phases, each driven by different causes. The first phase struck during the latest Cation as glaciation began. The second phase occurred during the early Hernantian as glaciation intensified. Together, these two extinction pulses eliminated approximately 85% of marine species. Glaciation drove the extinction by causing sea level fall and habitat loss. As ice sheets grew on the supercontinent Gondwana, which was positioned over the South Pole, water became locked in continental ice. Sea level dropped by perhaps 50 to 100 meters, draining the vast shallow epicontinental seas that covered much of the continents. These shallow seas hosted the highest diversity of marine life. When they disappeared, countless species went extinct simply through loss of habitat. Oxygen fluctuations contributed to extinction. Thallium isotope data reveal that the initial biodiversity decline coincided with a rapid global expansion of oxygen minimum zones in the latest Cation. This was followed by rapid contraction of these zones in the early Hernantian. The rapid oscillations in ocean oxygenation, combined with habitat loss from sea level fall, drove extinction pulses. Species adapted to oxygenated conditions could not survive anoxic episodes, while species tolerant of low oxygen could not compete when oxygen increased again. The extinction was selective. Tropical species were hit particularly hard in the first wave, probably because tropical shallow seas experienced the most severe habitat loss. Cool water species suffered worst in the second pulse as glaciation intensified and temperatures dropped globally. Species limited to single epicontinental seas were devastated because their entire habitat could disappear during a single glacial pulse. Cosmopolitan species with broad geographic ranges fared better because populations in some regions survived even when others went extinct. The extinction involved reductions in alpha diversity within communities rather than complete elimination of communities. Individual communities became impoverished, containing fewer species than before. Beta diversity, the turnover between communities in different locations, remained high because extinction affected different communities differently. Those taxa that survived the first extinction wave commonly succumbed to the second, reflecting the contrasting causes of each phase. Recovery and legacy. Despite the severity of the late Ordovician extinction, recovery began quickly in the Silurian period that followed. The glaciation ended as Gondwana drifted away from the pole. Sea level rose, reflooding the continental shelves and recreating shallow marine habitat. Oxygen levels stabilized at higher concentrations. Surviving lineages radiated to fill niches left vacant by extinction. The Ordovician radiation, despite being truncated by extinction, fundamentally reshaped marine ecosystems. The Paleozoic evolutionary fauna established during the Ordovician would dominate marine environments for the next 250 million years, until the Permian-Triassic extinction replaced it. The ecological structures, community organization patterns, and diversity-generating processes that evolved during the Ordovician became templates for later marine ecosystems. The invasion of land during the Ordovician initiated a transformation that would continue throughout the Paleozoic. By the Devonian, forests covered the continents. By the Carboniferous, terrestrial ecosystems rivaled marine systems in complexity and diversity. The tentative first steps during the Ordovician, when primitive plants and fungi established footholds on barren land, began the greening of Earth that continues today. 450 million years later, descendants of those pioneering organisms cover nearly every land surface, having transformed Earth from a water world with barren continents to a planet where life thrives on land as successfully as in the sea. Chapter 23: The Age of Hellish. The Devonian period began 419 million years ago, ushering in an era that would come to be called the Age of Fishes. Fish had existed since the Cambrian, but during the Devonian they exploded into extraordinary diversity, dominating every marine environment from shallow reefs to the deep ocean. Armored placoderms, fish covered in bony plates, ruled as apex predators. The first sharks with their cartilaginous skeletons prowled the waters. Ray-finned fish, which would eventually give rise to most modern fish species, appeared and diversified. Most significantly for the future of life on land, lobe-finned fish evolved muscular fins with internal bone structures that would eventually become limbs. The Devonian lasted until 359 million years ago, spanning 60 million years, during which vertebrates completed their conquest of the oceans and took their first tentative steps onto land. Simultaneously, plants transformed the terrestrial world from barren rock to forested landscapes, fundamentally altering Earth's surface and atmosphere. Understanding the Devonian requires examining both the aquatic innovations that produced diverse fish faunas and the terrestrial developments that laid groundwork for all later land life. Placoderm dominance. Placoderms were the dominant vertebrate predators of Devonian seas. These armored fish possessed bony plates covering their heads and the front portions of their bodies, providing protection from predators while allowing flexibility in their tails for swimming. The armor consisted of articulated plates that could move relative to each other, unlike the solid shells of turtles. This articulation allowed placoderms to grow larger while maintaining mobility. Dunkleosteus represents the most fearsome placoderm predator. This massive fish reached lengths of up to 6 meters, roughly the size of a modern great white shark. Instead of teeth, Dunkleosteus possessed sharp bony plates in its jaws that functioned as self-sharpening blades. The jaw muscles generated bite forces estimated at 4,000 to 5,000 pounds per square inch, sufficient to crush through the armor of other placoderms or the shells of large mollusks. Dunkleosteus occupied the apex predator niche in late Devonian seas. Smaller placoderms exploited diverse ecological niches. Bothriolpes, an anti-arch placoderm, lived on the seafloor and fed on bottom sediments or detritus. Its heavily armored body and small size, typically around 30 centimeters, suggested it faced significant predation pressure. Bothriolpes was extraordinarily abundant and widespread, with fossils found on every continent. This global distribution indicates anti-archs successfully adapted to varied environments from marine to freshwater habitats. Despite their success during the Devonian, placoderms went extinct during the late Devonian extinctions. By the end of the Devonian, all placoderm lineages had disappeared. Competition with other fish groups, particularly sharks and bony fish, may have contributed to their extinction. The environmental changes that drove late Devonian extinctions eliminated many placoderm habitats. Whatever the causes, placoderms left no descendants, representing an evolutionary dead end despite their 100-million-year reign. Shark evolution. The first abundant sharks appeared during the Devonian. Cladoslas, one of the earliest well-known shark genera, cruised Devonian seas as an active predator. Unlike modern sharks with their replacement teeth that continuously grow throughout life, Cladoslas teeth did not replace themselves. The teeth wore down through use, suggesting cladoslash had a relatively short lifespan or fed on soft-bodied prey that did not damage teeth excessively. Early sharks possessed cartilaginous skeletons like modern sharks, providing flexibility and reducing weight compared to bony skeletons. Cartilage does not fossilize as readily as bone, making the shark fossil record incomplete. Most shark fossils consist of teeth, which are mineralized and preserve well. Occasionally, exceptional preservation captures complete shark fossils, including soft tissues, revealing body forms and fin structures. Devonian sharks were morphologically diverse. Some resembled modern sharks with streamlined bodies and powerful tails. Others had unusual features not seen in later sharks. The diversity suggests rapid experimentation with different body plans and ecological strategies as sharks radiated into available niches. Successful designs persisted and were elaborated in later periods, while unsuccessful experiments went extinct. Sharks survived the late Devonian extinctions that eliminated placoderms. Throughout the Carboniferous and later periods, sharks continued diversifying, eventually becoming one of the most successful groups of vertebrate predators. Modern sharks represent the culmination of 400 million years of evolution, retaining the basic body plan established during the Devonian while refining it through countless generations of natural selection. Lobe-finned fish and tetrapod origins. Lobe-finned fish, or sarcopterygians, were the most diverse group of bony fish during the Devonian. These fish possessed distinctive fins with fleshy lobes containing bones and muscles. The fin bones were homologous to the bones in tetrapod limbs, representing the same structures modified for different functions. In lobe-finned fish, the bones supported fins for swimming. In tetrapods, the same bones would support limbs for walking on land. Molecular and paleontological evidence indicates that tetrapods originated from lobe-finned fish during the early Devonian, earlier than previously thought. Analysis suggests this transition occurred around 397 to 416 million years ago during the early Devonian. Environmental factors, including rising oxygen levels and the diversification of terrestrial arthropods and coral reefs, created conditions favorable for vertebrate terrestrialization. Tetrapod trackways dated to approximately 395 million years ago from the Middle Devonian provide the earliest direct evidence of limbed vertebrates. These tracks show digit impressions, indicating the animals possessed feet rather than fins. The tracks also demonstrate that the animals could thrust their limbs forward in a walking motion impossible for fish like Tiktaalik that lacked fully developed limbs. The trackways predate the oldest tetrapod body fossils by 18 million years, indicating that the fossil record of early tetrapods is incomplete. Tiktaalik, discovered in Arctic Canada and dated to 375 million years ago, represents a transitional form between fish and tetrapods. This creature possessed a flat head with eyes on top, similar to crocodiles, allowing it to lie in shallow water while watching for prey above. The neck was mobile, unlike in fish where the head connects rigidly to the shoulders. Most significantly, Tiktaalik possessed fins with internal bones arranged similarly to tetrapod limbs. These sturdy fins could support the animal's weight, allowing it to push itself up and move through shallow water or possibly venture briefly onto land. The anatomy of Tiktaalik demonstrated that the transition from fin to limb occurred partly in water-dwelling organisms before vertebrates colonized land. Previously, scientists assumed terrestrial limbs evolved after organisms left water as adaptations for land locomotion. Tiktaalik showed that limb-like structures evolved in aquatic environments, probably as adaptations for moving through shallow, vegetation-choked waters where swimming was difficult. The pre-adaptation of limbs in aquatic environments made the eventual transition to land possible. Plant diversification. While fish diversified in the oceans, plants transformed the terrestrial world. Early Devonian vegetation consisted of small primitive plants lacking true leaves or extensive root systems. By the late Devonian, forests of large trees covered the continents, fundamentally altering landscapes and atmospheric composition. The diversification of vascular plants proceeded rapidly during the Devonian. Vascular tissue, consisting of xylem for water transport and phloem for nutrient transport, allowed plants to grow taller by efficiently moving materials throughout the plant body. Early vascular plants like Cooksonia reached only a few centimeters in height. By the late Devonian, vascular plants had evolved into trees exceeding 30 meters tall. Archaeopteris represents the earliest known tree to form extensive forests. This genus appeared during the late Devonian around 370 million years ago and dominated floodplain environments globally. Archaeopteris possessed a woody trunk with secondary vascular tissue, growth rings, and a branching pattern similar to modern conifers. However, its leaves resembled fern fronds rather than conifer needles, giving it a distinctive appearance. Archaeopteris forests covered every continent, creating the first truly forested landscapes on Earth. The evolution of seeds occurred during the late Devonian. Elkinsia, an early seed fern, possessed structures interpreted as primitive seeds. Seeds provided enormous advantages over spores by protecting the developing plant embryo and providing it with stored nutrients. Seeds allowed plants to reproduce successfully in drier environments where spore-dependent reproduction would fail. The seed plants that evolved during the Devonian would eventually dominate terrestrial floras, though spore-producing plants remained abundant in moist environments. Root systems became increasingly sophisticated throughout the Devonian. Early plants possessed simple rhizoid structures that anchored them but provided minimal support. Later Devonian plants developed extensive root systems that penetrated deeply into soil, physically breaking apart rocks and extracting minerals. These roots worked with mycorrhizal fungi to enhance nutrient uptake, creating mutually beneficial relationships that persist in most modern plants. Atmospheric transformation. The spread of forests during the Devonian fundamentally altered atmospheric composition. Photosynthesis by vast numbers of plants removed carbon dioxide from the atmosphere while releasing oxygen. This process had been occurring since cyanobacteria evolved billions of years earlier, but the scale increased dramatically when forests appeared. The large biomass of trees meant enormous quantities of carbon were locked in wood rather than circulating through the atmosphere. Oxygen concentrations rose throughout the Devonian, though they had not yet reached the extreme levels of the later Carboniferous. Estimates suggest oxygen increased to perhaps 25% of atmospheric concentration by the late Devonian, compared to 21% today. This rising oxygen enabled the evolution of larger, more active animals by making aerobic respiration more efficient. The development of soil accelerated during the Devonian. Plant roots broke apart rocks mechanically while secreting acids that dissolved minerals chemically. Dead plant material accumulated and was decomposed by bacteria and fungi, creating organic-rich soils. These soils retained water, prevented erosion, and provided habitat for invertebrates and eventually vertebrates. The transformation from barren rock surfaces to soil-covered landscapes represented one of the most significant environmental changes in Earth's history. Rivers and streams changed character as vegetation colonized their banks. Previously, rivers flowed across bare rock, rapidly eroding banks and frequently changing course. Vegetation stabilized banks, reducing erosion and allowing rivers to establish more permanent channels. Sediment transport decreased as plant roots held soil in place. The appearance of forests fundamentally altered how water moved across continents, establishing hydrological patterns that persist. Late Devonian extinctions. The Devonian ended with a series of extinction pulses that eliminated many marine organisms. The Kellwasser event occurred near the Frasnian-Faymunian boundary approximately 372 million years ago. This crisis primarily affected marine communities, particularly warm, shallow water organisms. Reef ecosystems were devastated. Placoderms, which had dominated throughout the Devonian, began their terminal. The Kellwasser event may actually have consisted of two closely spaced extinction pulses, indicated by two distinct anoxic shale layers in the geological record. These black shales formed when ocean waters became depleted of oxygen, killing aerobic organisms. The dead organisms accumulated on the seafloor without being decomposed by aerobic bacteria, which could not survive in the anoxic conditions. The organic-rich sediments eventually lithified into black shales. The Hangenberg event, The final extinction pulse of the Devonian occurred at the Devonian Carboniferous boundary around 359 million years ago. This event completed the elimination of placoderms and many other Devonian groups. The causes of these extinctions remain debated, with proposed mechanisms including volcanism, climate change, sea level fluctuations, and ocean anoxia. Multiple factors likely operated simultaneously, creating environmental stress beyond what many organisms could tolerate. Forests largely disappeared in the wake of the late Devonian extinctions. Archaeopteris forests, which had dominated floodplains globally, were eliminated or drastically reduced. Forests on the scale of those in the late Devonian would not recur until well into the Carboniferous, when new types of woody trees appeared. The cause of this forest collapse remains unclear, though climate change associated with the marine extinctions may have made terrestrial environments less favorable for tree growth. Despite the severity of late Devonian extinctions, survivors recovered and diversified during the subsequent Carboniferous period. The ecological niches left vacant by extinction provided opportunities for surviving lineages to radiate. Sharks and bony fish inherited the predator roles formerly occupied by placoderms. New plant groups colonized terrestrial environments, establishing forests even more extensive than those of the Devonian. The extinctions reset ecosystems, but did not prevent the continued expansion of life into new environments and the evolution of increasingly complex organisms. Chapter 24: Carboniferous Coal Forests. The Carboniferous period began 359 million years ago in the aftermath of the late Devonian extinctions. This period, lasting until 299 million years ago, would become known as the Coal Age due to the vast coal deposits that formed from its extensive swamp forests. Lush vegetation covered low-lying areas on every continent, creating forests unlike any before or since. Giant lycophyte trees, relatives of modern club mosses but reaching heights of 30 meters or more, dominated these swamps. Tree ferns grew in the understory. Early seed plants occupied drier upland areas. The enormous biomass of these forests, accumulating in swampy conditions where decomposition was incomplete, eventually transformed into the coal seams that would power human industrial civilization hundreds of millions of years later. Simultaneously, atmospheric oxygen rose to unprecedented levels, reaching perhaps 35% concentration compared to 21% today. This oxygen-rich atmosphere enabled the evolution of giant arthropods while setting the stage for the evolution of reptiles, the first vertebrates fully adapted to terrestrial life. The Carboniferous represents a pivotal period when life on land achieved complexity rivaling marine ecosystems. Forest structure. Carboniferous forests bore little resemblance to modern forests. The dominant trees were lycophytes, scale trees so named for the diamond-shaped leaf scars covering their trunks that resembled reptile scales. Lepidodendron and Sigillaria, the most common genera, grew rapidly in swampy lowlands. These trees possessed minimal branching, with most photosynthesis occurring in a crown of simple leaves at the top. The root systems, called stigmaria, spread horizontally through waterlogged soils, anchoring the trees in unstable substrates. Lycophyte trees grew quickly but were structurally weak compared to modern trees. Their wood contained limited lignin, the polymer that provides strength to modern tree trunks. Most of the trunk's bulk consisted of bark, which could be over half a meter thick. When trees fell, either through wind or natural decay, they typically did not rot completely. The swampy, waterlogged conditions were anoxic, preventing the bacteria and fungi that normally decompose wood from functioning effectively. Tree ferns occupied the understory beneath lycophyte canopies. These ferns, some reaching 10 meters in height, provided a middle layer in forest structure. Unlike lycophytes, tree ferns had more delicate, branching fronds. They reproduced through spores released from structures on leaf undersides, limiting them to moist environments where spores could germinate successfully. Seed plants, including early conifers and seed ferns, grew in better-drained upland areas adjacent to swamps. These plants were better adapted to seasonal drought than spore-producing plants. Seeds could remain dormant during dry periods, germinating when moisture returned. This adaptation allowed seed plants to colonize environments unavailable to ferns and lycophytes, beginning their rise to dominance that would culminate in later periods. Oxygen extremes. Atmospheric oxygen concentrations during the Carboniferous reached levels unprecedented in Earth's history. While estimates vary, most studies suggest oxygen peaked around 30 to 35% of atmospheric composition, 50% higher than modern levels. This hyperoxic atmosphere resulted from the unique conditions of Carboniferous forests combined with limited decomposition of plant material. Photosynthesis by the vast Carboniferous forests removed carbon dioxide from the atmosphere while releasing oxygen. Carbon that would normally recycle back to the atmosphere through decomposition was instead sequestered in accumulating peat. Each ton of peat represents approximately 1.5 tons of carbon dioxide removed from the atmosphere and replaced by oxygen. The scale of peat accumulation was enormous, eventually producing coal seams dozens of meters thick. Fungi and bacteria capable of efficiently decomposing lignin had not yet evolved. Modern wood-rotting fungi possess specialized enzymes that break down lignin, allowing them to access the cellulose within wood cell walls. These enzymes evolved later, possibly during the Permian or Triassic. In the Carboniferous, without efficient lignin decomposers, dead wood accumulated rather than recycling, locking carbon away for hundreds of millions of years. The hyperoxic atmosphere had profound effects on life. Oxygen is essential for aerobic respiration, but it is also chemically reactive and can damage cells through oxidative stress. Organisms living in high oxygen environments must balance the benefits of efficient respiration against the dangers of oxidative damage. Some organisms thrived in these conditions, while others may have been excluded from oxic environments, retreating to refugia with lower oxygen concentrations. Giant arthropods. The most spectacular consequence of hyperoxic conditions was the evolution of giant arthropods. Meganeura, a griffinfly related to modern dragonflies, had a wingspan exceeding 70 centimeters, comparable to a large hawk. Arthropleura, a millipede-like arthropod, reached lengths over 2 meters, making it the largest terrestrial arthropod ever known. These giant sizes were possible only in the oxygen-rich Carboniferous atmosphere. Arthropods breathe through tracheal systems, networks of tubes that carry air directly to tissues. Unlike vertebrates with circulatory systems that transport oxygen-carrying blood, arthropods rely on diffusion through tracheal tubes. Diffusion rates limit how far oxygen can penetrate from tracheal openings to deep tissues. In modern atmospheric oxygen levels, this diffusion limitation constrains arthropod body size. Larger bodies require oxygen to reach more distant tissues, but diffusion becomes ineffective over long distances. Higher atmospheric oxygen increases the oxygen gradient driving diffusion. With 35% oxygen in the atmosphere instead of 21%, diffusion rates increase proportionally. This allows oxygen to reach tissues located farther from tracheal openings, permitting larger body sizes. Experimental studies raising modern dragonflies in hyperoxic conditions confirmed this principle. Dragonflies grown in 31% oxygen developed wingspans 15% larger than those grown in normal 21% oxygen. Meganeura probably hunted smaller insects, other arthropods, and possibly small vertebrates. Its large compound eyes provided excellent vision for detecting prey. Strong flying muscles powered rapid, agile flight. Grasping legs captured prey in midair. The abundance of flying insects during the Carboniferous, themselves enlarged by high oxygen, provided ample food for predatory griffinflies. Arthropleura was likely an herbivore or detritivore feeding on decaying plant material. Its massive size provided defense against predators. Few Carboniferous animals could tackle a 2-meter-long armored arthropod. Arthropleura fossils are found in coal measure sediments, indicating these animals inhabited the same swampy forest environments that produced coal deposits. The evolution of amniotes. The most significant vertebrate innovation of the Carboniferous was the evolution of the amniotic egg. This egg type, possessed by reptiles, birds, and mammals, but not by amphibians, contains specialized membranes that protect the developing embryo and allow gas exchange. The amnion membrane surrounds the embryo in fluid, preventing desiccation. The chorion membrane facilitates oxygen diffusion while retaining water. The allantois stores metabolic wastes. These membranes allow embryos to develop completely within the egg, independent of water. Amphibians, the descendants of tetrapods that first emerged from water during the Devonian, still required water for reproduction. Amphibian eggs lack protective membranes and dry out rapidly in air. Amphibian larvae are aquatic, breathing through gills. Only after metamorphosis can amphibians colonize terrestrial environments, and even then most species remain tied to moist habitats. The amniotic egg freed vertebrates from dependence on water for reproduction. Amniotes could lay eggs in terrestrial environments, allowing them to colonize dry habitats unavailable to amphibians. This innovation opened vast new ecological opportunities, driving the radiation of reptiles during the Carboniferous and subsequent periods. The earliest known amniote is Sylvanopeton from the early Carboniferous, identified as the last common ancestor of all living amniotes through phylogenetic analysis. Early amniotes were small, resembling lizards in body form. They fed primarily on insects and other invertebrates. These modest beginnings would eventually give rise to the spectacular diversity of reptiles, including dinosaurs, pterosaurs, marine reptiles, and eventually birds and mammals. By the late Carboniferous, amniotes had diversified into multiple lineages. Some retained ancestral characteristics, remaining small insectivores. Others grew larger, exploiting new food sources. The split between sauropsids, the lineage leading to modern reptiles and birds, and synapsids, the lineage leading to mammals, occurred during this period. Each lineage would pursue different evolutionary paths, eventually dominating different eras. Coal formation. The coal deposits that give the Carboniferous its name formed through the accumulation and transformation of plant material over millions of years. Lycophyte forests growing in swampy environments died and fell into stagnant water where oxygen was depleted. Without oxygen, decomposition proceeded slowly and incompletely. Partially decayed plant material accumulated as peat, just as it does in modern peat bogs. As peat accumulated, its weight compressed lower layers, squeezing out water and compacting the material. Chemical changes occurred as volatile compounds evaporated and carbon concentration increased. With increasing burial depth and temperature, peat transformed through stages, first to lignite or brown coal, then to bituminous coal, and finally under extreme pressure and temperature to anthracite coal. The carbon content increases through these stages, with anthracite consisting of nearly pure carbon. Coal seams preserve evidence of the forests that produced them. Fossil stumps are sometimes found in growth position within coal measures, showing where trees stood when alive. Root systems preserved as stigmaria extend through the rock beneath coal seams, representing the forest floor. Leaves, seeds, and other plant parts occur as compression fossils in shales adjacent to coal seams. These fossils allow detailed reconstruction of Carboniferous forest composition and structure. The geographic distribution of coal deposits reflects Carboniferous paleogeography. Most major coal seams formed in equatorial regions where warm, wet climate favored extensive swamps. The Appalachian coal fields of North America, the Ruhr Basin of Europe, and the coal fields of China all formed in tropical lowlands during the Carboniferous. As tectonic plates moved over subsequent hundreds of millions of years, these coal deposits were carried to their present locations, sometimes far from the tropics. Climate and glaciation. Despite equatorial warmth that supported lush swamp forests, the Carboniferous experienced extensive glaciation at high southern latitudes. The supercontinent Pangaea was assembling during this period through collisions of multiple continents. Part of Pangaea extended over the South Pole, allowing continental glaciation to develop. Glacial deposits from this Carboniferous ice age are found in modern South America, Africa, India, Antarctica, and Australia, continents that were joined at high southern latitudes during the Carboniferous. The coexistence of tropical swamps and polar glaciation demonstrates the extreme climate zonation during the Carboniferous. Equatorial regions experienced hot, humid conditions with seasonal rainfall supporting year-round plant growth. Polar regions were frozen under ice sheets hundreds of meters thick. Mid-latitude regions had more seasonal climates with distinct wet and dry periods. This climate diversity created varied habitats supporting different organisms adapted to local conditions. Sea level fluctuated throughout the Carboniferous in response to glacial cycles. During glacial maxima, when ice sheets expanded, sea level fell as water was locked in ice. During interglacials, when ice melted, sea level rose, flooding low-lying continental areas. These sea level fluctuations affected coastal swamp forests, alternately expanding and contracting their extent. The cycles are recorded in coal measure sequences as repeating patterns of coal seams, marine limestones, and terrestrial sediments. By the end of the Carboniferous 300 million years ago, Earth had been transformed by 100 million years of forest development. Atmospheric composition had been permanently altered. Coal deposits representing hundreds of billions of tons of carbon had been removed from the active carbon cycle. Life on land had achieved diversity and ecological complexity, matching marine ecosystems. The stage was set for the Permian period, when new innovations, including more efficient terrestrial adaptations in both plants and animals, would drive further evolutionary radiations before the catastrophic end Permian extinction reset the biosphere once again. Chapter 25: The Permian and the Great Dying. The Permian period began 299 million years ago as Earth recovered from the Carboniferous Ice Age. This period would witness the continued dominance of synapsids, the lineage that includes mammals, as they diversified into forms ranging from massive herbivores to saber-toothed predators. The early pelycosaurs, with their distinctive sail-like structures, gave way to more advanced therapsids, the true mammal-like reptiles that possessed increasingly mammalian characteristics. The supercontinent Pangaea reached its maximum extent during the Permian, unifying nearly all continental landmasses into a single enormous continent stretching from pole to pole. This configuration created extreme climates with vast desert interiors and limited coastal habitats. The Permian ended 252 million years ago with the most catastrophic extinction event in Earth's history, the Permian-Triassic extinction that eliminated an estimated 96% of marine species and 70% of terrestrial vertebrate species. This Great Dying, as it is aptly named, came closer to ending complex life on Earth than any event before or since. Understanding the Permian requires examining both the remarkable synapsid radiation that dominated this period and the volcanic catastrophe that brought it to a devastating end. Pelycosaur dominance. The early Permian was dominated by pelycosaurs, primitive synapsids that had evolved during the late Carboniferous. These animals possessed the characteristic synapsid feature of a single temporal fenestra, an opening in the skull behind each eye that distinguished them from other reptiles. The most famous pelycosaurs were the sail-backed forms, particularly Dimetrodon and Edaphosaurus, which are often mistakenly called dinosaurs despite living millions of years before dinosaurs evolved. Dimetrodon was a carnivorous pelycosaur reaching lengths up to 4.5 meters. Its most distinctive feature was the large sail running along its back, formed by elongated neural spines extending from the vertebrae and covered by skin in life. The function of this sail remains debated. The most popular hypothesis suggests it served as a thermoregulatory device, allowing Dimetrodon to rapidly warm its body by orienting the sail toward the sun or cool by positioning it edge-on. Alternative hypotheses propose the sail functioned in display, either to intimidate rivals or attract mates. Edaphosaurus, a contemporary of Dimetrodon, also possessed a sail but was herbivorous rather than carnivorous. This represents a remarkable case of parallel evolution, where two unrelated lineages independently evolved similar structures. Edaphosaurus sails were distinctive, featuring small crossbars on the neural spines, unlike the smooth spines of Dimetrodon. Edaphosaurus teeth were small and peg-like, adapted for processing plant material rather than tearing flesh. The skull was broader and more robust than in Dimetrodon, suggesting powerful jaw muscles for grinding vegetation. By the Middle Permian, pelycosaurs had declined and were replaced by more advanced synapsids called therapsids. The transition occurred around 270 million years ago as climate conditions shifted. The development of seasonally arid savanna-like environments favored therapsids with their higher metabolic rates and improved thermoregulation. Pelycosaurs, adapted to the humid Carboniferous conditions, could not compete with therapsids in these new environments. By the end of the Middle Permian, pelycosaurs had gone extinct, leaving therapsids as the dominant terrestrial vertebrates. Therapsid radiation. Therapsids were far more mammal-like than pelycosaurs, showing numerous anatomical features foreshadowing true mammals. Their legs were positioned more directly under their bodies rather than sprawling out to the sides, allowing more efficient locomotion. The temporal fenestra was larger, providing more space for jaw muscles and enabling more powerful bites. The teeth were differentiated into incisors, canines, and molars, allowing more efficient food processing. Some therapsids may have possessed fur and elevated metabolic rates, though direct evidence is difficult to obtain from fossils. Therapsids diversified into multiple lineages during the Middle and Late Permian. Dinosphalians were large-bodied forms, some herbivorous and others carnivorous, that dominated Middle Permian ecosystems. These animals reached sizes exceeding 3 meters and masses of over 1,000 kilograms. The skull bones were massively thickened, particularly in the forehead region, suggesting head-butting behavior similar to modern bighorn sheep or musk oxen. Dicynodonts were herbivorous therapsids characterized by turtle-like beaks and often two protruding tusks. They ranged in size from small burrowing forms to massive animals exceeding 5 meters in length. Dicynodonts became extraordinarily successful, occupying herbivore niches across Pangaea. Lystrosaurus, a pig-sized dicynodont, would prove crucial for understanding the end Permian extinction because it was one of the very few large animals to survive that catastrophe. Cynodonts were the most mammal-like therapsids, possessing numerous advanced features. Their skulls showed evidence of secondary palates allowing breathing while eating. The lower jaw consisted primarily of the dentary bone, with other bones reduced as in mammals. Postcranial anatomy suggested increasingly mammalian posture and locomotion. Some cynodonts may have possessed fur and lactation, though such features do not fossilize. Cynodonts were the ancestors of mammals, and the transition from cynodont to mammal occurred during the Triassic, with changes so gradual that defining exactly when mammals appeared becomes arbitrary. Gorgonopsians were saber-toothed predators that dominated late Permian carnivore guilds. These therapsids possessed enormous canine teeth, some exceeding 12 centimeters in length, used to inflict killing wounds on prey. Gorgonopsians ranged from dog-sized animals to massive predators exceeding 4 meters in length. They hunted the abundant dicynodonts and other herbivorous therapsids. The extinction of Gorgonopsians at the end of the Permian created an ecological void, eventually filled by archosaurs during the Triassic. Pangaea supercontinents. The assembly of Pangaea profoundly affected global climate and biogeography during the Permian. This supercontinent stretched from the North Pole to the South Pole, encompassing virtually all continental landmass. The interior regions of Pangaea were thousands of kilometers from any ocean, creating extreme continental climates. Coastal areas remained relatively humid with seasonal precipitation, but vast interior deserts dominated much of the supercontinent. The unification of continents eliminated barriers between terrestrial biotas that had been evolving in isolation. Therapsids from one region could migrate across Pangaea and colonize new areas. This mixing reduced global diversity because endemic species faced competition from immigrants adapted to similar niches. Cosmopolitan species that could disperse widely came to dominate, replacing local specialists. The fossil record shows declining diversity through the Permian as biotas homogenized. Mountain building accompanied Pangaea's assembly. The collision of continents created enormous mountain ranges comparable to the modern Himalayas. The Appalachian Mountains in North America and the Ural Mountains between Europe and Asia formed during these collisions. These mountains influenced climate by blocking moisture flow and creating rain shadows. Continental interiors became increasingly arid as effective moisture transport diminished. Sea level fell during the Permian as ocean water was displaced by continental masses. Lower sea level reduced the extent of shallow epicontinental seas, eliminating productive marine habitats that hosted high diversity during earlier periods. The reduction in shallow marine habitat contributed to declining marine diversity throughout the Permian even before the terminal extinction event. The Siberian Traps. The end Permian extinction was triggered by the eruption of the Siberian Traps, one of the largest volcanic events in Earth's history. Beginning approximately 252 million years ago, massive volumes of basaltic lava erupted across what is now Siberia. The eruptions continued for roughly 2 million years. Spanning the Permian-Triassic boundary, the total volume of erupted material exceeded 3 million cubic kilometers, enough to cover an area the size of Europe to a depth of 1 kilometer. These were not conventional volcanic eruptions with towering explosive columns. Instead, lava poured out through long fissures in the crust, flowing across the landscape in sheets that could travel hundreds of kilometers before solidifying. Individual flows reached thicknesses of tens of meters. Layer after layer accumulated, building a volcanic plateau. The modern Siberian traps preserve the eroded remnants of this plateau, though much of the original volume has been removed by erosion. The eruptions released enormous quantities of greenhouse gases, including carbon dioxide and methane. Estimates suggest that 100,000 billion tons or more of carbon dioxide were added to the atmosphere over the eruption interval. Additionally, sulfur dioxide and other volatiles poisoned the atmosphere. When magma intruded through coal seams and other organic-rich sediments, it released additional greenhouse gases and toxic compounds through contact metamorphism. Mercury anomalies in sediments deposited during the end Permian crisis provide strong evidence linking the Siberian traps to the extinction. Volcanic eruptions release mercury, which disperses globally in the atmosphere before being deposited in sediments. The presence of mercury spikes coinciding with extinction horizons demonstrates that massive volcanism occurred during the crisis, supporting the hypothesis that the Siberian traps caused the extinction. Kill mechanisms. The extinction unfolded through multiple interconnected kill mechanisms operating simultaneously. Global warming from greenhouse gases raised temperatures by perhaps 10 to 15 degrees Celsius. Ocean surface temperatures may have exceeded 40 degrees Celsius in tropical regions, approaching the thermal tolerance limits of most marine organisms. On land, interior Pangaea became uninhabitable during summer months when temperatures soared above 50 degrees Celsius. Ocean acidification resulted from the enormous influx of carbon dioxide. When carbon dioxide dissolves in seawater, it forms carbonic acid, lowering pH. The acidification made it difficult for organisms to build calcium carbonate shells and skeletons. Reef-building organisms were particularly vulnerable, and Permian reefs collapsed worldwide. The loss of reef ecosystems eliminated habitat for countless species adapted to reef environments. Ocean anoxia spread as warming waters held less dissolved oxygen. The warmer water became, the less oxygen it could contain. Simultaneously, enhanced weathering on land delivered excess nutrients to the ocean, stimulating massive algal blooms. When these algae died and sank, their decomposition consumed oxygen, creating anoxic dead zones. Uranium and calcium isotope records indicate that anoxic zones expanded to cover vast portions of the ocean floor during the crisis. Toxic metal release from volcanic gases poisoned both terrestrial and marine environments. Nickel concentrations spiked in extinction boundary sediments, suggesting that nickel released from Siberian trap magmas reached toxic levels. High nickel concentrations would have poisoned photosynthetic organisms, collapsing primary productivity and destabilizing entire food chains. Hypercapnia, elevated carbon dioxide in blood, affected terrestrial vertebrates directly. When atmospheric carbon dioxide reaches sufficiently high concentrations, it interferes with respiration in air-breathing animals. The excess carbon dioxide prevents efficient gas exchange in lungs, essentially suffocating animals even in oxygen-rich air. Therapsids, which may have possessed relatively mammalian respiratory systems, would have been particularly vulnerable to hypercapnia. Aftermath and recovery. The extinction killed approximately 96% of marine species and 70% of terrestrial vertebrate species, making it the most severe biodiversity crisis in the past 540 million years. Entire ecosystems collapsed. Reef ecosystems disappeared completely. Forests were replaced by simple vegetation. The few survivors inhabited a devastated world where ecological complexity had been reduced to Precambrian levels. Lystrosaurus, the pig-sized dicynodont therapsid, became extraordinarily abundant in the early Triassic, representing up to 95% of terrestrial vertebrate fossils in some deposits. This disaster taxon thrived in the harsh post-extinction environment where most other animals perished. Lystrosaurus possessed adaptations including a barrel chest, suggesting efficient oxygen extraction, a beak suitable for processing poor-quality vegetation, and possibly semi-aquatic habits, allowing it to escape heat stress by entering water. These pre-adaptations allowed Lystrosaurus to survive conditions that killed most other therapsids. Recovery from the extinction was extraordinarily slow, taking millions of years. Throughout the early Triassic, biodiversity remained low and ecosystems remained simple. The hot, anoxic oceans could not support diverse communities. On land, harsh climates and sparse vegetation limited herbivore diversity, which in turn constrained carnivore diversity. Only in the Middle Triassic, roughly 8 to 10 million years after the extinction, did biodiversity begin increasing substantially. The delayed recovery resulted from persistent environmental stresses. High temperatures and anoxic conditions continued long after the eruptions ended because greenhouse gases remained elevated. Ocean acidification persisted as the oceans slowly equilibrated with the atmosphere. Low biological competition, resulting from the paucity of surviving species, meant that evolution proceeded slowly without strong selective pressures driving innovation. Recovery only accelerated when environmental conditions improved sufficiently, and surviving lineages began radiating to fill vacant ecological niches. The end Permian extinction reset the evolutionary trajectory of life on Earth. Therapsids, which had dominated terrestrial ecosystems throughout the Permian, never recovered their former diversity. Although some lineages, including cynodonts, survived and eventually gave rise to mammals, therapsids were replaced as dominant large animals by archosaurs during the Triassic. The extinction created opportunities that allowed dinosaurs to rise, ultimately leading to avian and terrestrial ecosystems dramatically different from those of the Permian. Chapter 26: The Triassic Transition. The Triassic period began 252 million years ago in the immediate aftermath of the worst mass extinction in Earth's history. The surviving species inherited a devastated planet where ecosystems had been reduced to the simplest structures seen since the Paleozoic began. The early Triassic was characterized by extreme heat, ocean anoxia, and low biodiversity as life struggled to recover from the end Permian catastrophe. Yet from these harsh beginnings, the Triassic would see the rise of new dominant groups including the archosaurs, the reptilian lineage encompassing crocodilians, dinosaurs, pterosaurs, and ultimately birds. The first dinosaurs appeared during the late Triassic, initially small and unremarkable members of archosaur communities dominated by other groups. Mammals also originated during the Triassic, evolving from cynodont therapsids but remaining small and nocturnal in the shadow of reptilian dominance. The Triassic ended 201 million years ago with another major extinction that cleared the way for dinosaur dominance in the Jurassic. The Triassic thus represents a transitional period when the Paleozoic fauna gave way to the Mesozoic fauna that would characterize the age of dinosaurs. Early Triassic harsh conditions. The early Triassic epoch, spanning the first 5 million years after the end Permian extinction, was characterized by extraordinarily harsh environmental conditions. Global temperatures remained elevated, with estimates suggesting average temperatures exceeded those of the late Permian by several degrees. The interior of Pangaea experienced extreme continental climates, with summer temperatures possibly exceeding 50 degrees Celsius, making vast areas effectively uninhabitable for large animals. Deserts dominated the continental interior. The supercontinent configuration prevented moisture from penetrating inland, creating arid conditions across most terrestrial environments. Only coastal regions and high-latitude areas received sufficient precipitation to support substantial vegetation. The widespread aridity limited the extent of productive terrestrial ecosystems, constraining the diversity of herbivores and consequently carnivores that could be supported. Ocean conditions remained hostile to complex life. Surface waters in tropical regions were extremely hot, exceeding 35 degrees Celsius. Deep ocean anoxia persisted, with oxygen minimum zones expanded compared to the Permian. Episodes of euxinia, where hydrogen sulfide accumulated in the water column, occurred repeatedly. These toxic conditions periodically drove extinction pulses during the early Triassic, preventing sustained recovery and keeping diversity suppressed. The pole to equator temperature gradient was unusually flat. Unlike modern Earth, where temperatures vary dramatically from cold poles to hot equator, early Triassic Earth had relatively uniform warm temperatures globally. This weak temperature gradient reduced atmospheric circulation patterns, limiting precipitation and contributing to widespread aridity. The flat gradient also allowed tropical species to extend their distributions to high latitudes, as evidenced by the global distribution of ammonoids and other marine groups during this time. Lystrosaurus and disaster fauna. The early Triassic terrestrial fauna was dominated by a handful of disaster taxa, species that thrived in post-extinction conditions where most organisms struggled. Lystrosaurus was the most abundant of these survivors, representing up to 95% of vertebrate fossils in some early Triassic assemblages. This extraordinary dominance reflects both the success of Lystrosaurus and the paucity of other vertebrates. Lystrosaurus from China grew larger on average than their South African relatives and showed distinctive cranial morphology, suggesting possible taxonomic distinction. The Chinese specimens showed rapid, sustained bone growth interrupted by periodic growth marks, indicating fast development under environmental stress. None of the sampled bones reached maximum size, suggesting that even the largest known Chinese specimens had not finished growing when they died. This rapid growth strategy may have been adaptive in the unstable early Triassic environment, where reaching reproductive maturity quickly improved survival odds. Other therapsid lineages survived the extinction in much lower abundance. The Rosphalians, including Tetracynodon and Moscorhinus, crossed the Permian-Triassic boundary, though they never regained the diversity they possessed in the Permian. Cynodonts, the mammal ancestors, survived and began diversifying during the Middle Triassic, though they remained relatively small and uncommon compared to emerging archosaur groups. The low diversity and high dominance by single taxa characterized early Triassic ecosystems both on land and in the sea. This pattern reflects the harsh environmental conditions that only a few pre-adapted species could tolerate. As conditions gradually improved through the early Triassic, diversity slowly increased, but full recovery to pre-extinction levels required millions of years. Archosaur rise. Archosaurs evolved from earlier diapsid reptiles and first appeared in the Middle Triassic around 246 million years ago. These reptiles possessed distinctive anatomical features, including an improved ankle structure that allowed more upright posture and teeth set in sockets rather than grooves. The upright posture made archosaurs more efficient walkers and runners compared to sprawling reptiles, providing competitive advantages in pursuit of prey or escape from predators. The Triassic takeover saw archosaurs displace therapsids as the largest and most ecologically prolific terrestrial amniotes. This transition was not instantaneous, but unfolded over tens of millions of years during the Middle and Late Triassic. Initially, therapsids remained common, but archosaurs progressively occupied more ecological niches. By the Late Triassic, archosaurs dominated as large herbivores, large carnivores, and aerial flyers, relegating surviving therapsids to small body sizes and nocturnal habits. The causes of archosaur success over therapsids remain debated. Some researchers emphasize superior locomotor efficiency, allowing archosaurs to outcompete therapsids for food resources. Others point to differences in respiratory systems, with archosaurs possibly possessing more efficient lung ventilation through air sacs similar to modern birds. Still others suggest that archosaurs were simply lucky, surviving random environmental perturbations that happened to eliminate therapsid competitors. Archosaurs diversified into two main lineages during the Triassic. Crurotarsi includes modern crocodilians and their extinct relatives. During the Triassic, Crurotarsans were far more diverse than crocodilians are today, including fully terrestrial forms, armored herbivores, and bipedal predators. Avametatarsalia includes dinosaurs, pterosaurs, and their descendants, including modern birds. The divergence of these lineages occurred early in archosaur evolution, with both groups radiating extensively during the Middle and Late Triassic. First, dinosaurs. Dinosaurs appeared during the Carnian stage of the Late Triassic, around 230 million years ago. The earliest known dinosaurs were small bipedal carnivores or omnivores resembling Aeoraptor and Herosaurus from Argentina. These animals were unremarkable members of late Triassic faunas, neither particularly abundant nor ecologically dominant. Other archosaurs, including Rorisuchians and various Crurotarsans, filled the roles of large predators and herbivores. The first dinosaurs were divided into two main groups based on hip structure. Saurischians, the lizard-hipped dinosaurs, included theropods, the carnivorous dinosaurs that would eventually include birds, and sauropodomorphs, the long-necked herbivores. Ornithischians, the bird-hipped dinosaurs, were all herbivorous and included ancestors of later groups like stegosaurs, ankylosaurs, and ceratopsians. The Saurischian-Ornithischian split occurred very early in dinosaur evolution, with both lineages present by the middle of the late Triassic. Prosauropods, early long-necked herbivorous dinosaurs, were the first dinosaurs to achieve large body sizes and ecological prominence. Forms like Plateosaurus reached lengths exceeding 8 meters and masses approaching several tons. These animals were likely bipedal or facultatively bipedal, able to walk on all fours when feeding, but capable of rising on hind limbs to reach high vegetation. Prosauropods became relatively common in late Triassic ecosystems, foreshadowing the later dominance of their sauropod descendants. Pterosaurs and marine reptiles. Pterosaurs. The flying reptiles appeared during the late Triassic alongside early dinosaurs. The earliest pterosaurs were long-tailed forms with wingspans around 1 to 2 meters. Their wings consisted of skin membranes stretched between elongated fourth fingers and the body, a completely different wing structure from bird wings or bat wings. Pterosaurs possessed hollow bones and likely high metabolic rates, supporting the energetic demands of powered flight. The evolution of powered flight in vertebrates represented a major innovation. Pterosaurs were the first vertebrates to achieve this, preceding birds by roughly 80 million years. Flight allowed pterosaurs to exploit aerial insects and opened new ecological opportunities unavailable to ground-dwelling animals. Pterosaurs would dominate aerial niches throughout the Mesozoic until the end Cretaceous extinction, when they vanished along with non-avian dinosaurs. Marine reptiles diversified extensively during the Triassic. Ichthyosaurs, dolphin-shaped reptiles, became fully aquatic with streamlined bodies, flippers instead of legs, and tail flukes for propulsion. Some ichthyosaurs grew to enormous sizes exceeding 15 meters. Plesiosaurs appeared in the late Triassic, characterized by 4 large flippers and either long necks with small heads or short necks with large heads, depending on the group. These marine reptiles filled ecological roles as top predators in marine ecosystems. Mammal origins. Mammals evolved from cynodont therapsids during the late Triassic around 225 to 200 million years ago. The transition from cynodont to mammal involved numerous anatomical changes occurring gradually. Key mammalian features including fur, lactation, and precise temperature regulation likely evolved incrementally. Defining exactly when cynodonts became mammals proves arbitrary because the transition was so gradual. The earliest mammals were tiny, most weighing less than 100 grams. They were insectivores with sharp teeth adapted for catching and processing insects. Their small size and nocturnal habits allowed them to avoid competition with and predation by larger reptiles. The Triassic takeover by archosaurs may have driven the evolution of nocturnal behavior in early mammals, forcing them into nighttime activity when diurnal reptilian competitors were inactive. Nocturnal life drove the evolution of mammalian characteristics. Fur provided insulation, allowing maintenance of body temperature during cool nights. Enhanced hearing and smell compensated for reduced vision in darkness. Higher metabolic rates supported continuous activity regardless of environmental temperature. Lactation allowed mothers to provision offspring continuously, increasing survival rates. These adaptations, evolved for nocturnal life in the shadow of dinosaurs, would eventually prove crucial for mammalian success after the dinosaur extinction. End Triassic extinction. The Triassic ended with another major extinction around 201 million years ago. The extinction eliminated approximately 76% of marine and terrestrial species, opening ecological opportunities that dinosaurs would exploit during the Jurassic. The cause of the extinction was volcanic eruptions of the Central Atlantic Magmatic Province, or CAMP, which formed as Pangaea began rifting apart. Camp volcanism occurred along the rift that would eventually become the Atlantic Ocean. Basaltic lavas erupted through fissures extending from what is now the eastern coast of North America through Morocco and other parts of northwest Africa. The eruptions were not continuous, but occurred in multiple pulses over several 100,000 years. Mercury anomalies in sediments record these pulses, indicating repeated episodes of massive volatile release. The kill mechanisms resembled those of the end Permian extinction, though at smaller magnitude. Carbon dioxide release caused global warming and ocean acidification. Sulfur dioxide created acid rain that damaged terrestrial vegetation. Ocean anoxia expanded as warming waters held less oxygen. The repeated volcanic pulses prevented ecosystem recovery between perturbations, driving progressive extinction over hundreds of thousands of years rather than a single catastrophic event. The extinction was selective, affecting some groups severely while sparing others. Marine organisms suffered heavily, with widespread extinction among ammonoids, bivalves, and other groups. On land, large archosaurs including most crurotarsans went extinct, eliminating dinosaur competitors. Early dinosaurs survived the extinction relatively unaffected, possibly because their small body sizes and possibly higher metabolic rates provided resilience against environmental stress. The post-extinction Jurassic world would be dramatically different from the Triassic. Dinosaurs radiated to fill niches left vacant by extinction, becoming the dominant large animals on land. Pterosaurs diversified in the air. Marine reptiles continued evolving in the oceans. Mammals remained small and nocturnal, but persisted, awaiting their opportunity that would not come for another 150 million years. The Triassic transition was complete. The Mesozoic era, the age of dinosaurs, had truly begun. Chapter 27: The Jurassic World. The Jurassic period began 201 million years ago in the aftermath of the end Triassic extinction. This middle period of the Mesozoic era would become famous as the time when dinosaurs achieved true dominance, diversifying into the spectacular array of forms that capture human imagination today. Enormous sauropods, long-necked herbivorous dinosaurs that included the largest land animals ever to walk the earth, thundered across Jurassic landscapes in herds that could shake the ground. Theropod predators like Allosaurus hunted these giants, using speed, teeth, and slashing claws to bring down prey many times their own size. In the oceans, plesiosaurs and ichthyosaurs ruled as apex predators, while ammonites spiraled through the water in countless species. The skis belonged to pterosaurs that had diversified into numerous forms ranging from small insectivores to larger fish-eaters. Most significantly for the future, the first birds appeared during the late Jurassic, evolving from small feathered theropod dinosaurs and beginning their eventual conquest of the aerial realm. The Jurassic lasted until 145 million years ago, spanning 56 million years, during which the breakup of Pangaea created new ocean basins. While dinosaurs established their dominance, that would continue for another 80 million years into the Cretaceous. Pangea fragments. The Jurassic witnessed the beginning of Pangea's breakup, initiating continental movements that would eventually produce the modern distribution of continents. By the early Jurassic, rifting had begun, splitting Pangea into northern Laurasia and southern Gondwana. The separation proceeded gradually over tens of millions of years. The central Pangean mountains that had formed during Pangea's assembly began eroding as the supercontinent pulled apart. By the Middle Jurassic, Laurasia and Gondwana were becoming clearly separated. The Tethys Ocean, which had existed as an embayment on Pangea's eastern side, expanded westward as the split propagated. This growing seaway would eventually extend completely across the former supercontinent, creating a vast east-west ocean separating the northern and southern landmasses. The opening of new ocean basins between the fragmenting continents altered ocean circulation patterns and climate. The separation of Laurasia and Gondwana had biological consequences. Dinosaur faunas on the two landmasses began diverging as gene flow between northern and southern populations was interrupted. Jurassic dinosaurs in Laurasia evolved differently from their relatives in Gondwana. This continental separation helps explain why dinosaur fossils from Africa, South America, and Australia, the Gondwanan continents, differ from species found in North America, Europe, and Asia, the Laurasian continents. The biogeographic patterns established during Jurassic continental drift would influence evolutionary trajectories for the remainder of the Mesozoic. The breakup changed global climate by affecting ocean circulation and moisture distribution. When Pangea was intact, its interior was isolated from oceanic moisture, creating extensive deserts. As the supercontinent fragmented, seaways penetrated inland, bringing moisture to formerly arid regions. Precipitation increased across many areas that had been desert during the Triassic. The improved moisture availability supported more extensive vegetation, which in turn supported higher densities and diversities of herbivorous dinosaurs. Sauropod giants. Sauropods, the long-necked herbivorous dinosaurs, reached their peak diversity and their largest body sizes during the Jurassic. These animals possessed extraordinarily long necks, containing 10 to 19 elongated vertebrae, allowing them to reach vegetation inaccessible to other herbivores. Their tails were equally long, functioning as counterbalances to the extended necks and possibly as defensive weapons that could be swung at predators. The body was barrel-shaped, containing the enormous digestive system needed to process vast quantities of plant material. Brachiosaurus exemplified large Jurassic sauropods. This dinosaur reached lengths exceeding 25 meters and masses estimated at 30 to 60 tons, roughly equivalent to 8 to 12 elephants. Unlike many sauropods where the forelimbs were shorter than hindlimbs, Brachiosaurus possessed longer forelimbs, creating a giraffe-like profile with the shoulders elevated above the hips. The nostrils were positioned high on the skull, once thought to allow breathing while submerged, but now interpreted as aiding thermoregulation. Diplodocus represented a different sauropod body plan, emphasizing length over height. This dinosaur reached lengths approaching 30 meters, making it one of the longest land animals ever, though it was relatively lightly built with a mass perhaps only 15 to 20 tons. The extremely long tail contained over 80 vertebrae and may have been capable of being whipped at supersonic speeds, creating loud cracks that could deter predators or establish dominance within herds. The evolution of gigantism in sauropods resulted from multiple factors. Their bird-like respiratory system, with air sacs extending throughout the body, reduced effective body weight while maintaining structural support. The long neck allowed exploitation of food resources unavailable to competitors without requiring a large, heavy head. Continuous growth throughout life meant that surviving individuals could reach enormous sizes. The Jurassic climate was warm and vegetation was abundant, supporting the massive food requirements of these giants. Theropod predators. Theropod dinosaurs, the carnivorous bipedal forms, diversified extensively during the Jurassic. These dinosaurs ranged from small chicken-sized forms to massive predators exceeding 10 meters in length. All theropods were characterized by hollow bones, three-toed feet with sharp claws, and hands adapted for grasping. The skull was large relative to body size in most forms, with powerful jaws filled with serrated teeth designed for slicing flesh. Allosaurus dominated as the apex predator in late Jurassic North America and Europe. This 9-meter-long theropod possessed a skull that was simultaneously light yet strong, with large openings reducing weight while maintaining structural integrity. The teeth were blade-like with serrations on both front and rear edges, ideal for cutting through flesh. The arms, though relatively small compared to body size, bore 3-fingered hands with sharp curved claws useful for grasping prey. Evidence suggests Allosaurus hunted the abundant sauropods that shared its environment. Tooth marks matching Allosaurus teeth have been found on sauropod bones. Some paleontologists propose that Allosaurus hunted in packs, allowing multiple individuals to bring down prey far larger than any single predator could tackle. Others suggest Allosaurus was primarily a scavenger, feeding on already dead animals. Most likely, Allosaurus was an opportunistic predator that both hunted when possible and scavenged when opportunities arose. Smaller theropods occupied different ecological niches. Ceratosaurus, another late Jurassic predator, possessed a prominent horn on its snout and bony ridges over its eyes, possibly used in display or combat with rivals. Ornitholus was a small, agile theropod probably specializing in catching smaller prey like lizards, early mammals, and insects. These smaller theropods were likely much more common than large predators, but are less frequently preserved as fossils. Marine reptiles. Jurassic oceans teemed with marine reptiles that had evolved from terrestrial ancestors and returned to aquatic life. Ichthyosaurs were the most fish-like, having evolved streamlined bodies, flippers instead of legs, and tail flukes for propulsion. Some ichthyosaurs grew to enormous sizes exceeding 15 meters. Their huge eyes, sometimes exceeding 20 centimeters in diameter, indicate they dove to great depths, where they hunted squid and fish in dark waters. Unlike most reptiles that lay eggs, ichthyosaurs gave birth to live young, as evidenced by fossils preserving females with embryos inside, and even fossils capturing the act of birth. Plesiosaurs possessed a different body plan, characterized by 4 large flippers used for underwater flight, similar to sea lions. 2 main groups existed: pliosaurs with large heads, short necks, and massive jaws for catching large prey, and long-necked plesiosaurs with small heads used to catch smaller, more agile prey. Plesiosaurs also gave birth to live young, allowing them to remain permanently at sea without returning to land. Ammonites, though not reptiles but cephalopod mollusks related to squids and octopuses, were extraordinarily diverse in Jurassic oceans. These animals possessed coiled shells divided into chambers. As the animal grew, it secreted new, larger chambers while sealing off older ones. The sealed chambers contained gas that provided buoyancy, allowing the ammonite to control its depth in the water column. Ammonites ranged in size from a few centimeters to over 2 meters in diameter. They were important prey for marine reptiles, with numerous plesiosaur and ichthyosaur fossils containing ammonite remains in their stomach regions. The first birds. The most significant evolutionary development of the Jurassic was the appearance of the first birds. Archaeopteryx, discovered in late Jurassic limestone deposits in Germany, dated to approximately 150 million years ago, represents the earliest known bird. This animal possessed a mosaic of bird and dinosaur features, clearly demonstrating the evolutionary transition from theropod dinosaurs to birds. Archaeopteryx possessed features unmistakably avian. Feathers covered its wings and body, with flight feathers arranged exactly as in modern birds. The wings could fold against the body when not in use. The feathers were asymmetric, the design that produces lift during flight. These features indicate Archaeopteryx could fly, though whether it could take off from the ground or required climbing to gain altitude before gliding remains debated. Simultaneously, Archaeopteryx retained numerous dinosaurian characteristics. The jaws contained teeth rather than being covered by a beak. The tail was long and bony, composed of multiple vertebrae rather than the short pygua style of modern birds. 3 fingers extended from each wing, ending in sharp claws useful for climbing. The brain case was intermediate between theropods and modern birds. These primitive features link Archaeopteryx clearly to its theropod ancestors. Recent discoveries from China have revealed that numerous small theropods possessed feathers, demonstrating that feathers evolved before flight. Feathers initially served functions like insulation, display, or brooding eggs. Flight evolved later as an additional function for structures that already existed. The exact pathway by which flight evolved remains debated. The ground-up hypothesis proposes that running theropods began flapping their forelimbs while chasing prey, eventually gaining enough lift to become airborne. The trees-down hypothesis suggests that arboreal theropods began gliding between trees, with flapping evolving as a way to extend glide distance. Both scenarios may be partially correct, with different lineages exploring both pathways. Jurassic climate. The Jurassic climate was warm and humid, with no evidence of polar ice caps. Global temperatures averaged several degrees warmer than today. The poles were temperate rather than frozen, supporting forests that grew in darkness during winter months. Tropical temperatures were similar to modern tropics, but extended to higher latitudes. The equator to pole temperature gradient was weaker than today, meaning less temperature variation across latitudes. High sea levels characterized much of the Jurassic as warm temperatures, and the absence of polar ice reduced water stored on land. Shallow epicontinental seas flooded low-lying continental areas, creating extensive marine habitats. These shallow seas were highly productive, supporting diverse communities of ammonites, bivalves, marine reptiles, and fish. The fossil record from these seas is extraordinarily rich, providing detailed windows into Jurassic marine life. Carbon dioxide concentrations were elevated compared to modern pre-industrial levels, probably reaching 4 to 5 times current concentrations. This enhanced greenhouse effect contributed to the warm global temperatures. The warmth, combined with the fragmentation of Pangaea, created conditions where moisture could penetrate inland, supporting lush vegetation across most continents. Deserts were less extensive than during the Triassic, though arid regions still existed in continental interiors. The warm, equable climate supported high dinosaur diversity. Sauropods could maintain their enormous body sizes because abundant vegetation provided sufficient food year-round. Theropods had ample prey to support healthy populations. The lack of seasonal extremes meant that animals did not need adaptations for dealing with cold winters or long, dry seasons. The Jurassic represented something of a golden age for dinosaurs, when environmental conditions were nearly optimal for their success. These favorable conditions would continue into the Cretaceous, allowing dinosaurs to maintain their dominance for another 80 million years, until the asteroid impact ended their reign. Chapter 28: The Cretaceous and the Asteroid. The Cretaceous period began 145 million years ago as the final chapter in the Age of Dinosaurs. This period would witness both the peak of dinosaur diversity and their ultimate extinction. New groups appeared, including the iconic tyrannosaurs, horned ceratopsians, and duck-billed hadrosaurs that are the most familiar dinosaurs to modern audiences. The most significant botanical development was the appearance and rapid radiation of flowering plants or angiosperms, which transformed terrestrial ecosystems and eventually became the dominant plant group. The Cretaceous climate was even warmer than the Jurassic, with atmospheric carbon dioxide exceeding 1,000 parts per million and tropical temperatures extending far toward the poles. The Cretaceous ended 66 million years ago with the impact of an asteroid approximately 10 to 15 kilometers in diameter that struck what is now Mexico's Yucatan Peninsula. The resulting Cretaceous Paleogene or KPG extinction eliminated approximately 75% of species on Earth, including all non-avian dinosaurs, pterosaurs, and marine reptiles, clearing the way for the age of mammals that would follow. Understanding the Cretaceous requires examining both the extraordinary diversity that evolved during its 139 million years and the catastrophe that brought it to an abrupt end. Continental drift continues. The fragmentation of Pangaea continued throughout the Cretaceous, progressively separating the continents toward their modern configuration. Laurasia, the northern landmass, began breaking apart as the Atlantic Ocean opened. North America separated from Europe around 100 million years ago as seafloor spreading created new oceanic crust between them. This separation proceeded from south to north, with the southern Atlantic opening earlier than the northern Atlantic. Gondwana, the southern landmass, underwent more complex fragmentation. Africa separated from South America as the South Atlantic opened. India broke away from Madagascar and began its journey northward toward Asia, a collision that would eventually create the Himalayan mountains during the Cenozoic. Australia remained attached to Antarctica throughout the Cretaceous, but began rifting toward the period's end. By the late Cretaceous, the continents were approaching their modern arrangement, though they remained connected in several places. The ongoing continental drift created biogeographic patterns visible in the dinosaur fossil record. North American and Asian dinosaurs shared similarities because these landmasses remained connected through Beringia, a land bridge where Alaska and Siberia approached each other. South American and African dinosaurs showed relationships reflecting their more recent separation. Australian dinosaurs were unique, isolated on their southward drifting continent. These patterns demonstrate how continental movements influenced evolution by creating and eliminating dispersal corridors. Sea level during the Cretaceous was substantially higher than today, with estimates suggesting levels were 100 to 200 meters higher during peak transgression in the late Cretaceous. The Western Interior Seaway divided North America from north to south, creating eastern and western landmasses. Similar epicontinental seas flooded other continents. These shallow seas provided extensive marine habitats supporting extraordinary biodiversity, but they also limited terrestrial area, concentrating dinosaur populations into smaller geographic ranges. Flowering plant revolution. The appearance and radiation of flowering plants or angiosperms during the Cretaceous represents one of the most significant evolutionary events in plant history. The earliest angiosperm fossils date to approximately 125 million years ago in the early Cretaceous. These early flowering plants were small, weedy species occupying disturbed habitats. They remained relatively uncommon for approximately 25 million years before beginning a dramatic radiation around 100 million years ago that would make them the dominant plant group. Angiosperms possess unique reproductive structures, including flowers and fruits. Flowers attract pollinators, including insects, birds, and eventually bats through colors, scents, and nectar rewards. The pollinators transfer pollen between plants, enabling sexual reproduction and genetic mixing. Fruits protect developing seeds and aid in seed dispersal. Animals eating fruits transport seeds away from parent plants, reducing competition and allowing colonization of new areas. These innovations gave angiosperms advantages over gymnosperms like conifers that relied on wind pollination and lacked protective fruits. The rapid diversification of angiosperms during the mid-Cretaceous, sometimes called the Cretaceous terrestrial revolution, fundamentally altered terrestrial ecosystems. Flowering plants provided new food sources for herbivores in the form of nutritious leaves, fruits, and seeds. The diversification of flowering plants drove corresponding diversifications in herbivorous insects that fed on them and the predators that consumed the herbivores. Ecosystems became more complex, with more trophic levels and more specialized interactions between species. Herbivorous dinosaurs adapted to exploit flowering plant resources. Hadrosaurs or duck-billed dinosaurs possessed complex dental batteries with hundreds of teeth arranged in rows, ideal for processing tough plant material. Ceratopsians possessed sharp beaks and shearing teeth suitable for cropping and slicing vegetation. Both groups diversified dramatically during the late Cretaceous, coinciding with angiosperm dominance. The correlation suggests that flowering plants provided resources supporting higher dinosaur diversity. Late Cretaceous dinosaurs. Dinosaur diversity reached its peak during the late Cretaceous as new groups appeared and diversified. Tyrannosaurs evolved into massive apex predators. Tyrannosaurus rex, the most famous dinosaur, reached lengths exceeding 12 meters and masses approaching 9 tons. The skull was massive and heavily built, capable of generating bite forces exceeding 6 tons, the highest bite force of any terrestrial animal. The teeth were thick and conical rather than blade-like, designed for crushing bone rather than just slicing flesh. Ceratopsians, or horned dinosaurs, diversified extensively during the late Cretaceous. These dinosaurs possessed large bony frills extending backward from the skull and horns of varying numbers and arrangements depending on the species. Triceratops, the most famous ceratopsian, possessed 2 brow horns over a meter long and a shorter nasal horn. The frill was solid bone, unlike in some earlier ceratopsians where the frill contained large openings. The function of horns and frills remains debated, with proposed explanations including defense against predators, intraspecific combat for mates or territory, and display for species recognition or mate attraction. Hadrosaurs, or duck-billed dinosaurs, were extraordinarily diverse, with dozens of species described from late Cretaceous rocks. These dinosaurs possessed flattened, beak-like snouts resembling duck bills, hence their common name. Many hadrosaurs possessed elaborate crests on their heads, formed from nasal bones extended into hollow chambers. These crests functioned as resonating chambers, allowing hadrosaurs to produce distinctive calls for communication. Different species possessed differently shaped crests, suggesting the sounds produced aided in species recognition. Ankylosaurs, armored dinosaurs covered in bony plates and spikes, also diversified during the late Cretaceous. The most derived ankylosaurs possessed massive tail clubs formed from fused vertebrae and osteoderms, capable of delivering powerful blows. Computer modeling suggests these clubs could break the leg bones of tyrannosaurs, providing effective defense against the period's apex predators. Other defensive features included spikes protecting the shoulders and thick armor covering the back and sides. Cretaceous thermal maximum. The late Cretaceous experienced the warmest temperatures of the entire Mesozoic era during the Cretaceous thermal maximum around 90 to 94 million years ago. Atmospheric carbon dioxide reached levels exceeding 1,000 parts per million, roughly 3 times pre-industrial concentrations. This enhanced greenhouse effect drove global temperatures to extraordinary heights. Sea surface temperatures at high southern latitudes reached 35 to 37 degrees Celsius, comparable to modern tropical waters. These temperatures occurred at paleolatitudes of 60 to 70 degrees south, corresponding to modern locations well inside the Antarctic Circle. The polar regions were ice-free and supported temperate forests. Winter darkness would have lasted for months at these high latitudes, yet temperatures remained above freezing, demonstrating the power of the greenhouse effect. Tropical temperatures may have reached the upper thermal tolerance limits of many organisms. Some evidence suggests tropical regions became too hot during peak warming, forcing tropical species to shift to higher latitudes where temperatures were more moderate. This creates a paradox where high-latitude regions had higher biodiversity than the tropics, the reverse of the modern pattern. The evidence remains debated, but the possibility of tropics becoming uninhabitably hot provides a cautionary tale for modern climate change. The extreme warmth was maintained by multiple feedbacks. High carbon dioxide from volcanism provided the initial forcing. The warm oceans released methane from seafloor methane hydrates, adding another powerful greenhouse gas. The lack of polar ice reduced Earth's albedo, meaning less solar radiation was reflected to space. The flat temperature gradient between equator and pole weakened atmospheric circulation, reducing the efficiency of heat transport to high latitudes. All these factors combined to create and maintain the extraordinary warmth. The Chicxulub impact. 66 million years ago, an asteroid approximately 10 to 15 kilometers in diameter struck Earth's surface in what is now Mexico's Yucatan Peninsula. The impact occurred in shallow ocean. Excavating a crater 180 kilometers in diameter and 20 kilometers deep, the energy released exceeded 100 million megatons of TNT, roughly 2 million times more powerful than the largest nuclear weapon ever tested. The impact instantly vaporized the asteroid and thousands of cubic kilometers of rock, creating a fireball that expanded through the atmosphere. Ejecta from the impact blanketed Earth's surface globally. Material thrown above the atmosphere re-entered at hypersonic velocities, heating the upper atmosphere to incandescence. This thermal pulse ignited wildfires across continents. The soot from these fires joined dust and rock vapor in the atmosphere, blocking sunlight. Within hours, Earth was plunged into darkness that would last for months. The sulfur-rich rocks at the impact site vaporized, releasing massive quantities of sulfur dioxide. These molecules reacted with water vapor in the stratosphere to form sulfuric acid aerosols. Unlike the dust, which settled out within weeks, the sulfate aerosols persisted for years. They blocked sunlight efficiently while also causing acid rain that acidified surface waters. Computer simulations indicate these aerosols were the primary driver of the mass extinction, more important than the immediate effects of the impact itself. Temperatures plummeted within days of the impact. Tropical regions that had been 27 degrees Celsius dropped to 5 degrees Celsius. Polar regions froze solid. Even more dramatically, within weeks temperatures dropped below freezing globally. Continental annual mean temperatures in the tropics fell to -22 degrees Celsius. This impact winter persisted for years until the sulfate aerosols finally settled out. Only after approximately 30 years did temperatures recover to pre-impact levels. The mass extinction. The KPG extinction eliminated approximately 75% of species on Earth. All non-avian dinosaurs went extinct. The massive tyrannosaurs and horned ceratopsians that had dominated late Cretaceous landscapes vanished. Pterosaurs, which had ruled the seas for 160 million years, disappeared. Marine reptiles including plesiosaurs, mosasaurs, and the last ichthyosaurs went extinct. Ammonites, successful for hundreds of millions of years, were eliminated. The extinction mechanisms were multiple and reinforcing. The initial impact killed everything within thousands of kilometers through blast effects, thermal radiation, and megatsunamis. The global darkness shut down photosynthesis, collapsing food chains from the base upward. Herbivores starved without plants. Carnivores starved without herbivores. The extreme cold killed tropical and subtropical species that had never experienced freezing temperatures. Ocean acidification from sulfuric acid killed organisms with calcium carbonate shells. Selective survival patterns reveal which traits aided survival. Small body size improved odds, possibly because small animals required less food and could survive on seeds, roots, and detritus. Aquatic organisms, particularly freshwater species, survived at higher rates than terrestrial species, possibly because aquatic food chains based on detritus were less disrupted than terrestrial food chains based on photosynthesis. Species with wide geographic ranges survived better than narrow endemics, because populations in some areas survived even when others perished. Birds survived when non-avian dinosaurs perished. The survivors were primarily ground-dwelling omnivores and scavengers rather than specialized tree-dwellers or predators. These generalist survivors could exploit the limited food resources available in the post-impact wasteland. From these survivors, birds would eventually radiate during the Paleogene, diversifying into the 10,000 species alive today. Mammals also survived, though many Cretaceous lineages went extinct. The survivors were small omnivores and insectivores. Within 10 million years of the extinction, mammals had radiated into diverse forms, including the first large herbivores and carnivores, beginning their rise to dominance. The asteroid that ended the age of dinosaurs inaugurated the age of mammals, setting the stage for the evolution of primates and eventually humans. The extinction demonstrates that evolutionary success, even sustained for 150 million years, provides no immunity against catastrophic external perturbations. The dinosaurs' reign ended not through evolutionary inadequacy, but through cosmic bad luck. Chapter 29: The Age of Mammals. The Paleogene period began 66 million years ago in a world devastated by the asteroid impact that ended the Cretaceous. This period, spanning from 66 to 23 million years ago, witnessed the explosive radiation of mammals into the ecological niches left vacant by the extinction of non-avian dinosaurs. Within 10 million years of the extinction, Mammals had diversified from small insectivorous forms into an extraordinary array of herbivores, carnivores, omnivores, and specialists adapted to environments from forests to grasslands to oceans. The Paleogene encompasses three epochs: the Paleocene from 66 to 56 million years ago, the Eocene from 56 to 34 million years ago, and the Oligocene from 34 to 23 million years ago. During the Paleocene, mammals remained relatively small as ecosystems recovered from the extinction. The Eocene saw peak warmth and the appearance of modern mammalian orders, including primates, the lineage that would eventually produce humans. The Oligocene witnessed global cooling and the beginning of grassland expansion. The Paleogene represents the foundation of the age of mammals, establishing the mammalian dominance that continues to the present day. Post-extinction recovery. The earliest Paleocene, immediately following the KPG extinction, was a time of ecological devastation and slow recovery. Forests had been destroyed by wildfires and the prolonged darkness. Many plant species went extinct, with survivors mainly including species that produced seeds capable of remaining dormant until conditions improved. The recovery of vegetation took thousands of years as pioneer species recolonized barren landscapes. Mammals that survived the extinction were small, generalist omnivores and insectivores weighing less than 1 kilogram. These survivors included members of groups that exist today, such as early placental mammals and marsupials, as well as groups now extinct, particularly multituberculates. Multituberculates, rodent-like mammals unrelated to true rodents, had been diversifying ecologically for at least 20 million years before the extinction and continued this radiation across the KPG boundary. This demonstrates that mammalian diversification had begun before the dinosaur extinction, though it accelerated dramatically afterward. Within 1 to 2 million years after the extinction, mammals began increasing in body size. By 10 million years after the extinction, during the Middle Paleocene, mammals had evolved forms exceeding 100 kilograms. This size increase occurred simultaneously with ecosystem recovery as forests redeveloped and plant productivity increased. Larger body sizes allowed mammals to exploit food resources that small mammals could not efficiently process, particularly low-quality vegetation that required large digestive systems. The diversification was explosive. Starting from perhaps 15 to 20 mammalian families that survived the extinction, mammals radiated into over 130 families by the end of the Eocene. This represents nearly a tenfold increase in family-level diversity within 40 million years. The radiation filled ecological niches as herbivores, carnivores, insectivores, frugivores, and numerous specialists. The absence of dinosaurs meant that mammals faced no competition from large terrestrial reptiles and could grow to substantial sizes. Primate origins. Primates, the mammalian order that includes monkeys, apes, and humans, first appeared in the fossil record near the boundary between the Paleocene and Eocene around 56 million years ago. However, molecular clock analyses suggest primates actually originated earlier, possibly as far back as 90 million years ago during the late Cretaceous. The absence of Paleocene primate fossils may reflect either that early primates were rare and lived in environments where fossilization was unlikely, or that they were small and morphologically similar to other mammals, making them difficult to identify in the fossil record. The earliest identifiable primates were small arboreal animals adapted to life in trees. They possessed grasping hands and feet with opposable digits, allowing secure grip on branches. Forward-facing eyes provided stereoscopic vision essential for judging distances when leaping between branches. Large eye sockets indicate these early primates were nocturnal, active at night when they hunted insects and gathered fruits in the forest canopy. The appearance of modern primate groups, including the ancestors of monkeys and apes, occurred during the Paleocene-Eocene thermal maximum, a period of rapid global warming discussed below. The warming created tropical conditions extending to high latitudes, allowing tropical forests to expand dramatically. These expanded forests provided habitat supporting primate diversification. Modern orders including Artiodactyla, even-toed ungulates like deer and pigs, and Perissodactyla, odd-toed ungulates like horses and rhinos, also appeared at this time, suggesting the environmental changes favored radiation across multiple mammalian lineages simultaneously. Early primates diversified into multiple lineages during the Eocene. Adapiforms, lemur-like primates, became common in North America and Europe. Hominids, more closely related to tarsiers, were diverse and widespread. These early primates remained relatively small, mostly weighing less than 5 kilograms. They were primarily frugivorous or insectivorous, occupying ecological niches in forest canopies. The Eocene primates established the basic primate body plan and behavioral repertoire that would characterize the order throughout its subsequent evolution. The PATM, the Paleocene-Eocene thermal maximum, occurring approximately 56 million years ago, represents one of the most dramatic climate events of the Cenozoic era. Within 15 to 20,000 years, global temperatures increased by 5 to 8 degrees Celsius. Deep ocean temperatures rose by 5 to 6 degrees. The warming was driven by massive carbon release into the atmosphere, with more than 2,000 gigatons of carbon injected over the warming interval. The trigger for the PETM was volcanism from the North Atlantic igneous province associated with the opening of the North Atlantic Ocean. Elevated mercury levels in sediments deposited immediately before and during the early PETM provide evidence for pulsed volcanism. The initial volcanic carbon release triggered crossing of a tipping point, after which carbon stored in other reservoirs was released through positive feedbacks. Possible additional carbon sources include methane hydrates on the seafloor that destabilized as ocean temperatures rose, releasing methane that oxidized to carbon dioxide. PETM was associated with the largest deep-sea mass extinction event in the last 93 million years. Deep-sea foraminifera, single-celled organisms that build calcium carbonate shells, suffered extinction rates exceeding 30%. The extinction resulted from ocean acidification as the massive carbon dioxide influx lowered ocean pH, making it difficult for organisms to build carbonate shells. Ocean anoxia may have contributed as warming waters held less oxygen. On land, the PETM drove remarkable diversification rather than extinction. The appearance of modern mammalian orders including primates, Artiodactyla, and Perissodactyla coincided precisely with the PETM onset. The warming extended tropical and subtropical conditions to high latitudes, expanding forest habitats. The rapid environmental changes created ecological opportunities that mammals exploited through adaptive radiation. The PETM demonstrates that rapid warming can drive extinction in some ecosystems while simultaneously driving diversification in others. Recovery from the PETM required approximately 150,000 years as natural weathering processes gradually removed excess carbon dioxide from the atmosphere. The event provided a natural experiment demonstrating Earth system responses to rapid carbon release. The PETM warming rate of approximately 0.25 degrees Celsius per 1,000 years was actually slower than current anthropogenic warming rates, suggesting modern climate change may produce even more severe ecosystem disruptions than those observed during the PETM. Eocene warmth. The Eocene epoch from 56 to 34 million years ago was characterized by warm global temperatures with minimal ice at the poles. Tropical conditions extended to approximately 45 degrees latitude, much farther from the equator than today. Palm trees grew in Alaska and crocodilians inhabited the Arctic, indicating winter temperatures remained above freezing even at high latitudes. Atmospheric carbon dioxide during the Eocene exceeded 1,000 parts per million, roughly 3 times pre-industrial levels. This elevated greenhouse gas concentration maintained warm temperatures despite solar radiation being slightly weaker than today due to gradual solar evolution. Ocean circulation patterns differed from modern patterns because the continents were still moving toward their current positions. The absence of ice meant sea levels were substantially higher flooding low-lying continental areas and creating extensive shallow seas. Mammalian diversity reached its Paleogene peak during the Eocene. Forests covered most continents, providing habitat for diverse arboreal mammals. Large herbivores, including early relatives of horses, rhinos, and elephants, browsed on forest vegetation. Carnivores, including creodonts, an extinct group only distantly related to modern carnivores, hunted these herbivores. Primates were diverse and widespread, inhabiting forests in North America, Europe, Asia, and Africa. Marine mammals diversified during the Eocene as some terrestrial mammals returned to aquatic life. Early whales evolved from terrestrial artiodactyls, gradually becoming more adapted to marine existence. By the late Eocene, fully aquatic whales had appeared, having lost their hind limbs and evolved flippers and tail flukes. The return of mammals to the oceans demonstrated the evolutionary plasticity that characterized mammalian radiation during the Paleogene. Oligocene cooling. The transition from Eocene to Oligocene around 34 million years ago was marked by dramatic global cooling. Temperatures dropped by several degrees Celsius within a geologically brief interval of less than 1 million years. The cooling was sufficient to allow permanent ice sheets to form on Antarctica for the first time in the Cenozoic. The formation of Antarctic ice sheets marked the beginning of the modern icehouse climate state that persists today. The cooling resulted from multiple factors. Atmospheric carbon dioxide decreased as volcanism declined, and weathering processes gradually removed carbon from the atmosphere. The opening of ocean passages between Antarctica and other continents, particularly the Drake Passage between Antarctica and South America, allowed the Antarctic circumpolar current to develop. This current thermally isolated Antarctica, preventing warm waters from reaching the continent and allowing ice accumulation. The cooling had profound effects on terrestrial ecosystems. Tropical forests contracted toward the equator. Seasonal climates with distinct wet and dry seasons became more widespread. Grasslands began expanding in mid-latitude regions, particularly in North America, where open grasslands started replacing forests by the late Oligocene around 26 million years ago. The shift from forests to grasslands was driven by climate drying, particularly during winter seasons when precipitation decreased. Mammalian faunas changed in response to cooling and habitat shifts. In North America and Eurasia, forest-adapted mammals declined while open country forms increased. Browsing herbivores adapted to eating leaves from trees gave way to grazing herbivores adapted to eating grasses. The evolution of hypsodont teeth, high-crowned teeth that continue growing throughout life to compensate for abrasion from grass silica, appeared in multiple herbivore lineages. These adaptations foreshadowed the extensive grassland ecosystems that would dominate during the subsequent Neogene period. Chapter 30. Toward the Human World. The Neogene period began 23 million years ago as global cooling and grassland expansion accelerated. This period, extending until 2.6 million years ago, encompasses the Miocene epoch from 23 to 5.3 million years ago and the Pliocene epoch from 5.3 to 2.6 million years ago. The Neogene witnessed the transformation of Earth's vegetation as grasslands expanded across continents, replacing forests in mid-latitude regions and creating vast savannas and steppes. These grasslands supported diverse megafaunal communities, including horses, elephants, rhinos, antelopes, and the predators that hunted them. Most significantly for the human story, the Neogene saw the evolution and diversification of hominins, the lineage that includes modern humans and our extinct relatives. The transition from forest-dwelling apes to bipedal tool-using hominins occurred during the late Miocene and Pliocene in Africa. The Neogene set the stage for the Quaternary period, which includes the Pleistocene Ice Age and the current Holocene epoch, during which humans evolved full behavioral modernity and established global dominance. The Grassland Revolution. The Neogene witnessed the most dramatic expansion of grasslands in Earth's history. While grasslands had begun developing during the Oligocene, the Neogene saw them spread across vast areas in North America, South America, Africa, and Asia. By the late Miocene, grasslands covered more terrestrial area than at any previous time. Savannas, pampas, steppes, and prairies replaced forests that had dominated these regions for millions of years. The spread of grasslands resulted from continuing global cooling and the drying of continental interiors. The uplift of major mountain ranges, including the Himalayas and Andes, created rain shadows, regions where mountains block moisture-bearing winds and create arid conditions on the leeward side. The Himalayan uplift particularly affected Asian climate, creating the monsoon system and drying interior regions. The closure of the Isthmus of Panama approximately 3.5 million years ago altered ocean circulation, contributing to cooling. Grass evolution contributed to grassland expansion through positive feedbacks. Grasses, particularly C4 grasses that evolved during the Neogene, are highly adapted to frequent fires. Fire kills tree seedlings, but grasses regrow quickly from underground rhizomes. As grasslands expanded, fires became more frequent, which further favored grasses over trees. This grassland fire feedback mechanism maintained and even expanded grasslands once they became established, creating a self-reinforcing cycle. The shift from C3 to C4 grasses occurred during the late Miocene, around 8 to 6 million years ago. C4 grasses use a different photosynthetic pathway that is more efficient in hot, dry conditions and at low atmospheric carbon dioxide concentrations. As carbon dioxide continued declining from Eocene levels, C4 grasses gained competitive advantages over C3 grasses and broadleaf plants. The C4 expansion is recorded in fossil records through changes in stable carbon isotopes preserved in soils and mammalian tooth enamel. Grassland expansion profoundly affected mammalian evolution. Grazing herbivores diversified extensively. Horses evolved from small multi-toed forest browsers into large single-toed grazers capable of running at high speeds across open plains. Bovids, including antelopes, cattle, and buffalo, radiated into dozens of lineages. Elephants diversified into multiple families adapted to various grassland and savanna habitats. Predators, including early big cats, hyenas, and canids, evolved to hunt these grazing herbivores across open landscapes. Hominin origins. The human lineage diverged from other apes during the late Miocene, approximately 7 to 6 million years ago in Africa. The earliest potential hominins include Sahelanthropus from Chad, dated to approximately 7 million years ago, and Auroran from Kenya, dated to approximately 6 million years ago. These species show mosaic features combining ape-like and human-like characteristics, making their evolutionary positions debated. By 4.4 million years ago, definitive hominins including Ardipithecus had appeared. Ardipithecus possessed a mix of arboreal adaptations, suggesting it still spent significant time in trees and features indicating bipedal locomotion on the ground. The evolution of bipedalism, walking upright on 2 legs rather than 4, represents the defining hominin characteristic. Bipedalism evolved before other human features, including large brains and stone tool use. The causes of bipedalism remain debated. The traditional savanna hypothesis proposed that as forests gave way to grasslands, bipedalism allowed early hominins to see over tall grass and travel efficiently across open country. However, evidence suggests the earliest bipedal hominins inhabited woodland environments rather than open grasslands. Alternative hypotheses include that bipedalism freed the hands for carrying food or offspring, allowed more efficient long-distance walking while foraging, or helped with thermoregulation by reducing the body surface exposed to direct sunlight. Australopithecines appeared by 4 million years ago and diversified into multiple species. These hominins were fully bipedal on the ground, as evidenced by footprints and skeletal anatomy, though they retained some arboreal adaptations, suggesting they still climbed trees. Brain sizes remained small, approximately 400 to 550 cubic centimeters, only slightly larger than chimpanzees. Australopithecines did not make stone tools. They used their hands for manipulation, but had not yet developed the cognitive abilities for systematic tool manufacture. The genus Homo appeared approximately 2.8 to 2.5 million years ago. Early Homo species possessed larger brains than Australopithecines, approximately 600 to 800 cubic centimeters. They manufactured simple stone tools called Oldowan tools, marking the beginning of the Paleolithic or Stone Age. These tools were sharp flakes struck from stone cores, useful for butchering animals and processing plant materials. The appearance of Homo with increased brain size and tool use represents a major transition in human evolution. Ice Age cycles. The Pleistocene epoch began 2.6 million years ago, marking the onset of the Quaternary period. The Pleistocene is characterized by repeated glacial-interglacial cycles, alternating between cold glacial periods when ice sheets expanded across high latitudes and warmer interglacial periods when ice retreated. These climate oscillations, driven by variations in Earth's orbit and axial tilt, occurred with periods of approximately 41,000 years early in the Pleistocene and approximately 100,000 years for the past 1 million years. During glacial maxima, ice sheets covered northern North America, northern Europe, and parts of Asia. The ice reached thicknesses exceeding 2 kilometers in some regions. Sea level dropped by approximately 120 meters as water was locked in continental ice, exposing land bridges including Beringia connecting Asia and North America. Global temperatures averaged approximately 5 degrees Celsius cooler than today, with high latitudes experiencing even more extreme cooling. Megafauna thrived during much of the Pleistocene, exploiting the productive grasslands and tundra environments created by glacial conditions. Mammoths, mastodons, woolly rhinos, giant ground sloths, saber-toothed cats, and numerous other large mammals inhabited these Ice Age landscapes. These animals experienced boom and bust cycles as they tracked rapid climate changes. Short-lived pulses of optimal conditions created bonanzas for megafaunal grazers, resulting in population expansions recorded in the fossil record. Human evolution continued throughout the Pleistocene. Homo erectus appeared approximately 2 million years ago and was the first hominin to migrate out of Africa, reaching Asia and Europe. Homo heidelbergensis appeared approximately 700,000 years ago and was likely the common ancestor of both Neanderthals and modern humans. Neanderthals evolved in Europe and Western Asia around 400,000 to 250,000 years ago. Anatomically modern Homo sapiens appeared in Africa approximately 300,000 years ago. Cognitive revolution. Between 70,000 and 30,000 years ago, Homo sapiens underwent a cognitive revolution characterized by the appearance of new ways of thinking and communicating. Archaeological evidence shows dramatic increases in cultural complexity, including sophisticated tools, art, jewelry, and symbolic behavior. Cave paintings, Venus figurines, and burial rituals indicate abstract thinking and symbolic thought had emerged. The cause of the cognitive revolution remains debated. The most common hypothesis proposes that genetic mutations altered brain structure, enabling entirely new cognitive capabilities. These mutations may have perfected language, allowing humans to communicate about abstract concepts, past events, and future possibilities. Language enabled sharing of information, coordinating complex activities, and transmitting culture across generations. Alternative hypotheses emphasize gradual accumulation of cultural innovations rather than sudden genetic changes. The cognitive revolution coincided with human expansion out of Africa in a migration that would eventually populate every continent except Antarctica. Modern humans reached the Middle East by 70,000 years ago, Australia by 60,000 years ago, Europe by 45,000 years ago, and the Americas by at least 15,000 years ago. Wherever modern humans went, they encountered and often interbred with archaic human populations, including Neanderthals and Denisovans, before these archaic populations went extinct. Human expansion was associated with megafaunal extinctions across multiple continents. In Australia, large marsupials went extinct within a few thousand years of human arrival. In the Americas, approximately 80% of megafaunal genera went extinct between 13,000 and 11,000 years ago, shortly after humans crossed Beringia and spread south. In Eurasia, megafaunal extinctions occurred more gradually, but accelerated with human expansion. The correlation between human arrival and extinction suggests humans played a major role, though climate change also contributed. The Holocene. The current Holocene epoch began 11,700 years ago as the last glacial period ended and climate warmed into the current interglacial. The Holocene has been characterized by relatively stable, warm climate that has permitted human civilization to develop. The climate stability contrasts with the rapidly oscillating conditions of the Pleistocene, providing a predictable environment where agriculture could succeed. The transition to agriculture began approximately 12,000 to 10,000 years ago independently in multiple regions, including the Fertile Crescent, China, Mesoamerica, and the Andes. Hunter-gatherers began cultivating plants and domesticating animals, transitioning to settled agricultural lifestyles. Agriculture allowed higher population densities and accumulation of surplus food, leading to specialization of labor, social stratification, and the rise of complex societies. Civilizations emerged in multiple regions during the Holocene. Mesopotamia, Egypt, the Indus Valley, China, Mesoamerica, and the Andes all developed complex urban societies with writing, monumental architecture, and centralized governments. These civilizations transformed landscapes through agriculture, irrigation, deforestation, and urbanization. Human impact on Earth systems accelerated dramatically as populations grew and technologies advanced. The last several centuries have witnessed unprecedented human impacts on Earth systems. Industrialization, beginning approximately 250 years ago, dramatically increased energy consumption, resource extraction, and waste production. Human population grew from approximately 1 billion in 1800 to over 8 billion today. Atmospheric carbon dioxide has increased from 280 parts per million pre-industrially to over 420 parts per million currently, driving global warming of approximately 1.2 degrees Celsius. Many scientists propose that we have entered the Anthropocene, a new geological epoch defined by pervasive human influence on Earth systems. Human activities are driving the sixth mass extinction, with current extinction rates estimated at 100 to 1,000 times natural background rates. Approximately 1 million species are threatened with extinction. Climate change, habitat destruction, pollution, invasive species, and overexploitation all contribute to biodiversity loss. The question of whether we are truly in a sixth mass extinction comparable to the Big Five extinctions of the geological past remains debated. Current extinction rates are elevated, but have not yet reached the catastrophic levels of past mass extinctions that eliminated 75% or more of species. However, if current trends continue unabated, extinction rates could reach mass extinction levels within centuries. Unlike previous extinctions caused by volcanic eruptions, asteroid impacts, or natural climate changes, this extinction is caused entirely by one species, humans. We possess both the power to drive a mass extinction and the knowledge to prevent it. The choice is ours. From the first prokaryotic cells 3.5 billion years ago to modern humans reshaping the planet, life's journey has been one of extraordinary creativity, resilience, and transformation. Through billions of years, life has survived snowball glaciations, asteroid impacts, massive volcanic eruptions, and dramatic climate changes. It has colonized every environment from deep-sea vents to high mountain peaks. It has evolved from simple chemical replicators to conscious beings capable of understanding their own origins. The story of life on Earth is far from over. What happens next depends on the choices made by one remarkable species during this pivotal moment in planetary history. Chapter 31: The Mystery of Beginnings. Understanding how life began on Earth remains one of science's greatest unsolved mysteries. 4 billion years ago, Earth was a violent world bombarded by asteroids, with volcanic activity far exceeding anything seen today. Yet somehow, within this chaos, non-living chemistry gave rise to living organisms capable of reproduction, metabolism, and evolution. This transition from chemistry to biology, known as abiogenesis, left no direct fossil evidence because the first life forms were microscopic and lacked hard parts that fossilize readily. Scientists must therefore reconstruct the origin of life through experiments, chemical logic, and traces preserved in the most ancient rocks. Multiple competing hypotheses attempt to explain how the first cells assembled themselves from simple molecules, where this assembly occurred, and what the earliest life forms were like. These questions touch on fundamental issues about the nature of life itself and whether similar processes might have produced life elsewhere in the universe. The answers remain incomplete, but decades of research have revealed plausible pathways by which chemistry could have become biology. The primordial soup. The primordial soup hypothesis proposes that life originated in a warm pond or shallow ocean enriched with organic molecules. In 1924, Russian biochemist Alexander Oparin proposed that Earth's early atmosphere, lacking free oxygen, could have supported the synthesis of organic compounds from simple gases. British scientist J.B.S. Haldane independently proposed similar ideas in 1929. Both suggested that these organic compounds would accumulate in bodies of water, creating a soup rich in the building blocks of life. The Oparin-Haldane hypothesis predicted that organic molecules could form spontaneously under early Earth conditions. In 1953, Stanley Miller and Harold Urey tested this prediction in what became one of the most famous experiments in origin of life research. They constructed an apparatus containing water, methane, ammonia, and hydrogen, representing the presumed early atmosphere. Electric sparks simulating lightning discharged through the gases. Within days, the water had turned pink, then deep red. Analysis revealed the formation of several amino acids, the building blocks of proteins, along with other organic molecules. The Miller-Urey experiment demonstrated that complex organic molecules could arise from simple precursors under plausible prebiotic conditions. Subsequent variations of the experiment have produced even more diverse organic compounds, including nucleobases, sugars, and lipids. However, the experiment has limitations. The atmospheric composition Miller and Urey used is now thought to be incorrect. Early Earth's atmosphere probably contained more carbon dioxide and nitrogen than methane and ammonia, making it less reducing than the Miller-Urey atmosphere. Modified Miller-Urey experiments using more realistic atmospheric compositions have shown that amino acids can still form, though in lower yields. The addition of minerals like calcium carbonate to buffer the solution or iron compounds to inhibit oxidation greatly increases yields. This demonstrates that even in a less favorable atmosphere, organic synthesis could proceed under the right geochemical conditions. The experiments prove that abiotic organic synthesis is possible, though they do not prove it actually occurred this way on early Earth. The RNA world. The RNA world hypothesis proposes that before the modern system of DNA, RNA, and proteins, life was based solely on RNA molecules that served both as genetic material and as catalysts. This hypothesis addresses a fundamental chicken-and-egg problem in origin of life research. Modern cells require DNA to store genetic information, RNA to transfer that information, and proteins to catalyze the reactions needed for life. But DNA cannot replicate without proteins, and proteins cannot be made without DNA. How could this interdependent system originate? RNA provides a solution because it can perform both functions. RNA stores genetic information in its sequence of nucleotides, just as DNA does. Additionally, certain RNA molecules, called ribozymes, possess catalytic activity, able to speed up chemical reactions, including the synthesis of more RNA. The discovery of ribozymes in the 1980s provided strong support for the RNA world hypothesis, by demonstrating that RNA could potentially have functioned as both genome and enzyme in early life. The RNA world hypothesis proposes that the first self-replicating molecules were RNA sequences that arose spontaneously in the primordial soup. These early RNA molecules could copy themselves imperfectly, creating variants. Some variants might have catalyzed reactions more efficiently or replicated more accurately. Natural selection would favor these more successful variants, leading to increasingly sophisticated RNA-based systems. Eventually, these systems enclosed themselves in lipid membranes, creating the first true cells. Critical challenges remain for the RNA world hypothesis. The spontaneous formation of RNA under prebiotic conditions is difficult. RNA requires ribose sugar, phosphate, and nucleobases, all of which must combine in specific ways. The chemistry is thermodynamically unfavorable and requires specialized conditions. Once formed, RNA is unstable, degrading rapidly at high temperatures or extreme pH. The RNA world may have required acidic conditions, like those in volcanic regions, to stabilize certain reactions, though this remains speculative. Hydrothermal vent hypothesis. An alternative to the primordial soup hypothesis locates the origin of life at deep-sea hydrothermal vents. These underwater hot springs occur at mid-ocean ridges where tectonic plates spread apart and seawater circulates through hot volcanic rocks. Two main types exist: black smokers that emit superheated acidic water exceeding 400 degrees Celsius, and alkaline vents that emit cooler water around 40 to 90 degrees Celsius with high pH. Alkaline hydrothermal vents, like the Lost City field discovered in 2000, provide environments potentially favorable for life's origin. These vents create natural proton gradients across thin mineral membranes. Hot alkaline fluid from inside Earth meets cold acidic ocean water, creating chemical disequilibrium. This disequilibrium provides energy that organisms can harness, similar to how modern cells generate energy using proton gradients across membranes. The mineral structures at alkaline vents contain tiny pores and channels that could have served as protocells. These naturally occurring compartments provide several advantages. They concentrate reactants, increasing reaction rates. The mineral surfaces catalyze reactions, particularly those involving iron-sulfur compounds that are central to many metabolic pathways. The thermal and chemical gradients provide energy-driving reactions away from equilibrium. These features make alkaline vents attractive candidates for life's origin. The hydrothermal vent hypothesis emphasizes metabolism first rather than replication first. According to this view, the first step toward life was establishing chemical cycles that could extract energy from the environment. Only later did information-carrying molecules like RNA emerge to regulate and improve these metabolic processes. This contrasts with the RNA world hypothesis, which emphasizes replication and evolution before metabolism. Both scenarios face challenges, and it is possible that features of both were necessary. Panspermia and pseudopanspermia. Panspermia proposes that life did not originate on Earth, but instead arrived from space, perhaps on meteorites or comets. This hypothesis does not explain how life originated, merely relocating the question to elsewhere in the universe. However, it could explain life's early appearance on Earth if abiogenesis is extremely rare and unlikely to occur on any single planet within the universe's current age. The strong version of panspermia, suggesting fully formed living cells traveled through space and survived to colonize Earth, faces significant obstacles. Space is hostile to life, with intense radiation, extreme temperatures, and vacuum conditions. Microorganisms would need to survive not only space exposure, but also the violent entry into Earth's atmosphere. While experiments show that some hardy bacteria can survive brief space exposure, surviving interstellar journeys lasting millions of years seems implausible. Pseudopanspermia represents a weaker, well-supported version of the hypothesis. This proposes that organic molecules rather than living cells arrived from space and contributed to life's origin on Earth. Evidence strongly supports this idea. Meteorites contain amino acids, sugars, nucleobases, and other organic compounds. The Murchison meteorite, which fell in Australia in 1969, contains over 70 different amino acids, most not found in terrestrial biology. The comet Wild 2 contains the amino acid glycine. Complex organic molecules exist throughout space. Glycolaldehyde, a sugar molecule and RNA precursor, has been detected around protostars. Cosmic dust contains complex organics with mixed aromatic aliphatic structure. NASA studies suggest that all 4 DNA nucleobases could form in space. This demonstrates that prebiotic chemistry operates on cosmic scales, not just on planets. The organic molecules delivered to early Earth by meteorites and comets may have supplemented or even dominated the inventory of organics available for life's origin. Protocells and self-assembly. The transition from individual molecules to integrated living cells required the development of compartments that could separate internal chemistry from the external environment. Modern cells are bounded by lipid membranes, double layers of fatty molecules that create selective barriers. How could such membranes have originated, and what role did they play in life's origin? Lipid molecules can spontaneously self-assemble into membrane structures when placed in water. The molecules possess hydrophobic tails that avoid water and hydrophilic heads that interact with water. In aqueous solution, lipids organize themselves to minimize unfavorable interactions, forming spherical vesicles with bilayer membranes. These protocells can encapsulate molecules inside, creating compartments isolated from the external environment. Protocells can grow, divide, and compete, exhibiting lifelike behaviors despite lacking sophisticated biochemistry. Elevated temperatures promote protocell nucleation and growth. Lipid networks formed from interconnected nanotubes can rapidly swell into microcompartments when heated. These compartments can spontaneously encapsulate RNA fragments. Adjacent protocells, connected by nanotubular bridges, can fuse, redistributing their contents and potentially combining beneficial molecules. The protocell model suggests a pathway from chemistry to life. Initially, simple membranes formed spontaneously and encapsulated whatever molecules happened to be present. Most protocells contained random, non-functional molecules. Rarely, a protocell might encapsulate a self-replicating molecule like RNA. This molecule would replicate, eventually filling the protocell. When the protocell divided, both daughter cells would inherit copies of the replicating molecule. Natural selection would favor protocells containing molecules that enhanced growth, stability, or replication efficiency. Over time, increasingly sophisticated chemistry would evolve within protocells, eventually reaching the complexity of true living cells. LUCA and the genetic code. All modern life, from bacteria to humans, shares fundamental biochemical features, including the genetic code, ribosomes, and basic metabolic pathways. This universality indicates that all living organisms descend from a common ancestor called the last universal common ancestor, or LUCA. LUCA was not the first living thing, but rather the ancestor of all surviving lineages. Earlier life forms probably existed but left no descendants. LUCA possessed a sophisticated genetic system. It had DNA or RNA as genetic material, ribosomes for translating genetic information into proteins, and the universal genetic code. Modified bases in transfer RNA, required for proper codon-anticodon pairing during translation, were present. LUCA possessed a lipid membrane, probably a bilayer similar to modern cells. It had basic metabolic capabilities, including energy generation and biosynthesis of essential molecules. Estimates of LUCA's age range from 3.5 to 4.3 billion years ago. LUCA lived relatively soon after Earth's formation 4.6 billion years ago, and after the late heavy bombardment that ended approximately 3.8 billion years ago. This suggests that once conditions became permissive, life originated and diversified relatively quickly. LUCA itself was already quite complex, implying substantial evolution had occurred between the first living entity and LUCA. Inferring which genes were present in LUCA requires finding genes present in all modern organisms, or at least in representatives of bacteria and archaea, the two main domains of cellular life. Conservative estimates identify only 30 genes universally present, but these probably underestimate LUCA's complexity because many ancient genes have been lost in some lineages. More liberal estimates suggest LUCA possessed approximately 355 genes, giving it metabolic capabilities comparable to some modern bacteria. LUCA was not a simple primordial cell, but rather a relatively sophisticated organism, product of perhaps hundreds of millions of years of evolution before it. The gap between LUCA and the truly first life remains filled with uncertainty. LUCA descended from earlier cells that were presumably simpler, though how much simpler remains unknown. Some researchers propose a pre-LUCA ancestor called FUCA, the first universal common ancestor, which would have lived even earlier and spawned multiple cellular lineages, only one of which led to LUCA and all modern life. If FUCA existed, its other descendant lineages are now extinct, though some of their genes may have been transferred horizontally into LUCA's descendants and persist cryptically in modern genomes. Chapter 32: The Distant Future. Earth's story extends far beyond the present into a future measured in hundreds of millions and even billions of years. The processes that have shaped Earth throughout its 4.6 billion-year history will continue operating. Continents will drift, climates will shift, life will evolve, and eventually the sun itself will change in ways that doom Earth as an abode for life. Predictions about Earth's far future are possible because the laws of physics and geology operating today will continue operating tomorrow. Continental drift proceeds at measurable rates that allow projection of future plate movements. Solar physics provides a well-understood model of how stars like the sun evolve over billions of years. These projections paint a picture of Earth's distant future that is both fascinating and sobering. Understanding this future provides perspective on humanity's place in the vast sweep of cosmic time and raises profound questions about the far future fate of life and intelligence. Pangea Ultima. Continental drift continues today at rates of a few centimeters per year, the same speed that fingernails grow. The Atlantic Ocean widens as North America and South America drift westward away from Europe and Africa. The Pacific Ocean shrinks as the Ring of Fire, a ring of subduction zones encircling the Pacific, consumes oceanic crust. These motions will eventually cause the continents to collide and assemble into a new supercontinent. Multiple scenarios exist for how the next supercontinent might form. The Pangea Ultima scenario predicts that the Atlantic will stop opening and begin closing approximately 50 million years from now. Over the following 200 million years, the Atlantic will close as the Americas drift back eastward, colliding with Africa and Europe. By approximately 250 million years from now, a new supercontinent will form at the equator, with the continents assembled into a configuration roughly resembling Pangea, but with details reversed. Alternative scenarios include Nova Pangea, where the Americas drift westward to collide with Asia across the closing Pacific, and Amasia, where the continents drift northward to merge around the North Pole. Computer models suggest Amasia formation within 50 to 200 million years as Eurasia collides with the Americas. Which scenario actually unfolds depends on complex interactions in Earth's mantle that remain incompletely understood. However, all scenarios agree that continents will eventually reunite into a supercontinent, repeating the cycle that has occurred multiple times throughout Earth's history. Pangea Ultima's climate will likely be extremely hostile to life, particularly mammalian life. Computer models predict that much of the supercontinent will experience temperatures exceeding 40 degrees Celsius, with vast interior regions becoming uninhabitable deserts. The concentration of land near the equator in the Pangea Ultima scenario creates the worst possible configuration for life. Continental interiors, thousands of kilometers from any ocean, will be hot, dry, and essentially lifeless. Multiple factors will make Pangea Ultima hostile. Volcanic activity driven by continental collision will release enormous quantities of carbon dioxide, creating a powerful greenhouse effect. The sun will be approximately 2.5% more luminous than today because gradual changes in solar fusion rates increase the sun's energy output over hundreds of millions of years. This additional solar radiation will further heat the planet. The configuration of land at the equator means tropical heat will extend across most of the supercontinent. Regions near coastlines may remain habitable, but interior areas covering 3/4 of the landmass will be too hot for most mammals. Some life will likely persist even in this hostile world. Specialized heat-tolerant organisms, analogous to modern desert extremophiles, may survive. Whether mammals specifically survive is uncertain. Some researchers suggest that mammalian lineages might evolve heat tolerance, allowing survival in the hot conditions, perhaps through nocturnal habits, smaller body sizes that dissipate heat more efficiently, or physiological adaptations. Others are more pessimistic, suggesting that mammals may face extinction or near extinction during Pangea Ultima. If the supercontinent forms near the North Pole instead of the equator, conditions would be cooler and more habitable. Solar evolution. The Sun formed approximately 4.6 billion years ago from the gravitational collapse of a molecular cloud. For the past 4.6 billion years, it has been fusing hydrogen into helium in its core, releasing the energy that powers Earth's climate and biosphere. This process will continue for another approximately 5 billion years before the hydrogen fuel is exhausted. As the Sun ages, it gradually brightens. The fusion of hydrogen into helium produces helium that accumulates in the core. Helium is denser than hydrogen, so the core gradually contracts under its own weight. This contraction increases core temperature and pressure, which accelerates the fusion rate. The increased fusion produces more energy, making the Sun brighter. Over the past 4 billion years, solar luminosity has increased by approximately 30%. This trend will continue, with the Sun becoming approximately 10% brighter over the next billion years and 25% brighter within 3 billion years. The gradual brightening will eventually make Earth too hot for liquid water to exist on the surface. Estimates suggest that within approximately 1 billion years, the enhanced solar radiation will trigger a runaway greenhouse effect. Increased temperatures will cause oceans to evaporate more rapidly. Water vapor is a powerful greenhouse gas, so increased atmospheric water vapor will trap more heat, causing further warming and more evaporation. This positive feedback will continue until the oceans boil away completely. The loss of oceans will doom photosynthetic life. Plants and photosynthetic microorganisms require liquid water. Without water, photosynthesis will cease, eliminating the base of food chains. Atmospheric oxygen, continuously replenished by photosynthesis, will be lost as it reacts with surface rocks. The atmosphere will transition to a hot, dense envelope of water vapor and carbon dioxide resembling Venus. Any life that survives will be restricted to extremophiles capable of tolerating these conditions, perhaps in caves or subsurface aquifers where temperatures remain marginally tolerable. The red giant phase. In approximately 5.4 billion years, the Sun will exhaust the hydrogen in its core. When this happens, fusion in the core will cease, and the core will begin collapsing under its own gravity. The collapse will heat the core, eventually becoming hot enough to ignite hydrogen fusion in a shell surrounding the inert helium core. This shell burning will cause the Sun's outer layers to expand dramatically. The Sun will enter its red giant phase, expanding to approximately 250 times its current radius. The expanded Sun will become a red giant with its surface extending beyond the current orbit of Venus and possibly beyond Earth's orbit. Even if Earth's orbital distance increases due to the Sun losing mass and thereby weakening its gravitational pull, Earth will likely be engulfed by the Sun's expanding atmosphere. If Earth somehow avoids being engulfed, it will be heated to temperatures exceeding 1,000 degrees Celsius. The surface will melt, forming a global magma ocean. Any remaining water or organic material will vaporize. The atmosphere will be stripped away by the intense solar wind. Earth will become a bare, molten rock orbiting near the surface of a dying star. No life of any kind could survive these conditions. After approximately 1 billion years as a red giant, the Sun will eject its outer layers, creating a planetary nebula. The core will collapse into a white dwarf, an Earth-sized remnant composed of degenerate matter. The white dwarf will gradually cool over trillions of years, eventually becoming a cold, dark black dwarf. Earth, if it still exists, will orbit as a frozen, dead world around a stellar remnant, illuminated only by the faint light of distant stars. Life's future evolution. Assuming life survives the environmental challenges of the next billion years, how will it evolve? Predicting evolutionary trajectories is notoriously difficult because evolution is not deterministic. Random mutations, environmental contingencies, and historical accidents all shape evolutionary outcomes. However, some general trends can be anticipated. If Earth remains habitable, life will continue adapting to changing conditions. As temperatures increase over the next billion years, thermophilic organisms adapted to hot environments will gain advantages. Heat-tolerant plants able to photosynthesize at higher temperatures may evolve. Animals may become smaller to facilitate heat dissipation, shift to nocturnal habits to avoid daytime heat, or evolve more efficient cooling mechanisms. Desert ecosystems will expand as conditions become hotter and drier, selecting for organisms adapted to aridity. Human influence adds unprecedented unpredictability. Humans are causing rapid environmental changes, including climate warming, habitat destruction, and species extinctions at rates unprecedented in the geological record, except during mass extinctions. If these trends continue, Earth may enter a sixth mass extinction comparable to the Big Five extinctions of the past. Alternatively, humans might use technology to mitigate environmental damage, preserve biodiversity, and even enhance evolutionary processes through synthetic biology. Synthetic biology, the engineering of organisms with designed functions, offers tools to address climate change and biodiversity loss. Engineered organisms could capture carbon dioxide more efficiently than natural plants. Synthetic microorganisms could produce biofuels or biomaterials sustainably. Engineered crops could tolerate heat, drought, or poor soils, maintaining agricultural productivity under deteriorating conditions. Conservation efforts could use genetic engineering to rescue endangered species or even resurrect extinct species from preserved DNA. These technologies could shape life's future evolution in ways impossible through natural selection alone. Beyond Earth. If life on Earth is ultimately doomed by solar evolution, could life escape this fate by spreading beyond Earth? Humans have already sent spacecraft beyond the solar system and have established a continuous presence in space aboard the International Space Station. While human spaceflight currently extends only to low Earth orbit, the technological capabilities exist to venture farther. Colonization of other planets or moons in the solar system could provide refuges for life during Earth's final billion years. Mars, despite being cold and lacking a thick atmosphere, could be terraformed through geoengineering to become marginally habitable. The moons of Jupiter and Saturn, particularly Europa and Enceladus, have subsurface oceans that could potentially host life. Even if these environments cannot be made fully Earth-like, humans and other organisms could survive in habitats providing controlled environments. Interstellar colonization remains far beyond current capabilities, but is not physically impossible. Generation ships that travel for centuries or millennia could carry human populations and frozen embryos of thousands of species to potentially habitable exoplanets around other stars. As of 2025, astronomers have identified thousands of exoplanets, including dozens in habitable zones where liquid water could exist. While none appear identical to Earth, some may be close enough to support life with technological assistance. Whether humanity or its descendants will undertake such journeys remains speculative. Interstellar travel requires technologies far beyond anything currently achievable and resource commitments spanning generations or centuries. However, if life from Earth does spread beyond this planet, it could potentially persist for trillions of years, far longer than Earth itself will remain habitable. Life that began in Earth's ancient oceans billions of years ago might ultimately spread throughout the galaxy, ensuring that the story begun on one small world continues across cosmic time and space. Whether this occurs depends on choices humanity makes during the critical centuries ahead, when we possess both the power to destroy our world and the potential to ensure life's perpetuation far into the future. Chapter 33. Life at the Exteriors. Life on Earth has colonized virtually every conceivable environment, including conditions that would seem utterly inhospitable to most organisms. From boiling hot springs, where temperatures exceed the boiling point of water, to frozen Antarctic lakes, where temperatures remain below zero for most of the year. From acidic mine drainage, with pH comparable to battery acid, to hypersaline lakes saltier than seawater. Organisms called extremophiles thrive in conditions that would instantly kill most life forms. These remarkable organisms are not evolutionary oddities, but rather represent a substantial fraction of Earth's biodiversity, particularly among microorganisms. Many extremophiles belong to the domain Archaea, ancient prokaryotes that diverged from bacteria billions of years ago and have retained biochemical adaptations, allowing survival in extreme environments. However, extremophiles also include bacteria and even some eukaryotes. Understanding how life survives at the extremes provides insights into the fundamental requirements for life, the limits of biological adaptation, and the possibility that life might exist in extreme environments on other worlds. These organisms demonstrate that the habitable zone for life is far broader than once imagined. Thermophiles and hyperthermophiles. Thermophiles are organisms adapted to high temperatures, typically defined as thriving above 45 degrees Celsius. Hyperthermophiles take this to extremes, growing optimally at temperatures exceeding 80 degrees Celsius and surviving temperatures that would cook most organisms. These heat-loving microbes inhabit environments like volcanic hot springs, geothermal vents, and deep-sea hydrothermal systems where temperatures can reach 464 degrees Celsius, though no organism has been found actively metabolizing above 122 degrees Celsius. Pyrolobus fumare holds the record for the highest known growth temperature, multiplying at 113 degrees Celsius. This hyperthermophilic archaeon lives near deep-sea hydrothermal vents, extracting energy from chemical reactions involving hydrogen and nitrate. It can survive autoclaving at 121 degrees Celsius for 1 hour, conditions specifically designed to kill all known organisms in sterilization procedures. The ability to not merely survive, but actively grow at such temperatures requires extensive biochemical adaptations. Thermophile proteins are stabilized through increased ionic interactions, hydrogen bonding, and hydrophobic packing. The amino acid sequences are subtly different from their mesophilic counterparts, with changes that increase the melting temperature of the folded protein structure. Cell membranes in thermophiles contain specialized lipids with chemical modifications that prevent them from becoming too fluid at high temperatures. DNA is protected by specialized proteins and by modifications to the DNA itself, including unusual nucleotides that stabilize the double helix. The enzymes from thermophiles, called thermozymes or extremozymes, have revolutionary applications in biotechnology. The most famous example is Taq polymerase from Thermus aquaticus, a bacterium discovered in Yellowstone hot springs. This heat-stable enzyme is essential for polymerase chain reaction, or PCR, a technique that amplifies DNA and has become fundamental to molecular biology, forensics, and medical diagnostics. The enzyme must survive repeated heating cycles to 95 degrees Celsius without denaturing, something impossible for enzymes from organisms adapted to moderate temperatures. Psychrophiles and cryophiles. At the opposite temperature extreme, psychrophiles or cryophiles thrive in permanently cold environments below 15 degrees Celsius. These cold-loving organisms inhabit polar regions, glaciers, deep ocean waters, and permafrost. Some remain metabolically active at temperatures as low as -20 degrees Celsius, growing slowly but steadily in conditions where most biochemistry ceases to function. Antarctic krill exemplify macroscopic psychrophiles, remaining active in southern ocean waters that hover near -1.9 degrees Celsius year-round. These crustaceans possess antifreeze proteins in their blood that prevent ice crystal formation, which would otherwise rupture cell membranes. The antifreeze molecules bind to nascent ice crystals, inhibiting their growth and maintaining liquid water in tissues despite sub-zero temperatures. Microbial psychrophiles employ similar antifreeze strategies along with other adaptations. Their enzymes remain flexible at low temperatures through decreased hydrogen bonding and increased surface area, allowing catalysis to proceed despite reduced molecular motion. Cell membranes contain unsaturated fatty acids that remain fluid rather than solidifying into gel-like states. Some psychrophiles produce special cold shock proteins that help other proteins fold correctly in the cold. Permafrost, permanently frozen ground extending kilometers deep in Arctic regions, hosts viable microorganisms that have remained frozen for hundreds of thousands or even millions of years. When permafrost samples are thawed under controlled laboratory conditions, bacteria revive and begin growing. These microorganisms were metabolically active when the permafrost originally formed, but entered a state of suspended animation when frozen. The discovery raises concerns about climate change, thawing permafrost and releasing ancient microbes, some of which might be pathogens to which modern organisms lack immunity. Acidophils and alkaliphils. Acidophils thrive in highly acidic environments with pH values of 2 or below, comparable to stomach acid or battery acid. These organisms inhabit acid mine drainage, volcanic hot springs, and acidic soils. Picrophilus torridus holds dual extremophile status as a thermoacidophile, growing optimally at 60 degrees Celsius and pH 0.7, among the most acidic conditions compatible with life. The primary challenge for acidophils is maintaining neutral internal pH despite the acidic external environment. Cell membranes are modified to be less permeable to protons, reducing acid influx. Active transport systems pump protons out of cells as quickly as they leak in, maintaining the pH gradient. Proteins exposed to the acidic environment are stabilized through increased positive charge that resists denaturation in acid. Remarkably, acidophile cytoplasm remains near neutral pH, meaning their internal biochemistry functions normally despite the extreme external conditions. Alkaliphils inhabit the opposite extreme, growing in highly basic environments with pH values of 8.5 to 11 or higher. Soda lakes, formed in arid regions where evaporation concentrates carbonate salts, reach pH values exceeding 10. These environments also tend to be hypersaline, so organisms living there must cope with both high pH and high salinity simultaneously. Alkaliphils face challenges similar to acidophils, but reversed. They must prevent hydroxide ions from entering cells and raising internal pH to lethal levels. Halophils. Halophils thrive in hypersaline environments with salt concentrations far exceeding normal seawater, while seawater contains approximately 3.5% salt. Halophilic environments can reach salt saturation at 30% or higher. The Dead Sea, Great Salt Lake, and salt evaporation ponds host diverse halophil communities that give the water characteristic red or pink coloration from carotenoid pigments. Osmotic stress is the primary challenge in hypersaline environments. Water naturally flows from regions of low solute concentration to high solute concentration by osmosis. In hypersaline environments, water tends to flow out of cells, causing dehydration and death. Halophils counter this through compatible solutes, organic molecules accumulated at high internal concentrations to balance external osmotic pressure. Common compatible solutes include glycerol, betaine, and specialized amino acids. Some extreme halophils, particularly in the archaeal genus Halobacterium, use an alternative strategy called the saltin approach. Rather than excluding salt and accumulating organic molecules, they allow potassium and chloride ions to enter cells at high concentrations, matching external osmotic pressure. This requires that all cellular proteins be adapted to function in high salt, a more extensive evolutionary commitment than the compatible solute approach, but one that avoids the metabolic cost of synthesizing organic solutes. Tardigrades and cryptobiosis. Tardigrades, also known as water bears, are microscopic animals approximately half a millimeter long that exhibit extraordinary survival capabilities across multiple extreme conditions simultaneously. These eight-legged creatures with tubular bodies can survive temperatures from near absolute zero to 150 degrees Celsius, radiation doses hundreds of times higher than would kill humans pressures exceeding those in the deepest ocean trenches and the vacuum of space. The secret to tardigrade extremophile abilities is cryptobiosis, a state of suspended animation where metabolism slows to 0.01% of normal levels. When faced with desiccation, the most common trigger for cryptobiosis, tardigrades expel 95% of their body water and contract into a structure called a ton. In this state, they can remain viable for decades or potentially centuries, reviving within hours when water becomes available. During cryptobiosis, tardigrades produce trehalose, a sugar that forms a gel-like substance protecting cellular structures. This bioprotective glass stabilizes proteins and membranes, preventing damage from dehydration. Tardigrades also produce large quantities of antioxidants that protect against oxidative damage when metabolism resumes. Remarkably, they synthesize a unique protein that protects DNA from radiation damage, shielding the genome during space exposure or other radiation-intensive environments. The deep biosphere. The deep biosphere, the vast network of microbial life inhabiting the subsurface below the first few meters of soil and seafloor, represents one of Earth's largest ecosystems. This subsurface realm extends 10 kilometers below continents and 21 kilometers below the seafloor, encompassing temperatures up to 120 degrees Celsius and pressures hundreds of times atmospheric pressure. The deep biosphere accounts for approximately 90% of bacterial and archaeal biomass on Earth and 15% of total biosphere biomass. Life in the deep biosphere faces extraordinary challenges. Nutrients are scarce, requiring organisms to subsist on minimal energy inputs. Reproduction rates are extremely slow, with generation times measured in decades or centuries rather than hours or days. Some deep biosphere microbes may be surviving in a maintenance mode, expending just enough energy to repair cellular damage without growing or dividing. Despite these challenges, the deep subsurface hosts remarkable genetic diversity, rivaling surface ecosystems. The deep terrestrial biosphere contains a core microbiome, a set of microbial taxa found consistently across geographically distant groundwater systems worldwide. This suggests that subsurface life is not simply random contamination from the surface, but rather represents adapted communities that colonized the subsurface billions of years ago and have persisted there since. The presence of a global core microbiome implies that subsurface habitats select for specific metabolic capabilities suited to the extreme oligotrophic conditions. Energy sources in the deep biosphere include hydrogen from water rock reactions, methane, reduced sulfur compounds, and organic matter buried in sediments. Some deep biosphere organisms are chemolithotrophs, deriving energy from inorganic chemical reactions without requiring organic carbon or sunlight. These organisms fill niches fundamentally different from surface ecosystems, representing a biosphere within a biosphere that operates on entirely different energy economics. The discovery of the deep biosphere has profound implications for understanding life's distribution on Earth and the possibility of life elsewhere. If life can thrive kilometers beneath Earth's surface, then similar subsurface biospheres might exist on Mars, Europa, Enceladus, or other worlds with subsurface liquid water. The deep biosphere also provides insights into early life on Earth, as subsurface conditions may resemble those where life originated. The extremophiles inhabiting Earth's deep interior demonstrate that habitable environments exist far beyond the familiar surface ecosystems, expanding the potential habitats for life throughout the universe. Chapter 34, PATTRNS in Evolution. Evolution is not a random process, but rather operates according to patterns that emerge repeatedly across different lineages, environments, and timescales. These patterns reveal fundamental principles governing how organisms change over time, how diversity originates, and how life responds to environmental challenges. Convergent evolution produces strikingly similar adaptations in unrelated lineages facing similar selective pressures. Coevolution creates intricate relationships between species that shape each other's evolution over millions of years. Adaptive radiation generates bursts of diversification when organisms colonize new environments or when mass extinctions create ecological opportunities. Meanwhile, developmental constraints limit evolution's creativity, channeling change along pathways determined by the architecture of development. Understanding these patterns allows prediction of evolutionary trajectories and reveals that evolution, while not deterministic, is also not completely unpredictable. The same solutions appear repeatedly because certain designs simply work better than others for particular problems. Convergent evolution. Convergent evolution occurs when unrelated lineages independently evolve similar features in response to similar environmental challenges or opportunities. The classic example involves the streamlined bodies of sharks, dolphins, and ichthyosaurs. Sharks are fish, dolphins are mammals, and ichthyosaurs were reptiles, yet all three possess nearly identical body plans featuring fusiform shapes, dorsal fins, and tail flukes. The convergence occurred because all three groups faced the same physical challenge, moving efficiently through water to catch prey. Water is approximately 800 times denser than air, creating enormous drag resistance. The fusiform body shape minimizes drag by reducing turbulence. The streamlined form allows faster swimming with less energy expenditure, providing advantages in capturing prey and escaping predators. Since the three lineages faced identical challenges and physics operates the same way for all organisms, natural selection drove them toward the same solution. The similarities extend beyond gross morphology to detailed features. Dolphins and ichthyosaurs both possessed smooth, nearly hairless skin rather than scales or mammalian fur, reducing drag. Both had blubber layers for insulation and buoyancy. Both gave birth to live young rather than laying eggs, avoiding the need to return to land. Even coloration patterns converged, with countershading, dark backs, and light undersides, providing camouflage against both prey below and predators above. Convergent evolution appears across all domains of life and at all scales from molecular to morphological. Eyes have evolved independently at least 40 times in different lineages, ranging from simple eye spots detecting light direction to sophisticated camera eyes with lenses and retinas. Flight evolved independently in insects, pterosaurs, birds, and bats, each developing wings from different body structures but arriving at similar aerodynamic solutions. Burrowing lifestyles produced mole-like body forms independently in placental moles, golden moles from Africa, and marsupial moles from Australia, despite these groups being only distantly related. Coevolution. Coevolution describes reciprocal evolutionary changes between interacting species where each exerts selective pressure on the other. The most studied examples involve plants and their pollinators, relationships that have shaped both groups over more than 100 million years. Flowering plants provide nectar and pollen rewards to pollinators, while pollinators provide pollination services, transferring pollen between plants and enabling sexual reproduction. The evolution of long nectar spurs in flowers often corresponds to evolution of long tongues or beaks in pollinators. Charles Darwin famously predicted the existence of a long-tongued moth to pollinate the Madagascar star orchid Angraecum sesquipedale, which has nectar spurs exceeding 25 centimeters. 40 years after Darwin's prediction, the predicted sphinx moth was discovered with a tongue exactly long enough to reach the orchid's nectar. This mutualism benefits both partners. The orchid ensures pollination by a specialized visitor unlikely to waste pollen on other plant species, while the moth gains access to a nectar resource unavailable to competitors with shorter tongues. Coevolution can be diffuse, involving multiple species simultaneously or pairwise between two species. Flowering plants and their pollinator communities exhibit diffuse coevolution, with plants influenced by multiple pollinator species and pollinators visiting multiple plant species. The web of interactions creates complex selection pressures where changes in one species ramify through the entire community. These coevolutionary networks can stabilize or destabilize depending on the strength and specificity of interactions. Antagonistic coevolution between predators and prey or parasites and hosts produces evolutionary arms races. As prey evolve better defenses, predators evolve ways to overcome those defenses, which selects for even better defenses in prey, continuing indefinitely. This Red Queen dynamic, named after the character in Through the Looking Glass, who must run constantly just to stay in place, can drive rapid evolution. Host-parasite coevolution is particularly intense because parasites typically have shorter generation times and can evolve faster than hosts, requiring hosts to continuously evolve resistance to avoid extinction. Adaptive radiation. Adaptive radiation describes the rapid diversification of a lineage into multiple ecological roles. Classic examples include Darwin's finches on the Galapagos Islands, which radiated from a single ancestor into multiple species with different beak sizes and shapes adapted to different food sources, and the Hawaiian honeycreepers, which underwent similar radiation on Hawaiian islands. Adaptive radiations typically occur when organisms colonize new environments with many available ecological niches, or when mass extinctions eliminate competitors. Ecological opportunity is the primary driver of adaptive radiation. On isolated islands like the Galapagos or Hawaii, arriving colonists find environments with few existing species and many available resources. Without competition, the colonists can diversify rapidly into different niches. Each population, adapting to a different niche, experiences different selective pressures, driving divergence. Over time, the descendants become so different that they constitute distinct species, all descended from the single colonizing population. Mass extinctions create global-scale ecological opportunities by removing dominant species and opening niches. After the Permian-Triassic extinction eliminated approximately 90% of species, surviving lineages, including archosaurs, radiated extensively during the Triassic. After the Cretaceous-Paleogene extinction removed non-avian dinosaurs, mammals radiated from small insectivorous forms into the spectacular diversity seen today. The extinctions removed competitors and allowed new groups to exploit resources previously monopolized by the extinct forms. Adaptive radiations demonstrate evolutionary innovation. The diversifying lineage must possess traits allowing rapid adaptation to new niches. These might include generalist diets allowing colonization of multiple food sources, behavioral flexibility enabling exploration of new habitats, or morphological plasticity allowing body form modifications. Lineages lacking such evolvability cannot undergo adaptive radiation even when opportunities exist. The interplay between ecological opportunity and evolutionary capability determines which lineages. Key innovations. Key innovations or evolutionary novelties are traits that open access to new ecological opportunities and often trigger adaptive radiations. The evolution of flight in insects approximately 400 million years ago is a key innovation that allowed exploitation of aerial niches unavailable to ground-dwelling arthropods. Flight enabled insects to escape predators, disperse to new habitats, and access food resources in tree canopies. The innovation contributed to insects becoming the most diverse animal group on Earth. Photosynthesis ranks among the most important biological innovations in Earth's history. Oxygenic photosynthesis, which produces oxygen as a byproduct, appeared approximately 2.4 to 3 billion years ago in cyanobacteria. This innovation had planet-wide consequences, oxygenating the atmosphere and enabling the evolution of aerobic respiration, a far more efficient energy-generating process than anaerobic alternatives. The evolution of eukaryotic photosynthesis through endosymbiosis, where a cyanobacterium became enslaved as a chloroplast, enabled the diversification of algae and plants. Multicellularity evolved independently multiple times in different lineages. This key innovation allowed organisms to grow larger, differentiate specialized cell types, and occupy new ecological niches impossible for unicellular organisms. Multicellular organisms can create complex structures like roots, leaves, and limbs that single cells cannot achieve. The evolution of multicellularity in plants enabled colonization of land, while multicellularity in animals allowed the evolution of mobile predators and diverse body plans. Endosymbiosis, the incorporation of one organism inside another, represents perhaps the most consequential evolutionary innovation. The origin of mitochondria through endosymbiosis of an alpha protobacterium into an archaeal host created the eukaryotic cell. Mitochondria provide far more energy than prokaryotic metabolism, enabling eukaryotes to support the energetic costs of large genomes, complex cellular structures, and multicellularity. Similarly, the endosymbiotic origin of chloroplasts enabled eukaryotic photosynthesis and the subsequent greening of Earth. Sexual reproduction. Sexual reproduction, involving the mixing of genomes from two parents, is nearly universal in eukaryotes. The ubiquity suggests the last eukaryotic common ancestor was already sexual, meaning sex evolved very early in eukaryote history. Sexual reproduction is costly compared to asexual reproduction. It requires finding mates, produces offspring that are only 50% related to each parent, and breaks up successful gene combinations. Yet despite these costs, sex persists because it provides overwhelming advantages through increased genetic diversity. Meiosis, the specialized cell division that produces gametes with half the normal chromosome number, is central to sexual reproduction. During meiosis, homologous chromosomes pair and undergo recombination or crossing over, where DNA segments are exchanged between maternal and paternal chromosomes. This shuffles genes into new combinations. Additionally, independent assortment randomly distributes chromosomes to gametes, ensuring each gamete receives a unique combination of chromosomes. When two gametes fuse during fertilization, the resulting offspring possesses a genome unlike either parent or any siblings. The genetic diversity generated by sex provides raw material for natural selection. In asexually reproducing populations, all offspring are clones of their parent, possessing identical genomes except for rare mutations. Beneficial mutations arising in different individuals cannot be combined, limiting adaptation. In sexual populations, recombination brings together beneficial mutations from different parents, accelerating adaptation. Sex also helps purge deleterious mutations by allowing selection to act on different gene combinations. The Red Queen hypothesis proposes that sex evolved primarily to combat rapidly evolving parasites and pathogens. Parasites adapt to exploit common host genotypes. In asexual populations, where all individuals are genetically identical, parasites can evolve to efficiently infect the entire population. In sexual populations, the genetic diversity means each individual presents a different target, preventing parasites from adapting to a single host genotype. Hosts must continually evolve through sex to stay ahead of parasites, explaining the persistence of sex despite its costs. Developmental constraints. Despite evolution's creativity, developmental constraints limit possible evolutionary pathways and explain why certain body plans never evolve despite apparent advantages. The phylotypic stage, a conserved phase during embryonic development when different members of the same phylum look most similar, demonstrates these constraints. During the phylotypic stage, the basic body plan is laid out. The number and organization of body segments, the positioning of organs, and the fundamental architecture that will characterize the adult. Changes during the phylotypic stage are strongly selected against because this developmental period has high interactivity between tissues and low modularity. Multiple developing organs induce each other's formation through complex signaling cascades. Altering one structure disrupts development of other structures, typically producing inviable embryos. Experiments show that embryos are most vulnerable to developmental perturbations during the phylotypic stage, with disruptions causing more abnormalities and lethality than at earlier or later stages. The conservation of phylotypic stages explains why animal body plans are so conservative. All vertebrates share the same basic body plan established during the phylotypic stage: a segmented vertebral column, paired appendages, bilateral symmetry, and a head with concentrated sensory organs. Despite hundreds of millions of years of evolution, producing everything from fish to whales to birds to humans, the fundamental body plan remains unchanged. Evolution tinkers with details, modifying limb proportions or vertebral numbers, but cannot redesign the basic architecture without producing inviable monsters. Later developmental stages have increased modularity, allowing greater evolvability. Once the body plan is established, individual organs or structures can be modified independently without disrupting others. Limbs can elongate or shorten. Necks can contain different numbers of vertebrae. Teeth can change shape. These later modifications produce the spectacular diversity of form within body plans, but the body plans themselves remain locked in by developmental constraints acting during the phylotypic stage. Evolution is creative within limits, but those limits are set by the logic of development inherited from billions of years of history. Chapter 35: The Search for Other Worlds. The discovery that Earth is not unique began 500 years ago when Copernicus proposed that Earth orbits the Sun rather than occupying the universe's center. Since then, successive discoveries have continued displacing Earth from any special position. Our Sun is one of hundreds of billions of stars in the Milky Way galaxy, which itself is one of hundreds of billions of galaxies in the observable universe. The logical extension of this Copernican principle suggests that life on Earth should not be unique either, that countless other worlds harbor biology ranging from simple microbes to complex intelligent civilizations. Yet despite decades of searching, no definitive evidence for extraterrestrial life has been found, creating a profound tension between expectation and observation. This tension drives modern astrobiology, the scientific study of life in the universe. Astronomers have discovered thousands of planets orbiting other stars, some potentially habitable. Missions to Mars and the outer solar system are searching for signs of past or present life. Powerful telescopes are being designed to detect biosignatures in the atmospheres of distant exoplanets. The question is no longer whether life exists elsewhere, but rather where it exists and how we can detect it. The habitable zone. The habitable zone, or Goldilocks zone, defines the orbital distances around a star where conditions are neither too hot nor too cold for liquid water to exist on a planet's surface. Liquid water is considered essential for life as we know it, serving as a solvent for biochemical reactions and enabling molecular transport within cells. The habitable zone concept provides a first-order filter for identifying potentially life-bearing worlds among the thousands of discovered exoplanets. For stars like our Sun, the habitable zone extends from approximately 0.9 to 1.5 astronomical units, where 1 astronomical unit equals the Earth-Sun distance. Earth orbits at 1 astronomical unit, comfortably within the habitable zone. Venus at 0.7 astronomical units is too close and experiences runaway greenhouse heating, while Mars at 1.5 astronomical units is near the outer edge and may have been habitable when the young Sun was dimmer. The exact boundaries depend on atmospheric composition, cloud cover, and other factors that affect planetary heat balance. The habitable zone's location and width depend on the star's temperature and luminosity. Hot, luminous stars have wider habitable zones located farther from the star. Cool, dim red dwarf stars have narrower habitable zones hugging close to the star. Red dwarfs are particularly interesting for habitability searches because they are the most common star type, comprising approximately 70% of stars, and because their small size makes detecting planets easier. However, red dwarf habitability remains debated because planets in their habitable zones orbit so closely that they likely become tidally locked with one face, perpetually facing the star. The habitable zone concept has limitations. It assumes Earth-like planetary properties and ignores subsurface habitats that do not require sunlight. Europa and Enceladus, icy moons orbiting outside the conventional habitable zone, may harbor subsurface oceans heated by tidal friction rather than solar radiation. These worlds demonstrate that habitability extends beyond the simple habitable zone calculation. Nevertheless, the habitable zone remains useful as a starting point for prioritizing which exoplanets to study in detail. Exoplanet detection. The first confirmed detection of a planet orbiting a Sun-like star came in 1995 when astronomers discovered a Jupiter-sized planet orbiting the star 51 Pegasi. This discovery inaugurated the exoplanet era. Since then, over 5,000 exoplanets have been confirmed, with thousands more candidates awaiting verification. These discoveries demonstrate that planets are common, with most stars hosting at least one planet. The transit method detects exoplanets by measuring the slight dimming of a star when a planet passes in front of it from our perspective. The amount of dimming reveals the planet's size relative to the star. If multiple transits are observed, the orbital period can be determined, which combined with the star's mass yields the orbital distance. The transit method has been extraordinarily successful, with NASA's Kepler Space Telescope discovering most known exoplanets before its retirement. The method preferentially detects large planets orbiting close to their stars because these produce the largest signals. The radial velocity method detects exoplanets through the gravitational wobble they induce in their host star. As a planet orbits, the star also moves in a small orbit around the system's center of mass. This motion causes periodic Doppler shifts in the star's spectrum. The star appears slightly bluer when moving toward Earth and redder when moving away. Measuring these shifts reveals the planet's mass and orbital characteristics. The method works best for massive planets orbiting close to small stars because these produce the largest wobbles. Direct imaging captures actual photographs of exoplanets. This is extraordinarily challenging because planets are much fainter than their host stars and very close to them in angular separation. Specialized instruments block the star's light to reveal orbiting planets, analogous to blocking the sun with your thumb to see dimmer objects nearby. Direct imaging works best for large young planets that are still hot from formation and orbit far from their stars. As technology improves, direct imaging may eventually resolve surface features or detect biosignatures. Biosignatures. Biosignatures are observable features that indicate the presence of life. Detecting biosignatures on exoplanets represents astrobiology's ultimate goal, providing evidence that life exists beyond Earth. However, distinguishing true biosignatures from abiotic mimics requires understanding the planetary context and carefully evaluating alternative explanations. Atmospheric oxygen is the most discussed biosignature because oxygen is highly reactive and would disappear from Earth's atmosphere within millions of years without continuous biological replenishment. On Earth, oxygen accumulated approximately 2.4 billion years ago due to oxygenic photosynthesis by cyanobacteria and remains abundant because plants and photosynthetic microorganisms continuously produce it. Detecting oxygen in an exoplanet atmosphere would suggest biological production, though abiotic oxygen production through water photolysis is possible on planets without protecting ozone layers. Methane combined with oxygen creates a powerful biosignature because these gases react rapidly and their coexistence requires continuous production. On Earth, methane is produced biologically by methanogenic archaea and various other organisms, then oxidized to carbon dioxide within approximately a decade. The steady-state methane concentration reflects the balance between biological production and chemical destruction. Finding methane and oxygen together in an exoplanet atmosphere would indicate chemical disequilibrium consistent with life, though abiotic methane sources exist and must be ruled out. Phosphine and nitrous oxide are also proposed biosignatures. Phosphine, detected controversially in Venus's atmosphere, is produced by anaerobic bacteria on Earth and degrades rapidly in oxygen-rich atmospheres. Nitrous oxide is produced by soil bacteria during nitrification and denitrification. Both gases lack known abiotic sources at detectable abundances, making them strong biosignature candidates. However, our ignorance of exotic geochemistry on very different planets means that abiotic sources cannot be definitively excluded. The biosignature framework requires multiple lines of evidence. Detecting a single potential biosignature is insufficient. Astronomers must characterize the star, determine planetary properties, including mass and radius, model the climate and atmospheric chemistry, assess whether detected molecules are in chemical disequilibrium, and exclude false positives. Bayesian analysis combines these factors to calculate the probability that life exists, mapping to confidence levels from very unlikely below 10% to very likely above 90%. Only by integrating multiple observations and models can astronomers claim credible biosignature detection. Europa and Enceladus. Within our own solar system, the most promising candidates for hosting life are Europa, a moon of Jupiter, and Enceladus, a moon of Saturn. Both worlds possess subsurface oceans beneath thick ice crusts, potentially harboring life in dark environments heated by tidal energy rather than sunlight. These ocean worlds represent fundamentally different habitats than Earth's surface biosphere, expanding the range of environments where life might exist. Europa's subsurface ocean likely contains twice as much water as all of Earth's oceans combined. The ocean is kept liquid by tidal heating generated as Jupiter's gravity flexes Europa during its elliptical orbit. The ice crust may be only a few kilometers thick in some regions, making the ocean potentially accessible to robotic landers. Cracks in the ice hint at geological activity that could transport organic materials between the ocean and surface. Magnetic field measurements suggest the ocean is salty and electrically conductive, consistent with dissolved salts and possibly dissolved gases from hydrothermal vents. Enceladus dramatically announced its ocean's presence by spraying geysers of water vapor and ice particles into space from cracks near its south pole. The Cassini spacecraft flew through these plumes and detected water, salts, silica particles indicating hydrothermal activity, and simple organic molecules. The plume composition suggests Enceladus's ocean contacts a warm rocky core where water-rock reactions could provide chemical energy for life. The detection of molecular hydrogen in the plumes indicates ongoing hydrothermal processes that could support methanogenic life. NASA experiments testing organic molecule preservation under Europa and Enceladus surface conditions found that amino acids and other biomolecules could survive in ice just below the surface for millions of years despite intense radiation. Radiation from Jupiter and Saturn degrades organic molecules on the surface, but at depths of approximately 8 to 20 centimeters, molecules are protected. This finding means that landers do not need to drill kilometers through ice to detect biosignatures. Sampling just below the surface might reveal organic molecules transporting from the subsurface ocean. The rare earth hypothesis. The rare earth hypothesis, proposed by paleontologist Peter Ward and astronomer Donald Brownlee in 2000, argues that while simple microbial life may be common in the universe, complex multicellular life is extraordinarily rare. The hypothesis lists numerous requirements for complex life, suggesting that the simultaneous satisfaction of all requirements occurs on very few planets. If correct, Earth may be one of a tiny number of worlds hosting complex life in the observable universe. Key requirements include a favorable galactic location outside the dense galactic core where supernovae and radiation would sterilize planets, but inside the galactic habitable zone where heavy elements needed for rocky planets are abundant. The central star must be long-lived and stable, neither too massive that it burns out quickly nor so small that flares sterilize planets. The planet must orbit in the circumstellar habitable zone at the correct distance for liquid water. Gas giants like Jupiter should orbit at intermediate distances, deflecting comets and asteroids without destabilizing terrestrial planet orbits. The planet itself must satisfy numerous criteria. Sufficient mass is needed to retain an atmosphere yet allow plate tectonics. A large moon stabilizes axial tilt, preventing extreme climate variations. A molten core generates a protective magnetic field shielding the surface from radiation. Plate tectonics recycles carbon, regulates climate, and creates diverse environments. The right amount of water must exist. Too little, and the planet is desert. Too much, and it becomes a water world without exposed continents. Oxygen must appear at the right time after complex life evolves the ability to use it. The rare Earth hypothesis contrasts sharply with the principle of mediocrity, which holds that Earth is typical and life should be common. The debate cannot currently be resolved because we lack sufficient data on exoplanet properties and the prevalence of life. Future observations detecting biosignatures on multiple exoplanets would refute rare Earth, while continued failure to detect life would support it. The hypothesis provides one explanation for the Fermi paradox, the puzzle of why we have not detected intelligent extraterrestrial civilizations despite the vast number of stars and apparent likelihood of life emerging. The Fermi paradox and SETI. The Fermi paradox, named for physicist Enrico Fermi, who famously asked, "Where is everybody?" poses the question of why Earth has not been visited by aliens given the immense age and size of the universe. If even a tiny fraction of stars host civilizations, and if even a tiny fraction of those civilizations develop interstellar travel, the galaxy should have been colonized millions of years ago. Yet we see no evidence for extraterrestrial visitors or civilizations. This apparent contradiction between expectation and observation has numerous proposed resolutions. The Drake equation attempts to estimate the number of communicating civilizations in our galaxy. The equation multiplies several factors: the star formation rate, the fraction of stars with planets, the number of habitable planets per star system, the fraction where life arises, the fraction where intelligence evolves, the fraction developing detectable technology, and the average lifetime of technological civilizations. Most factors are poorly constrained, allowing estimates ranging from 0 to millions of civilizations depending on assumed values. SETI, the search for extraterrestrial intelligence, scans the skies for artificial signals. Radio telescopes listen for narrowband transmissions or unusual patterns that would indicate technological origin. Optical telescopes search for laser pulses. So far, searches have covered only a tiny fraction of the galaxy's volume and frequency space, sampling far less than 1% of potential signals. The famous WOW signal detected in 1977 remains unexplained but has never repeated. The absence of confirmed detections may simply reflect insufficient searching rather than absence of civilizations. Great Filter Hypothesis proposes that some barrier prevents civilizations from becoming interstellar. This filter could lie in our past, if abiogenesis or the evolution of intelligence is extraordinarily unlikely. Alternatively, the filter could lie in our future, if technological civilizations typically destroy themselves through nuclear war, environmental collapse, or artificial intelligence before achieving interstellar travel. If the filter lies ahead, this bodes poorly for humanity's future. The resolution of the Fermi paradox and the success or failure of SETI will profoundly affect how we view our place in the universe and our cosmic future. Chapter 36: Consciousness and Meaning. The evolution of life on Earth culminated in organisms capable of contemplating their own existence and the universe that produced them. Consciousness, the subjective experience of being, represents perhaps the most profound mystery in science. How does electrochemical activity in 3 pounds of neural tissue generate the rich inner world of sensations, emotions, and thoughts that define human experience? This is the hard problem of consciousness. Distinguishing subjective phenomenal experience from objective physical processes. While neuroscience has made remarkable progress understanding the neural correlates of consciousness, the mechanisms by which matter becomes aware of itself remain deeply puzzling. Consciousness likely evolved gradually through increasingly complex nervous systems, from simple awareness in invertebrates to sophisticated self-awareness in mammals and birds. The emergence of human consciousness approximately 300,000 years ago fundamentally changed life's trajectory on Earth. For the first time, organisms could understand the processes that created them, manipulate their environment through technology, and contemplate their place in the cosmic story. Understanding consciousness provides insight into what makes humans unique and raises profound questions about the nature of mind, meaning, and purpose in a universe governed by physical laws. Evolution of consciousness. Consciousness is not unique to humans, but rather evolved progressively through animal evolution. The earliest traces appear in invertebrates with simple nervous systems capable of basic awareness of their environment. Proto-consciousness in these organisms allows detection of stimuli and generation of appropriate responses, providing survival advantages through improved decision-making compared to purely reflexive behavior. The elaboration of consciousness proceeded through several stages correlated with increasing neural complexity. Early multicellular animals possessed nerve nets allowing coordination of body parts, but lacking centralized control. The evolution of ganglia, clusters of neurons serving as primitive brains, enabled more sophisticated information processing. Working memory appeared, allowing animals to retain information temporarily and make decisions based on recent experience. Long-term memory emerged, permitting learning from past events and modification of behavior accordingly. Invertebrates, particularly endothermic birds and mammals, consciousness acquired distinct functional features including sensory filtering, causal reasoning, and adaptive arbitration between competing drives. The development of complex neural architectures, including the cortex in mammals and pallium in birds, provided substrate for these enhanced cognitive capabilities. These animals can form mental representations of their environment, plan future actions, and understand cause and effect relationships. They possess working memory, allowing manipulation of mental content, and episodic memory, recording specific experiences. Natural selection favored consciousness because conscious experiences are causally potent, influencing behavior in ways that enhance survival. The ability to consciously weigh alternatives, anticipate consequences, and choose actions based on expected outcomes provides enormous advantages. Consciousness allows incorporating learning into behavior more effectively than non-conscious pathways, enabling better choices between alternative actions. The evolutionary origins of consciousness demonstrate that subjective experience, far from being epiphenomenal, plays functional roles in guiding behavior. Human consciousness and language. Human consciousness differs from other animal consciousness in degree, if not necessarily in kind. The human brain is 3 times larger than expected for a primate of our body size, providing the neural substrate for uniquely sophisticated cognition. The neocortex, particularly the frontal lobes responsible for executive function and planning, expanded disproportionately during human evolution. These anatomical changes enabled cognitive capabilities, including abstract reasoning, metacognition or thinking about thinking, and explicit self-awareness as separate entities persisting through time. Language represents the most transformative human innovation, perhaps more important for human evolution than any anatomical change. Symbolic language allows communication about abstract concepts, events not immediately present, and hypothetical scenarios. Language transforms thought by providing a system for encoding, manipulating, and transmitting information with unprecedented fidelity and complexity. The link between language and symbolic activity is so close that evolutionary pathways toward complex syntactic language can be inferred from archaeological records of symbolic artifacts. The evolution of symbolic communication from indexical or referential communication involved a qualitative transition. Indexical signals have sign-object relationships, where a signal refers directly to an object or state. An alarm call warning of predators is indexical. The signal refers to the predator. Symbolic signals have sign-sign relationships, where signals refer to other signals and meaning is negotiated through dialogue. Language is symbolic. Words mean what communities agree they mean, not what they inherently denote. This arbitrary relationship between signifier and signified allows infinite flexibility in what can be communicated. Language served as neuroenhancement in the acquisition and representation of symbolic concepts. Through language, humans construct cognitive niches, allowing manipulation of information in ways impossible without linguistic scaffolding. Abstract concepts like justice, mathematics, and hypothetical counterfactuals exist only through linguistic encoding. Language allows cultural transmission of knowledge across generations, with far higher fidelity than possible through observation alone. The cumulative cultural evolution enabled by language transformed humans from another primate species into world-reshaping agents. Cultural evolution and memetics. Humans are unique among Earth's species in accumulating complex culture that evolves according to principles resembling biological evolution, but operating orders of magnitude faster. Cultural evolution, also called memetic evolution, describes how ideas, technologies, beliefs, and practices spread through populations, replicate across generations, and change over time. Memes, the basic units of cultural transmission analogous to genes in biological evolution, include skills, knowledge, habits, songs, stories, and any information that can be transmitted from mind to mind. Memes spread through observation and social learning. An individual observes another person's behavior, internalizes the underlying skill or knowledge, and incorporates it into their own behavioral repertoire. This process requires several transmission mechanisms, including imitation, reinforcement learning, and linguistic instruction. Once these mechanisms exist even at rudimentary levels, memetic evolution accelerates, building progressively more sophisticated cultural software on foundations of previously transmitted memes. The cumulative nature of cultural evolution distinguishes humans from other species. Each generation inherits the cultural knowledge of previous generations through teaching and observation, builds upon that foundation, and transmits enhanced culture to the next generation. This creates exponential growth in cultural complexity over time, a process called the ratchet effect. While other animals show simple cultural transmission, only humans exhibit the cumulative ratchet that produces progressively more complex technology and knowledge systems. External information storage dramatically increased cultural evolution's efficiency. Writing, invented approximately 5,000 years ago, allowed information persistence beyond individual memories and enabled transmission across space and time without face-to-face contact. Printing presses multiplied the speed and scale of information transmission. Digital computers and the internet have accelerated cultural evolution to unprecedented speeds, allowing global transmission of information in seconds and providing nearly unlimited storage. The cultural information available to a modern human vastly exceeds what any individual could generate through direct experience, demonstrating culture's power. The hard problem. Despite remarkable progress in neuroscience, the hard problem of consciousness remains unsolved. The hard problem asks why and how physical processes in brains give rise to subjective phenomenal experiences or qualia. Why does seeing red feel like something rather than simply being information processing? Why is there something it is like to be conscious rather than neural activity proceeding without awareness? How does the subjective first-person perspective of consciousness arise from the objective third-person processes that neuroscience studies? The easy problems of consciousness, by contrast, concern functional questions that are scientifically tractable even if not yet fully solved. How do brains integrate information from different sensory modalities? How does attention select certain stimuli for processing while ignoring others? How do memories form and get retrieved? These problems are easy not because they are simple, but because they involve explaining capacities and functions that can be studied through standard scientific methods. Solving the easy problems does not automatically solve the hard problem. Several theoretical frameworks attempt to address the hard problem. Physicalist approaches argue that consciousness is entirely physical, emerging from neural processes through principles not yet understood. Once neuroscience sufficiently advances, consciousness will be explained without invoking non-physical entities. Dualist approaches propose that consciousness involves non-physical properties not reducible to physics and chemistry. Integrated information theory quantifies consciousness as integrated information, proposing that any system integrating information possesses some degree of consciousness. Global workspace theory suggests that consciousness arises when information is broadcast to multiple brain systems simultaneously. The hard problem intersects with profound philosophical questions about the nature of reality, the relationship between mind and matter, and the place of consciousness in a physical universe. Some philosophers argue the hard problem is genuine and may be scientifically unsolvable. Others suggest it arises from confused thinking and will dissolve once we properly understand neural processes. Regardless of whether the hard problem has a solution, consciousness remains the most direct and undeniable aspect of reality. The one thing we know with absolute certainty exists because we experience it directly. Meaning and purpose. The evolution of consciousness raises questions about meaning and purpose that earlier life forms could not ask. Humans, aware of their own existence and mortality, inevitably wonder why they exist and whether existence has purpose. These questions become particularly acute when viewing life through an evolutionary lens that explains the biological world through blind, purposeless mechanisms. From a scientific perspective, life has no predetermined cosmic purpose. Evolution operates through random mutation and natural selection, mechanisms that are indifferent to meaning or purpose. Organisms exist because their ancestors survived and reproduced, not because the universe intended their existence. The spectacular diversity of life, including human consciousness itself, arose through 4 billion years of contingent historical accidents and could easily have turned out differently. This scientific view seems to drain existence of inherent meaning. Yet humans create meaning despite, or perhaps because of the absence of cosmic purpose. Consciousness allows us to value experiences, form relationships, pursue goals, and find significance in art, knowledge, love, and countless other domains. These meanings are not objectively inscribed in the universe's structure, but are real nonetheless, grounded in the subjective experiences of conscious beings. The evolutionary origin of consciousness does not diminish the reality or importance of the meanings we create. The story of life on Earth is not merely a sequence of events, but a narrative arc from simple chemistry to conscious minds capable of understanding their origins. For nearly 4 billion years, Earth was inhabited by organisms that could not comprehend the processes that shaped them. Bacteria divided without knowing why. Trilobites scuttled across Cambrian seafloors unaware of evolution. Dinosaurs dominated without contemplating their place in the cosmos. Only with humans did the universe develop the capacity to understand itself. We are quite literally the universe made conscious, matter organized in such a way that it can reflect on its own existence. This realization transforms how we might view humanity's role. We are not separate from nature, but rather nature's way of knowing itself. The 4 billion-year journey from primordial chemistry to conscious observers was not predetermined, but having occurred, it gives us both privilege and responsibility. We alone can appreciate the cosmic story that produced us. We alone can work to preserve the web of life that evolved alongside us. Whether we fulfill this role or squander it through short-sighted destruction remains to be determined. The next chapters of Earth's story remain unwritten, and for the first time in history, one species holds the pen. What we write will determine not just human fate, but the fate of countless species that share our world and depend on our choices. The power is awesome. The responsibility is immense. The opportunity is unprecedented. 4 billion years of evolution have brought life to this moment. What happens next is up to us. Chapter 37: The Biodiversity Crisis. Earth's biodiversity represents 4 billion years of evolutionary experimentation, a vast library of genetic information encoding solutions to countless ecological challenges. Today, this biodiversity faces unprecedented threats as human activities reshape the planet at rates and scales never before experienced in the Phanerozoic. Habitat destruction eliminates the places where species live, while climate change shifts environmental conditions faster than many species can adapt. Pollution poisons ecosystems with chemicals and plastics that accumulate in food chains. Invasive species introduced by human transport overwhelm native organisms that evolved without defenses against these newcomers. The combined effects of these threats are driving extinction rates to levels suggesting we may be entering the sixth mass extinction in Earth's history. Unlike previous mass extinctions caused by volcanic eruptions or asteroid impacts, this crisis is entirely human-caused and therefore potentially human-solvable. Understanding the scope of biodiversity loss and the value of what we stand to lose provides motivation for action. The diversity of life is not merely an aesthetic treasure, but the foundation of ecosystem services that sustain human civilization and all life on Earth. Biodiversity hotspots. Biodiversity is not uniformly distributed across Earth's surface, but rather concentrated in specific regions called biodiversity hotspots. These areas contain exceptionally high numbers of species, particularly endemic species found nowhere else, while facing exceptional threats from human activities. Conservation International has identified 36 biodiversity hotspots, covering just 2.4% of Earth's land surface, yet harboring over half of all plant species and 43% of terrestrial vertebrate species as endemics. Tropical rainforests constitute the most species-rich terrestrial ecosystems on Earth. The Amazon rainforest alone contains approximately 10% of all species on the planet, with individual hectares sometimes hosting more tree species than exist in entire countries at higher latitudes. This extraordinary diversity results from multiple factors, including high net primary productivity, providing abundant energy, spatial heterogeneity, creating numerous microhabitats, and millions of years of evolutionary time, allowing diversity to accumulate. Warm temperatures and consistent rainfall year-round permit continuous growth and reproduction, enabling species to specialize on narrow niches that would be impossible in seasonal environments. Coral reefs, though covering less than 1% of the ocean floor, host over 25% of all marine species. These underwater rainforests are built by corals, colonial animals that secrete calcium carbonate skeletons forming three-dimensional structures. The complex physical structure provides countless hiding places, feeding areas, and breeding grounds for fish, invertebrates, and other organisms. The Coral Triangle in Southeast Asia represents the global epicenter of marine biodiversity, hosting over 600 species of reef-building corals, more than 75% of the world's total, and nearly 3,000 species of reef fish. The extraordinary diversity of coral reefs accumulated slowly over geological time. The Indo-Pacific coral reefs have built their unrivaled richness not through rapid speciation, but through stable conditions that allowed diversity to accumulate over millions of years without major extinction events. This deep-time perspective makes current threats to reefs particularly concerning. The diversity that took millions of years to assemble could be destroyed within decades if current trends continue. Once lost, recovery would require similar timescales, meaning that reef biodiversity lost today would not recover for millions of years, even if conditions improved. Ecosystem services. Biodiversity provides ecosystem services, benefits that humans and all organisms derive from functioning ecosystems. These services are often invisible and undervalued in economic systems, yet are essential for survival. Regulating services include pollination of crops, water purification by wetlands, carbon sequestration by forests, and pest control by predators. Provisioning services include food, fresh water, fuel, and medicinal compounds. Cultural services include recreational, aesthetic, and spiritual benefits. Pollination by insects, birds, and bats is essential for approximately 75% of crop species humans cultivate. Without pollinators, yields of fruits, vegetables, nuts, and oilseeds would collapse, threatening food security for billions of people. The global economic value of pollination services is estimated at hundreds of billions of dollars annually. Yet pollinator populations are declining worldwide due to habitat loss, pesticide use, disease, and climate change. The loss of pollination services would require either massive increases in hand pollination, economically infeasible for most crops, or abandonment of many food crops. Water purification by wetlands and forests prevents contamination and reduces water treatment costs. Wetlands filter pollutants, trap sediments, and break down harmful chemicals through biological processes. Forests regulate water flow, preventing both floods and droughts while maintaining stream temperatures suitable for aquatic organisms. The loss of these natural water treatment systems would require construction of expensive artificial treatment facilities and would still result in degraded water quality compared to naturally filtered water. Carbon sequestration by forests, wetlands, and oceans helps regulate climate by removing carbon dioxide from the atmosphere. Forests store carbon in wood and soil. Tropical rainforests alone store approximately 250 billion tons of carbon, equivalent to 25 years of current global carbon dioxide emissions. When forests are destroyed, this stored carbon is released, contributing to climate change. Protecting and restoring forests represents one of the most cost-effective climate mitigation strategies available. Habitat loss and fragmentation. Habitat destruction is the primary threat to biodiversity globally. When forests are cleared for agriculture, wetlands are drained for development, or grasslands are converted to crop fields, the species inhabiting those ecosystems lose their homes. Many species have specific habitat requirements and cannot survive in human-modified landscapes. The total amount of natural habitat has declined dramatically, with estimates suggesting humans have modified 75% of Earth's land surface through agriculture, urbanization, and other activities. Habitat fragmentation, the breaking apart of continuous habitat into smaller isolated patches, threatens species even when total habitat area is partially preserved. Analysis of global forest cover reveals that 70% of remaining forest is within 1 kilometer of the forest's edge, subject to degrading edge effects, including altered microclimates, increased wind exposure, and higher predation rates. Fragmentation reduces biodiversity by 13 to 75% across multiple biomes and taxa. Small habitat fragments support fewer species than large continuous areas due to fundamental ecological principles. Small populations are vulnerable to random demographic fluctuations that can drive them to extinction. Inbreeding in small, isolated populations reduces genetic diversity and fitness. Species requiring large territories, such as apex predators, cannot survive in small fragments. Immigration from other populations becomes impossible when fragments are isolated, preventing recolonization after local extinctions. Edge effects alter conditions within fragments, effectively reducing usable habitat area. In tropical forests, edge effects penetrate hundreds of meters into fragments, causing loss of large old trees that are replaced by pioneer species. Shifts in species composition change ecosystem functioning, reducing biomass and altering nutrient cycles. The combined effects of reduced area, increased isolation, and edge degradation create extinction debt, delayed extinctions that will occur over coming decades, even if no additional habitat is lost. Ocean acidification. Ocean acidification, sometimes called climate change's evil twin, results from oceans absorbing approximately 30% of carbon dioxide emitted by human activities. When carbon dioxide dissolves in seawater, it forms carbonic acid, lowering ocean pH. Since industrialization, ocean surface pH has declined from approximately 8.2 to 8.1, representing a 30% increase in acidity. Projections suggest pH could drop to 7.8 by 2100 under high-emission scenarios. Acidification threatens organisms that build calcium carbonate structures, including corals, mollusks, crustaceans, and some plankton. Lower pH reduces carbonate ion concentration, making it thermodynamically harder to form calcium carbonate skeletons and shells. Corals exposed to acidification show reduced calcification rates, slower growth, and increased susceptibility to disease. Under severe acidification, carbonate structures can begin dissolving, with net dissolution exceeding formation. The combination of ocean warming and acidification creates a double threat for coral reefs. Warming causes coral bleaching, the expulsion of symbiotic algae that provide corals with most of their nutrition. Bleached corals can recover if temperatures decrease quickly, but prolonged bleaching leads to death. Acidification weakens surviving corals, reducing their ability to rebuild skeletons damaged by storms or grazing. The combination means that even reefs protected from warming long enough to avoid bleaching will face increasing acidification stress. Experimental studies exposing corals to projected future conditions show concerning results. High carbon dioxide levels cause bleaching and productivity loss in both corals and coralline algae, another crucial reef-building group. Coralline algae appear most sensitive, with high carbon dioxide leading to negative productivity and net dissolution of their calcium carbonate structures. If coralline algae disappear, reef frameworks will lack the cement that binds coral colonies into stable structures, potentially causing physical collapse of reef ecosystems. Invasive species. Invasive species are non-native organisms introduced to new environments where they spread rapidly and cause harm to native ecosystems. Human transportation of species, whether intentional or accidental, has created opportunities for organisms to colonize regions they could never reach naturally. Some introduced species establish populations that explode without the predators, parasites, or competitors that controlled them in their native ranges. These biological invasions represent a major threat to biodiversity, particularly on islands and in isolated ecosystems. Invasive species harm native biodiversity through multiple mechanisms. Competition for resources disadvantages native species that did not evolve with the invader. Predation by invasive predators decimates native prey that lack appropriate defenses. Habitat alteration by invasive plants changes physical environments, making them unsuitable for native species. Disease transmission from invasive species to natives can cause devastating epidemics. Hybridization between invasive and native species can eliminate unique native genotypes through genetic swamping. The impacts are particularly severe on islands where species evolved in isolation with limited competition. The introduction of rats to Pacific islands caused extinctions of numerous endemic bird species that nested on the ground and had lost the ability to recognize mammalian predators. The brown tree snake accidentally introduced to Guam eliminated most native forest birds, causing ecosystem-wide changes as seed dispersal and insect control collapsed. Invasive plants like kudzu in the southeastern United States smother native vegetation, creating monocultures that support far less biodiversity than the diverse communities they replace. Invasive species indirectly cause native species declines through habitat alteration. Plant invasions alter carbon and nitrogen cycles and fire regimes in invaded ecosystems. Downy brome, an invasive grass in western North America, increases fire frequency in sagebrush ecosystems. The increased fires favor the grass while killing native shrubs, creating a feedback that converts diverse shrublands to grass-dominated areas. Such ecosystem transformations eliminate habitat for numerous native species adapted to the original ecosystem. Pollution. Pollution introduces harmful substances into ecosystems at concentrations that damage organisms. Pollution types include chemical pollutants from agriculture and industry, plastic debris accumulating in oceans and terrestrial environments, nutrient pollution causing eutrophication of aquatic systems, and light and noise pollution disrupting animal behavior. The combination of multiple pollutant types creates synergistic effects where the total impact exceeds the sum of individual pollutant effects. Nutrient pollution from agricultural runoff containing excess nitrogen and phosphorus causes eutrophication of lakes, rivers, and coastal waters. The nutrients stimulate explosive algal blooms that block sunlight and consume oxygen when they die and decompose. The resulting dead zones, areas with insufficient oxygen to support most animal life, cover increasing areas of coastal oceans. The Gulf of Mexico dead zone, fed by Mississippi River nutrients from Midwest agriculture, covers over 20,000 square kilometers during summer months. eliminating habitat for fish and bottom-dwelling organisms. Microplastic pollution represents an emerging threat whose full impacts remain incompletely understood. Plastic debris breaks down into particles smaller than 5 millimeters that contaminate water, soil, and organisms. Microplastics are ingested by organisms ranging from plankton to whales, accumulating in food chains. They can block digestive systems, release toxic chemicals, and provide surfaces for harmful bacteria. Recent research shows microplastics interact with nutrient pollution, absorbing nitrogen and phosphorus that is either taken up by algae or released into water, exacerbating eutrophication. Agricultural microplastics from pesticide containers, films, and fertilizers are washed into waterways by rainfall. These microplastics combine with nutrients from the same agricultural sources, creating combined pollution that is harder to address than either pollutant alone. The microplastics can also affect soil nitrogen storage and nitrogen emissions, interfering with fundamental ecosystem processes. Addressing these combined threats requires integrated approaches targeting multiple pollutant sources simultaneously rather than focusing on single pollutants in isolation. Chapter 38, PATHWAYS Forward. Despite the severity of biodiversity and climate crises, pathways exist to avoid the worst outcomes and potentially restore damaged ecosystems. Technology provides tools for reducing environmental impacts while maintaining human prosperity. Conservation strategies protect remaining natural areas and restore degraded ecosystems. Policy changes can redirect economic incentives towards sustainability. Cultural shifts in values and behaviors can reduce consumption and waste. No single solution is sufficient, but the combination of multiple approaches implemented globally could stabilize climate, halt biodiversity loss, and create a sustainable civilization. The window for action is narrowing. The decisions made in the next few decades will determine whether humanity becomes Earth's destroyer or its steward. Understanding what is possible provides hope and motivation for the work ahead. The tools exist. The knowledge exists. What remains uncertain is whether the collective will exist to use them before critical tipping points are crossed. Climate change mitigation. Climate change mitigation involves reducing greenhouse gas emissions to limit future warming. The Paris Agreement, signed by nearly 200 countries, aims to limit warming to well below 2 degrees Celsius and preferably to 1.5 degrees above pre-industrial levels. Achieving these targets requires rapid transformation of energy systems, transportation, industry, and agriculture. The European Union has committed to climate neutrality by 2050, requiring greenhouse gas emissions to be balanced by removal. Renewable energy technologies including solar, wind, hydroelectric, and geothermal power provide alternatives to fossil fuels. Solar and wind costs have declined dramatically over the past decade, making them cost-competitive with fossil fuels in many locations. Solar photovoltaic costs decreased by approximately 90% between 2010 and 2020, while wind costs dropped by approximately 70%. These cost reductions mean renewable energy deployment is accelerating. Renewable electricity generation must increase substantially to replace fossil fuels and provide power for electrified transportation and industry. Energy efficiency reduces the total energy needed to provide the same services, cutting emissions while saving money. Buildings can be retrofitted with insulation, efficient lighting, and smart heating systems. Industrial processes can be optimized to reduce energy waste. Transportation efficiency improves through lighter vehicles, better engines, and modal shifts to more efficient options like rail. Efficiency improvements in one sector can free up resources for investments in other sectors, creating positive feedback loops. Carbon capture and storage technologies remove carbon dioxide from power plants and industrial facilities before it enters the atmosphere, transporting it to underground geological formations for permanent storage. CCS provides a pragmatic solution for transitioning to low-carbon economies without immediately dismantling current energy infrastructure. The technology has demonstrated potential to reduce global carbon dioxide emissions by approximately 19% by 2050. However, CCS faces challenges including high costs, energy requirements for capture, and public acceptance of underground storage. CCS works best when integrated with renewable energy systems, providing backup power while renewables handle baseline demand. Climate change adaptation. Even with aggressive mitigation, some warming is unavoidable due to greenhouse gases already emitted, requiring adaptation strategies to cope with changing conditions. Adaptation includes building seawalls to protect coastal communities from rising seas, developing drought-resistant crops for regions where rainfall decreases, improving early warning systems for extreme weather events, and relocating communities from areas becoming uninhabitable. Adaptation is particularly crucial for vulnerable populations in developing countries that contributed minimally to emissions but face severe impacts. Natural climate solutions use ecosystem conservation and restoration to sequester carbon while providing adaptation benefits. Protecting forests prevents carbon release and maintains rainfall patterns. Restoring wetlands stores carbon while providing flood protection. Mangrove restoration protects coastlines from storms while creating fish nurseries. These nature-based approaches provide multiple benefits simultaneously, often at lower cost than engineered alternatives. Investing in natural infrastructure creates resilience while addressing climate. Conservation and restoration. Protected areas including national parks, wildlife reserves, and marine protected areas conserve biodiversity by restricting human activities that harm ecosystems. Currently, approximately 15% of land and 7% of oceans are protected, far below the targets of protecting 30% of land and ocean by 2030 proposed by conservation organizations. Expanding protected areas requires identifying priority regions with high biodiversity, securing funding for management, and working with local communities to ensure their needs are met. Rewilding represents an innovative conservation approach that restores ecosystems through species reintroductions and allowing natural processes to function without human intervention. Rewilding involves several steps: assessing ecosystem condition, restoring habitat by removing threats, reintroducing keystone species whose presence structures entire ecosystems, and monitoring outcomes to guide adaptive management. Keystone species, including large herbivores and predators, restore natural processes like grazing and predation that are essential for ecosystem functioning. Successful rewilding projects demonstrate the approach's potential. Yellowstone National Park's wolf reintroduction transformed ecosystems through trophic cascades. Wolves controlled elk populations, allowing willow and aspen regeneration along streams. The restored vegetation stabilized stream banks, creating better habitat for beavers, fish, and birds. Similar cascades occur when herbivores are reintroduced to areas where vegetation has become overgrown without grazing pressure. Rewilding allows ecosystems to recover complexity and resilience that were lost through previous human impacts. Species restoration programs target individual endangered species through captive breeding, habitat protection, and reintroduction. The California condor, reduced to 27 individuals in 1987, now numbers over 500 through intensive breeding and release programs. Black-footed ferrets, functionally extinct in the wild, have been bred in captivity and reintroduced to several sites. These programs require enormous effort and expense, but demonstrate that species can be pulled back from the brink of extinction when society commits resources. Sustainable development. Sustainable development meets present needs without compromising the ability of future generations to meet their needs. This requires transforming economic systems from linear models based on extraction, use, and disposal to circular models where resources are reused, waste becomes feedstock, and ecosystem regeneration is prioritized. The circular economy represents a systemic shift in how societies produce and consume goods and services. Digital technologies enable circular economy transitions by improving resource management and supply chain transparency. Internet of Things sensors provide real-time monitoring of resource flows. Artificial intelligence optimizes processes to reduce waste and energy consumption. Blockchain creates transparent supply chains, allowing verification of sustainability claims. Big data analytics identify inefficiencies and predict maintenance needs, extending product lifespans. These technologies help decouple economic growth from resource consumption and environmental degradation. Product design changes can dramatically improve sustainability. Designing for durability extends product lifespans, reducing the need for replacements. Modular design allows component replacement rather than discarding entire products when one part fails. Designing for disassembly enables recycling and material recovery at end of life. Selecting materials based on renewability, recyclability, and environmental impact during production reduces life cycle footprints. These design principles require manufacturers to consider products' entire life cycles rather than just initial production. Industrial symbiosis creates networks where waste from one process becomes feedstock for another, mimicking natural ecosystems where nothing is wasted. Kalundborg symbiosis in Denmark involves multiple companies exchanging materials, energy, and water. A power plant provides steam to a refinery and pharmaceutical company, its fly ash to cement producers, and its gypsum to a wallboard manufacturer. The refinery provides gas to the power plant and sulfur to a sulfuric acid producer. Such networks reduce virgin material consumption, minimize waste, and lower costs for all participants. The role of technology. Technology provides tools for environmental protection and restoration that were impossible in previous generations. Satellite remote sensing monitors deforestation, illegal fishing, and environmental changes in real time. Drones survey wildlife populations and detect poachers. Environmental DNA extracted from water or soil samples reveals which species inhabit an area without needing to observe them directly. These technologies make conservation more effective and efficient. Synthetic biology engineers organisms to perform useful functions. Microorganisms can be designed to produce biofuels from waste materials, synthesize medications without chemical factories, break down plastic pollution, or capture carbon dioxide more efficiently than natural photosynthesis. Gene editing could help endangered species adapt to changing climates or resist diseases, driving them toward extinction. These technologies raise ethical questions, but offer powerful tools for addressing environmental challenges. Artificial intelligence assists in climate modeling, species identification, and optimization of conservation interventions. Machine learning algorithms analyze satellite imagery to detect changes in land cover. Computer vision identifies individual animals in camera-trapped photos, automating wildlife monitoring. AI predicts which areas are most likely to experience deforestation or where interventions will be most effective, allowing limited conservation resources to be allocated optimally. As AI capabilities advance, these tools will become increasingly important for environmental management. The integration of these technologies with effective policies and international cooperation could enable stakeholders to make informed decisions that minimize harm to ecosystems and wildlife. Technology alone is insufficient without the political will to use it and the social changes necessary to make sustainable choices. However, technology expands what is possible, providing tools that previous generations lacked. Whether we use these tools wisely will determine whether we navigate the polycrises of climate change, biodiversity loss, and pollution, or succumb to it. The capability exists. The knowledge exists. The question is whether the wisdom and will exist to apply them before it is too late. The story of life on Earth has survived 5 mass extinctions. Whether it survives the 6th depends on choices humanity makes in the years immediately ahead. The next chapter is being written now. Its ending is not yet determined. Chapter 39: The Intelligence of Nature. Intelligence manifests across the tree of life, in forms radically different from human cognition, yet no less remarkable in their sophistication. Ravens and crows solve multi-step puzzles, use tools, and even plan for future needs, demonstrating cognitive abilities once thought exclusive to primates. Plants communicate through chemical signals and fungal networks, warning neighbors of herbivore attacks and sharing resources with kin. Social insects construct elaborate colonies with millions of individuals coordinating behavior without central control, exhibiting swarm intelligence that emerges from simple individual rules. These diverse manifestations of intelligence challenge narrow definitions based solely on brain size or human-like reasoning. Intelligence is better understood as the capacity to acquire information, process it adaptively, and modify behavior to solve problems relevant to survival and reproduction. This broader view reveals that natural selection has repeatedly discovered solutions to information processing challenges, producing cognitive systems as varied as the ecological niches organisms inhabit. Understanding intelligence across its full biological spectrum illuminates both the unity and diversity of life, showing how evolution converges on similar solutions while simultaneously exploring radically different implementations. Corvid cognition. Corvids, the family including crows, ravens, magpies, and jays, possess cognitive abilities rivaling those of great apes despite having brains structured completely differently from mammalian brains. While primates rely on the neocortex for advanced cognition, birds lack this structure entirely. Instead, corvids possess a densely packed pallium with neuronal density far exceeding mammalian cortex. This demonstrates that intelligence is substrate-independent, arising from neural organization and connectivity rather than specific anatomical structures. Tool use in corvids demonstrates flexible problem-solving. New Caledonian crows manufacture hooks from twigs, stripping leaves, and fashioning the exact tool geometry needed to extract insects from crevices. In captivity, crows have spontaneously bent straight wires into hooks to retrieve food from tubes, inventing solutions never encountered in nature. Ravens use stones to crack nuts and sticks to probe for hidden food. These behaviors require mental representation of problems, planning sequences of actions, and understanding cause and effect relationships between tool properties and outcomes. Corvids exhibit episodic-like memory, recalling specific past events including what happened, where it happened, and when. Scrub jays cache food in hundreds of locations and remember not just where they hid items, but also what type of food they stored and how long ago. They preferentially recover perishable foods before they spoil and protect caches from potential thieves by rehiding food when they have been observed caching. This cache protection behavior requires theory of mind, understanding that other individuals have knowledge states different from one's own. Ravens demonstrate future planning, a cognitive capacity thought to require sophisticated temporal reasoning. In experiments, ravens selected and saved tools they would need 15 hours later rather than consuming immediate food rewards. This capacity to delay gratification in service of future goals requires inhibitory control, prospective cognition, and valuation of delayed rewards, abilities central to human executive function. The convergent evolution of such sophisticated cognition in birds and mammals, separated by 300 million years of evolution, demonstrates that complex intelligence can emerge through radically different neural architectures. Plant communication. Plants lack brains and nervous systems, yet exhibit sophisticated information processing and communication. When herbivores attack a plant, damaged tissues rapidly synthesize and release volatile organic compounds that serve multiple functions. These airborne chemicals warn neighboring plants of danger, triggering preemptive activation of defensive compounds in undamaged individuals. The chemicals also attract predators and parasitoids that attack the herbivores, recruiting bodyguards to defend the plant. Some volatiles directly repel herbivores, creating a chemical shield around damaged plants. The specificity of plant communication is remarkable. Different herbivore species elicit different volatile profiles, allowing receiver plants to identify the specific threat and mount appropriate defenses. Plants can distinguish damage from chewing insects versus piercing sucking insects versus mechanical damage, tailoring responses to each threat type. Some plants recognize volatile signals from genetic relatives and respond more strongly to kin than to unrelated individuals, suggesting plants distinguish self from non-self through chemical cues. Underground communication occurs through common mycorrhizal networks, fungal threads, connecting the root systems of multiple plants. These networks allow resource sharing, with carbon, nitrogen, and phosphorus moving between plants through fungal intermediaries. Mature trees supply seedlings growing in deep shade with sugars through mycorrhizal networks, subsidizing offspring until they reach sufficient size to photosynthesize effectively. Dying trees dump nutrients into the network, transferring resources to the next generation. Mycorrhizal networks also transmit warning signals. When one plant is attacked by pathogens or herbivores, defense-related signals travel through the fungal network to connected plants, priming their immune systems before infection arrives. This underground communication complements airborne volatile signaling, creating multi-channel warning systems. The fungal partners benefit by maintaining healthy host plants that provide carbohydrates. This mutualistic three-way interaction among plants, fungi, and the information they exchange demonstrates that intelligence and communication do not require neurons, merely mechanisms for acquiring, processing, and transmitting adaptively relevant information. Social behavior and cooperation. Cooperation, where individuals pay costs to benefit others, poses an evolutionary puzzle because natural selection favors self-interest. Yet cooperation is ubiquitous in nature, from microbes forming biofilms to wolves hunting in packs to humans building civilizations. Two main theories explain how cooperation evolves despite selection for selfishness: kin selection and reciprocal altruism. Kin selection operates when helping relatives increases the survival of shared genes even if the helper does not reproduce. Hamilton's rule formalizes this. Cooperation evolves when the benefit to the recipient multiplied by genetic relatedness exceeds the cost to the helper. This explains sterile worker castes in social insects, alarm calling in ground squirrels that warns relatives at risk to the caller, and cooperative breeding where non-breeding helpers assist parents in raising siblings. By helping relatives reproduce, helpers propagate copies of their own genes carried by kin. Reciprocal altruism operates when individuals help non-relatives with the expectation that help will be reciprocated in the future. Vampire bats share blood meals with roostmates who failed to feed, with recipients reciprocating when roles reverse. This system depends on repeated interactions, allowing cheaters to be identified and excluded, stable group membership, and cognitive abilities to recognize individuals and track their behavior. Reciprocal altruism is most developed in long-lived social species with good memories, particularly primates. Combining kin selection and reciprocal altruism dramatically expands the conditions permitting cooperation. A small amount of reciprocal altruism greatly reduces the relatedness threshold required for kin selection to favor cooperation, and vice versa. Considering both mechanisms together rather than as alternatives better predicts cooperation in nature. Most social systems involve mixtures of kin and non-kin, with different individuals connected through kinship, reciprocity, or both. The multi-layered social networks emerging from these overlapping relationships create stable cooperative systems resistant to exploitation. Sensory worlds. Animals perceive reality through sensory systems attuned to specific aspects of the environment relevant to their ecology. Each species inhabits a unique sensory world or umwelt determined by which stimuli its sensory organs detect and how its nervous system processes those signals. Understanding sensory diversity reveals that the human sensory world represents merely one of countless possible perceptual realities. Vision varies enormously across species in spatial resolution, temporal resolution, color discrimination, and sensitivity to different wavelengths. Eagles possess visual acuity 8 times greater than humans, resolving prey from kilometers away. Mantis shrimp see 12 color channels compared to human 3, perceiving wavelengths from ultraviolet to infrared, invisible to humans. Some species perceive polarized light, allowing navigation by sky patterns invisible to humans. Critical flicker fusion frequency, the rate at which intermittent stimuli blend into continuous perception, varies from 25 Hz in some animals to 300 Hz in others, fundamentally changing how motion and time are perceived. Echolocation in bats and toothed whales demonstrates alternative ways of constructing spatial representations without vision. These animals emit sounds and analyze returning echoes to build three-dimensional maps of their surroundings. Bats emit ultrasonic calls up to 200 kHz, while humans hear only to 20 kHz. The Doppler shift in echoes reveals target velocity. Echo delay indicates distance. Sound intensity and spectral characteristics reveal target size, shape, and material properties. Bats navigate dense forests and capture flying insects in complete darkness by reconstructing reality from acoustic reflections. Electroreception allows some fish and monotremes to detect electric fields. Sharks and rays possess ampullae of Lorenzini, specialized organs detecting voltage gradients as small as 5 nanovolts per centimeter. This sensitivity detects bioelectric fields from muscle contractions in buried prey, allowing sharks to hunt animals completely hidden in sand. Weakly electric fish generate their own electric fields and detect distortions caused by objects, creating an electric sense analogous to active echolocation. These electric senses reveal aspects of reality completely inaccessible to human perception, demonstrating how profoundly sensory biology shapes experienced reality. Navigation and migration. Animal migration spans thousands of kilometers with navigational precision that requires integrating multiple sensory cues and internal maps. Arctic terns migrate from Arctic to Antarctic and back, covering approximately 44,000 kilometers annually. Monarch butterflies migrate from Canada to specific Mexican forests, a journey requiring multiple generations with no individual completing the round trip. These navigational feats require mechanisms for determining position, direction, and distance. Magnetic navigation allows animals to orient using Earth's magnetic field. Sea turtles, hatchlings emerge from nests, scramble to the ocean, and swim into open water where they begin transoceanic migrations. Young loggerheads from Florida enter the North Atlantic Gyre and spend years circulating the Atlantic before returning to nest on the same beaches where they hatched. Experiments exposing hatchlings to magnetic fields from different locations elicit swimming directions appropriate for those locations, demonstrating an inherited magnetic map where regional field parameters serve as navigational markers. The magnetic map sense derives from detecting both inclination angle, the angle Earth's field makes with the surface, and intensity, the field's strength. Both parameters vary predictably across Earth's surface. Inclination ranges from 0 at the magnetic equator to 90 degrees at magnetic poles. Intensity varies from approximately 25 microtesla at the equator to approximately 65 microtesla at the poles. By detecting these parameters, animals determine their position within a magnetic coordinate system. Sun compass navigation uses the sun's position corrected for time of day. Because the sun moves across the sky, animals must compensate for this movement using an internal circadian clock. Experiments rotating the light-dark cycle shift animal orientations by predictable amounts, confirming clock-based sun compensation. Star compass navigation uses stellar patterns, requiring learning constellation configurations during development. Olfactory maps use chemical gradients, with salmon imprinting on the chemical signature of their natal stream as juveniles and following that scent back as adults. Integration of multiple cues provides redundancy and accuracy, ensuring successful navigation even when individual cues become unavailable. Chapter 40: Evolutionary Dynamics. Evolution is not a steady march toward increasing complexity, but rather a dynamic process driven by ecological interactions that generate ever-changing selective pressures. Predator-prey relationships create evolutionary arms races where adaptations in one species select for counter-adaptations in the other, producing escalating cycles of improvement. Parental care strategies balance investment in current offspring against future reproductive opportunities, with different life histories favoring different investment levels. Learning allows individuals to modify behavior based on experience, providing flexibility that genetically programmed responses cannot match. Ecosystem engineers physically modify habitats in ways that affect entire communities, demonstrating how evolution operates at levels beyond individual organisms. These dynamics reveal evolution as an ongoing process rather than a historical event, with selection pressures continually shifting as environments change and species adapt. Understanding evolutionary dynamics provides insight into how biodiversity is generated and maintained, and how ecosystems respond to environmental change. The interplay between evolution and ecology occurs on timescales ranging from years to millennia, with ecological changes driving evolutionary responses that in turn alter ecological conditions in feedback loops connecting evolutionary and ecological time. Predator-prey arms races. Predator-prey coevolution creates reciprocal selection pressures where improvements in predator hunting abilities select for better prey defenses, which in turn select for better predator offenses, continuing indefinitely. This arms race dynamic produces escalating adaptations in both lineages, with neither side gaining permanent advantage. The process is analogous to the red queen in Through the Looking Glass, who must run constantly just to stay in place. In evolutionary terms, species must continually evolve simply to maintain their relative fitness as other species evolve around them. Predators evolve enhanced hunting capabilities through multiple pathways. Sensory systems become more acute, with raptors evolving exceptional vision and canids developing powerful olfaction. Speed and agility increase through skeletal and muscular modifications, allowing faster pursuit and more agile maneuvering. Specialized weapons evolve, including venoms, talons, and teeth, optimized for capturing and killing specific prey. Hunting strategies become more sophisticated through both genetic programming and social learning of cooperative tactics. Prey evolve diverse defensive strategies to reduce predation risk. Escape mechanisms include rapid locomotion like the gazelle's speed, aerial maneuverability in flying fish, and autotomy where lizards sacrifice tails to predators while the body escapes. Enhanced predator detection evolves through acute senses and sentinel behavior where individuals watch for predators while others forage. Warning signals, including alarm calls, coordinate group escape responses. Camouflage makes prey difficult to detect through cryptic coloration matching backgrounds. Disruptive coloration breaks up body outlines with bold patterns, making it hard to discern edges. Countershading, dark backs and light undersides, counteracts shadowing and flattens three-dimensional appearance. Some prey change coloration to match different backgrounds, including seasonal color changes in Arctic animals and rapid color changes in cephalopods. Mimicry evolves where palatable prey resemble toxic models, gaining protection from predators that have learned to avoid the model. The offense-defense balance shifts over evolutionary time through coevolutionary alternation. As predators evolve new offensive traits, prey experience selection for defensive counter-adaptations. When prey evolve effective defenses, predators face selection for traits overcoming those defenses. This creates cyclical dynamics where neither side maintains permanent advantage. The arms race can escalate indefinitely or reach evolutionary stable strategies where further escalation provides no advantage. Population dynamics couple to evolutionary dynamics, with predation intensity depending on relative adaptations and evolutionary rates depending on population sizes and generation times. Parental investment. Parental care involves any investment by parents that increases offspring survival at some cost to the parent's ability to invest in other offspring or future reproduction. The evolution of parental care reflects trade-offs between offspring number and offspring quality. Parents producing many offspring with little investment maximize reproductive output if offspring survival depends minimally on parental care. Parents producing few offspring with substantial investment, maximize offspring quality when parental care greatly improves survival. Parental investment varies enormously across taxa. Many fish and amphibians provide no care beyond producing gametes, with fertilization external and offspring developing independently. Some fish, including cichlids, provide extensive care through mouthbrooding, where parents hold eggs and young in their mouths, protecting them from predators at the cost of being unable to feed. Female cichlids may starve while mouthbrooding, with all nutrients going to offspring. Birds typically provide intensive biparental care. Both parents build nests, incubate eggs, and provision chicks with food. The duration and intensity of care varies with development mode. Precocial species produce relatively mature chicks capable of feeding themselves shortly after hatching, requiring less parental investment per offspring, but involving greater prenatal investment in larger, more developed eggs. Altricial species produce helpless chicks, requiring extensive feeding and protection, but allowing parents to lay smaller eggs with less prenatal investment. Mammalian parental investment is female-biased due to internal gestation and lactation. Females invest heavily through pregnancy, childbirth, and nursing. Male investment varies from absent in species like deer, where males provide only sperm, to substantial in species like primates, where males provision and protect offspring. The level of male investment correlates with mating system, with monogamous species showing higher male investment than polygynous species, where males invest effort in competing for multiple mates rather than caring for offspring. Trade-offs between current and future reproduction constrain parental investment in iteroporous species that reproduce multiple times. Resources invested in current offspring reduce resources available for self-maintenance and future reproduction. Parents must balance offspring demands against their own survival and future reproductive potential. Young parents with many reproductive opportunities ahead should invest less per offspring than older parents nearing the end of their reproductive lifespan. Environmental quality also affects optimal investment, with harsh conditions favoring reduced investment to preserve parental survival for future years. Learning and behaviors. Learning, the modification of behavior based on experience, allows organisms to respond flexibly to environmental variation. While innate behaviors are genetically programmed and appear without experience, learned behaviors develop through interaction with the environment. The balance between innate and learned behavior varies across species, with long-lived animals in complex environments showing more learning capacity than short-lived animals in simple environments. Habituation, the simplest form of learning, involves decreased response to repeated harmless stimuli. Animals initially respond to novel stimuli with alertness or escape responses. If the stimulus proves harmless through repeated exposure, the response diminishes, conserving energy and attention for genuine threats. Habituation allows animals to ignore irrelevant stimuli like passing shadows or rustling leaves while remaining responsive to novel potential threats. The specificity of habituation prevents generalization, so animals habituate to specific harmless stimuli while retaining sensitivity to variations that might indicate danger. Classical conditioning associates a neutral stimulus with a meaningful stimulus through repeated pairing. Pavlov's dogs learned to salivate to bells paired with food. The bell, initially neutral, acquired motivational significance through association with food. Classical conditioning is widespread in nature, allowing animals to learn predictive relationships between environmental cues and biologically important events. Pollinators learn floral colors and scents, predicting nectar rewards. Predators learn prey cues, predicting capture success. Operant conditioning modifies behavior through consequences. Behaviors followed by rewards increase in frequency, while behaviors followed by punishment decrease. Animals learn to press levers for food, navigate mazes to escape shock, and modify virtually any behavior through appropriate reinforcement contingencies. Operant conditioning allows animals to learn arbitrary relationships between actions and outcomes, providing extreme behavioral flexibility. Insight learning involves suddenly perceiving solutions to problems without trial and error learning. Chimpanzees solving problems by stacking boxes to reach bananas or using sticks to rake in food demonstrate insight. This highest form of learning requires mental representation of problems and simulation of potential solutions before execution. Insight learning is rare outside primates and corvids, suggesting it requires sophisticated cognitive capabilities. Ecosystem engineers. Ecosystem engineers are organisms that physically modify environments in ways that alter resource availability for other species. Unlike keystone predators that affect communities through trophic interactions, engineers affect communities by changing physical habitat structure. The impacts extend beyond the engineer's lifetime, with modifications persisting and influencing community composition long-term. Beavers exemplify allogenic engineers that transform environments through their behavior. By damming streams, beavers create ponds that flood riparian forests, converting terrestrial to aquatic habitats. The impounded water kills trees but creates habitat for aquatic plants, fish, amphibians, and waterfowl. Beaver ponds trap sediment, improving water quality downstream. The elevated water table extends wetland habitat into surrounding areas. When beaver colonies abandon sites, dams breach and ponds drain, leaving meadows that eventually succeed back to forest. This cycle creates habitat heterogeneity across landscapes, supporting higher biodiversity than any single habitat state. The impacts of beaver engineering cascade through communities. Amphibian diversity increases in beaver ponds, which provide breeding habitat and refugia. Waterfowl abundance increases due to enhanced foraging opportunities. The rare St. Francis satyr butterfly depends on beaver-created wetlands. Plant diversity increases due to habitat heterogeneity. Even after beavers abandon sites, the legacy of their engineering persists for decades in soil nutrient distributions and plant community composition. Coral reefs demonstrate autogenic engineers that create habitat through their physical structures. Coral polyps secrete calcium carbonate skeletons that accumulate over centuries into massive reef structures. These three-dimensional habitats support over 25% of marine species despite covering less than 1% of ocean floor. The complex physical structure provides countless niches, hiding places, and feeding opportunities. Without coral engineering, these diverse communities could not exist. Earthworms engineer soil environments through burrowing and organic matter processing. Burrows improve soil aeration and water infiltration. Earthworm castings mix organic matter throughout soil profiles, improving fertility and structure. Microbial communities shift in response to earthworm activity, altering decomposition and nutrient cycling. Plant communities change as some species benefit more than others from earthworm-modified soils. These seemingly modest modifications by small animals dramatically affect ecosystem processes and primary productivity. Ecosystem engineers demonstrate that evolution operates at multiple levels simultaneously. Individual selection favors engineering behaviors that benefit the engineer, but engineering also creates frequency-dependent selection where the value of engineering depends on engineer density. At low densities, engineers experience strong benefits. At high densities, competition for engineered resources may reduce individual benefits. This creates complex evolutionary dynamics where engineering behaviors, population densities, and community structure co-evolve in feedback loops, connecting individual adaptation, population dynamics, and ecosystem function across ecological and evolutionary timescales. Chapter 41: The Microbial Majority. Microorganisms constitute the vast majority of life's diversity, biomass, and metabolic innovation on Earth. Bacteria and archaea, the two prokaryotic domains, have existed for at least 3.5 billion years and have colonized virtually every environment on the planet. These microscopic organisms perform essential ecosystem functions, including nutrient cycling, decomposition, and primary production. Without bacteria breaking down dead organic matter, nutrients would remain locked in corpses and ecosystems would grind to a halt. Without photosynthetic cyanobacteria and other microbes, atmospheric oxygen would disappear within millions of years. Prokaryotes also inhabit the human body in numbers that equal or exceed human cells, forming complex communities called microbiomes that influence health, immunity, and even behavior. Despite their microscopic size, prokaryotes dominate Earth's biosphere. They occupy more ecological niches, exhibit greater metabolic diversity, and contain more genetic information collectively than all plants, animals, and fungi combined. Understanding microbial life is essential for understanding life itself. The visible organisms that humans instinctively consider important represent merely decorative branches on the tree of life, while the trunk and main limbs consist entirely of microscopic. Archaeal diversity and metabolism. Archaea were recognized as a distinct domain of life only in 1977, when Carl Woese discovered that certain organisms previously classified as bacteria possessed ribosomal RNA sequences fundamentally different from both bacteria and eukaryotes. This discovery revolutionized biology by revealing that life consists of 3 domains rather than 2. Archaea superficially resemble bacteria, being single-celled organisms without nuclei, but their biochemistry, genetics, and evolutionary history differ profoundly. Archaea exhibit extraordinary metabolic diversity, including pathways absent from bacteria and eukaryotes. Methanogenesis, the production of methane as a metabolic end product, occurs exclusively in archaea. Methanogenic archaea inhabit anaerobic environments including wetlands, rice paddies, and the digestive tracts of ruminants and termites. These organisms generate approximately 70% of atmospheric methane through their metabolism. The pathway involves carbon dioxide reduction using hydrogen as an electron donor, producing methane and releasing energy that methanogens harness through chemiosmosis. Carbohydrate metabolism in archaea involves modified versions of classical pathways that differ fundamentally from bacterial and eukaryotic routes. The Mden-Meyerhof-Parnas pathway, the standard glycolytic pathway breaking glucose into pyruvate, exists in modified form in archaea with different enzymes catalyzing analogous reactions. Some thermophilic archaea use a dual-function enzyme, fructose 1,6-bisphosphate aldolase phosphatase, that plays unique roles in gluconeogenesis. Pentose sugars are degraded through novel pathways that exploit catalytic versatility of archaeal enzymes. Archaea also possess unique biosynthetic pathways for essential molecules. Carbon dioxide fixation occurs through novel pathways including the 3-hydroxypropionate 4-hydroxybutyrate cycle and the dicarboxylate hydroxybutyrate cycle, both absent from bacteria. Acetate assimilation proceeds through the methylaspartate cycle in some archaea. The biosynthesis of membrane lipids follows completely different chemistry than bacterial lipid synthesis, producing ether-linked lipids rather than ester-linked lipids. These fundamental biochemical differences suggest that archaea and bacteria diverged extremely early in life's history, perhaps before many metabolic pathways were established. The human microbiome. The human body hosts trillions of microorganisms, collectively called the microbiome, with bacterial cells equaling or slightly exceeding the number of human cells. The gut microbiome alone contains approximately 38 trillion bacteria, representing thousands of species. These microorganisms colonize the skin, mouth, respiratory tract, and particularly the gastrointestinal tract. The relationship is symbiotic, with humans providing habitat and nutrients, while microbes provide essential services including digestion, vitamin synthesis, and immune system development. Gut microbiota influence systemic immunity throughout the body, not just in the intestinal tract. Intestinal bacteria shape the development and function of immune cells, including T cells, B cells, and innate lymphoid cells. Early life exposure to symbionts promotes antibody repertoire diversity required for optimal bacterial resistance. Gut microbes produce metabolites including short-chain fatty acids that travel through the bloodstream and affect immune function in distant tissues. Disruption of the microbiome through antibiotics or diet changes can alter systemic immunity and contribute to inflammatory diseases. The mechanisms by which gut microbes influence systemic immunity remain incompletely understood, but include both direct and indirect effects. Direct effects occur when microbial molecules or metabolites enter the bloodstream and interact with immune cells. Bacterial cell wall components like lipopolysaccharide can trigger inflammatory responses. Short-chain fatty acids produced by fiber fermentation modulate immune cell activity and gene expression. Indirect effects occur through the gut-associated lymphoid tissue, where immune cells encounter microbial antigens and receive signals affecting their differentiation and function. The microbiome provides essential functions that humans cannot perform independently. Bacteria break down dietary fiber into short-chain fatty acids that provide energy to colon cells and regulate inflammation. They synthesize vitamins, including vitamin K and certain B vitamins. They outcompete pathogenic bacteria for nutrients and space, providing colonization resistance against infections. They metabolize bile acids and influence cholesterol metabolism. Disruption of the microbiome through antibiotics, poor diet, or disease can lead to obesity, inflammatory bowel disease, allergies, and other conditions. Understanding and maintaining a healthy microbiome has become a major focus of medical research. Horizontal gene transfer. Horizontal gene transfer, the transmission of genetic material between organisms outside of parent to offspring inheritance, is a major force in prokaryotic evolution. Unlike eukaryotes, where genetic information flows vertically from parents to offspring, prokaryotes routinely exchange genes horizontally between unrelated organisms. This genetic promiscuity allows rapid adaptation as beneficial genes spread through communities regardless of species boundaries. Antibiotic resistance genes, for example, can spread from harmless bacteria to pathogens within days. Three main mechanisms enable horizontal gene transfer in prokaryotes. Transformation involves uptake of naked DNA from the environment. When bacteria die and lyse, they release DNA fragments that can be absorbed by living cells. Some bacteria actively take up environmental DNA through specialized machinery. Transformation is enhanced in biofilms where cells live in close proximity and DNA accumulates in the extracellular matrix. Conjugation involves direct transfer of genetic material between cells connected by tube-like structures called pili. Plasmids, circular DNA molecules independent of chromosomes, often transfer through conjugation. Transduction involves viruses called bacteriophages that accidentally package host DNA and transfer it when infecting new cells. Mobile genetic elements facilitate horizontal gene transfer. Plasmids carry genes for antibiotic resistance, virulence factors, and metabolic capabilities that can spread between cells and species. Transposons or jumping genes can excise themselves from one DNA location and insert elsewhere, moving between chromosomes and plasmids. Integrative conjugative elements combine features of both, integrating into chromosomes but able to excise and transfer to other cells. These mobile elements have dramatically shaped prokaryotic genomes, with substantial fractions of bacterial and archaeal genomes consisting of horizontally transferred sequences. The prevalence of horizontal gene transfer complicates the reconstruction of prokaryotic phylogeny because genes can have different evolutionary histories than the organisms carrying them. A gene transferred horizontally will appear more closely related to its source organism than to other genes in the recipient's genome. This creates reticulated rather than tree-like evolutionary relationships. Some biologists argue that the concept of species is problematic for prokaryotes because gene flow between distantly related organisms blurs species boundaries. Nevertheless, core genes involved in basic cellular functions like translation show more vertical inheritance and can be used to reconstruct phylogenetic relationships. Viruses and lytic-lysogenic cycles. Viruses are not technically alive by most definitions because they cannot reproduce independently or maintain metabolism. They consist of genetic material, either DNA or RNA, surrounded by a protein coat and sometimes a lipid envelope. Viruses replicate by hijacking host cells using cellular machinery to produce viral components that assemble into new viruses. Bacteriophages, viruses that infect bacteria, are the most abundant biological entities on Earth, with an estimated 10 to the 31st viruses globally. Temperate bacteriophages can follow either lytic or lysogenic reproductive cycles. In the lytic cycle, the virus injects its DNA into a bacterial cell, commandeers cellular machinery to produce viral components, assembles hundreds of new viruses, and lyses or bursts the cell to release them. This kills the host, but produces many viral offspring. In the lysogenic cycle, viral DNA integrates into the bacterial chromosome as a prophage and replicates passively as the bacterium divides. The integrated virus can remain dormant for many generations until environmental stress triggers induction into the lytic cycle. The lytic-lysogenic decision represents a life history switch with profound evolutionary implications. Recent models reveal that viruses switch from lytic to lysogenic when their population grows faster as prophage than as virions produced by lysis. The switch depends on the relative abundance of susceptible hosts and environmental conditions. When hosts are abundant, lytic reproduction maximizes viral spread. When hosts are scarce, lysogenic reproduction ensures viral persistence until conditions improve. This adaptive switching optimizes viral fitness across varying environments. Lysogeny facilitates horizontal gene transfer through transduction. When a prophage excises from the bacterial chromosome to enter the lytic cycle, it occasionally packages adjacent bacterial DNA along with viral genes. If this hybrid virus infects another bacterium and integrates lysogenically, it transfers the bacterial genes to the new host. This virus-mediated gene transfer has distributed antibiotic resistance, toxin genes, and metabolic capabilities across bacterial communities. Lysogeny thus connects the viral and bacterial realms, with viruses serving as vectors for bacterial evolution. Prions and infectious proteins. Prions are infectious agents composed entirely of misfolded proteins without any nucleic acid genome. This violates the central dogma that information flows from nucleic acids to proteins, not the reverse. Prions cause transmissible spongiform encephalopathies, including mad cow disease in cattle, scrapie in sheep, and Creutzfeldt-Jakob disease in humans. These fatal neurodegenerative diseases result from prion proteins accumulating in the brain and causing sponge-like damage. The cellular prion protein exists normally in neurons with a predominantly alpha-helical structure. When exposed to misfolded prions, the normal protein undergoes conformational change to a beta-sheet-rich structure that tends to aggregate. This misfolded isoform then templates the conversion of additional normal proteins into the misfolded form through direct physical interaction. The process propagates exponentially, with misfolded proteins accumulating into fibrils that disrupt cellular function and cause neurodegeneration. Prion propagation occurs in phases. During the nucleation phase, misfolded conformations become stabilized by oligomerization forming nuclei. During the elongation phase, protofilaments grow as additional proteins add to the nuclei. In the fragmentation phase, larger fibrils break into smaller units. Further cycles of elongation and fragmentation result in exponential increase of misfolded prions. The kinetics resemble crystallization more than traditional infection. Prion-like mechanisms may underlie other neurodegenerative diseases, including Alzheimer's and Parkinson's diseases. Proteins including amyloid beta, tau, and alpha-synuclein can misfold, aggregate, and spread between cells in patterns reminiscent of prion propagation. While these proteins are not infectious in the classical sense, their self-templating misfolding and cell-to-cell transmission suggest prion-like behavior. Understanding these mechanisms may illuminate common principles underlying multiple neurodegenerative disorders and suggest therapeutic strategies targeting protein misfolding. Chapter 42, MECHANISMS of Complexity. Life's journey from simple self-replicating molecules to complex multicellular organisms required not just accumulation of genes, but fundamental innovations in how genetic information is organized, regulated, and deployed. The evolution of developmental complexity involved gene regulatory networks that control when, where, and how much each gene is expressed. Small changes in gene regulation can produce large effects on body form without requiring new genes, explaining how the same genetic toolkit generates the spectacular diversity of animal body plans. Epigenetic mechanisms, including DNA methylation and regulation, by non-coding RNAs add layers of control beyond the DNA sequence itself, allowing cells with identical genomes to differentiate into muscle, nerve, skin, and hundreds of other cell types. These mechanisms reveal that complexity emerges not primarily from having more genes, but from more sophisticated ways of using existing genes. Understanding how regulatory complexity evolved provides insight into major evolutionary transitions and illuminates the deep principles governing development. The architecture of gene regulation channels evolution along certain pathways while constraining others, determining which phenotypes are developmentally accessible and which remain forever unrealized. Prebiotic chemistry and life's origin. The origin of life required a transition from prebiotic chemistry, reactions occurring naturally in the environment, to biology, self-replicating systems capable of evolution. Early Earth provided the chemical building blocks and energy sources necessary for complex organic synthesis. The atmosphere approximately 3.5 billion years ago contained nitrogen, carbon dioxide, and smaller amounts of carbon monoxide, ammonia, and methane. This reducing or neutral atmosphere contrasts with the current oxygen-rich atmosphere, which would oxidize organic molecules and prevent their accumulation. Energy sources drove the synthesis of organic molecules on prebiotic Earth. Sunlight, particularly ultraviolet radiation unfiltered by an ozone layer, provided energy for photochemical reactions. Volcanic heat and hydrothermal systems created high-temperature environments where thermodynamically unfavorable reactions could proceed. Lightning discharges, like those simulated in the Miller-Urey experiment, drove synthesis of amino acids and other organic compounds. Radioactive decay from more abundant radioactive isotopes than exist today contributed energy. The combination of these energy sources maintained far from equilibrium chemical conditions necessary for organic synthesis. Recent research demonstrates that prebiotic chemical systems can self-organize and evolve in structured ways under realistic conditions. Exposing organic molecules to repeated wet-dry cycles, which would have occurred in tidal zones or evaporating ponds, causes continuous transformation, selective organization, and synchronized population dynamics. Chemical systems display emergent behaviors, including selective amplification of certain molecules and suppression of others. These observations suggest that prebiotic environments played active roles in shaping molecular diversity through physical processes that selected for particular chemical properties. The transition from complex chemistry to life remains incompletely understood, but likely involved autocatalytic networks, sets of reactions where products catalyze formation of the reactants that produce them. Such networks can grow and evolve, exhibiting primitive metabolism without requiring genes or proteins. RNA or similar molecules capable of both information storage and catalysis could have initiated Darwinian evolution by providing heritable variation subject to selection. The exact sequence of events leading to the first living cells remains debated, but the fundamental requirements are understood. Chemical systems must achieve self-replication, metabolism, and compartmentalization in membrane-bounded structures. The tree of life. The phylogenetic tree of life represents the evolutionary relationships connecting all organisms. This tree has three main branches or domains: bacteria, archaea, and eukarya. Bacteria and archaea are prokaryotes, single-celled organisms lacking membrane-bound nuclei. Eukarya includes all organisms with eukaryotic cells, protists, fungi, plants, and animals. The three-domain system, proposed by Carl Woese in 1990, replaced earlier two-kingdom and five-kingdom classifications by recognizing that archaea are as different from bacteria as either is from eukarya. The root of the tree of life, representing the last universal common ancestor, LUCA, lived approximately 3.5 to 4 billion years ago. LUCA was not the first living organism, but rather the most recent organism from which all current life descends. Earlier forms existed, but left no surviving descendants. LUCA already possessed sophisticated cellular machinery, including ribosomes, the genetic code, and basic metabolic pathways. The existence of shared features across all three domains indicates these features evolved before the domains diverged. Phylogenetic trees are constructed by comparing gene sequences and identifying similarities due to common ancestry. Ribosomal RNA genes are commonly used because they evolve slowly and exist in all organisms, allowing comparison across vast evolutionary distances. Mori genes provide more data and more reliable trees. Whole genome comparisons confirm relationships inferred from individual genes, while revealing complexities like horizontal gene transfer that create reticulated evolutionary patterns rather than simple branching trees. Recent phylogenetic analyses suggest that eukaryotes may have originated from within archaea rather than as a sister group. If correct, this means the tree of life has two domains, bacteria and archaea, with eukarya nested within archaea. This two-domain system reflects the discovery that eukaryotic cells originated through endosymbiosis, when an archaeal host cell engulfed bacterial symbionts that became mitochondria. The host's archaeal heritage explains why eukaryotic information processing machinery resembles archaea, while eukaryotic metabolism resembles bacteria. The debate over 2 versus 3 domains continues as more genomic data. Evolutionary developmental biology. Evolutionary developmental biology, or EvoDevo, studies how developmental processes evolve and how development constrains evolution. A central discovery revolutionized understanding of evolution and development. Widely divergent organisms share deep genetic and developmental similarities. The genes controlling body plan development in flies also control body plan development in mice, worms, and humans, despite these organisms looking completely different and being separated by over 500 million years of evolution. Hox genes exemplify this deep conservation. These genes encode transcription factors, proteins that regulate expression of other genes by binding to DNA control regions. Hox genes function as master regulators, controlling whole developmental pathways by activating or repressing groups of downstream genes. Hox genes are organized into clusters on chromosomes and expressed in sequential patterns along the body axis, with genes at one end of the cluster controlling head development and genes at the other end controlling tail development. This collinearity between gene position and expression domain is conserved across bilaterally symmetrical animals. Changes in Hox gene expression have produced major evolutionary innovations, including the limbless snake body plan. Snakes evolved from four-legged ancestors by expanding the body region where Hox genes suppress limb development. This did not require inventing new genes or eliminating limb-building genes, merely changing where and when Hox genes are expressed. Similarly, differences in vertebrate body plans often result from variations in Hox expression patterns rather than Hox gene sequences. The same genetic toolkit produces different outcomes depending on when and where the tools are deployed. Gene regulatory networks link transcription factors to their target genes, creating hierarchies of developmental control. Master regulators like Hox proteins activate or repress intermediate transcription factors, which in turn regulate downstream genes, including realisator genes directly involved in growth and morphogenesis. Changes at different levels of the hierarchy have different evolutionary consequences. Changes to master regulators typically disrupt development and are lethal. Changes to intermediate transcription factors affect specific organs or structures. Changes to realisator genes produce fine-scale morphological variation. Evolution thus operates more freely at the bottom of regulatory hierarchies than at the top. Epigenetics, and non-coding RNA. Epigenetics describes heritable changes in gene expression that do not involve altering DNA sequence. Cells with identical genomes differentiate into distinct cell types through epigenetic mechanisms that activate different sets of genes. Once established, epigenetic states are maintained through cell divisions, allowing daughter cells to inherit the cell type identity of their parent despite having the same DNA sequence. The main epigenetic mechanisms include DNA methylation, histone modifications, and regulation by non-coding RNAs. DNA methylation involves adding methyl groups to cytosine bases, typically silencing genes in methylated regions. Heavily methylated genes are tightly packaged into chromatin and inaccessible to transcription machinery. During development, specific genes are methylated in some cell types, but not others, determining which genes can be expressed. DNA methylation patterns are copied when DNA replicates, allowing epigenetic information to be inherited through cell divisions. Inappropriate methylation patterns are associated with cancer and other diseases. Histone modifications include acetylation, methylation, phosphorylation, and other chemical changes to histone proteins around which DNA wraps. Different modifications have different effects. Histone acetylation typically loosens chromatin and activates transcription. Histone methylation can either activate or repress transcription depending on which amino acids are modified. Combinations of modifications form a histone code, determining whether genes are expressed or silenced. These modifications create functional differences between regions of the genome despite identical DNA sequences. Non-coding RNAs, RNA molecules that do not encode proteins, play crucial regulatory roles. MicroRNAs bind to messenger RNAs and either block their translation or target them for degradation, fine-tuning protein levels. Small interfering RNAs guide enzymes that methylate DNA and modify histones, directing epigenetic modifications to specific genomic locations. Long non-coding RNAs scaffold the assembly of protein complexes that modify chromatin. The discovery that most of the human genome is transcribed into non-coding RNAs, despite only 2% encoding proteins, reveals that RNA regulation is central to genome function. RNA interference pathways connecting non-coding RNAs to epigenetic modifications may maintain and regulate the epigenome. Small interfering RNAs guide methylation and histone modification of repetitive sequences, which comprise 2/3 of the human genome. MicroRNAs can induce DNA methylation changes, altering gene expression patterns. These RNA-directed mechanisms allow sequence-specific epigenetic modifications that can be transmitted through generations, creating heritable changes without altering DNA sequence. Understanding how non-coding RNAs feed back into epigenetic regulatory networks reveals RNA's central role in controlling gene expression beyond simply encoding proteins. The interplay between genetic and epigenetic mechanisms creates developmental complexity from finite genetic information. Humans possess approximately 20,000 protein-coding genes, only slightly more than roundworms with 1,000 cells. Yet humans construct bodies with trillions of cells organized into hundreds of cell types. This complexity emerges from regulatory networks that integrate genetic information with epigenetic modifications, producing an exponential increase in regulatory possibilities from a linear genome. The architecture of these networks, built over billions of years of evolution, determines how genetic information translates into phenotypes and channels evolution along pathways determined by developmental possibilities. Life's complexity reflects not just what genes exist, but how those genes are orchestrated in space and time. Chapter 43: Reading the Fossil Record. Fossils are the preserved remains or traces of ancient organisms, providing the primary evidence for life's history on Earth. Fossil record, though incomplete, contains billions of specimens spanning over 3 billion years, documenting the rise and fall of countless lineages and the major transitions in life's complexity. Understanding how fossils form, what they can and cannot tell us, and how to interpret them requires knowledge of taphonomy, the study of death, decay, and preservation. Only a tiny fraction of organisms that ever lived became fossilized because preservation requires specific conditions that rarely occur. Most organisms decay completely, their molecules recycled by decomposers. Yet despite these limitations, the fossil record reveals patterns of evolutionary change, documents mass extinctions and recoveries, and provides transitional forms linking major groups. Fossils are time machines allowing us to glimpse worlds profoundly different from today, inhabited by creatures bizarre and wonderful. They demonstrate both evolution's creativity and its constraints, showing how similar solutions emerge repeatedly while certain body plans, once established, persist for hundreds of millions of years. Fossilization processes. Fossilization occurs through multiple mechanisms, each preserving different types of information. Permineralization happens when mineral-rich water percolates through porous tissues like bone or wood, depositing minerals within empty spaces. The original organic material may remain while minerals fill cavities, creating fossils that are heavier and harder than the original structures but retain fine anatomical details. Petrified wood forms through permineralization when silica or other minerals not only fill spaces but also replace cellulose molecule by molecule, preserving cellular structure in stone. Replacement occurs when original skeletal material dissolves and is replaced by different minerals. Shell calcium carbonate may be replaced by silica or pyrite while maintaining the original three-dimensional form. Replacement can preserve external morphology faithfully while destroying internal structures, depending on the rate of dissolution relative to mineral deposition. Gradual replacement preserves more detail than rapid replacement, where the structure collapses before new minerals stabilize it. Carbonization preserves organisms as thin carbon films. This process occurs when volatile elements including hydrogen, oxygen, and nitrogen escape from organic tissues under heat and pressure, leaving behind carbon residue that retains the organism's outline. Carbonization commonly preserves plants, leaves, and soft-bodied animals like worms and jellyfish that lack mineralized hard parts. The Burgess Shale and similar Lagerstätten, sites of exceptional fossil preservation, contain carbonized soft tissues revealing anatomical details normally lost. Unaltered preservation occurs when original tissues remain chemically unchanged. Amber preserves insects and other small organisms trapped in tree resin that hardened into transparent fossilized resin. The organisms retain original colors, three-dimensional form, and even DNA fragments. Ice preserves woolly mammoths and other Pleistocene megafauna so completely that muscle tissue, fur, and stomach contents remain intact for tens of thousands of years. Tar pits preserve bones soaked in natural asphalt that prevents decay. These exceptional cases provide windows into soft anatomy and behavior unavailable from typical fossils. Molds and casts form when organisms buried in sediment decay completely, leaving cavities that preserve external morphology. The cavity is the mold, a negative impression of the organism's shape. If minerals fill the mold, they create a cast, a three-dimensional replica of the organism's exterior. Molds and casts lose all internal anatomical information, but accurately preserve external features, including ornamentation, growth lines, and attachment scars, useful for identifying species and inferring ecology. Transitional fossils. Transitional fossils exhibit mixtures of ancestral and derived characteristics, documenting evolutionary transitions between major groups. These forms are not necessarily direct ancestors of later groups, but demonstrate that organisms with intermediate characteristics existed, refuting claims that evolutionary transitions lack fossil support. The transitional fossil record has grown substantially as paleontological exploration expands and analytical techniques improve. Archaeopteryx, discovered in 1861, only 2 years after Darwin published On the Origin of Species, was the first widely recognized transitional fossil. This Jurassic creature possessed features diagnostic of both reptiles and birds. Reptilian features include teeth in both jaws, a long bony tail, and clawed fingers on the wings. Avian features include feathers with asymmetrical veins, indicating flight capability, a wishbone or fused clavicles, and a reversed first toe suggesting perching ability. Archaeopteryx demonstrates that birds evolved from theropod dinosaurs through a series of intermediates that combined dinosaurian skeletal structure with feathered integument and eventually powered flight. Tiktaalik rosy, discovered in 2004 in Arctic Canada, documents the fish-to-tetrapod transition. This 375-million-year-old lobe-finned fish possessed features of both fish and tetrapods. Fish features include scales, fins with fin rays, and gills indicating aquatic respiration. Tetrapod features include a mobile neck, allowing independent head movement, robust ribs suggesting air breathing, and limb-like pectoral fins with bones homologous to tetrapod humerus, radius, and ulna. The fin's structure with a mobile wrist joint indicates Tiktaalik could prop itself up in shallow water, an intermediate stage toward terrestrial locomotion. Ambulocetus, the walking whale, documents the transition from terrestrial mammals to fully aquatic whales. This 49-million-year-old whale from Pakistan possessed legs capable of walking on land while also being an accomplished swimmer. The skull shows nostrils positioned dorsally rather than at the snout tip, an intermediate stage toward the blowhole of modern whales. The limbs were powerful enough for terrestrial locomotion, but the feet were webbed, and the tail was muscular for aquatic propulsion. Ambulocetus probably inhabited coastal environments, hunting in water like modern seals, but capable of moving on land. These and numerous other transitional fossils document that major evolutionary transitions occurred through series of intermediate forms rather than sudden jumps. Each intermediate was a fully functional organism adapted to its environment, not a deficient step towards some future goal. Evolution does not anticipate future needs, but modifies existing structures for new functions. The fossil record of transitions demonstrates evolution's opportunistic nature, building novelty through incremental modification of inherited structures. The Big Five mass extinctions. The Phanerozoic eon, spanning the past 541 million years, includes 5 mass extinction events called the Big Five. Each eliminated over 75% of species and fundamentally restructured global ecosystems. Understanding these ancient catastrophes provides context for evaluating the current biodiversity crisis and predicting recovery trajectories if extinctions continue. The Endordovian extinction occurred approximately 444 million years ago, eliminating approximately 85% of marine species. The ultimate cause was tectonic changes that isolated the supercontinent Gondwana over the South Pole, triggering glaciation. Proximate causes included cooling temperatures, sea level fall as water was locked in ice sheets, and ocean circulation changes that disrupted nutrient delivery to marine ecosystems. Marine invertebrates including trilobites, brachiopods, and graptolites suffered severe losses. The extinction proceeded in 2 pulses separated by hundreds of thousands of years, reflecting glacial advance and retreat. The late Devonian extinction, approximately 375 million years ago, eliminated approximately 75% of species. Multiple pulsed extinction events occurred over several million years, complicating identification of ultimate causes. Proposed causes include ocean anoxia from algal blooms, bolide impacts, and cooling related to plant colonization of land. The rise of forests with deep root systems enhanced chemical weathering of rocks, drawing down atmospheric carbon dioxide and cooling the planet. Reef ecosystems collapsed, with reef-building organisms, including stromatoporoids and tabulate corals, nearly eliminated. The Permian-Triassic extinction, approximately 251 million years ago, was the most severe biodiversity crisis in Earth's history, eliminating approximately 96% of marine species and 70% of terrestrial vertebrates. The ultimate cause was eruption of the Siberian Traps, a massive flood basalt province covering an area the size of Europe. The proximate causes cascaded from volcanic emissions. Carbon dioxide caused extreme warming, Methane from heated coal deposits further amplified warming, hydrogen sulfide accumulated in anoxic oceans, and poisoned terrestrial environments when outgassing and ocean acidification from dissolved carbon dioxide inhibited carbonate skeleton formation. Recovery from the Permian-Triassic extinction required longer than any other mass extinction. Full recovery took 30 million years, delayed by successive waves of extinction that inhibited recovery and prolonged environmental stress that continued into the early Triassic. The extinction fundamentally reset ecosystem structure, eliminating dominant Paleozoic groups, including trilobites, that had thrived for 300 million years, and opening ecological opportunities for new groups, including dinosaurs. The Triassic-Jurassic extinction, approximately 201 million years ago, eliminated approximately 80% of species. The Central Atlantic Magmatic Province eruption, associated with the breakup of Pangaea and opening of the Atlantic Ocean, triggered the extinction through warming, ocean acidification, and possibly toxic volcanic gases. The extinction removed competitors and allowed dinosaurs to dominate terrestrial ecosystems for the next 135 million years. The Cretaceous-Paleogene extinction, approximately 66 million years ago, eliminated approximately 75% of species, including all non-avian dinosaurs. A bolide impact created the Chicxulub crater in Mexico, throwing dust and aerosols into the atmosphere that blocked sunlight for months to years. Photosynthesis collapsed, eliminating food chains from the bottom up. Massive wildfires ignited by impact ejecta covered continents. The extinction was geologically instantaneous rather than gradual, distinguishing it from other Big Five events. The elimination of dominant dinosaurs opened ecological opportunities for mammals that radiated into the spectacular diversity seen today. Chapter 44: Biological Innovations. Evolution has produced numerous innovations that fundamentally changed what organisms could do and where they could live. The adaptive immune system allows vertebrates to recognize and remember virtually unlimited antigens, providing protection against rapidly evolving pathogens. Bioluminescence, the production of light through chemical reactions, evolved independently multiple times and serves functions from predation to communication to mate attraction. Circadian rhythms synchronize physiology and behavior with daily light-dark cycles through molecular clocks conserved across all domains of life. Sexual selection drives the evolution of extravagant ornaments and displays that seem to reduce survival, yet increase reproductive success. Understanding these innovations reveals evolution's creativity in solving biological problems through molecular, physiological, and behavioral mechanisms. Each innovation opened new ecological opportunities and often triggered adaptive radiations as lineages exploited the advantages conferred. These case studies demonstrate that evolution does not merely tinker with existing structures, but occasionally produces genuine novelties that transform life's possibilities. Adaptive immunity. The adaptive immune system, found exclusively in vertebrates, provides antigen-specific protection that improves through repeated exposures. Unlike innate immunity, which recognizes broad categories of pathogens through fixed receptors encoded directly in germline DNA, adaptive immunity generates enormous receptor diversity through somatic recombination, allowing recognition of virtually any molecular structure. This anticipatory repertoire prepares the immune system for pathogens never before encountered. T cells and B cells are the lymphocytes mediating adaptive immunity. T cells develop in the thymus and recognize antigens presented by major histocompatibility complex molecules on cell surfaces. Helper T cells coordinate immune responses by secreting cytokines that activate other immune cells. Cytotoxic T cells directly kill infected cells, displaying foreign antigens. B cells develop in bone marrow in mammals or the bursa of Fabricius in birds and secrete antibodies, proteins that bind specific antigens and mark them for destruction. Receptor diversity arises through VDJ recombination, a process unique to jawed vertebrates. T cell receptor and B-cell receptor genes are assembled from libraries of variable diversity and joining gene segments. Recombinase activating genes 1 and 2 initiate the process by making double-strand breaks at recombination signal sequences flanking gene segments. Different V, D, and J segments are randomly joined, generating millions of possible combinations. Additional diversity arises from imprecise joining that adds or deletes nucleotides at junctions, and in B cells from somatic hypermutation that introduces point mutations in antibody genes. Immunological memory is the defining feature of adaptive immunity. When B cells and T cells are activated by encountering their cognate antigen, some differentiate into memory cells that persist for years or decades. Memory cells are more numerous than naive cells specific for the same antigen and respond more rapidly upon re-encounter. This creates the secondary immune response, stronger and faster than the primary response, providing the basis for vaccination. Memory T cells and memory B cells form a living database of previous infections, allowing the immune system to mount effective responses before pathogens can establish infections. The adaptive immune system's ability to recognize self versus non-self prevents autoimmunity. T cells undergo selection in the thymus, where those recognizing self-antigens too strongly are eliminated by negative selection. This central tolerance removes most autoreactive T cells during development. Additional peripheral tolerance mechanisms suppress autoreactive cells that escape central tolerance. The orchestration by T cells, whose receptors are shaped to discriminate self from non-self, provides safeguards against autoimmunity while maintaining ability to recognize pathogens. Bioluminescence evolution. Bioluminescence, the enzymatic production of visible light, has evolved independently at least 40 times across bacteria, dinoflagellates, fungi, cnidarians, mollusks, arthropods, and chordates. This repeated evolution suggests strong selective advantages in diverse ecological contexts. The biochemical mechanisms vary, but all involve an enzyme called luciferase oxidizing a substrate called luciferin, producing light with minimal heat. Firefly bioluminescence is the best-studied terrestrial system. Fireflies produce light using beetle luciferin oxidized by luciferase in the presence of ATP and molecular oxygen. The reaction occurs in specialized light organs called lanterns containing photocytes packed with mitochondria and peroxisomes. Neural control regulates oxygen delivery to photocytes, allowing precise control of flash patterns used in mate recognition. Different firefly species produce characteristic flash patterns that facilitate species recognition and reduce hybridization. Genetic analyses reveal that firefly luciferase evolved from fatty acyl-CoA synthetases through gene duplication and neofunctionalization. These ancestral enzymes adenylate fatty acids, activating them for metabolism. The luciferase retains this adenylation chemistry but acts on luciferin rather than fatty acids. This illustrates enzymatic promiscuity, where enzymes can catalyze reactions with substrates other than their primary targets. Promiscuous activity provides raw material for evolution, with gene duplication allowing one copy to retain original function while the other acquires new specificity. The evolution of luciferin biosynthesis pathways remains less understood than luciferase evolution. Fireflies must synthesize luciferin from precursors because it is not obtained from diet. Transcriptomic analysis of light organs identifies candidate genes involved in luciferin metabolism, including a specialized luciferin sulfotransferase that sulfonates luciferin prior to oxidation. The genes for luciferase and sulfotransferase are located on separate chromosomes, indicating they do not form a simple operon, but rather coordinate through regulatory networks. Bioluminescence likely originated in an aposomatic context, warning predators of toxicity. Early bioluminescent beetles may have used whole-body luminescence that increased during predator attacks when spiracles opened and oxygenated hemolymph. This startle response could deter predators while communicating unpalatability. Later evolution refined control to produce the discrete flash patterns used in mate choice. This transition from defense to communication exemplifies how traits evolved for one function can be co-opted for different functions. Circadian rhythms. Circadian rhythms are endogenous biological oscillations with approximately 24-hour periods that synchronize physiology and behavior with daily environmental cycles. These molecular clocks exist in organisms from cyanobacteria to humans, demonstrating ancient origins predating the diversification of major lineages. Circadian rhythms provide adaptive advantages by allowing organisms to anticipate predictable daily changes in light, temperature, and food availability rather than merely reacting to them. The molecular mechanism of circadian rhythms involves transcriptional translational feedback loops. In mammals, the core loop involves clock and BMAL1 proteins that heterodimerize and activate transcription of period and cryptochrome genes. PER and cry proteins accumulate in cytoplasm, dimerize, and translocate to the nucleus where they inhibit clock BMAL1 activity, suppressing their own transcription. As PER and cry proteins are degraded, clock BMAL1 activity increases, beginning a new cycle. The entire cycle takes approximately 24 hours due to delays in transcription, translation, protein accumulation, and degradation. The suprachiasmatic nucleus in the hypothalamus serves as the master circadian pacemaker in mammals. SCN neurons exhibit intrinsic oscillations synchronized by light input from the retina through the retinohypothalamic tract. Light activates signaling pathways that induce clock gene expression, resetting the clock to match external day-night cycles. The SCN controls peripheral clocks throughout the body through neural, hormonal, and behavioral pathways, ensuring that all tissues remain temporally coordinated. Melatonin is a key hormonal output of the circadian system. The pineal gland synthesizes melatonin from serotonin primarily during darkness, with levels rising in evening and falling in morning. Melatonin acts through MT1 and MT2 receptors widely expressed in central and peripheral tissues. MT1 promotes sleep by acutely suppressing neuronal firing in the SCN. MT2 adjusts circadian timing and realigns misaligned biological clocks. The rhythmic secretion of melatonin under SCN control translates internal clock dynamics into systemic physiological regulation, affecting sleep, body temperature, immune function, and metabolism. Disruption of circadian rhythms through shift work, jet lag, or irregular sleep schedules causes adverse health effects. Circadian misalignment increases risk of metabolic disorders, cardiovascular disease, cancer, and neurodegenerative conditions. These effects demonstrate that circadian organization is not merely convenient, but essential for health, reflecting millions of years of evolution synchronizing internal physiology with the rotating Earth's daily cycles. The circadian system exemplifies how evolution has internalized external environmental periodicity, creating molecular timekeeping mechanisms that optimize fitness by coordinating biology with predictable temporal structure. Sexual selection and the handicap principle. Sexual selection, distinct from natural selection for survival, arises from competition for mates and mate choice. Darwin recognized that traits reducing survival could spread if they increased reproductive success through enhanced mating opportunities. Male peacocks bear enormous, elaborate tail trains that impair flight and attract predators, yet females prefer males with larger, more ornate trains. Understanding why selection favors such seemingly maladaptive traits requires distinguishing natural selection from sexual selection. The handicap principle, proposed by Amos Zahavi in 1975, explains ornaments as honest signals of quality. According to this theory, females prefer elaborate ornaments because only high-quality males can afford the survival costs of producing and bearing them. A male surviving despite handicaps must possess superior genes, making him an attractive mate. The ornament is honest because low-quality males cannot fake it. They would die trying to produce ornaments as elaborate as those of high-quality males. Traditional formulations of the handicap principle stipulated that ornaments must impose survival costs to serve as honest signals. However, recent theoretical work demonstrates that ornaments need not directly reduce survival to function as signals. Ornaments can honestly signal quality if their development depends on condition, even without ongoing survival costs. A peacock that grew a large train during development when food was abundant signals that he was able to acquire resources, a trait likely heritable. The train need not currently reduce his survival to convey honest information about his developmental history and genetic quality. The C-value paradox, the lack of correlation between genome size and organismal complexity, illustrates similar principles. Single-celled amoebae possess genomes 100 times larger than humans despite vastly less complexity. This paradox arises because genome size is determined not just by protein-coding genes, but by repetitive DNA, including transposons, tandem repeats, and introns. Polyploidy whole genome duplication dramatically increases genome size without adding unique genetic information. Counterbalancing mechanisms, including diploidization and DNA deletion, prevent genomes from expanding indefinitely. The paradox is partly resolved by recognizing that large genomes impose costs through cell economy. Larger genomes require more resources for DNA replication and transcription, constrain cell division rates, and increase cell size. These costs select for genome streamlining in organisms where rapid growth and small cell size provide advantages, explaining compact genomes in bacteria and some rapidly reproducing eukaryotes. Conversely, organisms where large cell size is advantageous tolerate or even benefit from genome expansion. This demonstrates that genome architecture evolves under selection pressures, balancing the benefits of genetic information against the costs of maintaining and replicating large genomes, principles analogous to those governing sexually selected ornaments. Chapter 45, MECHANISMS of Chain. Evolution operates through multiple mechanisms beyond natural selection, each contributing to the patterns of genetic and phenotypic variation observed across life. Speciation, the process by which one species splits into two or more reproductively isolated lineages, occurs through geographic separation or within a single population through various mechanisms, agging and senescence. The progressive decline in physiological function with time emerged through cellular mechanisms including telomere shortening and accumulated damage. Plants have evolved remarkable adaptations to extreme environments, particularly deserts where water scarcity drives evolution of specialized morphological and physiological traits. Animal locomotion, from swimming to flying to walking, reflects biomechanical constraints and convergent evolution toward efficient movement in different media. These diverse topics reveal evolution's versatility in solving problems across scales from molecules to ecosystems. Understanding these mechanisms illuminates not just how organisms came to be, but how they continue changing in response to environmental pressures, both natural and human-caused. Speciation and reproductive isolation. Speciation occurs when populations diverge genetically to the point that they can no longer interbreed and produce viable fertile offspring. The process requires the evolution of reproductive isolating mechanisms that prevent gene flow between diverging populations. These mechanisms fall into two categories: prezygotic barriers that prevent fertilization and postzygotic barriers that reduce hybrid fitness. Allopatric speciation, the most common mode, occurs when populations become geographically separated by barriers like mountains, rivers, or oceanic distances. Geographic isolation prevents gene flow, allowing populations to diverge through drift and selection, acting on different mutations in different environments. Over time, genetic differences accumulate until populations would no longer interbreed, even if brought back into contact. The longer populations remain isolated, the more prezygotic and postzygotic barriers evolve. Prezygotic isolation mechanisms prevent mating or fertilization. Temporal isolation occurs when populations breed at different times of day, season, or year. Behavioral isolation emerges from divergence in courtship displays, calls, or pheromones that lead to assortative mating, where individuals prefer mates from their own population. Mechanical isolation develops when reproductive structures become incompatible, preventing successful copulation or pollen transfer. Gametic isolation arises when sperm cannot survive in the reproductive tract, or when molecular recognition systems prevent sperm-egg fusion. Postzygotic isolation reduces hybrid fitness through multiple mechanisms. Hybrid inviability occurs when hybrid zygotes fail to develop properly, often because chromosomal incompatibilities disrupt gene expression during development. Hybrid infertility produces viable but sterile hybrids, exemplified by mules from horse-donkey crosses, typically because chromosomes from the two parental species cannot pair properly during meiosis. Hybrid breakdown occurs when first-generation hybrids are fertile, but subsequent generations show reduced fitness, indicating that parental genomes are compatible individually, but specific combinations in later generations produce deleterious interactions. Sympatric speciation occurs within a single geographic area without physical barriers to gene flow. This requires strong disruptive selection, favoring extreme phenotypes or reproductive isolation arising through mechanisms like polyploidy. Polyploidy, the doubling of entire chromosome sets, instantly creates reproductive isolation because triploid offspring from diploid-tetraploid crosses are typically sterile. Polyploid speciation is common in plants, with approximately 30 to 70% of flowering plant species having polyploid ancestry. In animals, sympatric speciation may occur through sexual selection when mate preferences diverge, ecological specialization that reduces gene flow between populations adapted to different resources, or chromosomal rearrangements that reduce hybrid fitness. Aging and cellular senescence. Aging is the progressive loss of physiological integrity with time, leading to increased vulnerability to death. Evolutionary theories explain why aging exists despite its obvious fitness costs. The mutation accumulation theory proposes that deleterious mutations with effects manifesting late in life are not strongly selected against because few individuals survive to old age in nature. The antagonistic pleiotropy theory suggests genes with beneficial effects early in life, but harmful effects late in life are favored by selection because early benefits outweigh late costs. The disposable soma theory proposes that organisms allocate limited resources between maintenance and reproduction, with optimal allocation favoring reproduction over indefinite maintenance. Natural selection shapes investment strategies to maximize lifetime reproductive success given ecological constraints. In dangerous environments where extrinsic mortality is high, investing heavily in maintenance provides little benefit because individuals will likely die from external causes before aging becomes limiting. Selection favors shifting investment toward early reproduction at the expense of longevity. In safe environments, longer lifespans allow more reproductive opportunities, favoring greater investment in maintenance. Cellular senescence, the irreversible cell cycle arrest occurring in response to various stresses, contributes to organismal aging. Replicative senescence occurs when telomeres, repetitive DNA sequences protecting chromosome ends, shorten through repeated cell divisions. Telomeres shorten because DNA polymerase cannot fully replicate chromosome ends, losing approximately 50 to 200 base pairs per division. After approximately 50 to 70 divisions in human cells, telomeres reach a critical length triggering growth arrest called the Hayflick limit. The telomere theory of aging rests on three principles. First, aging is programmed, controlled by specific genetic mechanisms rather than being merely accumulated damage. Second, irreversible cell cycle arrest occurs in response to telomere shortening. Third, the total number of cell divisions in the absence of telomerase, the enzyme that extends telomeres, cannot exceed the Hayflick limit. Telomere shortening serves as a molecular clock measuring cellular age, with critically short telomeres triggering DNA damage responses that induce senescence. Senescent cells accumulate with age, and contribute to age-related pathology through the senescence-associated secretory phenotype. Senescent cells secrete inflammatory cytokines, growth factors, and proteases that damage surrounding tissues and promote inflammation. While senescence initially evolved to suppress cancer by preventing damaged cells from proliferating, the accumulation of senescent cells creates chronic inflammation that drives aging. Selective elimination of senescent cells in mice extends lifespan and delays age-related pathologies, demonstrating causal roles in aging. Understanding cellular senescence mechanisms opens possibilities for interventions targeting aging through senolytics, drugs that selectively eliminate senescent cells. Desert plant adaptations. Desert plants face extreme challenges including scarce and unpredictable water availability, intense solar radiation, extreme temperature fluctuations, and nutrient-poor soils. These selective pressures have driven evolution of xerophytes, plants specialized for arid environments through morphological, anatomical, and physiological adaptations that minimize water loss while maintaining photosynthesis and growth. Succulents, the storage of water in enlarged fleshy tissues, characterizes cacti, agaves, and other desert plants. Succulent stems or leaves contain water-storing parenchyma cells with large vacuoles holding water reserves that sustain metabolism during drought. The stored water increases plant mass, creating thermal inertia that buffers temperature fluctuations. However, succulents trades off against photosynthetic efficiency because storage tissues displace photosynthetic tissues. Crassulation acid metabolism, a specialized photosynthetic pathway, allows CAM plants to open stomata at night rather than during the day. At night, when temperatures are cooler and humidity is higher, stomata open for gas exchange. Carbon dioxide enters and is fixed into organic acids stored in vacuoles. During the day, stomata close, minimizing water loss. The stored acids release carbon dioxide internally, which is used for photosynthesis via the Calvin cycle. This temporal separation of carbon dioxide uptake and fixation allows CAM plants to lose 1/10 as much water per unit of carbohydrate synthesized compared to C3 plants that open stomata during the day. CAM plants can idle metabolism during severe drought. When water-stressed, CAM plants keep stomata closed both day and night, nearly stopping gas exchange and water loss. However, metabolism continues at low levels in still moist tissues. This idling allows rapid response when water becomes available, with plants resuming full growth within 24 to 48 hours after rain. Non-CAM plants require longer to revive from deep drought, missing opportunities to exploit ephemeral moisture. Additional xerophyte adaptations include reduced leaf area or complete leaf loss, sunken stomata, protected in pits that trap humid air, dense coverings of hairs or wax that reflect radiation and reduce water loss, and extensive root systems that maximize water uptake. Deep taproots access groundwater, while shallow lateral roots exploit brief surface moisture from light rains. Some desert plants are drought deciduous, shedding leaves during dry periods to minimize water loss and regrowing them when water is available. Others survive as seeds during harsh conditions, germinating only when conditions are favorable. These diverse strategies demonstrate that no single solution exists to desert survival. Instead, different lineages have evolved different combinations of adaptations. Locomotion, biomechanics. Animal locomotion involves generating forces to overcome drag, lift the body against gravity, and propel forward through media with different physical properties. The biomechanics of locomotion reflect constraints imposed by physics and the historical contingency of inherited body plans. Convergent evolution produces similar solutions in distantly related lineages facing similar locomotor challenges. Aquatic locomotion involves overcoming drag in a medium approximately 800 times denser than air. Fish achieve efficient swimming through streamlined bodies that minimize drag and lateral body undulations or tail beats that generate thrust. The evolution of aquatic propulsion in secondarily aquatic tetrapods that return to water after their ancestors colonized land required modifications of terrestrial body plans. Marine mammals including whales, seals, and sea otters evolved from terrestrial ancestors and readapted limbs for swimming. Birds, including penguins' modified wings, evolved for flight into flippers for underwater propulsion. Convergence in aquatic locomotion produces remarkable similarities between distantly related swimmers. Ichthyosaurs, dolphins, and sharks independently evolved streamlined fusiform bodies, dorsal fins, and tail flukes despite representing reptiles, mammals, and fish, respectively. This convergence reflects physical constraints on efficient aquatic locomotion, where specific body shapes minimize drag. Even the kinematics of swimming show convergence, with similar undulating patterns in flying birds and swimming vertebrates, reflecting fundamental constraints on oscillatory propulsion. Aerial locomotion requires generating lift to support body weight and thrust to overcome drag. Powered flight evolved independently in insects, pterosaurs, birds, and bats through different anatomical modifications. Insect wings are extensions of the body wall supported by veins. Pterosaur wings were membranes supported by elongated fourth fingers. Bird wings are modified forelimbs with feathers providing the airful surface. Bat wings are membranes stretched between elongated fingers. Despite these different implementations, all flying animals converge on similar wing shapes and kinematics because aerodynamics constrains efficient flight. Terrestrial locomotion must support body weight against gravity while generating forward thrust. Walking and running involve alternating periods of stance when feet contact the ground and swing when feet move forward through air. The mechanics vary with size, speed, and skeletal structure. Small animals face relatively high metabolic costs per unit distance traveled because their short limbs require many steps. Large animals move more economically but require stronger skeletal structures to support their weight. The transition from sprawling reptilian posture to erect mammalian posture increased locomotor efficiency by aligning limbs vertically beneath the body, allowing muscles to focus on forward propulsion rather than supporting the body against gravity. Chapter 46. Evolutionary innovations IVISITD. Some evolutionary innovations are so profound that they fundamentally reorganized life and opened entirely new possibilities for complexity and diversity. Endosymbiosis, the incorporation of one organism inside another as an organelle, created eukaryotic cells through the acquisition of mitochondria and chloroplasts. Molecular evolution, at the level of proteins and genes, proceeds at rates that can be quantified through molecular clocks, providing tools for dating evolutionary events. Warning coloration and mimicry create complex coevolutionary dynamics where multiple species converge on similar color patterns. Kin recognition mechanisms allow organisms to identify relatives and preferentially direct cooperation toward them through greenbeard effects. Evolutionary medicine applies evolutionary principles to understand health and disease, revealing why antibiotic resistance evolves and how interventions might slow it. These topics demonstrate that evolution is not merely a historical process, but an ongoing dynamic shaping the biological world at every level, from molecules to ecosystems. Endosymbiotic theory. The endosymbiotic theory proposes that mitochondria and chloroplasts originated as free-living bacteria that were engulfed by host cells and became permanent residents. This radical idea, championed by Lynn Margulies beginning in 1967, initially met skepticism, but is now widely accepted as explaining the origin of eukaryotic cells. The theory revolutionized understanding of cellular evolution by showing that major innovations arose through symbiosis between different organisms rather than gradual modification of a single lineage. Mitochondria evolved from an alpha protobacterium engulfed by an archaeal host cell approximately 1.5 to 2 billion years ago. The engulfed bacterium was an aerobic organism capable of oxidative phosphorylation, a far more efficient energy-generating process than the anaerobic metabolism of the host. Rather than being digested, the bacterium established a symbiotic relationship, providing ATP to the host while receiving nutrients and protection. Over time, most bacterial genes transferred to the host nucleus, with the bacterium becoming an organelle completely dependent on the host. Evidence supporting the bacterial origin of mitochondria includes their double membranes reflecting the engulfment process, their own circular DNA resembling bacterial chromosomes, their ribosomes being bacterial type sensitive to antibiotics that block bacterial translation, and phylogenetic analyses showing mitochondrial genes cluster with alpha protobacteria. The DNA remaining in mitochondria encodes only 13 proteins in humans, with over 1,000 mitochondrial proteins encoded in the nucleus and imported. This extensive gene transfer demonstrates that mitochondria are no longer independent organisms, but integrated components of eukaryotic cells. Chloroplasts evolved through a separate endosymbiotic event when a cyanobacterium was engulfed by a eukaryotic cell that already possessed mitochondria. This primary endosymbiosis occurred approximately 1.6 billion years ago in the ancestor of Archaeplastida, the lineage including land plants and green, red, and glaucophyte algae. Chloroplasts retain more DNA than mitochondria, with genomes encoding approximately 120 proteins. Like mitochondria, chloroplasts have double membranes, circular DNA, bacterial-type ribosomes, and phylogenetic affinity to cyanobacteria. Secondary endosymbiosis occurred when eukaryotic algae were engulfed by other eukaryotes, creating lineages with chloroplasts surrounded by 3 or 4 membranes representing multiple layers of engulfment. This process distributed photosynthesis across diverse eukaryotic lineages, including diatoms, brown algae, and dinoflagellates. The endosymbiotic theory thus explains not only the origin of organelles, but also the complex distribution of photosynthesis across the eukaryotic tree of life. Margulies proposed that flagella also originated through endosymbiosis from spirochete bacteria, but this hypothesis lacks supporting evidence and is not accepted. Molecular clocks. The molecular clock hypothesis proposes that mutations accumulate in DNA sequences at approximately constant rates, allowing molecular differences to measure evolutionary time. If true, comparing DNA or protein sequences between species reveals not just phylogenetic relationships, but also the timing of divergence events. Molecular clocks provide the only method for dating evolutionary events that lack fossil records. The molecular clock hypothesis emerges from neutral theory, which proposes that most genetic variation is selectively neutral. If mutations have no fitness effects, they accumulate at rates determined by mutation rates rather than selection. The rate of neutral substitution equals the mutation rate, which should be relatively constant over time. This predicts that genetic differences between species increase linearly with time since divergence, creating a molecular clock. Empirical studies reveal that molecular clocks are imperfect but useful. Proteins evolve at different rates depending on functional constraints, with highly constrained proteins like histones evolving slowly and less constrained proteins evolving faster. Even within proteins, regions under strong selection evolve slowly, while flexible regions evolve rapidly. Generation time affects clock rates because mutations occur primarily during DNA replication, so species with shorter generations accumulate substitutions faster. Metabolic rate may also affect mutation rates through oxidative damage. Despite these complications, molecular clocks provide valuable dating tools when properly calibrated. Calibration uses fossils to establish divergence times at specific nodes in phylogenies, then extrapolates clock rates to date nodes lacking fossils. Relaxed clock models accommodate rate variation across lineages rather than assuming strict constant rates. These models reveal that approximately 1/3 of clock violations detectable in protein structures are not detectable from sequences, highlighting the value of structural data for detecting evolutionary rate changes potentially driven by positive selection. Clock violations, deviations from constant rates, often correlate with functional changes. Proteins that change function through gaining or losing gene ontology or interpro annotations show stronger clock violations than proteins maintaining constant function. This suggests that evolutionary rate accelerations accompany adaptation to new functions, consistent with positive selection driving rapid evolution during adaptive episodes. Molecular clocks thus provide not just dating tools, but windows into the tempo and mode of evolution, revealing when lineages experienced adaptive radiations or functional innovations. Mimicry and warning coloration. Aposematism, warning coloration that advertises toxicity or unpalatability to predators, creates evolutionary dynamics where multiple species benefit from signaling similarity. Bayesian mimicry occurs when palatable species evolve to resemble toxic models, gaining protection through deception. Mullerian mimicry occurs when multiple toxic species converge on similar warning patterns, sharing the costs of educating predators. These interactions create complex coevolutionary systems involving mimics, models, predators, and signal receivers. Warning coloration benefits toxic prey by allowing predators to learn avoidance without killing the prey. Predators that attack warningly colored prey experience negative consequences through toxins, stings, or bad taste. After a few such experiences, predators learn to avoid the warning signal, benefiting both predator and prey. The evolution of conspicuous coloration seems paradoxical because it makes prey easier to detect, but the benefits of predator learning outweigh the costs of conspicuousness for sufficiently defended prey. Mullerian mimicry evolves when unrelated toxic species converge on similar patterns. Each predator that learns to avoid one species simultaneously learns to avoid all species sharing the pattern. This dilutes predation across all mimics, reducing per capita mortality compared to if each species signaled uniquely. The shared signal also accelerates predator learning because predators encounter the pattern more frequently when multiple species display it. Selection favors mimetic resemblance, driving convergence on common warning patterns. Bayesian mimicry occurs when palatable species evolve resemblance to toxic models. The mimic gains protection without investing in toxin production, a dishonest signal that works only if mimics remain rare relative to models. If mimics become too common, predators encounter them frequently and learn that the pattern does not reliably predict toxicity, eroding the protection. This frequency-dependent selection maintains mimics at low frequency, creating stable polymorphisms where mimetic and non-mimetic forms coexist. The genetic architecture of mimicry often involves supergenes, tightly linked clusters of genes that are inherited as units. These supergenes control multiple aspects of warning patterns, including color, pattern geometry, and behavior. The tight linkage prevents recombination from breaking up co-adapted gene combinations that together produce effective mimicry. The evolution of supergenes demonstrates how selection can shape genome architecture to preserve beneficial gene combinations. Kin recognition and Greenbeard effects. Kin recognition allows organisms to discriminate relatives from non-relatives and preferentially direct cooperation toward kin. This provides a mechanism for the evolution of altruism by ensuring that costly helping behaviors benefit individuals sharing genes with the altruist. The Greenbeard effect, named after a thought experiment by Richard Dawkins, describes situations where recognition and cooperation both depend on the same genetic locus. The Greenbeard gene hypothetically produces three effects: a distinctive phenotype or beard, the ability to recognize that phenotype in others, and preferential cooperation with individuals displaying the phenotype. Individuals carrying the Greenbeard allele display the beard, recognize it in others who carry the allele, and help those individuals. Because the gene causes both the signal and the behavioral response, bearers automatically cooperate with others who share the allele. Empirical examples of Greenbeard effects exist, though they are rare. In side-blotched lizards, orange-blue-yellow color morphs correspond to alternative mating strategies. Blue males recognize and cooperate with other blue males in defending territories cooperatively against orange males. The color locus is linked to genes controlling recognition and cooperative behavior, creating a Greenbeard system. Mapping studies show that self-recognition behavior, recognition of blue color, and the color locus all map to linked genomic regions, demonstrating genetic correlation among the three traits required for greenbeard interactions. Greenbeard systems create cycles of cooperation and defection. Initially, greenbeard alleles spread through populations because bearers cooperate with each other. However, mutations can produce deceptive alleles that display the signal and receive cooperation without reciprocating cheetah greenbeards. These cheetahs exploit cooperators, reducing the value of indiscriminate cooperation. This selects for more stringent recognition systems or conditional cooperation, leading to evolutionary cycles. As cooperation evolves, cheating emerges and counter-strategies develop. Kin recognition more generally allows organisms to direct help toward relatives sharing genes by common descent rather than by shared alleles at a single locus. Recognition mechanisms include learning familiar individuals during development, recognizing matching phenotypes, and detecting similarity at polymorphic genetic markers. These mechanisms allow organisms to measure relatedness and adjust helping behavior accordingly, decreasing help as relatedness decreases. Understanding kin recognition mechanisms reveals how organisms solve the problem of identifying appropriate recipients for altruism, maintaining cooperation despite incentives to cheat. Evolutionary medicine and antibiotic resistance. Evolutionary medicine applies evolutionary principles to understanding health and disease. One crucial application addresses antibiotic resistance, one of the greatest threats to modern medicine. Bacteria evolve resistance to antibiotics through mutations and horizontal gene transfer, creating populations of pathogens that antibiotics cannot eliminate. Understanding the evolutionary dynamics of resistance can inform strategies to slow its spread. Antibiotic use creates strong selection for resistance by eliminating susceptible bacteria while allowing resistant mutants to proliferate. In the absence of antibiotics, resistance alleles often impose fitness costs because resistance mechanisms like efflux pumps or target modifications require energy or reduce efficiency. These costs prevent resistant strains from dominating in the absence of selection. However, antibiotic exposure reverses selection, making resistance highly beneficial. The result is classic balancing selection, where resistance frequency increases during antibiotic use and decreases in its absence. Hygiene practices can attenuate the relationship between antibiotic use and resistance evolution. Meta-community theory predicts that hygiene limits the ecological response to antibiotic treatment by altering community structure and competitive dynamics. Good hygiene reduces pathogen transmission between individuals, decreasing infection rates and antibiotic usage. Hygiene also prevents the spread of resistant strains between hosts, maintaining isolated communities where resistance that evolves locally does not spread globally. Data from European countries show that hygiene improvements weaken the correlation between antibiotic consumption and resistance prevalence, supporting the hypothesis that hygiene and antibiotics interact to determine resistance dynamics. Biofilm growth, where bacteria form structured communities attached to surfaces, affects resistance evolution differently than planktonic growth in well-mixed liquid cultures. Biofilms generate greater genetic diversity than planktonic cultures because spatial structure reduces competition between genotypes, allowing multiple variants to coexist. The evolutionary pathways to resistance depend on environmental structure, with biofilms exploring different mutational paths than planktonic populations. Understanding how environmental structure affects evolution can guide treatment strategies, perhaps using spatial structure to limit resistance evolution or alternating treatments to exploit trade-offs between resistance mechanisms. The evolutionary perspective reveals that resistance is inevitable given sufficient antibiotic use, but its rate can be managed through judicious antibiotic stewardship, hygiene practices, and treatment protocols informed by evolutionary principles. Evolutionary medicine transforms how we view disease from a static condition to a dynamic evolutionary process, recognizing that pathogens continuously adapt and that sustainable medicine requires strategies that account for evolution rather than ignoring it. Chapter 47, Teoianesephoamations and Ionovations. Life has evolved remarkable developmental strategies and physiological capabilities that allow organisms to exploit resources and environments in novel ways. Insect metamorphosis represents one of the most dramatic transformations in nature, with organisms completely reorganizing their bodies between larval and adult stages through hormonal control. Plants synthesize thousands of secondary metabolites, including alkaloids, terpenes, and phenolics, that serve defensive functions against herbivores and pathogens, while also providing pharmaceutical compounds for human medicine. Venom has evolved independently dozens of times across the animal kingdom, with snakes, spiders, scorpions, and other venomous creatures using toxins for prey capture and defense. Sleep, particularly the distinct states of REM and non-REM sleep, appears nearly universal among animals with nervous systems, though its evolutionary origins and functions remain debated. These innovations demonstrate evolution's creativity in solving biological challenges through molecular, physiological, and developmental mechanisms that fundamentally alter what organisms can do and where they can live. Insect metamorphosis. Metamorphosis, the dramatic transformation from larva to adult through intermediate stages, evolved in insects approximately 350 million years ago and has contributed to their spectacular diversity with over 1 million described species. Two major forms exist: incomplete metamorphosis, where nymphs resemble miniature adults and gradually acquire adult features through successive molts, and complete metamorphosis, where larvae differ radically from adults and transform through a pupal stage. Complete metamorphosis, or holometaboly, characterizes approximately 85% of insect species, including beetles, flies, butterflies, and bees. Larvae are specialized for feeding and growth, often with entirely different diets and habitats than adults. Caterpillars consume leaves, while adult butterflies drink nectar. Maggots eat decaying matter, while adult flies feed on liquids. This ecological separation eliminates competition between juveniles and adults, allowing both stages to specialize. The evolution of complete metamorphosis involved modifications to hormonal regulation during embryonic development. Juvenile hormone suppresses development of adult characteristics. In insects with incomplete metamorphosis, juvenile hormone is absent during embryogenesis, allowing embryos to develop into nymphs that resemble miniature adults. In complete metamorphosis, juvenile hormone appears early in embryogenesis and remains elevated throughout larval stages, suppressing adult development and promoting larval-specific features. The larval stage represents a profound alteration of the ancestral developmental program. During the evolution of holometaboly, embryogenesis was altered to produce a larval body plan rather than progressing directly toward the adult form. The larva becomes dedicated entirely to growth, molting multiple times while increasing in size but not developing adult structures. When the larva reaches a critical size threshold, juvenile hormone levels drop, triggering metamorphosis. The pupal stage, unique to holometabolous insects, is a non-feeding stage during which larval tissues are broken down and adult structures develop. Imaginal discs, groups of cells set aside during embryogenesis, proliferate and differentiate during pupation to form adult structures including wings, legs, compound eyes, and reproductive organs. Much of the larval body is histolized through programmed cell death, with nutrients recycled to fuel construction of adult tissues. This radical reorganization requires approximately 1 to 2 weeks in many species, though duration varies enormously. The success of holometabolous insects demonstrates the power of developmental innovations. By decoupling larval and adult stages, complete metamorphosis allowed insects to exploit resources unavailable to hemimetabolous insects. Larvae could evolve specialized feeding structures and behaviors without constraints imposed by adult requirements. Adults could evolve flight, complex sensory systems, and reproductive structures without carrying feeding-related baggage. This developmental innovation opened ecological opportunities that drove an adaptive radiation, producing the majority of described animal species. Plant secondary metabolites. Plants synthesize over 100,000 secondary metabolites, organic compounds not directly involved in growth, development, or reproduction, but serving specialized ecological functions. Unlike primary metabolites including carbohydrates, proteins, and lipids that are essential for basic cellular processes, secondary metabolites are often produced by specific lineages in response to particular ecological challenges. The major classes include terpenes, phenolics, and alkaloids, each comprising thousands of compounds. Terpenes constitute the largest group of plant secondary metabolites with approximately 25,000 known compounds. Synthesized from isoprene units, terpenes range from volatile monoterpenes and sesquiterpenes to larger diterpenes, triterpenes, and polyterpenes. Volatile terpenes emitted from damaged tissues serve multiple defensive functions. They directly deter herbivores through toxicity or repellent properties. They attract predators and parasitoids that attack herbivores, recruiting bodyguards. They warn neighboring plants, triggering preemptive defense. Many terpenes exhibit direct toxicity to herbivores by disrupting cellular processes. Pyrethrins from chrysanthemums interfere with sodium channels in insect neurons, causing paralysis and death. Humans exploit this property in pyrethroid insecticides. Gossypol from cotton disrupts mitochondrial function and inhibits digestive enzymes, deterring many herbivores. Some herbivores have evolved resistance mechanisms, including detoxification enzymes that break down terpenes or modified target sites that are less sensitive to toxins. Phenolic compounds including flavonoids, tannins, and lignins serve defensive and structural roles. Tannins bind proteins, reducing digestibility of plant tissues and making them less nutritious to herbivores. Condensed tannins form complexes with plant proteins in the herbivore digestive tract, rendering the proteins unavailable for absorption. Some herbivores produce tannin-binding proteins in saliva that neutralize this defense. Lignin strengthens cell walls, making plant tissues physically tougher and more difficult to chew or digest. Alkaloids are nitrogen-containing compounds that interfere with animal nervous systems. Approximately 20% of plant species produce alkaloids. Nicotine from tobacco binds nicotinic acetylcholine receptors, disrupting neurotransmission in insects. At low doses, nicotine acts as a stimulant, at high doses as a poison. Caffeine inhibits insect feeding and is toxic at high concentrations. Morphine from poppies binds opioid receptors in mammals, providing powerful analgesic effects humans exploit medicinally. These alkaloids defend plants while also serving as sources of pharmaceutical drugs. The evolution of plant secondary metabolites reflects coevolution with herbivores in an ongoing chemical arms race. Plants evolve novel defensive compounds or increase concentrations of existing defenses. Herbivores evolve counter-adaptations, including detoxification enzymes, modified target sites, or sequestration mechanisms that store plant toxins and reuse them for the herbivore's own defense. This reciprocal evolution drives chemical diversity, with related plant species often producing distinct secondary metabolite profiles, reflecting independent evolutionary trajectories in response to different herbivore pressures. Venom evolution. Venom, toxic secretions delivered through specialized structures for prey capture or defense, has evolved independently at least 100 times across the animal kingdom. Venomous animals include snakes, lizards, spiders, scorpions, centipedes, fish, mollusks, and even a few mammals. The repeated evolution of venom demonstrates strong selective advantages for organisms that can subdue prey or deter predators through chemical means. Snake venom evolution is driven by dietary specialization and predator-prey coevolution. Venom proteins evolved through gene duplication of genes encoding normal physiological proteins, followed by neofunctionalization, where duplicated copies acquired new toxic functions. Many venom toxins are modified versions of proteins originally involved in digestion, blood clotting, or immune function. Three-finger toxins evolved from secreted proteins that bind cell surface receptors. Phospholipases that normally metabolize membrane lipids were co-opted as toxins that destroy cell membranes. The composition and toxicity of snake venom varies dramatically between species, reflecting different ecological niches and diets. Elapid snakes, including cobras and krites, produce primarily neurotoxic venoms rich in alpha neurotoxins that block neuromuscular transmission by binding acetylcholine receptors. This causes paralysis, preventing prey from escaping and quickly immobilizing dangerous prey that might injure the snake. Viper venoms are primarily hemotoxic, containing enzymes that disrupt blood clotting, destroy blood vessels, and cause tissue necrosis. These venoms may digest prey tissues, facilitating digestion. Venom delivery systems have evolved remarkable diversity through convergent evolution. Tubular fangs for injecting venom deep into prey evolved independently in vipers, elapids, and atractaspidine snakes. These hollow teeth connect to venom glands and function like hypodermic needles. Rear-fanged snakes have grooved teeth that channel venom into wounds during chewing. The independent evolution of similar fang structures demonstrates that natural selection converges on effective solutions to the engineering challenge of venom delivery. Spider venom toxins show deep evolutionary origins dating to before the diversification of major spider lineages. Nearly all spiders rely on disulfide-rich peptides, small proteins stabilized by multiple disulfide bonds between cysteine residues. This reliance on a single molecular scaffold contrasts with most venomous animals that have recruited diverse toxins with independent origins. The conservatism of spider venom architecture suggests that the basic DRP toxin scaffold evolved early in spider evolution and proved so effective that spiders never abandoned it despite 250 million years of evolution. Contrasting evolutionary rates characterize venom in different lineages. Centipede and spider venoms evolve slowly despite long evolutionary histories, showing high conservation of toxin sequences. Snake and lizard venoms evolve rapidly, with toxin genes showing strong signatures of positive selection. These contrasting strategies may reflect different ecological pressures. Ancient lineages with stable ecology may maintain effective venoms without requiring rapid innovation. Younger lineages facing novel prey or intense predator-prey coevolution may require rapid venom diversification to maintain effectiveness against evolving prey defenses. Sleep and its evolution. Sleep, a reversible behavioral state characterized by reduced responsiveness to external stimuli and stereotype postures, appears in all animals with nervous systems examined to date. Even organisms as simple as nematodes and fruit flies exhibit sleep-like states with similar molecular regulation. This phylogenetic distribution suggests sleep evolved early in animal evolution and serves fundamental functions conserved across vast evolutionary distances. Mammals and birds exhibit two distinct sleep states: non-REM sleep characterized by slow synchronized brain waves and REM sleep characterized by rapid eye movements, muscle atonia, and brain activity resembling waking. These states alternate cyclically through the sleep period. Non-REM sleep appears more ancient, with features present in all vertebrates and possibly invertebrates. REM sleep may be a more recent innovation specific to amniotes. The evolutionary origin of REM and non-REM sleep remains debated. One hypothesis proposes sequential evolution, where non-REM sleep evolved first and REM sleep later differentiated from non-REM. An alternative hypothesis suggests both states evolved simultaneously as differentiation of a primitive unified sleep state. Studies in the echidna, a monotreme mammal, provide evidence for the simultaneous differentiation hypothesis. Echidnas show non-REM sleep, but either lack REM sleep or exhibit only rudimentary REM-like features, suggesting monotremes diverged before full differentiation of sleep states. Phylogenetic correlates of sleep duration reveal ecological influences on sleep evolution. Mammals with safe sleeping sites sleep longer than those vulnerable to predation. Altricial mammals born immature and helpless exhibit more REM sleep than precocial mammals born mature and mobile. High amounts of non-REM sleep correlate with high REM sleep across species. These patterns suggest sleep evolved under competing selective pressures, balancing the benefits of sleep against vulnerability. The functions of sleep remain incompletely understood despite its universal presence. Memory consolidation occurs during sleep, with learning-related neural patterns replayed during sleep, particularly REM sleep. Metabolic regulation and energy conservation may explain some sleep functions, with reduced activity during sleep-conserving resources. Synaptic homeostasis proposes that sleep allows synapses strengthened during waking to be pruned, preventing runaway synaptic strengthening. Clearance of metabolic waste products, including beta-amyloid from the brain, occurs more efficiently during sleep. Sleep likely serves multiple functions, with different sleep states contributing differently. Recent identification of genes regulating sleep provides molecular insights into sleep evolution. The SIC3 gene regulates non-REM sleep duration across species from nematodes to mammals. Loss of function decreases total sleep time in flies, nematodes, and mice. The conservation of this gene and its function across such vast phylogenetic distances indicates that non-REM sleep, or a precursor state, is an evolutionarily ancient feature. The molecular conservation contrasts with behavioral and electrophysiological diversity of sleep across animals, suggesting that core molecular mechanisms are conserved even as behavioral manifestations diverge. Chapter 48: Social Evolution and Specialization. The evolution of social behavior represents one of life's major transitions, producing organisms that function as integrated superorganisms. Eusociality, the most complex form of social organization, involves overlapping generations, cooperative brood care, and reproductive division of labor with sterile castes. This extreme form of cooperation evolved independently multiple times in insects, including all ants, all termites, many bees, and some wasps, as well as in a few mammals. Regeneration, the ability to regrow lost body parts or even entire organisms from fragments, exists in diverse lineages and involves stem cells capable of differentiating into multiple cell types. Thermoregulation, the maintenance of body temperature within optimal ranges, varies between ectotherms that rely on external heat sources and endotherms that generate heat metabolically. Sensory ecology explores how organisms perceive their environments through sensory systems shaped by evolution to detect stimuli relevant to fitness. These topics reveal how organisms have evolved mechanisms for cooperation, regeneration, physiological homeostasis, and environmental perception that expand life's possibilities. Eusociality and sterile castes. Eusociality represents the pinnacle of social evolution, characterized by reproductive division of labor, where most individuals in a colony are sterile workers that rear the offspring of reproductive individuals. This social organization poses an evolutionary puzzle. Why do individuals forgo personal reproduction to help others reproduce? Understanding eusocial evolution requires explaining how sterility can be favored by natural selection. Haplodiploidy, the genetic system where females are diploid and males haploid, was long thought to predispose lineages toward eusociality. Female Hymenoptera, including ants, bees, and wasps, are diploid with 2 sets of chromosomes, while males are haploid with 1 set. This creates asymmetries in relatedness. Sisters share 3/4 of their genes, on average, rather than the 1/2 typical of diploid organisms. Hamilton's rule predicts cooperation evolves when the benefit to recipients multiplied by relatedness exceeds the cost to the helper. Higher relatedness between sisters theoretically favors helping sisters over producing one's own offspring. However, haplodiploidy is neither necessary nor sufficient for eusociality evolution. Eusociality occurs without haplodiploidy in termites, aphids, beetles, shrimp, and naked mole rats, all diploid organisms. Haplodiploidy occurs in 92 families across 7 insect orders, but eusociality co-occurs with haplodiploidy in only 7 families. Many haplodiploid lineages never evolved eusociality. This demonstrates that haplodiploidy may facilitate, but does not cause eusocial evolution. Termite eusociality evolved through different mechanisms than hymenopteran eusociality. Termites are diploid, with both males and females contributing to worker and soldier castes. Kings remain with queens throughout their lives, continuously fertilizing queens as colonies grow. This contrasts with hymenoptera, where males die after mating. Termite soldiers defend colonies against predators, particularly ants. The evolution of the soldier caste likely involved strong selection from intraspecific competition and predation pressure, with colonies possessing effective defenders outcompeting those without. Ecological factors, including nest requirements, extended parental care, and monogamy appear crucial for eusocial evolution. Many eusocial species require elaborate nests that represent substantial investments, creating incentives for offspring to remain and inherit rather than dispersing. Extended parental care, requiring extended cohabitation of parents and offspring, provides opportunities for offspring to help raise siblings. Lifetime monogamy ensures high relatedness among offspring, making helping siblings genetically equivalent to producing offspring. These ecological and life history factors, combined with genetic structure, create conditions favoring eusocial evolution. Eusocial colonies function as superorganisms with division of labor analogous to division of labor among cells in multicellular organisms. Workers specialize in different tasks, including foraging, brood care, nest maintenance, and defense. This specialization increases efficiency compared to generalist workers attempting all tasks. The queen specializes exclusively in reproduction, often laying thousands of eggs daily. Soldiers in termites and some ants possess enlarged heads and mandibles for defense. The integration of specialized castes creates colonies capable of achievements impossible for solitary individuals. Regeneration and stem cells. Regeneration, the ability to replace lost body parts, varies dramatically across animal lineages, from minimal regenerative capacity in mammals to extraordinary regenerative abilities in planarians that can regrow entire organisms from tiny fragments. Understanding the mechanisms enabling regeneration may inform strategies for therapeutic regeneration in humans where regenerative capacity is limited. Planarians, free-living flatworms, exemplify extreme regenerative capacity. A planarian can be cut into dozens of pieces, and each piece will regenerate a complete organism. This requires adult pluripotent stem cells called neoblasts that can differentiate into all cell types. Neoblasts are the only dividing cells in adult planarians, with all other cells post-mitotic. Following injury, neoblasts proliferate and migrate to wound sites where they differentiate into missing tissues. The regeneration process involves precisely coordinated events. Immediately after injury, wound closure occurs through contraction and formation of a transient wound epithelium. Neoblasts proliferate extensively, forming a regeneration blastoma, a mass of proliferating stem cells at the amputation site. Patterning signals instruct blastoma cells about their position and what structures to form. Brain regeneration requires different signals than tail regeneration. Differentiation proceeds as neoblasts produce specialized cell types organized into functional organs. The entire process completes within 1 to 2 weeks. Salamanders among vertebrates retain impressive regenerative capacity, including the ability to regrow entire limbs, tails, jaws, hearts, and even portions of eyes and brain. Limb regeneration involves dedifferentiation, where specialized cells near the amputation site lose their specialized character and become proliferative progenitor cells. These cells form a blastoma similar to that in planarians. Patterning mechanisms re-establish positional information, ensuring the regenerating limb develops correct structures in correct locations. Redifferentiation produces bone, muscle, nerve, and connective tissue organized into a functional limb. Most mammals, including humans, have limited regenerative capacity, generally restricted to liver regeneration and wound healing. The liver can regrow to original size even after losing 70% of its mass, achieved through proliferation of remaining hepatocytes rather than stem cell-mediated regeneration. Wound healing in mammals typically produces scar tissue rather than perfect regeneration, with collagen-rich scars lacking the original tissue architecture. The limited mammalian regenerative capacity likely reflects trade-offs. The immune system that provides effective pathogen defense may suppress regeneration by creating inflammatory responses that promote scarring. The metabolic demands of endothermy may constrain resources available for regeneration. The relationship between regeneration and the immune system appears ancient, present in basal bilaterians. Planarians possess innate immune system components that are activated during injury and regeneration. The interplay between immune responses and regenerative signals remains incompletely understood, but appears critical for coordinating tissue repair. Understanding these interactions could inform strategies for promoting scar-free healing in mammals by modulating immune responses to support regeneration rather than fibrosis. Thermoregulation strategies. Thermoregulation, the maintenance of body temperature within optimal ranges, employs fundamentally different strategies in ectotherms and endotherms. These strategies involve different physiological mechanisms, metabolic costs, and ecological implications. The distinction between ectothermy and endothermy represents one of the major physiological dichotomies in animal biology. Ectotherms regulate body temperature primarily through behavioral mechanisms rather than metabolic heat production. Lizards bask in sunlight to warm up, retreat to shade to cool down, and adjust body orientation to regulate heat absorption. Many ectotherms select microhabitats with favorable thermal properties. Temperature-sensitive circadian mechanisms allow ectotherms to anticipate daily temperature cycles and adjust behavior preemptively. While ectotherms do not actively generate heat, they are not passive with respect to temperature. Behavioral thermoregulation allows precise control of body temperature when appropriate microclimates are available. Endotherms generate heat metabolically and regulate body temperature through physiological mechanisms. Metabolic heat production occurs continuously from cellular respiration, with brown adipose tissue specialized for heat generation through uncoupled respiration, where energy is released as heat rather than stored in ATP. Shivering thermogenesis generates heat through involuntary muscle contractions. Vasomotor responses regulate heat loss. Vasoconstriction in cold reduces blood flow to skin, minimizing heat loss, while vasodilation in heat increases skin blood flow, enhancing heat dissipation. Evaporative cooling through sweating or panting allows heat loss exceeding that possible through other mechanisms. The costs and benefits of endothermy versus ectothermy create different ecological constraints. Endotherms maintain high stable body temperatures, enabling activity across wide environmental temperature ranges, supporting complex behaviors and high aerobic capacity. However, endothermy requires approximately 10 times more food than ectothermy to fuel metabolic heat production. Ectotherms are energetically efficient but behaviorally constrained by environmental temperature, becoming sluggish or inactive when cold. These trade-offs shape ecological distributions, with endotherms dominating high latitudes where stable body temperature allows year-round activity, while ectotherms dominate warm regions where behavioral thermoregulation suffices. Body temperature affects longevity in both endotherms and ectotherms, with lower temperatures generally associated with longer lifespans. In ectotherms, this relationship likely reflects the temperature dependence of biochemical reaction rates, with lower temperatures slowing metabolic processes, including accumulation of molecular damage. In endotherms, the relationship is more complex because body temperature is actively regulated. Nevertheless, species with lower body temperatures tend to live longer, suggesting that reduced metabolic rate, even in endotherms, benefits longevity. Sensory ecology. Sensory ecology examines how variation in sensory systems influences animal behavior and evolution. The concept of Umwelt, the perceptual world unique to each species, recognizes that different organisms experience fundamentally different sensory realities. Understanding the Umwelt of study species is essential for understanding their behavior, ecology, and evolution. Sensory systems evolve under trade-offs between sensitivity, specificity, and energetic cost. High-sensitivity detection systems that respond to faint stimuli require amplification mechanisms and signal processing that consume energy. Specific systems that discriminate stimuli precisely require complex receptor arrays and neural processing. Organisms cannot optimize all sensory modalities simultaneously and must allocate limited resources among competing sensory demands. Phylogenetic, developmental, and allocation trade-offs constrain sensory evolution. Adaptation to different environments drives sensory system divergence. Nocturnal animals evolve enhanced low-light vision through enlarged eyes, more photoreceptors, and neural summation that amplifies weak signals. Aquatic animals evolve chemosensory systems tuned to waterborne molecules, while terrestrial animals detect airborne chemicals. Underground species lose visual systems while enhancing tactile and chemosensory modalities. These environment-specific adaptations demonstrate that sensory systems evolve to match the information available in different habitats. Behavioral plasticity depends on sensory integration, the ability to combine information from multiple sensory modalities. In complex environments, optimal decisions require integrating numerous stimuli. Multidimensionality complicates both organismal responses and scientific investigation. Understanding how organisms weight different sensory inputs and integrate them to guide behavior remains a major challenge in sensory ecology. The complexity of sensory integration means that subtle differences in sensory capabilities can produce large differences in behavioral outcomes and fitness. Sensory ecology increasingly incorporates evolutionary considerations. Phylogenetic constraints limit which sensory systems can evolve in different lineages. Developmental constraints affect sensory system organization. Evolutionary history shapes current sensory capabilities through path dependence, where present possibilities are constrained by past evolutionary decisions. Considering these evolutionary factors provides deeper understanding of why organisms sense their environments in particular ways and how sensory systems have diversified across the tree of life. The field of sensory ecology thus integrates mechanistic sensory biology with evolutionary theory to explain the spectacular diversity of ways organisms perceive and respond to their worlds. Chapter 49: Ecological Patterns. The distribution and abundance of species across landscapes reveal fundamental ecological principles that have shaped evolution. Island biogeography theory demonstrates how area and isolation determine species richness through balancing colonization and extinction rates. Host-parasite coevolution creates arms races where both parties continually adapt to each other, sometimes producing red queen dynamics where populations must evolve constantly just to maintain fitness. Life history strategies represent alternative solutions to the fundamental trade-off between reproduction and survival, with R-selected species favoring quantity of offspring and K-selected species favoring quality. Animals construct elaborate architectures, including nests, webs, and burrows, through both instinctive programs and learned behaviors. These patterns reveal that evolution operates not just on individual organisms, but on populations distributed across space and interacting with other species in complex ecological networks. Understanding these ecological patterns provides insight into community assembly, species coexistence, and the factors limiting biodiversity. Island biogeography theory. Island biogeography theory, developed by Robert MacArthur and Edward Wilson in the 1960s, explains patterns of species richness on islands through dynamic equilibrium between colonization and extinction. The theory applies not just to oceanic islands, but to any isolated habitat patches, including mountaintops, lakes, and forest fragments. The fundamental insight is that species richness results from ongoing turnover, with species continually arriving and going extinct, rather than representing a static assemblage. The species-area relationship describes how larger islands support more species than smaller islands. This pattern appears consistently across taxonomic groups and geographic regions. Several mechanisms generate the species-area relationship. Larger islands contain more habitat types and greater environmental heterogeneity, supporting species with different ecological requirements. Larger areas support larger populations, reducing extinction probability from demographic stochasticity. Target effects mean larger islands present bigger targets for dispersing organisms, experiencing higher colonization rates. More evolutionary diversification occurs on larger islands, where topographic complexity creates opportunities for allopatric speciation within islands. The species isolation relationship shows that isolated islands support fewer species than near islands of similar size. Distance from mainland sources affects colonization rates, with fewer propagules reaching distant islands. Low immigration rates prevent far islands from attaining the equilibrium species richness of near islands. Isolated islands also have lower habitat diversity in some cases. The rescue effect operates on near islands where immigration from the mainland or nearby islands prevents local extinctions by supplementing declining populations, while isolated islands lack this demographic subsidy. The equilibrium theory predicts that species richness reaches dynamic equilibrium, where immigration rate equals extinction rate. At equilibrium, species number remains approximately constant, even though identity changes as some species go extinct and others colonize. Immigration rate decreases as islands fill with species because arriving individuals increasingly belong to species already present. Extinction rate increases with species number due to smaller average population sizes as resources are divided among more species. The intersection of immigration and extinction curves determines equilibrium species richness. Different islands reach different equilibria depending on size and isolation. Large near islands have high colonization rates and low extinction rates, supporting the highest equilibrium richness. Small distant islands have low colonization rates and high extinction rates, supporting few species. Large distant islands and small near islands represent intermediate cases. These predictions have been tested extensively and generally supported, though violations occur when other factors, including habitat quality, disturbance regimes, or evolutionary processes, dominate. Host-parasite coevolution. Host-parasite interactions create some of the strongest reciprocal selection pressures in nature, driving rapid coevolution. Hosts evolve resistance to parasites, while parasites evolve counter-adaptations to overcome resistance. This antagonistic coevolution can produce two distinct dynamics: arms races, where successive mutations conferring resistance or virulence sweep through populations, or red queen dynamics, where allele frequencies cycle due to frequency-dependent selection. The distinction between arms race and red queen dynamics depends on the pattern of genotype by genotype interactions. Arms races occur when genetic variation for resistance and infectivity affects fitness without crossing reaction norms, meaning some host genotypes are universally resistant and some parasite genotypes universally infective. In this case, resistance alleles sweep to fixation, followed by virulence alleles that overcome resistance, followed by new resistance alleles in an escalating spiral. Red queen dynamics occur when reaction norms cross, meaning no host genotype is universally resistant and no parasite genotype is universally infective. Each host genotype is resistant to some parasites but susceptible to others. This produces negative frequency-dependent selection where rare genotypes have advantages, maintaining genetic variation and causing cyclical fluctuations. Empirical studies reveal both patterns in natural systems. The dinoflagellate host Alexandrium minutum and its parasite Parvoluciferous cinerea show strong genotype by genotype interactions for infection success and fitness. About 3/4 of the interaction variance is due to crossing reaction norms, indicating high potential for red queen dynamics. Each host genotype was successfully infected by 4 to 10 of the tested parasite genotypes, demonstrating specificity. Importantly, there were no general costs of resistance or infectivity, contradicting the assumption that resistance and virulence impose fitness costs in the absence of the interaction. The Red Queen hypothesis proposes that sexual reproduction is maintained because genetic recombination allows hosts to generate novel genotype combinations that parasites have not adapted to. Asexual lineages produce genetically identical offspring that parasites can specialize on, while sexual reproduction continuously creates new combinations. This hypothesis explains why most eukaryotes reproduce sexually despite the twofold cost of producing males. The hypothesis gains support from observations that parasites are more successful infecting common host genotypes, creating rare genotype advantage that favors sexual reproduction. Evolutionary trade-offs between transmission and virulence shape parasite evolution. Highly virulent parasites that rapidly kill hosts may have reduced transmission opportunities if the host dies before transmitting the parasite. This selects for intermediate virulence that balances exploitation rate against host lifespan. However, if transmission occurs before host death, or if dead hosts transmit parasites, selection may favor high virulence. The evolution of virulence thus depends on specific transmission modes and life history characteristics. Life history strategies. Life history theory examines how organisms allocate limited resources among competing demands, including growth, maintenance, reproduction, and survival. The fundamental insight is that organisms face trade-offs where investment in one function reduces resources available for others. These trade-offs generate alternative life history strategies adapted to different ecological conditions. The RK selection continuum describes a major axis of life history variation. R-selected species are adapted to unstable or ephemeral environments where population density is usually below carrying capacity. Selection favors rapid growth, early maturity, high reproductive rate, many small offspring, and minimal parental care. R-selected organisms are essentially opportunists that rapidly exploit resources when available. Examples include bacteria, weeds, insects, and small mammals like mice. K-selected species are adapted to stable environments where populations remain near carrying capacity and competition is intense. Selection favors slow growth, delayed maturity, low reproductive rate, few large offspring, and extensive parental care. K-selected organisms invest in competitive ability and offspring quality rather than quantity. Examples include elephants, whales, redwood trees, and humans. The name K-selection comes from the carrying capacity parameter K in logistic growth models. Modern life history theory recognizes that the RK continuum oversimplifies life history diversity. Organisms exhibit complex mosaics of traits that do not align perfectly along a single axis. Nevertheless, the RK framework remains useful for understanding major patterns. Life history strategies evolve in response to mortality schedules. High adult mortality favors early reproduction before death occurs, selecting for R traits. Low adult mortality allows delayed reproduction with larger body size and greater competitive ability, selecting for K traits. Trade-offs between current and future reproduction constrain life history evolution. Resources allocated to current reproduction are unavailable for growth, maintenance, or future reproduction. Reproducing early increases current fitness but may reduce future survival or reproductive capacity. Reproducing late allows greater growth and potentially more total offspring, but risks death before reproduction. The optimal allocation depends on mortality schedules, with high extrinsic mortality favoring early reproduction and low mortality favoring delayed reproduction. Parental investment varies dramatically across species as part of life history strategies. R-selected species produce many offspring with minimal investment per offspring, relying on sheer numbers to ensure some survive. K-selected species produce few offspring with substantial investment, including extended gestation, lactation in mammals, provisioning of young, and teaching of behaviors. The optimal investment per offspring depends on offspring survival returns. When parental investment greatly improves offspring survival, quality strategies are favored. When offspring survival is largely independent of parental investment, quantity strategies prevail. Animal architecture. Animals construct diverse structures including nests, webs, burrows, dams, and hives that modify environments and provide shelter, breeding sites, and prey capture devices. These constructions represent extended phenotypes, expressions of genes that extend beyond the organism's body to affect the environment. The evolution of construction behavior demonstrates how selection can shape complex behaviors producing sophisticated structures. Bird nests exemplify diverse architectural solutions to similar problems. Cup nests, constructed by songbirds, involve weaving plant materials into bowl-shaped structures that support eggs and nestlings. The construction sequence follows stereotyped patterns with variations reflecting species-specific adaptations. Birds of prey, including eagles and hawks, build massive platform nests called eyries atop trees or cliffs, using sticks and branches to create structures that may weigh hundreds of kilograms and be reused for years. Waterfowl create scrapes, shallow depressions lined with down feathers that provide insulation for eggs. The construction behavior is primarily innate rather than learned. Birds raised in isolation build species-typical nests without observing nest construction, demonstrating that the behavioral program is genetically encoded. However, experience improves construction efficiency and quality. First-time builders produce functional but crude nests, while experienced individuals construct refined nests more quickly. This suggests innate templates guide construction, with learning improving execution. Spider webs demonstrate instinctive architectural programs producing species-specific designs. Orb-weaver spiders construct radial webs with spoke-like threads radiating from a central hub and spiral threads connecting the spokes. The construction sequence is highly stereotyped, with spiders following fixed behavioral algorithms. Different spider species build recognizably different web architectures even when reared in isolation, proving the design is genetically encoded. Remarkably, some parasitic wasps manipulate spider web-building behavior, causing spiders to build abnormal webs, serving as cocoons for wasp larvae rather than prey capture devices. Burrows provide shelter from predators and environmental extremes. Prairie dogs excavate complex burrow systems with multiple entrances, sleeping chambers, and latrine areas. The architecture provides thermoregulation with stable temperatures despite extreme surface conditions, protection from predators through multiple escape routes, and social spaces for colonies. The construction is partly innate and partly learned, with young prairie dogs instinctively digging but learning burrow organization from colony members. The evolution of construction behavior involves selection on multiple levels. Individual selection favors constructions that improve builder fitness through enhanced survival or reproduction. The ability to construct effective shelters or prey capture devices is heritable, allowing selection to refine construction programs across generations. Gene culture coevolution may occur when learned improvements are transmitted socially, creating feedback between genetic and cultural evolution. The extended phenotype concept recognizes that animal constructions are as much expressions of genes as morphological traits, subject to the same evolutionary processes. Chapter 50: Adaptation and Variation. Adaptation occurs through diverse mechanisms operating at multiple scales, from genes to populations. Gene flow, the movement of genes between populations through migration and interbreeding, counteracts genetic differentiation and local adaptation, while also spreading beneficial mutations. Phenotypic plasticity allows single genotypes to produce multiple phenotypes in response to environmental variation, with polyphenism representing extreme cases where discrete alternative phenotypes develop. Photosynthesis evolved multiple times and in multiple forms, including C3, C4, and CAM pathways, representing adaptations to different environmental conditions. Biological rhythms synchronized to tidal and lunar cycles allow organisms to anticipate predictable environmental changes. Mutualistic networks connecting plants with pollinators and seed dispersers show nested architecture where specialists interact with subsets of the species used by generalists. These mechanisms demonstrate that adaptation is not a simple process of organisms matching environments, but rather involves complex interactions between genes, development, ecology, and evolution across multiple timescales. Gene flow and barriers. Gene flow is the transfer of genetic variation between populations through movement of individuals or gametes. Gene flow homogenizes populations by spreading alleles, counteracting differentiation caused by drift and local selection. The balance between gene flow and local selection determines whether populations remain unified or diverge. High gene flow prevents local adaptation because migrants introduce maladaptive alleles. Low gene flow allows populations to adapt to local conditions, but increases extinction risk through inbreeding and genetic drift. Barriers to gene flow are factors that reduce migration between populations, allowing differentiation. Physical barriers including mountains, rivers, and unsuitable habitat prevent movement. Behavioral barriers including differences in mate choice or breeding timing prevent interbreeding. Genetic incompatibilities reduce hybrid fitness, creating intrinsic barriers. Barriers can be detected through genetic analysis when populations on opposite sides show greater differentiation than expected from isolation by distance alone. Isolation by distance describes the pattern where genetic similarity decreases with geographic distance in continuously distributed populations. Individuals exchange genes primarily with nearby individuals, creating spatial genetic structure. Barriers distort this pattern. Populations on opposite sides of a barrier are more differentiated than their geographic distance alone predicts, while populations on the same side near the barrier are more similar than expected. Statistical methods can detect barriers from genomic data by identifying deviations from isolation by distance patterns. Isolation by adaptation occurs when gene flow is reduced between populations occupying ecologically dissimilar habitats due to selection against migrants. Individuals migrating to different habitats have reduced fitness because they carry alleles adapted to their natal environment. This creates effective isolation proportional to ecological difference rather than geographic distance, producing isolation by environment where genetic differentiation correlates with environmental dissimilarity. Recent reviews suggest isolation by adaptation is as common as isolation by dispersal limitation in structuring natural populations. The detectability of barriers depends on population size, generation time, and time since barrier formation. Large populations with long generation times show genetic signatures of barriers more slowly than small populations with short generations. Populations continue experiencing gene flow immediately after barrier formation, with genetic differentiation accumulating gradually. Analyses of species with large populations and long lifespans may fail to detect recent barriers because insufficient time has elapsed for genetic differentiation. Forward time simulations demonstrate that genetic structure becomes increasingly detectable with time in isolation. Consistent with population genetic theory predicting drift causes divergence when gene flow ceases. Phenotypic plasticity and polyphenism. Phenotypic plasticity is the capacity of a single genotype to produce different phenotypes in response to environmental variation. Plasticity allows organisms to match phenotypes to environments without requiring genetic changes, providing flexibility unavailable to genetically fixed developmental programs. Reaction norms describe relationships between environments and phenotypes, with steep reaction norms indicating high plasticity and flat norms indicating canalized development. Adaptive plasticity evolves when environmental variation is predictable and phenotypes matching specific environments have higher fitness. The environment provides cues indicating which phenotype is appropriate. Developmental mechanisms translate environmental signals into phenotypic changes through hormonal, epigenetic, or other pathways. Selection favors plasticity when the fitness benefit of producing appropriate phenotypes exceeds the costs of maintaining plastic mechanisms. Non-adaptive plasticity occurs when phenotypes vary with environment, but variation does not enhance fitness, representing developmental noise or constraint. Polyphenism is a special case of phenotypic plasticity, where discrete alternative phenotypes develop in response to environmental cues. Classic examples include butterfly seasonal polyphenism, where wet season and dry season forms differ in coloration, aphid wing polyphenism, where crowding induces winged dispersal morphs, and social insect caste polyphenism, where larvae develop into workers or reproductives. Polyphenisms involve developmental switches triggered by environmental thresholds, producing reproducible bifurcations in developmental. Epigenetic mechanisms, including DNA methylation and histone modifications, mediate many polyphenisms. Environmental stimuli during critical developmental windows trigger epigenetic changes affecting gene expression patterns. These changes are maintained through subsequent development, causing divergent differentiation even though genetic sequences remain identical. Honeybee caste determination exemplifies epigenetic polyphenism. Larvae-fed royal jelly develop into queens, while larvae-fed worker jelly develop into workers, with the nutritional difference triggering different epigenetic states affecting thousands of genes. The evolution of plasticity involves genetic variation in reaction norms. Populations contain individuals with different sensitivities to environmental cues, different developmental thresholds, or different magnitudes of plastic response. Selection acts on this variation, favoring reaction norms that produce appropriate phenotypes in relevant environments. Genetic accommodation occurs when plasticity initially allows populations to persist in new environments, followed by genetic evolution that refines or replaces plastic responses. Plasticity thus both facilitates and shapes adaptive evolution. Photosynthetic pathways. Photosynthesis, the light-driven conversion of carbon dioxide and water into carbohydrates, evolved multiple pathway variants adapted to different environmental conditions. All photosynthetic organisms use rubisco, the enzyme that catalyzes carbon dioxide fixation. However, the efficiency of rubisco varies with temperature, carbon dioxide concentration, and oxygen concentration, creating opportunities for improved photosynthetic pathways. C3 photosynthesis is the ancestral pathway where rubisco directly fixes carbon dioxide into 3 carbon compounds. This pathway operates efficiently under cool temperatures, high carbon dioxide, and low light. However, rubisco also catalyzes photorespiration, a wasteful process where oxygen competes with carbon dioxide for the active site, producing toxic compounds that must be recycled at metabolic cost. Photorespiration increases at high temperatures and low carbon dioxide concentrations, reducing photosynthetic efficiency under hot, dry conditions. C4 photosynthesis evolved independently over 60 times in response to declining atmospheric carbon dioxide and increasing temperatures. C4 plants concentrate carbon dioxide around rubisco, suppressing photorespiration. The pathway involves anatomical and biochemical modifications. Mesophyll cells initially fix carbon dioxide into 4 carbon compounds using PEP carboxylase, which lacks oxygenase activity. The 4 carbon compounds move to bundle sheath cells surrounding vascular tissue where they release carbon dioxide. The concentrated carbon dioxide is refixed by rubisco under conditions strongly favoring carboxylation over oxygenation. The evolution of C4 photosynthesis required coordinated changes in multiple traits. Leaf anatomy evolved crans anatomy with distinct mesophyll and bundle sheath cell layers. Enzymes including PEP carboxylase and carbonic anhydrase increased in abundance. Compartmentalization of enzymes between cell types developed with C4 cycle enzymes in mesophyll and Calvin cycle enzymes in bundle sheath. The light reactions of photosynthesis were modified to provide appropriate energy distribution between cell types. These changes accumulated through gradual evolution over millions of years. CAM photosynthesis, crassulacean acid metabolism, represents an alternative carbon concentrating mechanism adapted to arid environments. CAM plants open stomata at night when temperatures are cooler and humidity higher, fixing carbon dioxide into organic acids stored in vacuoles. During the day, stomata close, minimizing water loss. The stored acids release carbon dioxide internally for rubisco fixation. This temporal separation of carbon dioxide uptake and fixation reduces water loss by allowing stomata to remain closed during hot, dry daytime periods. CAM photosynthesis reduces water use per unit carbohydrate produced by an order of magnitude compared to C3 plants. Lunar and tidal rhythms. Biological rhythms synchronized to lunar and tidal cycles allow organisms to anticipate predictable environmental changes associated with the Moon's orbit. These rhythms are particularly important for marine organisms inhabiting intertidal zones, where tides create complex temporal patterns. The evolution of lunar rhythms demonstrates how organisms internalize environmental periodicities through endogenous biological clocks. The marine midge Clunio marinus exhibits semilunar emergence rhythms synchronized to spring tides. Adults live only a few hours, mating and ovipositing before dying. The brief adult lifespan creates strong selection for emergence timing that maximizes reproductive success. Emergence occurs during spring tides around new and full moons when tides are lowest, allowing adults to emerge during the extended low tide period. The timing involves both lunar rhythms determining which day's emergence occurs and circadian rhythms determining the time of day. Genetic control of lunar rhythms was demonstrated through crossing experiments between Clunio populations from different locations. Populations differ in lunar emergence time and in circadian emergence time due to local adaptation to different tidal regimes. Crossing experiments show both timing characters are heritable. Remarkably, lunar and circadian timing show genetic correlation, meaning genes affecting lunar timing also affect circadian timing in an adaptive manner that matches local tidal patterns. This represents the first demonstration of genetic control of lunar rhythms in any species. The molecular mechanisms underlying lunar clocks remain mysterious. Circadian clocks involve well-characterized transcriptional translational feedback loops with approximately 24-hour periods. Lunar clocks must measure approximately 29-day periods, far longer than circadian clocks. Proposed mechanisms include counting circadian cycles, though how organisms might count to 29 without error remains unknown. Alternative mechanisms might involve slow accumulation of molecular markers or light-intensity integration over lunar cycles. Discovering the molecular basis of lunar clocks represents a major challenge in chronobiology. Mutualistic networks. Mutualistic interactions between plants and their animal pollinators or seed dispersers create complex ecological networks. These networks show distinctive structural patterns, including nestedness, where specialists interact with subsets of the species used by generalists. Understanding network structure illuminates community, assembly, coevolution, and ecosystem stability. Connectance, the fraction of possible interactions actually established, decreases exponentially as network size increases. Larger networks contain more species but proportionally fewer interactions. As diversity increases, the absolute number of interactions increases, but at a decelerating rate. Pollination networks show lower connectance than seed dispersal networks, suggesting higher specificity in pollination. These patterns resemble food webs, suggesting general principles govern network structure across interaction types. Nestedness characterizes most mutualistic networks, with average nestedness exceeding 0.84 in both pollination and seed dispersal. In nested networks, specialists interact only with subsets of the species used by generalists. The interaction matrix can be arranged so filled cells form a compact nested pattern. Nestedness suggests asymmetric dependence, with specialists depending on generalists, but not vice versa. Nested structure may emerge from abundance distributions, body size matching, or phenological overlap, rather than requiring co-evolved specialization. Asymmetries in mutual dependence are pronounced in seed dispersal systems. Dependence values are strongly skewed toward low values, meaning most species depend weakly on most partners. Strong asymmetries mean some species depend heavily on partners that barely depend on them. These patterns may arise from multiplicative effects in multispecies assemblages due to variation in species number and abundance distributions. Weak interactions and asymmetries create flexible networks where rare species can persist, and alternative pathways provide resilience to perturbations. Diffuse coevolution operates in mutualistic networks where species interact with multiple partners. Rather than pairwise coevolution between single plant pollinator pairs, selection acts on plants through entire pollinator communities and vice versa. This diffuse selection can produce species sorting where species with compatible phenologies, morphologies, or behaviors assemble into networks without requiring genetic co-evolved changes. Nevertheless, some pairwise specialization occurs, particularly in highly nested interactions where specialists show morphological matching to specific partners. The balance between diffuse and specific coevolution shapes network evolution and structure over ecological and evolutionary timescales. Chapter 51: Ecological Dynamics and Community PATTONS. Ecological communities are dynamic assemblages shaped by processes operating across multiple spatial and temporal scales. Chemical ecology explores how organisms use volatile compounds for communication, defense, and manipulation of other species. Ecological succession describes the predictable sequence of community changes following disturbance, progressing from pioneer species through intermediate stages to stable climax communities. Keystone species exert disproportionate effects on community structure relative to their abundance, often through trophic cascades that propagate through food webs. Metapopulation dynamics describe how collections of local populations connected by dispersal persist through balancing colonization and extinction across habitat patches. These ecological patterns reveal that communities are not static collections of species, but rather dynamic systems continuously reshaped by species interactions, environmental change, and spatial processes. Understanding these dynamics is essential for predicting how communities respond to disturbance and for managing ecosystems in an era of rapid environmental. Chemical ecology and plant volatiles. Plants release diverse arrays of volatile organic compounds that mediate interactions with herbivores, predators, and neighboring plants. These herbivore-induced plant volatiles serve multiple simultaneous functions in plant defense. Direct effects include repelling herbivores through unpleasant odors or toxic properties. Indirect effects involve attracting natural enemies of herbivores, including predatory insects and parasitoids that locate prey through volatile cues. Plant-plant communication occurs when neighboring plants detect volatiles from attacked individuals and preemptively activate defenses. The composition of volatile blends changes depending on the attacking herbivore species. Different herbivores trigger distinct defense signaling pathways, with chewing insects activating jasmonic acid signaling, while phloem-feeding insects activate salicylic acid pathways. These hormonal cascades induce production of herbivore-specific volatile profiles. The specificity allows receiving plants to identify the type of threat and mount appropriate defenses. Generalist herbivores that feed on many plant species trigger different volatile responses than specialist herbivores adapted to particular hosts. Green leaf volatiles, including 6-carbon aldehydes, alcohols, and esters, are released immediately upon tissue damage. These compounds result from enzymatic breakdown of membrane lipids through the lipoxygenase pathway. GLVs serve as general damage signals perceived by the damaged plant itself, neighboring plants, and natural enemies of herbivores. Perception of GLVs activates defense-related gene expression and primes plants for stronger responses to subsequent attack. Priming allows plants to respond more rapidly and strongly when actual herbivore attack occurs, providing protection with lower constitutive costs than permanent defense activation. Within-plant signaling through volatiles allows undamaged leaves on attacked plants to prepare defenses. Volatile compounds produced at herbivore feeding sites diffuse through air to other parts of the same plant. Undamaged leaves perceive these airborne signals and activate defense responses, including production of proteinase inhibitors and accumulation of toxic secondary metabolites. This systemic response protects the entire plant from future attack. The speed of airborne signaling exceeds vascular signaling through phloem, allowing rapid whole-plant responses. Volatile-mediated plant-plant communication remains controversial, but has accumulated substantial supporting evidence. Neighboring plants exposed to volatiles from damaged individuals show elevated expression of defense genes and increased resistance to herbivores. Field experiments demonstrate that plants growing near damaged neighbors experience reduced herbivore damage compared to plants grown in isolation. The ecological significance depends on whether benefits of priming defenses through volatile perception exceed costs. For closely related plants growing near kin, cooperative warning through volatiles could evolve through kin selection. However, eavesdropping by unrelated individuals creates potential for cheating where receivers benefit without paying costs of volatile emission. Ecological succession. Ecological succession is the directional change in community composition following disturbance or formation of new habitat. Two major types exist: primary succession beginning on substrates lacking soil and organisms, and secondary succession beginning on disturbed sites where soil and seed banks remain. Both progress through predictable stages as early colonists modify environments, facilitating establishment of later species. The process culminates in climax communities that persist until major disturbance resets succession. Primary succession begins on barren substrates including volcanic rock, glacial till, or sand dunes. Pioneer species capable of colonizing these harsh environments are typically small, fast-growing organisms tolerant of extreme conditions. Lichens and mosses are often the first colonists, attaching directly to rock surfaces. These pioneers begin soil formation through weathering of rock and accumulation of organic matter from dead tissues. As soil develops, vascular plants including grasses and small herbs establish. These early successional plants are typically R-selected species producing many wind-dispersed seeds and growing rapidly. Secondary succession occurs on disturbed sites where soil and seed banks persist. Following agricultural abandonment, forest clearing, or fire, herbaceous plants rapidly colonize from seeds. Within 1 to 3 years, annual and perennial herbs dominate. Shrubs establish within 5 to 10 years, creating woody vegetation. Trees gradually overtop shrubs, forming closed canopy forests after 20 to 100 years, depending on climate and disturbance regime. Secondary succession proceeds faster than primary succession because soil, nutrients, and propagule sources are already present. The mechanisms driving succession include facilitation, tolerance, and inhibition. Facilitation occurs when early colonists modify environments in ways that benefit later species. Pioneer plants improve soil conditions through nitrogen fixation, organic matter accumulation, and moisture retention. Increased shade from vegetation favors shade-tolerant species while disadvantaging shade-intolerant pioneers. Tolerance describes situations where later species are neither helped nor harmed by early species, but simply tolerate conditions better. Inhibition occurs when early species suppress later colonists through competition or allelopathy, with succession proceeding only as early species die. Climax communities represent mature, stable endpoints of succession. These communities exhibit high species diversity, complex food webs, and well-developed vertical structure. Biomass accumulation reaches maximum levels with large trees or other dominant organisms. Nutrient cycling becomes tightly closed with efficient retention and recycling. The community composition becomes self-sustaining, with species regenerating under their own shade and maintaining dominance indefinitely absent disturbance. However, the concept of stable climax communities has been challenged, with many ecologists now viewing communities as dynamic mosaics in various successional stages rather than converging towards single equilibrium states. Keystone species and trophic cascades. Keystone species exert effects on community structure disproportionate to their numerical abundance or biomass. The keystone concept, introduced by Robert Payne in 1969 based on studies of starfish predation, recognizes that some species play critical roles maintaining community diversity and structure. Removal of keystone species causes dramatic community reorganization, often with reduced diversity and altered ecosystem function. Identifying keystone species is essential for conservation because protecting these species provides disproportionate benefits for entire ecosystems. Keystone predators maintain prey diversity by preventing competitive exclusion. Predators preferentially consume abundant prey species, preventing them from monopolizing resources and excluding inferior competitors. The starfish Pisaster ocraceus preys on mussels that would otherwise dominate intertidal rocks and exclude other sessile invertebrates. Removing starfish causes mussel beds to expand, reducing diversity from 15 species to 8 species dominated by mussels. The predator maintains diversity by keeping competitively dominant prey in check. Wolves in Yellowstone National Park exemplify keystone predators driving trophic cascades, indirect effects propagating through food webs. Before wolf extirpation in the 1920s, elk populations were regulated by predation. Without wolves, elk populations exploded to over 19,000 individuals by the 1990s. Dense elk populations overbrowsed woody vegetation including willows, aspens, and cottonwoods, preventing regeneration. Riparian vegetation collapsed, eliminating habitat for songbirds and beavers. Stream banks eroded without root stabilization. Wolf reintroduction in 1995 initiated a trophic cascade. Wolves reduced elk numbers through direct predation. More importantly, wolves altered elk behavior, causing them to avoid risky areas including valleys and stream corridors where escape from wolves is difficult. This landscape of fear allowed woody vegetation to recover in predator-rich areas. Willow and aspen regeneration increased dramatically. Songbird diversity rebounded as riparian habitat recovered. Beavers returned and built dams, creating wetlands supporting amphibians and waterfowl. The entire ecosystem transformed through the indirect effects of wolf predation, cascading through multiple trophic levels. Top-down trophic cascades occur when predator effects propagate downward through food chains. Predators reduce herbivore abundance, releasing plants from herbivore pressure and increasing plant biomass. This three-level cascade, predator to herbivore to plant, appears in diverse ecosystems. Orcas eating sea otters causes sea urchin populations to explode and kelp forests to collapse. Removing sharks causes mesopredator release where smaller predators increase and deplete their prey. These cascades demonstrate that apex predators indirectly structure entire ecosystems. Metapopulation dynamics. Metapopulation theory describes the dynamics of spatially structured populations inhabiting networks of habitat patches connected by dispersal. The theory recognizes that many species exist as collections of local populations rather than single panmictic populations. Local populations experience extinctions through demographic stochasticity, environmental variation, or catastrophes. Regional persistence requires that colonization of empty patches balances extinction of occupied patches. The fraction of patches occupied at equilibrium depends on colonization and extinction rates. The classic metapopulation model assumes all patches are identical and equally connected. Local extinction rate E represents the probability per unit time that an occupied patch goes extinct. Colonization rate C represents the probability that an empty patch becomes colonized. At equilibrium, the fraction of occupied patches P reaches balance, where colonization of empty patches equals extinction of occupied patches. The equilibrium fraction of occupied patches equals 1 minus E divided by C. Metapopulation persistence requires colonization rate exceeding extinction rate. Otherwise, all patches eventually become extinct. Habitat fragmentation converts continuous populations into metapopulations. Fragmentation reduces total habitat area, decreasing population sizes and increasing extinction risk. Fragmentation also reduces connectivity between remaining patches, decreasing colonization rates. If fragmentation is severe enough that colonization cannot balance extinction, the metapopulation enters an extinction debt, appearing viable in the short term but doomed to eventual extinction. Conservation strategies must maintain both sufficient habitat area to support viable local populations and sufficient connectivity to allow dispersal between patches. Realistic metapopulations violate the assumptions of classic models through spatial structure and patch heterogeneity. Patches differ in size, quality, and isolation. Large high-quality patches support larger populations with lower extinction rates and serve as source populations producing emigrants. Small low-quality patches experience frequent extinctions and depend on immigration for persistence, acting as population sinks. Nearby patches exchange migrants more frequently than distant patches, creating spatial clustering where occupied patches occur in groups. The rescue effect occurs when immigration prevents extinction of declining populations, creating positive density dependence where occupied patches near other occupied patches have lower extinction rates. Dynamic landscapes, where patch suitability changes over time, add further complexity. Wetlands appear and disappear with hydrological fluctuations. Disturbed patches become temporarily unsuitable but regenerate over time. Species must track moving habitat mosaics, with metapopulation occupancy depending on both demographic processes and environmental stochasticity. Extended dry periods decrease wetland availability, limiting colonization opportunities and increasing extinction risk. Species with limited dispersal ability are especially vulnerable because they cannot reach distant suitable patches when nearby patches become unsuitable. Understanding these spatio-temporal dynamics is essential for predicting species responses to environmental change and designing conservation strategies that account for landscape dynamics. Chapter 52: Evolutionary Patterns and Processes. Evolution produces both spectacular diversity and striking constraint, with some lineages radiating rapidly while others remain conserved for hundreds of millions of years. Speciation rates vary dramatically across lineages, with adaptive radiations producing rapid bursts of diversification driven by ecological opportunity or key innovations. Molecular mimicry occurs when pathogens evolve protein sequences resembling host proteins, evading immune detection while potentially triggering autoimmune responses. Evolutionary constraints limit phenotypic variation through developmental, genetic, and phylogenetic mechanisms that bias the direction of evolution. Community assembly results from interactions between neutral processes, including dispersal limitation, and niche processes, including environmental filtering. Phylogeography reveals how past climate changes, especially quaternary glaciations, shaped the geographic distribution of genetic variation through range contractions into refugia followed by recolonization. These patterns demonstrate that evolution is shaped not just by selection, but by historical contingency, developmental constraints, and stochastic processes that interact to produce the diversity and structure of life. Diversification and adaptive radiation. Diversification rate, the difference between speciation and extinction rates, determines how rapidly lineages accumulate species. Clades with high net diversification expand rapidly, while those with low or negative net diversification decline or go extinct. Understanding what drives variation in diversification rates is central to explaining the uneven distribution of biodiversity across the tree of life. Some small groups contain thousands of species, while other ancient lineages remain species poor. Adaptive radiation, the rapid diversification of a lineage into species exploiting diverse ecological niches, produces much of life's diversity. These radiations exhibit three hallmarks: rapid increase in species richness through elevated speciation rates, rapid accumulation of phenotypic disparity as lineages diverge morphologically, and rapid expansion of ecological diversity as species partition niche space. Classic examples include Darwin's finches on the Galapagos Islands, Hawaiian silver swords, and cichlid fishes in African rift lakes. The paradox of adaptive radiation is that most speciation models predict continuously decelerating diversification rates as niches fill. Competition intensifies as species accumulate, reducing opportunities for new species and decreasing speciation rates. Yet adaptive radiations show bursts of rapid speciation, maintaining high rates through multiple speciation events. Resolving this paradox requires understanding what prevents niche-filling dynamics from slowing diversification during radiations. Ecological opportunity drives adaptive radiations by providing access to underutilized resources. Colonization of isolated islands devoid of competitors allows founders to diversify into empty niche space. Mass extinctions eliminate competitors and open ecological opportunities for surviving lineages. Key innovations, including novel morphological structures or physiological capabilities, allow lineages to exploit previously inaccessible resources. These opportunities permit rapid diversification before competitive interactions intensify and slow further speciation. Extinction as well as speciation shapes diversification patterns. High extinction rates can drive diversification shifts by selectively eliminating some lineages while others persist and diversify. Lineages possessing key innovations conferring extinction resistance are buffered against crises, experiencing deferred diversification when competitors go extinct. Analysis of early amniote evolution shows that diversification shifts resulted from selective extinction followed by radiation of survivors rather than instantaneous effects of innovations. This demonstrates that innovations operate not just by increasing speciation, but by decreasing extinction, with diversification shifts emerging from the interaction between evolutionary innovation and extinction. Lineages with high ongoing diversification face elevated extinction risk. Amphibians with rapid current diversification rates have greater proportions of threatened species. This counterintuitive pattern may arise because factors promoting speciation also promote extinction. Range fragmentation increases speciation through geographic isolation, but also creates small, isolated populations vulnerable to extinction. Ecological specialization accelerates speciation by reducing gene flow between populations exploiting different resources, but makes species vulnerable to environmental change. These trade-offs create fundamental tension between processes generating diversity and those maintaining it. Molecular mimicry and immune evasion. Molecular mimicry describes situations where pathogens evolve protein sequences resembling host proteins. This form of adaptive convergence at the molecular level allows pathogens to evade immune detection by resembling self-proteins that the immune system is trained to tolerate. Mimicry exploits the immune system's mechanisms for preventing autoimmunity, which include deletion of T cells recognizing self-antigens during development in the thymus and peripheral tolerance mechanisms, suppressing autoreactive lymphocytes. Analysis of mimicry across 134 viruses reveals that mimicry abundance varies among viral families. Herpes viruses and pox viruses show particularly high levels of mimicry to human proteins. These large DNA viruses have greater genomic capacity to encode mimics compared to smaller RNA viruses. The mimicked proteins are not random, but show systematic biases. Viruses preferentially mimic proteins from autosomes and X chromosomes rather than Y chromosomes, consistent with selection for mimicking proteins present in all hosts rather than only males. Viruses disproportionately mimic proteins expressed during negative selection in the thymus. Negative selection eliminates T cells with high affinity for self-antigens, creating central tolerance. By mimicking proteins involved in this process, viruses exploit the immune system's tolerance mechanisms. This mimicry is predicted to improve evasion of adaptive immunity by limiting the epitopes targetable by host T cells. The viral antigens resemble self-proteins that would normally trigger deletion of T cells recognizing them. Molecular mimicry may contribute to autoimmune disease by breaking immune tolerance. When the immune system responds to pathogen antigens that resemble self-proteins, cross-reactive antibodies and T cells may attack host tissues. Multiple sclerosis, an autoimmune disease affecting myelin in the nervous system, shows associations with Epstein-Barr virus infection. Analysis reveals overlaps between EBV antigens and autoantigens targeted by antibodies from MS patients. This suggests EBV infection may trigger autoimmunity through molecular mimicry, with immune responses against viral proteins cross-reacting with human myelin proteins. The evolutionary dynamics of mimicry involve arms races between pathogen immune evasion and host immune recognition. Pathogens evolve mimics to evade detection. Hosts evolve enhanced discrimination abilities to distinguish pathogens from self despite mimicry. This coevolution may drive rapid evolution of immune system genes under positive selection. The major histocompatibility complex genes that present antigens to T cells are among the most polymorphic genes in vertebrate genomes, likely reflecting selection for diverse recognition capabilities, maintaining ability to distinguish diverse pathogens from self despite mimicry. Evolutionary constraints. Evolutionary constraints are factors limiting or biasing the direction of phenotypic evolution. Constraints prevent unlimited variation, causing evolutionary change to follow predictable trajectories rather than exploring all theoretically possible phenotypes. Three major categories of constraints exist. Phylogenetic constraints, where evolutionary history limits current possibilities. Developmental constraints, where ontogenetic mechanisms bias phenotypic variation. And genetic constraints, where patterns of genetic variation and pleiotropy limit possible evolutionary changes. The developmental hourglass model describes temporal variation in evolutionary constraint during ontogeny. Embryonic development begins with variable early stages where different species show different cleavage patterns and gastrulation modes. Development then passes through a conserved phylotypic stage where body plans are established and all members of a phylum share similar morphology. After the phylotypic stage, development again diverges as species-specific features develop. This hourglass pattern suggests maximum constraint at mid-development when body plans are specified. Body plans, the fundamental anatomical architectures distinguishing major animal groups, show striking evolutionary conservation. All arthropods share segmented bodies with jointed appendages. All chordates develop notochords, dorsal nerve cords, and pharyngeal slits during development. These body plans persist for over 500 million years despite enormous diversification within phyla. The conservatism of body plans reflects developmental constraints, where the complexity of integrated developmental programs makes radical reorganization unlikely. Genomic analyses reveal that genes expressed at mid-development are more conserved than genes expressed early or late. This pattern, called the genomic hourglass, parallels the morphological hourglass. Genes required for establishing body plans experience stronger purifying selection, preventing sequence changes that would disrupt body plan development. Interestingly, genomic constraints decrease monotonously over developmental time rather than showing the mid-developmental peak of morphological constraints. This suggests different types of constraints operate on genomic versus morphological levels. Pleiotropy, where single genes affect multiple traits, creates genetic constraints by causing correlated evolution of traits. Mutations beneficial for one trait may be deleterious for other traits affected by the same gene. Strong pleiotropic constraints limit independent evolution of traits, maintaining trait correlations across species. Modularity, the organization of traits into semi-independent units, reduces pleiotropy and allows greater evolutionary flexibility. The evolution of modularity may itself be an adaptation that reduces constraints, allowing lineages to explore larger regions of phenotypic space. Community assembly processes. Community assembly describes the processes determining which species from regional species pools colonize and persist in local communities. Two major classes of processes operate: Neutral processes, where species are ecologically equivalent and assembly, depends on dispersal and stochastic colonization-extinction dynamics, and niche processes where species differ ecologically and assembly depends on environmental filtering and species interactions. Real communities likely result from interactions between both process types. Neutral theory proposes that local community composition results from random colonization from regional species pools, with all species ecologically equivalent. Differences in species abundances arise from stochastic drift and dispersal limitation rather than niche differences. The theory predicts community patterns, including species abundance distributions and species area relationships, without invoking niche differentiation. Neutral models fit many observed patterns surprisingly well, suggesting stochastic processes play larger roles in community assembly than traditionally recognized. Niche-based community assembly emphasizes environmental filtering and competitive exclusion. Species differ in environmental tolerances, with local communities representing subsets of regional pools filtered by local conditions. Abiotic filters including climate, soil, and disturbance exclude species lacking appropriate tolerances. Biotic filters, including competition and predation, exclude species unable to coexist with residents. Niche theory predicts that communities contain species with divergent niches, allowing coexistence through niche partitioning. The community assembly phase space framework integrates neutral and niche processes. Rather than viewing community assembly as falling along a single continuum from pure neutral to pure niche processes, the framework recognizes that dispersal limitation and niche separation vary independently. A two-dimensional phase space with axes representing dispersal limitation and niche separation describes the full range of assembly processes. Pure neutral assembly with infinite dispersal and complete niche overlap occupies the origin. Pure niche assembly with no dispersal limitation and complete niche separation occupies the opposite corner. Real communities fall at intermediate positions, reflecting varying contributions of both processes. Experimental tests distinguish neutral from niche assembly by adding species to communities and monitoring establishment success. Neutral theory predicts random assembly independent of species traits, with establishment success unrelated to similarity between residents and invaders. Niche theory predicts that residents most strongly inhibit establishment of similar species through competitive exclusion. Prairie grassland experiments show structured non-neutral assembly, where residents inhibit similar species more than dissimilar species, supporting niche-based assembly. However, the relative importance of neutral versus niche processes varies among communities depending on environmental heterogeneity, dispersal rates, and strength of species interactions. Phylogeography and glacial refugia. Phylogeography examines the geographic distribution of genetic lineages to infer historical processes shaping biodiversity. Quaternary glacial cycles profoundly influence species distributions, forcing range contractions into refugia during glacial maxima, followed by range expansions during interglacials. These repeated range shifts created genetic signatures still detectable in contemporary populations. Understanding phylogeographic patterns illuminates how past climate change affected biodiversity and how future climate change may impact species. Northwestern North America experienced extensive Pleistocene glaciation that shaped biotic distributions. Two major refugia, Beringia in the northwest and the Pacific Northwest coastal region, harbored species during glacial maxima. Recent research reveals greater complexity than this simple two-refugia model. Additional refugia existed, including the Alexander Archipelago, Haida Gwaii, and ice-free areas within ice sheets. This refugia-within-refugia pattern created complex genetic structure, reflecting multiple isolated populations during glaciation. Species with ranges covering multiple refugia show genetic signatures of population subdivision and secondary contact. Distinct genetic lineages evolved in different refugia through isolation and drift. When ice sheets retreated, populations expanded from refugia, and met in contact zones where distinct lineages hybridize. Genetic analyses identify refugial locations through phylogeographic breaks and areas of high genetic diversity representing long-term stable populations. Species with high dispersal abilities were more likely to occupy multiple refugia, creating more complex genetic structure than poor dispersers restricted to single refugia. Mediterranean regions provided refugia during European glaciations. The high genetic diversity in Mediterranean populations reflects preservation of genotypes that went extinct in northern regions, plus accumulation of mutations in stable refugial populations. Maritime and Ligurian Alps harbored endemic species through multiple glacial cycles, with cumulative effects of repeated glaciations creating complex genetic patterns. Understanding refugial locations and post-glacial colonization routes is essential for predicting how species will respond to current climate. The genetic consequences of glacial refugia persist for thousands of years after ice retreat. Contemporary genetic structure reflects not just current ecological processes, but historical events during the Pleistocene. Populations show signatures of bottlenecks during refugial isolation and range expansions from refugia. Phylogeographic patterns reveal colonization routes and timing of range expansions. This historical perspective demonstrates that contemporary biodiversity patterns cannot be understood without considering past climate change and its enduring genetic legacy. As current climate change forces range shifts, understanding past responses provides crucial context for predicting future trajectories. Chapter 53: Genetic Exchange and Evolutionary Asteroids. Evolution operates through mechanisms beyond simple vertical inheritance from parent to offspring, with horizontal transfer and strategic behaviors shaping adaptation. Horizontal gene transfer allows bacteria to acquire genetic material from unrelated individuals, spreading antibiotic resistance genes through populations at rates far exceeding mutation. Niche construction occurs when organisms modify their environments in ways that feed back to influence subsequent evolution through ecological inheritance. Evolutionary game theory analyzes strategic behaviors using mathematical models, including hawk-dove games that predict evolutionary stable strategies. Bet hedging strategies evolve in unpredictable environments where spreading risk across variable outcomes increases long-term fitness despite reducing short-term performance. These mechanisms demonstrate that evolution involves not just gradual accumulation of mutations, but also dramatic genetic exchanges, organism-environment feedbacks, strategic interactions between individuals, and risk management strategies. Understanding these processes reveals the full complexity of evolutionary dynamics operating simultaneously across multiple levels, from genes to ecosystems. Horizontal gene transfer and antibiotic resistance. Horizontal gene transfer is the movement of genetic material between organisms outside of reproduction, contrasting with vertical transmission from parent to offspring. Three major mechanisms enable HGT in bacteria: transformation, where cells take up DNA from their environment; transduction, where viruses transfer DNA between cells; and conjugation, where plasmids transfer between cells through direct contact. This lateral exchange allows bacteria to acquire complex traits, including antibiotic resistance, without waiting for mutations to arise spontaneously. Plasmids are circular DNA molecules that replicate independently of chromosomal DNA. Many plasmids carry antibiotic resistance genes and can transfer between bacterial cells through conjugation. During conjugation, a donor cell extends a pilus to a recipient cell, forming a bridge through which plasmid DNA passes. The plasmid replicates during transfer, so both donor and recipient end up with copies. Because plasmids can cross species boundaries, antibiotic resistance genes spread rapidly through bacterial communities containing diverse species. Transposons are mobile genetic elements that can move within and between DNA molecules. These jumping genes carry antibiotic resistance genes along with enzymes that catalyze their own movement. Transposons can jump from chromosomes to plasmids or vice versa, mobilizing resistance genes that might otherwise remain fixed in one location. Some transposons are conjugative, able to transfer themselves between cells. Others require plasmids or other mobile elements for intercellular movement, but can insert into those elements and hitchhike between cells. The synergy between plasmids and transposons creates powerful systems for spreading antibiotic resistance. Transposons carrying resistance genes insert into conjugative plasmids. The plasmids then transfer between cells, carrying transposons to new hosts. The transposons can jump from plasmids into chromosomes, establishing permanent chromosomal resistance that no longer depends on maintaining plasmids. This multi-step process distributes resistance genes widely through bacterial populations far faster than vertical inheritance could achieve. Biofilms, structured bacterial communities attached to surfaces, enhance horizontal gene transfer. Cells in biofilms exist at high densities in close proximity, increasing opportunities for conjugation. The biofilm matrix concentrates extracellular DNA from lysed cells, facilitating transformation. Horizontal gene transfer rates in biofilms can exceed rates in planktonic cultures by orders of magnitude. This has major implications for medicine because bacterial infections often involve biofilms on tissues or medical devices, creating hot spots where resistance genes spread rapidly. Antibiotics themselves accelerate horizontal gene transfer of resistance genes. Antibiotic exposure activates stress responses that upregulate conjugation. The conjugative transposon CTN carries tetracycline resistance, and its transfer is stimulated by tetracycline presence. This creates a positive feedback loop where antibiotic use selects for resistance and simultaneously accelerates the spread of resistance genes through populations. Understanding these dynamics is crucial for developing strategies to slow resistance evolution. Niche construction theory. Niche construction is the process by which organisms modify their environments, creating ecological conditions that feed back to affect evolution. This process challenges traditional evolutionary models where environments select among organisms, but organisms do not substantially alter selection pressures. Niche construction theory recognizes that organisms and environments co-evolve through reciprocal interactions. Organisms adapt to environments through natural selection, while simultaneously changing environments through their activities. Ecological inheritance occurs when environmental modifications persist across generations, affecting descendant populations. Earthworms change soil structure through burrowing and organic matter processing. These modifications persist after individual earthworms die, affecting the next generation that inherits not just genes, but also modified soil conditions. Beaver dams create ponds that persist for years, providing aquatic habitat inherited by offspring. Unlike genetic inheritance, which transmits information through DNA, ecological inheritance transmits environmental states modified by previous generations. The feedback loop between organisms and environments creates eco-evolutionary dynamics operating on contemporary timescales. Traditional models separate ecological and evolutionary processes, treating ecology as occurring on short timescales and evolution on long timescales. However, niche construction creates situations where ecological changes drive evolutionary responses that further modify ecology in feedback loops. Populations alter environments through predation or habitat modification. Those environmental changes create selection pressures, causing evolutionary adaptation. The evolved populations alter environments differently than ancestral populations, changing selection pressures again. 5 empirical systems illustrate eco-evolutionary feedbacks through niche construction. Rotifer algae chemostat experiments show how rotifer evolution affects algal community composition, which feeds back to influence rotifer evolution. Alewife fish in lakes alter zooplankton communities through predation, changing nutrient cycling and primary production. Guppies in Trinidad streams exhibit rapid life history evolution in response to predation, with evolutionary changes affecting nutrient cycling through altered excretion rates. Avian seed predators select for plant seed defenses, which alter seed availability, affecting bird populations. Tree leaf chemistry evolution changes litter quality, affecting soil processes and nutrient availability for trees. These systems demonstrate that eco-evolutionary feedbacks operate across diverse taxa and ecosystems. Niche construction has major implications for evolutionary theory. It creates an additional source of inheritance beyond genes, with ecological legacies affecting descendant fitness. It can change the direction and rate of evolution by altering selection pressures. It can drive evolutionary dynamics that differ from predictions of standard models, ignoring organism-environment feedbacks. Incorporating niche construction into evolutionary theory provides a more complete understanding of how evolution operates in natural systems, where organisms continuously modify the selective environments they inhabit. Evolutionary game theory. Evolutionary game theory applies mathematical game theory to biological evolution, analyzing how strategies succeed or fail depending on the strategies employed by others in the population. Unlike classical game theory, where players make rational choices, evolutionary game theory treats strategies as inherited phenotypes with frequencies changing through natural selection. The central concept is the evolutionarily stable strategy, a strategy that cannot be invaded by alternative strategies when common in a population. The hawk-dove game is a classic model examining aggressive versus peaceful conflict resolution strategies. Hawks always fight over resources, escalating conflicts until one individual is injured and retreats. Doves display threateningly but retreat if opponents escalate. The payoff matrix defines fitness consequences of interactions. When hawk meets hawk, both fight with the winner gaining the resource, but both risking injury costs. When hawk meets dove, hawk gains the resource and dove retreats unharmed. When dove meets dove, they display with the resource randomly going to one individual and no injury. Whether hawk or dove strategies can invade depends on the costs and benefits. If resources are valuable and injury costs are low, hawks outperform doves because fighting pays. Hawks increase in frequency until they dominate the population. Pure hawk becomes an S because any dove entering a hawk population loses every interaction with hawks. However, if injury costs exceed resource value, hawk-hawk interactions impose net fitness costs. In hawk-dominated populations, the average hawk frequently encounters other hawks and suffers injuries. When injury costs exceed resource benefits, a mixed S emerges with hawks and doves coexisting. As hawk frequency increases, hawks increasingly encounter other hawks and suffer injury costs. This negative frequency dependence allows doves to invade because doves avoid injury costs. The equilibrium frequency balances the advantages of hawk when rare against its disadvantages when common. The S frequency can be calculated from payoff values, producing a stable polymorphism maintained by frequency-dependent selection. The hawk-dove game illustrates fundamental principles of evolutionary game theory. Fitness depends not on absolute performance, but on performance relative to population average. Strategies succeed or fail depending on what other individuals do, creating frequency-dependent selection. No single strategy is universally best. Optimal strategy depends on population composition. These insights apply broadly to social behaviors, including cooperation, conflict, and signaling. Game theory provides tools for analyzing how social behaviors evolve when fitness depends on strategic interactions. Bet hedging and risk management. Bet hedging is an evolutionary strategy that reduces variation in fitness across variable environments at the cost of reducing mean fitness in any single environment. This strategy evolves when environments fluctuate unpredictably, such that individuals cannot predict which phenotype will be optimal. Rather than committing to a single phenotype that might fail catastrophically in unfavorable environments, bet hedgers produce diverse phenotypes spreading risk across outcomes. The long-term geometric mean fitness of bet hedgers exceeds specialists, even though specialists perform better in each specific environment. Seed dormancy exemplifies bet hedging in plants. Annual plants in unpredictable environments face uncertainty about whether germination conditions will be followed by favorable growing conditions. If all seeds germinate in a year with catastrophic failure, the maternal plant's fitness is zero for that reproductive episode. Seed dormancy spreads germination across multiple years, ensuring that some seeds germinate in favorable years even if others germinate in unfavorable years. This temporal spreading reduces fitness variance across years. The bet hedging mechanism selecting for dormancy operates through geometric mean fitness. Consider a plant producing 100 seeds annually. If all germinate every year, fitness equals 100 times seedling survival. In favorable years with 90% survival, fitness is 90. In catastrophic years with 1% survival, fitness is 1. The geometric mean across years is the square root of 90 times 1, approximately 9.5. A bet hedger with 50% dormancy germinates 50 seeds per year. In favorable years, fitness is 45. In bad years, fitness is 0.5. The geometric mean is approximately 4.7 for germinating seeds, but 50 dormant seeds carry over with high survival, producing total geometric mean fitness exceeding 10. Conservative bet hedging produces a single intermediate phenotype rather than diverse phenotypes. Rather than specializing for specific conditions, conservative bet hedgers adopt generalist strategies performing adequately across conditions. This differs from diversified bet hedging, where single genotypes produce multiple phenotypes. Seed dormancy represents diversified bet hedging, with each seed making a binary decision to germinate or remain dormant. The diversity of outcomes within a clutch reduces fitness variance. The best bet strategy differs from bet hedging by tracking environmental cues to optimize germination timing. Rather than spreading germination randomly across time, best bet strategists germinate when conditions indicate high probability of subsequent success. Desert annual plants germinate after substantial rainfall, indicating sufficient moisture for completing life cycles. The distinction between bet hedging and best bet depends on environmental predictability. When reliable cues exist, best bet strategies outperform bet hedging by concentrating germination in favorable periods. When environments are truly unpredictable, bet hedging prevails. Bet hedging also applies beyond plants to diverse organisms. Bacterial persistence involves subpopulations entering dormant states resistant to antibiotics. If the population encounters antibiotics, persisters survive and resume growth. Amphibian breeding strategies include explosive breeders that reproduce synchronously and prolonged breeders that spread reproduction across time. Itroporous life histories that reproduce multiple times spread reproductive effort temporally, hedging against catastrophic failure in single years. These examples demonstrate that bet hedging is a general evolutionary response to unpredictability arising repeatedly across the tree of life. Chapter 54: Evolution and Adaptation. Species interactions drive reciprocal evolutionary changes as organisms adapt to each other through coevolutionary processes. Sexual dimorphism, differences in size or morphology between males and females, evolves through sexual selection and ecological divergence driven by resource competition between sexes. Cospeciation occurs when hosts and parasites or other symbionts speciate in parallel, producing congruent phylogenies. Character displacement is trait divergence driven by competition between similar species, reducing niche overlap in sympatry. The adaptive significance of traits must be distinguished from spandrels, byproducts of development or architecture that may be co-opted for new functions through exaptation. Dispersal strategies including wind, water, and animal-mediated seed dispersal represent adaptations to different selective pressures. These processes illustrate how species evolve in response to interactions with other organisms and how distinguishing adaptation from byproduct requires careful evolutionary analysis. Coevolution creates some of the most intricate adaptations in nature, while also generating constraints through interdependencies between species. Sexual dimorphism and resource competition. Sexual dimorphism is the difference in morphology, size, or coloration between males and females of a species. Sexual selection, competition for mates and mate choice, has long been considered the primary driver of sexual dimorphism. Males compete for access to females through combat or display, selecting for larger size or elaborate ornaments. However, ecological factors including resource competition between sexes also drive dimorphism evolution. Body size dimorphism varies enormously across animals. In many mammals including primates and ungulates, males are substantially larger than females. In many birds including raptors, females are larger than males. In most insects, females exceed males in size. Understanding this variation requires considering both sexual selection and natural selection on body size. Sexual selection favors larger size in the sex experiencing stronger competition for mates, typically males in polygynous systems. Natural selection may favor different optimal sizes for males and females based on ecological roles. Intersexual resource competition can drive sexual dimorphism when sexes compete for limiting resources. If males and females have identical morphology, they compete for identical resources. Niche differentiation reducing this competition provides fitness benefits. Dimorphism allows sexes to partition resources, reducing competition and increasing population carrying capacity. The evolution of dimorphism through resource competition depends on the strength of between-sex competition relative to within-sex competition. Models show that sexual dimorphism evolves most readily in small mating groups when selection for resource partitioning between sexes is strong. In large panmictic populations, dimorphism becomes difficult to evolve because genetic correlation between sexes constrains independent evolution. Males and females share most genes, creating genetic constraints on sex-specific adaptation. Nevertheless, sex-limited gene expression and sexually antagonistic selection can drive dimorphism evolution even with shared genomes. Traits expressed only in one sex or at different levels between sexes can evolve sex-specific optima. Sexual size dimorphism shows complex relationships with sexual selection intensity. Across species, the correlation between sexual selection strength and male-biased SSD is weaker than traditionally assumed. Other factors including fecundity selection favoring large females and ecological differences between sexes contribute substantially to SSD. Reproductive roles create fundamental differences between sexes, with females investing more in eggs and gestation. This selects for larger female size independent of sexual selection. Disentangling sexual selection from natural selection requires careful phylogenetic analyses controlling for multiple factors affecting body size evolution. Cospeciation and host parasite phylogenies. Cospeciation occurs when interacting lineages speciate in parallel, with speciation in one lineage driving speciation in associated lineages. Host parasite systems provide classic examples. When host populations become geographically isolated and diverge into separate species, their parasites also become isolated and may diverge into separate species. If this process occurs repeatedly, the phylogenies of hosts and parasites should show congruent branching patterns reflecting their shared history. Fahrenholz's rule postulates that parasites and hosts speciate in synchrony. This leads to predictions that host and parasite phylogenetic trees should be topologically identical, with speciation events occurring at the same times. Testing cospeciation requires constructing independent phylogenies for hosts and parasites and comparing their topologies. Congruence indicates cospeciation, while incongruence suggests other events, including host switching, parasite extinction, or independent speciation. Lice-parasitizing seabirds provide evidence for frequent cospeciation. Phylogenetic analyses of Pectinopagus lice and their pelicaniform hosts show significant congruence between host and parasite trees. Multiple cophylogenetic analysis methods detect frequent cospeciation events. When host lineages diverge, louse lineages diverge in parallel. This pattern emerges because lice are highly host-specific with limited dispersal ability. Geographic isolation of host populations necessarily isolates parasite populations, promoting parallel speciation. Correlation between host and parasite divergence times provides additional evidence for cospeciation. If hosts and parasites speciated synchronously and both have molecular clocks, parasite divergence should correlate with host divergence. Regression of parasite divergence against host divergence produces a line whose intercept measures parasite divergence when hosts speciate. An intercept of 0 implies perfectly synchronous cospeciation. Positive intercepts indicate parasite speciation lagged behind host speciation. Analyses of pocket gophers and their lice show strong correlations consistent with frequent cospeciation. Not all host parasite systems show strong cospeciation. Host switching allows parasites to colonize new host species without host speciation. Missing parasite lineages result from extinctions not affecting hosts. Independent parasite speciation occurs when parasites speciate within single host species through mechanisms like geographic isolation not affecting hosts. The frequency of cospeciation versus alternative events varies among systems depending on parasite dispersal ability, host specificity, and geographic structure. Comparing across systems reveals factors promoting or inhibiting cospeciation. Character displacement. Character displacement is evolutionary divergence of competing species driven by selection to reduce niche overlap. When similar species occur in sympatry, they compete for resources. This competition selects for divergence in traits affecting resource use, reducing overlap and competition. Character displacement predicts that species should be more different in sympatry where they compete than in allopatry where competition is absent. The competitive exclusion principle states that species with identical niches cannot coexist indefinitely. One species will competitively exclude the other. For stable coexistence, species must differ in resource use or other niche dimensions. Character displacement is the evolutionary process generating these differences. Through natural selection favoring phenotypes that reduce competition, species diverge until niche overlap is sufficiently reduced to permit coexistence. Classic examples of character displacement come from Darwin's finches on the Galapagos Islands. Finch species show greater differences in beak size and shape in sympatry than in allopatry. On islands with multiple species, beaks diverge with different species specializing on different seed sizes. On islands with single species, beak sizes are intermediate. This pattern indicates that competition in sympatry drives morphological divergence, reducing dietary overlap. Character displacement involves both morphological divergence and niche shifts. Morphological changes alter resource use abilities. Larger beaks handle larger seeds more efficiently. Smaller beaks handle small seeds more efficiently. As morphology diverges, resource use diverges with species partitioning the available seed size spectrum. The combination of morphological evolution and behavioral shifts in resource use reduces competition, allowing coexistence. Demonstrating character displacement requires showing that divergence is caused by competition rather than other factors. Differences between allopatric populations might result from adaptation to different abiotic environments rather than biotic interactions. Strong tests require experimental manipulation of competitor presence or measurements of competition and fitness consequences. Field experiments removing competitors show that remaining species shift resource use toward niches of removed competitors, confirming that competition constrains resource use. Combining observational patterns with experimental manipulations and fitness measurements provides robust evidence for character displacement. Exaptation and spandrels. The adaptive significance of traits cannot be assumed from current function. Traits may arise for one function and later be co-opted for different functions through exaptation. Alternatively, traits may arise as non-adaptive byproducts of other changes, called spandrels. Distinguishing adaptations from exaptations and spandrels requires historical evidence about how traits originated and whether they were shaped by selection for current functions. Spandrels are architectural byproducts that arise automatically as consequences of adaptations. The term comes from architecture, where spandrels are triangular spaces between arches. These spaces exist necessarily given arch construction, but were not designed for independent function. In biology, spandrels are traits arising as correlations of growth or pleiotropic side effects of selection on other traits. The human chin may be a spandrel resulting from selection on jaw size and shape rather than an adaptation for specific chin functions. Exaptation describes traits co-opted for functions different from their original function. Feathers initially evolved for insulation or display in theropod dinosaurs. Later, feathers were co-opted for flight in birds. The original function was thermoregulation or signaling, not flight. Flight represents an exaptation utilizing structures that evolved for other purposes. Many adaptive traits arise through exaptation of existing structures rather than de novo origin. Distinguishing adaptations from spandrels requires identifying what selection pressures shape trait origins. Traits that are adaptations show evidence of design for current functions, including complexity, efficiency, and cost-benefit trade-offs. Traits that are spandrels may show current utility, but lack evidence of historical selection for that utility. The difficulty is that only modern structures are available for study. Fossil sequences showing evolutionary transitions help identify when traits originated and what selective pressures existed at origins. Concept of spandrels emphasizes that not all traits are adaptations. This challenges adaptationist programs that assume all traits were shaped by selection for current functions. Many traits arise as byproducts or through drift, with subsequent co-option to useful functions. Recognizing spandrels and exaptations provides a more nuanced view of evolution, where organisms are patchworks of adaptations, exaptations, and spandrels accumulated through complex evolutionary histories. Dispersal strategies and seed movement. Dispersal, the movement of organisms from birthplaces to reproduction sites, profoundly affects population dynamics, gene flow, and colonization of new habitats. Plant seeds exhibit diverse dispersal mechanisms shaped by selection acting on multiple fitness components, including dispersal distance, directionality, and arrival patterns. Different dispersal strategies represent adaptations to different ecological contexts and evolutionary trade-offs. Wind dispersal relies on aerodynamic features, including wings, plumes, or small size, allowing seeds to remain airborne. Wind can carry seeds hundreds or thousands of kilometers, providing exceptional long-distance dispersal. However, wind dispersal lacks directionality, depositing seeds randomly relative to suitable habitats. This creates high mortality from seeds landing in unsuitable locations. Wind dispersal is advantageous in open habitats with favorable wind conditions, and when colonization of distant sites provides fitness benefits exceeding local mortality costs. Traits affecting wind dispersal include terminal velocity, the speed at which seeds fall, and wing loading, the ratio of seed mass to wing area. Seeds with low terminal velocity remain airborne longer and disperse farther. Seeds with low wing loading have large wings relative to mass, reducing fall rates. However, large wings require resource investment and may reduce seed provisioning. Trade-offs between dispersal ability and seed quality create variation in optimal strategies. Species in early successional habitats favor dispersal ability, while late successional species favor seed size and competitive. Water dispersal transports seeds through streams, rivers, and ocean currents. Buoyant seeds float and can travel long distances following water flow. Coastal plants, including mangroves, depend on water dispersal for colonizing shorelines. Like wind dispersal, water dispersal provides long-distance movement but limited control over arrival locations. Seeds must tolerate extended immersion and locate suitable germination sites after deposition. Water dispersal is advantageous for riparian and coastal species, where water bodies connect suitable habitats. Animal dispersal involves multiple mechanisms. Frugivores consume fruits and defecate or regurgitate seeds, transporting them during travel. Migratory birds provide extremely long-distance dispersal, potentially moving seeds thousands of kilometers. External transport occurs when seeds with hooks or sticky coatings attach to animal fur. Scatter-hoarding animals, including rodents, cache seeds with unconsumed caches, sometimes germinating. Animal dispersal provides directed movement toward habitats where animals travel and may deposit seeds in favorable locations like nutrient-rich feces. Coincident arrival of seeds creates competition and inbreeding risks. Wind dispersal models traditionally focused only on distance, but arrival patterns also affect fitness. When many seeds arrive simultaneously at the same location, they compete as seedlings and potentially interbreed as adults. Dispersal traits affecting temporal and spatial spread of seed arrival influence fitness by reducing sibling competition and inbreeding. Understanding how dispersal strategies balance distance, directionality, and arrival patterns requires two-dimensional analyses of seed deposition, accounting for atmospheric conditions and plant trait variation. Different species evolve different solutions to these complex trade-offs depending on their ecological contexts. Chapter 55: Evolutionary MECHNISMS and PATTONS. Evolution operates through multiple processes that generate diversity, constrain variation, and produce both predictable and unpredictable outcomes. Convergent evolution produces analogous structures in distantly related lineages facing similar selective pressures, demonstrating how natural selection repeatedly discovers similar solutions. Genetic drift, the random change in allele frequencies, becomes more powerful in small populations and can fix neutral or even mildly deleterious alleles through chance. Altruism, behavior that benefits others at cost to the actor, evolves through kin selection when Hamilton's rule is satisfied, with relatedness multiplied by benefit exceeding cost. Life history trade-offs emerge from resource allocation, constraints forcing organisms to balance competing demands, including growth, reproduction, and survival. These mechanisms reveal that evolution is not a simple process of gradual improvement, but rather involves complex interactions between selection, drift, historical contingency, and constraints. Understanding these mechanisms provides insight into why evolution sometimes produces remarkable convergence and other times generates unpredictable outcomes. Convergent evolution and analogous structures. Convergent evolution occurs when distantly related species independently evolve similar traits in response to similar environmental pressures or ecological niches. These similar traits are analogous structures that serve similar functions but did not arise from common ancestry. Convergent evolution demonstrates that natural selection is a powerful force capable of producing similar solutions to similar problems across vast phylogenetic distances. Flight evolved independently at least 4 times in vertebrates, including pterosaurs, birds, bats, and several extinct lineages. Each group evolved wings through modification of different ancestral structures. Pterosaurs developed membranes supported by elongated fourth fingers. Birds evolved feathered wings using entire forelimbs with feathers providing the airful surface. Bats evolved membranous wings stretched between elongated finger bones. Despite different anatomical implementations, all flying vertebrates converge on similar wing shapes and aspect ratios determined by aerodynamic constraints. Streamlined body forms evolved repeatedly in aquatic vertebrates, including sharks, ichthyosaurs, dolphins, and tuna. Sharks are cartilaginous fish that evolved streamlining over hundreds of millions of years. Ichthyosaurs were marine reptiles that independently evolved dolphin-like bodies during the Mesozoic. Dolphins are mammals that returned to the ocean and convergently evolved streamlined forms remarkably similar to ichthyosaurs despite being separated by 200 million years. All these lineages face similar hydrodynamic constraints, making streamlining advantageous for efficient swimming. The body forms converge not just generally, but in specific details. Dolphins and sharks both possess dorsal fins providing stability during swimming. They have fusiform bodies with greatest width, about 1/3 back from the head. They possess powerful tail flukes oriented vertically in mammals and horizontally in fish, but serving the same propulsive function. This detailed convergence reflects optimization under identical physical laws governing movement through water. Convergent evolution at the molecular level produces similar proteins in unrelated lineages. Antifreeze glycoproteins evolved independently in Arctic and Antarctic fish lineages to prevent ice crystal formation in body fluids. The proteins from different lineages have similar functions but different amino acid sequences and arose from different ancestral genes. This demonstrates convergence at the functional level without convergence at the sequence level. Natural selection can achieve similar ends through different molecular means. Genetic drift and neutral evolution. Genetic drift is the random change in allele frequencies due to sampling error when finite populations pass genes to the next generation. Unlike natural selection, which changes allele frequencies directionally based on fitness differences, drift changes frequencies randomly with no relationship to fitness. Drift is most powerful in small populations where chance events have larger proportional effects. Understanding drift is essential because it produces evolutionary change without adaptation. The probability that a neutral allele becomes fixed equals its initial frequency. An allele present at frequency p in a population has probability p of eventually fixing and probability 1 minus p of being lost. A new mutation occurring in a diploid population of size n starts at frequency 1 divided by 2n. The fixation probability for a new neutral mutation is therefore 1 divided by 2n. Most new mutations are lost by drift, regardless of their effects. Only a tiny fraction of mutations, even beneficial ones, ultimately fix. The time to fixation for neutral alleles depends on population size. The expected time for a neutral allele starting at frequency p to fix is negative 4n times 1 minus p divided by p generations, where n is the effective population size. For new mutations starting at very low frequency, fixation requires approximately 4n generations on average. Large populations take much longer for drift to fix alleles than small populations. This creates a molecular clock where substitution rates depend on mutation rates rather than selection in large populations where most mutations behave neutrally. Effective population size Ni determines drift strength and often differs substantially from census population size. Factors reducing Ni include unequal sex ratios, where the rarer sex constrains effective size, variation in reproductive success, where some individuals produce many offspring while others produce few, and population size fluctuations, where bottlenecks reduce effective size disproportionately. A population of 10,000 individuals might have effective size of only 1,000 if reproductive success is highly skewed. Genetic drift and natural selection interact to determine evolutionary outcomes. In large populations, selection is effective at removing even weakly deleterious alleles and fixing beneficial alleles. In small populations, drift overwhelms weak selection, allowing mildly deleterious alleles to fix by chance. The boundary between effective selection and drift depends on the product of effective population size and selection coefficient. When this product is much less than 1, drift dominates. When much greater than 1, selection dominates. This explains why small populations accumulate deleterious mutations faster than large populations. Altruism and Hamilton's rule. Altruism, behavior that benefits others at cost to the actor, poses an evolutionary puzzle because natural selection should favor selfish individuals who receive benefits without paying costs. How can natural selection maintain altruism when altruists have lower fitness than non-altruists? William Hamilton resolved this paradox by showing that genes for altruism can spread if recipients share those genes through common ancestry. This insight revolutionized understanding of social evolution. Hamilton's rule states that altruism evolves when RB exceeds C, where R is genetic relatedness between actor and recipient, B is the fitness benefit to the recipient, and C is the fitness cost to the actor. This simple inequality captures the conditions under which natural selection favors altruistic alleles. Relatedness measures the probability that recipient carries a copy of the altruism allele identical by descent to the actor's allele. Between full siblings, R equals 1/2 because they share half their genes on average. Between parent and offspring, R also equals 1/2. Between cousins, R equals 1/8. The inclusive fitness framework underlies Hamilton's rule. Inclusive fitness equals an individual's direct fitness from personal reproduction plus indirect fitness from effects on relatives' reproduction weighted by relatedness. Altruists pay direct fitness costs but gain indirect fitness when helping relatives reproduce. The gene's eye view recognizes that selection acts on genes, not individuals. A gene causing altruistic behavior increases in frequency if it helps copies of itself in other individuals more than it harms copies in the altruist. Empirical examples of altruism fitting Hamilton's rule include alarm calling in ground squirrels. Squirrels emit alarm calls when detecting predators, warning others but potentially attracting predator attention to the caller. The cost to callers is small, but the benefit to warned individuals is substantial through avoiding predation. Field studies show that individuals are more likely to call when relatives are nearby, consistent with Hamilton's rule. The alarm calling persists because the benefit to relatives multiplied by relatedness exceeds the cost to callers. Hamilton's rule maintains altruism polymorphisms when Rb equals C. At this boundary condition, altruistic and selfish alleles have equal fitness, allowing both to coexist. Small changes in costs, benefits, or social structure shift the balance, potentially maintaining variation through fluctuating selection. The rule applies not just to the spread of altruism, but also to its maintenance. Understanding when Rb equals versus exceeds C is crucial for predicting whether populations will exhibit altruism polymorphisms or fixation of altruistic or selfish alleles. Life history trade-offs. Life history trade-offs arise because organisms have finite resources and energy that must be allocated among competing demands. Resources invested in one function are unavailable for others, creating negative correlations between traits. These allocation constraints shape life history evolution, determining patterns of growth, reproduction, and survival. Understanding trade-offs reveals why organisms exhibit diverse life histories rather than maximizing all fitness components simultaneously. The reproduction survival trade-off is fundamental to life history evolution. Reproduction is energetically costly, requiring resources for gamete production, courtship, mating, gestation, or parental care. These reproductive costs reduce resources available for somatic maintenance, including immune function, tissue repair, and stress resistance. Increased reproductive effort therefore typically reduces survival probability. The optimal reproductive effort balances current reproduction against future reproduction through survival. Physiological mechanisms mediate trade-offs through resource allocation decisions. At the cellular level, organisms face choices about investing resources in protecting reproductive cells versus somatic cells. High investment in reproductive cell protection increases fitness when reproductive cell maturation rates are high or reproductive cell death rates are high. However, protecting reproductive cells diverts resources from somatic maintenance, potentially reducing survival. These cellular-level decisions scale up to organism-level trade-offs between reproduction and longevity. Environmental conditions modulate trade-off relationships. In resource-poor environments, organisms may prioritize survival over reproduction, delaying sexual maturity and conserving energy for maintenance. In environments with high extrinsic mortality, selection favors rapid reproduction despite reduced maintenance investment, because individuals are unlikely to survive regardless of maintenance levels. Physiological flexibility allows individuals to adjust allocation dynamically, producing adaptive variation in life history traits within populations. Trade-offs also manifest at behavioral levels. Foraging requires energy and time that could be allocated to other activities. Territorial defense diverts resources from growth or reproduction. Mate acquisition involves costs through courtship displays or male-male combat. High activity levels increase energy expenditure, forcing trade-offs between activity and growth or storage. The optimal behavioral allocation depends on how behavior affects fitness through multiple pathways, including survival, growth, and reproductive success. Empirical demonstrations of trade-offs include experimental manipulations showing that increased reproduction reduces survival. Lizard experiments altering reproductive investment show physiological costs in terms of energy storage, immune function, and disease levels. These physiological costs translate to demographic costs through reduced survival or future reproduction. However, trade-offs are not universal. In high-resource environments, individuals may increase both reproduction and survival simultaneously by acquiring more resources rather than facing strict allocation constraints. Trade-offs emerge most clearly under resource limitation. Chapter 56: Contemporary Evolutionary Challenges. Modern environmental changes create novel evolutionary pressures, while small populations face genetic threats that can drive them toward extinction. Biological invasions occur when species are transporting beyond their native ranges and establish populations that spread and impact native communities. The extinction vortex describes positive feedback loops where small population size leads to inbreeding, genetic drift, and demographic stochasticity that further reduce population size. Epigenetic inheritance transmits information across generations through DNA methylation, histone modifications, and non-coding RNAs rather than changes to DNA sequences. Evolutionary rescue occurs when populations adapt rapidly enough to survive environmental changes that would otherwise cause extinction. Parallel evolution produces similar adaptations in independent populations through selection on standing genetic variation. These phenomena demonstrate that evolution continues shaping life in real time, with outcomes depending on population size, genetic variation, and the pace of environmental, biological invasions, and community impacts. Biological invasions involve the introduction, establishment, and spread of species outside their native ranges. Invasions proceed through multiple stages. Transport moves species across biogeographic barriers they could not cross naturally. Introduction releases species into novel environments. Some introduced species establish breeding populations. A subset of established species spread extensively, becoming invasive. Understanding which species successfully complete each stage and what factors promote or inhibit invasion is crucial for predicting and managing biological invasions. Invasive species profoundly impact native communities through multiple mechanisms. Direct predation decimates naive prey lacking evolutionary experience with novel predators. The brown tree snake introduced to Guam extirpated or drastically reduced populations of most native bird species, native fruit bats, and native lizards. The snakes encountered prey with no anti-predator defenses against snakes, allowing explosive population growth. Similar devastating predation effects occur with invasive mammals on islands where native species evolved without mammalian predators. Competition from invasive species reduces native species through resource depletion. Invasive plants often exhibit higher growth rates, greater resource use efficiency, or earlier phenology than natives, providing competitive advantages. Evidence shows that biological invasions cause shifts in species composition of communities across space and time. Invasion by exotic grass species homogenizes native plant community composition by favoring dominance of few invasive species and excluding diverse natives. The competitive displacement restructures communities, reducing diversity and altering ecosystem functions. Hybridization between invasive and native species causes genetic extinction. When invasive species interbreed with closely related natives, genetic exchange can lead to loss of the unique genetic makeup of native species through genetic swamping. This is especially problematic when invasives become much more common than natives, causing introgression of invasive genes throughout native gene pools. Of 24 federally listed species in the United States that became extinct since the Endangered Species Act, 3 went extinct through hybridization with non-indigenous species. Invasive species also impact culturally significant species, affecting indigenous peoples who depend on native biodiversity. When biological invasions restructure terrestrial and aquatic communities while simultaneously impacting culturally significant biota, invasions also restructure socio-cultural systems reliant on native bioresources. Destruction of Native American basket-weaving traditions occurred when invasive species outcompeted native plants used for baskets. Invasive fish in White Mountain Apache tribal lands pushed culturally significant native Apache trout to near extinction, forcing conservation efforts to prevent cultural as well as biological loss. The extinction vortex. The extinction vortex describes positive feedback loops that accelerate population decline and increase extinction risk in small populations. Multiple factors interact synergistically, creating self-reinforcing cycles where problems compound each other. Understanding vortex dynamics is essential for conservation because it reveals why small populations face disproportionate extinction risk beyond simple demographic limitations. Genetic factors initiate vortex dynamics through inbreeding depression and loss of genetic diversity. Small populations experience increased inbreeding as relatives mate due to limited mate choice. Inbreeding exposes recessive deleterious alleles, reducing fitness through inbreeding depression. Lower fitness causes population decline, further reducing population size and increasing inbreeding in subsequent generations. Simultaneously, genetic drift in small populations erodes genetic variation through random loss of alleles. Reduced genetic variation limits adaptive potential, preventing populations from evolving in response to environmental changes. Demographic stochasticity disproportionately affects small populations through random fluctuations in birth and death rates. In large populations, individual variation in birth and death averages out, producing predictable population growth. In small populations, chance variation in survival and reproduction of few individuals substantially affects total population size. Random skews toward male-biased sex ratios or cohorts with poor recruitment accelerate declines. A few consecutive years of low reproduction by chance can push small populations toward extinction. Environmental stochasticity creates additional extinction risk through unpredictable environmental fluctuations. Small populations are highly vulnerable to droughts, floods, temperature extremes, and disease outbreaks. A single catastrophic event can cause extinction in small, isolated populations lacking demographic buffer capacity. Large populations with broader geographic distributions are more likely to have some subpopulations surviving environmental catastrophes, but small populations lack this spatial insurance. Allee effects further accelerate vortex dynamics by creating positive density dependence where fitness declines at low density. Individuals in small, sparse populations struggle to find mates, reducing reproductive success below levels in larger populations. Cooperative behaviors, including group hunting or predator defense, fail at low density. These Allee effects create demographic declines steeper than expected from simple population dynamics, potentially creating extinction thresholds below which populations cannot recover even if conditions improve. The feedback loop among genetic, demographic, and environmental factors creates the extinction vortex. As genetic diversity declines, inbreeding depression increases, which, coupled with demographic and environmental stochasticity, reduces reproductive success and survival. This further shrinks population size, exacerbating inbreeding and genetic load, and making populations increasingly vulnerable to stochastic events. The positive feedback continues until extinction occurs, unless interventions break the cycle through genetic rescue, habitat restoration, or captive breeding. Transgenerational epigenetic inheritance. Epigenetic inheritance transmits phenotypes across generations through mechanisms other than DNA sequence changes. Three major epigenetic mechanisms exist: DNA methylation that suppresses gene expression by adding methyl groups to cytosine bases, histone modifications that alter chromatin structure and gene accessibility, and non-coding RNAs that regulate gene expression post-transcriptionally. These epigenetic marks can be transmitted from parents to offspring, providing a form of inheritance distinct from genetic inheritance. DNA methylation patterns are generally reset during reproduction through epigenetic reprogramming. Male DNA undergoes systematic demethylation in many organisms, possibly through 5-hydroxymethylcytosine intermediates. Female DNA contributes acetylated histones that replace male protamines. However, some epigenetic marks escape reprogramming, particularly maternal DNA methylation, leading to parental imprinting where gene expression depends on parent of origin. Escaped marks provide a mechanism for transgenerational epigenetic inheritance. Environmental exposures can induce epigenetic changes that persist across generations. Exposure to endocrine-disrupting compounds, including vinclozolin and DDT, causes transgenerational changes to DNA methylation, histone retention, and non-coding RNAs in sperm. These alterations associate with increased disease susceptibility in offspring not directly exposed to the chemicals. The transgenerational effects demonstrate that environmental factors experienced by ancestors can affect descendant health through epigenetic mechanisms. Histone retention in sperm provides another transgenerational epigenetic mechanism. Most histones are replaced by protamines during spermatogenesis, but some histones are retained at specific genomic locations. Post-translational modifications of retained histones, including methylation changes, can be transmitted to offspring. Changes to histone 3 lysine 4-dimethylation in mouse sperm associate with transgenerational decreases in pup survival and impaired development, demonstrating functional consequences of transmitted histone modifications. The combined action of epigenetic factors in germ cells provides mechanisms by which environmental exposures promote inheritance of pathologies across generations. RNA-directed DNA methylation and DNA methylation-directed histone retention together create epigenetic transgenerational inheritance. These mechanisms expand the scope of heredity beyond genetic sequences, showing that environments experienced by parents or even grandparents can affect descendant phenotypes through molecular modifications transmitted through germ cells. Evolutionary rescue and rapid adaptation. Evolutionary rescue occurs when populations threatened by environmental change adapt sufficiently rapidly to avoid extinction. The phenomenon is characterized by U-shaped population dynamics, where population size initially declines as the environment becomes unfavorable, then rebounds as beneficial alleles increase in frequency and adaptation proceeds. Understanding evolutionary rescue is crucial as climate change and habitat destruction accelerate, forcing populations to adapt rapidly or face extinction. The probability of evolutionary rescue depends on genetic variation, population size, and the rate of environmental change. Slower environmental change increases the likelihood of rescue by allowing more time for beneficial mutations to arise and increase in frequency. Larger populations have higher standing genetic variation and generate beneficial mutations more frequently, improving rescue probability. Pre-existing genetic variation provides the most rapid rescue because beneficial alleles are already present and can immediately respond to selection. Experimental tests demonstrate that slow environmental change leads to improved performance at extreme conditions compared to fast change. Bacterial populations subjected to gradually increasing temperatures showed higher growth rates and biomass yields at extreme temperatures than populations experiencing rapid temperature increase. The gradual change allowed adaptation to proceed, tracking the changing environment, maintaining population size and genetic variation necessary for continued adaptation. Rapid change caused severe population bottlenecks that reduced genetic variation and adaptive potential. Evolutionary rescue from new mutations takes longer and involves smaller minimum population sizes than rescue from standing genetic variation. New mutations must first arise by chance, then increase from very low frequency. This process requires many generations and involves significant extinction risk, while mutations remain rare. Standing genetic variation responds immediately to selection, producing faster rescue with larger minimum population sizes. The time until rescued populations rebound and the population nadir both depend on whether rescue derives from new mutation or standing variation. Correlated traits affect evolutionary rescue outcomes through antagonistic evolution. Adaptation to changing environments may cause correlated evolution in other traits that reduces long-term survival despite improving short-term performance. If slow environmental change causes antagonistic correlated evolution, populations experiencing slow change might show poorer long-term survival than those experiencing fast change. These trade-offs complicate predictions about optimal rates of environmental change for maximizing evolutionary rescue probability. Parallel evolution in independent populations. Parallel evolution occurs when independent populations evolve similar phenotypes through similar genetic changes in response to similar selective pressures. This repeatability demonstrates that evolution can be highly predictable when populations share genetic variation and face similar environments. Parallel evolution provides natural experiments revealing which genetic variants underlie adaptation and whether evolution follows deterministic pathways or explores diverse genetic solutions. Stickleback fish provide dramatic examples of parallel evolution across independent populations adapting to similar environments. Populations from lakes with versus without sculpin predators show extensive genomic differentiation involving approximately 1.8% of the genome overlapping 584 genes. This parallel differentiation across multiple populations indicates natural selection rather than drift, because drift cannot produce repeated parallel evolution in association with specific environmental features. The genomic changes underscore rapid and profound effects of seemingly simple biotic interactions. Standing genetic variation maintained in ancestral marine populations provides the raw material for parallel freshwater adaptation. Marine stickleback harbor alleles that become adaptive in freshwater environments. When marine fish colonize freshwater lakes, selection sorts this standing variation predictably, with the same alleles selected repeatedly in independent populations. Genome-wide analyses reveal striking determinism in both the loci involved in parallel divergence and the direction in which alleles are selected. The same genetic variants spread in multiple independent populations facing similar selection. Asymmetric sorting of standing genetic variation occurs when different environments select alleles in different directions. Basic and acidic freshwater environments select opposite alleles at loci involved in pH adaptation. Basic environments select one allele, while acidic environments select the alternative allele. This asymmetric sorting results in more numerous selective sweeps in acidic populations compared to basic populations. The directionality of selection depends on specific environmental features, producing predictable but environment-specific evolutionary outcomes. Parallel evolution demonstrates that adaptation is not infinitely flexible, but rather constrained by available genetic variation. Populations evolve similar solutions because they share ancestral variation and face similar selection. The repeatability of parallel evolution across dozens or hundreds of populations reveals general principles about adaptation, including the importance of standing genetic variation, the predictability of selection on complex traits, and the genomic architecture of adaptation. Understanding parallel evolution illuminates both the deterministic and contingent aspects of evolutionary change. Chapter 57: Hidden Diversity and Developmental Evolution. Evolution produces diversity at multiple scales, from cryptic genetic differences, invisible to morphology, to fundamental changes in body plans orchestrated by developmental genes. Cryptic species are morphologically identical or nearly identical lineages that are genetically distinct and reproductively isolated, often revealed only through molecular techniques. Evolutionary developmental biology examines how changes in developmental genes, including Hox genes, produce morphological evolution and body plan diversity. Range expansion creates unique evolutionary dynamics at expanding edges where founder effects, bottlenecks, and genetic surfing drive rapid genomic divergence. Sexual conflict generates antagonistic coevolution between males and females as each sex evolves traits benefiting itself at the expense of the other. These phenomena reveal that diversity exists at levels ranging from invisible genetic differences to fundamental developmental reorganizations, with evolutionary processes operating differently at range edges than in stable core populations. Understanding these patterns illuminates how morphological stasis can mask genetic divergence and how developmental constraints channel morphological evolution. Cryptic species and hidden diversity. Cryptic species are two or more distinct species that are morphologically indistinguishable or nearly so, classified historically as a single species until molecular or other evidence reveals their distinctness. The discovery of cryptic species demonstrates that morphological similarity does not necessarily indicate genetic similarity or interbreeding. Molecular techniques, including DNA barcoding, have revealed that cryptic species are far more common than previously recognized, substantially increasing estimates of total biodiversity. 3 hypotheses explain morphological stasis among cryptic species. The morphological constraint hypothesis proposes that developmental or genetic constraints prevent morphological divergence even as genetic divergence accumulates. Body plans or specific morphological features may be so constrained by developmental architecture that changing them is difficult despite genetic changes in other traits. The phylogenetic niche conservatism hypothesis suggests that selection maintains morphological similarity among closely related species occupying similar niches. If species remain in similar environments exerting similar selective pressures, morphology may remain conserved while neutral genetic variation accumulates. The morphological convergence hypothesis proposes that independently evolved lineages converge on similar morphologies due to similar selection pressures, making them appear morphologically identical despite independent evolutionary origins. Cryptic species pose challenges for conservation because traditional morphology-based surveys underestimate diversity. Pollutant impacts may differ among cryptic species due to differential tolerance, with some cryptic lineages declining while others persist. If the declining lineage is not recognized as distinct, conservation efforts may fail to protect it. Identifying cryptic species requires molecular surveys that reveal genetic structure within morphologically uniform groups. Understanding the distribution and ecological requirements of each cryptic lineage is essential for effective conservation. The prevalence of cryptic species varies across taxonomic groups and environments. Marine invertebrates show particularly high levels of cryptic diversity, possibly because morphological convergence is common in marine environments or because life history features, including larval dispersal, create genetic isolation without morphological divergence. Terrestrial arthropods also harbor substantial cryptic diversity. Vertebrates show fewer cryptic species, but they exist, particularly in groups with conservative morphology like salamanders or bats. Multilevel genetic diversity challenges the cryptic species concept itself. Within nominal species, genetic structure may exist at multiple hierarchical levels, from populations to deeply divergent lineages. Deciding which level of genetic divergence constitutes species boundaries becomes subjective. Some researchers advocate abandoning the cryptic species concept in favor of recognizing continuous hierarchies of genetic structure. Others maintain that cryptic species remain useful when genetic divergence is accompanied by reproductive isolation, ecological differentiation, or fixed diagnostic genetic differences. Evolutionary developmental biology and Hox genes. Evolutionary developmental biology investigates how changes in developmental processes produce morphological evolution. The field emerged from recognition that developmental genes are conserved across vast phylogenetic distances, with the same genes controlling body plan formation in organisms as different as flies and humans. Understanding how these conserved developmental toolkits produce morphological diversity requires examining how gene expression patterns, regulatory sequences, and protein functions evolve. Hox genes are transcription factors containing homeobox DNA-binding domains that pattern the body axis by specifying regional identity during development. The Hox gene cluster contains 8 to 11 genes in most animals. Arranged along chromosomes in the same order, they are expressed along the anterior-posterior body axis. This collinearity between gene order and expression domains represents a fundamental organizational principle conserved for over 500 million years. Each Hox gene specifies the identity of body segments where it is expressed, determining whether segments develop as head, thorax, or abdomen in arthropods. Changes in Hox gene expression patterns drive morphological evolution. Shifts in expression boundaries alter which segments develop particular structures. In crustaceans, changes in ultrabithorax expression patterns determine whether segments bear walking legs or swimming appendages. In insects, Hox gene expression determines segment identity, with different expression patterns producing the diverse body plans of flies, beetles, grasshoppers, and other insect orders. The evolution of these expression patterns through changes in regulatory sequences allows morphological diversification while maintaining the underlying Hox gene toolkit. Arthropods provide exceptional model systems for studying evo-devo because phylogenetic relationships are well established and powerful genetic tools exist. Insects show remarkable morphological specialization, including jumping legs in grasshoppers, grasping legs in mantises, and helmet structures in treehoppers. These novelties evolved through changes in developmental gene expression patterns. The jumping leg of grasshoppers results from altered expression of leg patterning genes that enlarge specific leg segments. Helmet structures in treehoppers represent novel outgrowths from prothoracic segments produced by expressing wing development genes in novel locations. Conservation and variation in Hox genes across animals reveals fundamental constraints on body plan evolution. The Hox cluster organization is highly conserved, with genes maintaining similar sequences and functions across phyla. This conservation suggests strong selection against changes that would disrupt coordinated body patterning. However, subtle changes in Hox protein sequences, expression levels, or regulatory interactions produce morphological diversity. The balance between conservation, maintaining functional developmental programs, and variation, producing morphological novelty shapes body plan evolution. Range expansion and edge population dynamics. Range expansion occurs when species colonize new geographic areas beyond their historical distributions. The expanding edge experiences unique evolutionary dynamics distinct from stable core populations. Repeated founder events, as small numbers of colonists establish new populations, create genetic bottlenecks. Small population sizes at the expanding front enhance genetic drift. These processes combine to produce rapid genomic divergence at range edges through mechanisms including genetic surfing. Genetic surfing occurs when alleles at the expanding front increase to high frequency through stochastic processes rather than selection. As populations expand into empty habitat, individuals at the leading edge establish new populations ahead of the expansion front. If founding groups are small, random alleles present in founders can reach high frequency in descendant populations simply through being present at the right place and time. These surfing alleles ride the expansion wave, becoming fixed or reaching high frequency at range edges while remaining rare or absent in core populations. Empirical studies demonstrate genetic surfing during experimental range expansions. Replicate expanding populations show reduced correlation in allele frequencies at edge populations compared to core populations and compared to founding populations. This reduction in correlation indicates that stochasticity drives divergence, with different random alleles increasing in different replicates. Edge populations show approximately double the reduction in correlation compared to core populations, consistent with enhanced stochastic processes at expanding fronts. The demographic characteristics of range edges enhance neutral stochasticity. Edge populations have smaller effective population sizes than core populations, increasing drift strength. Repeated founding events as the range expands create successive bottlenecks. These demographic features make edge populations more susceptible to random genetic changes. Genetic diversity generally declines from core to edge as rare alleles are lost through drift during expansion. Genetic differentiation increases more rapidly in edge populations than core populations, despite edge populations being recently derived from cores. This pattern reflects the cumulative effects of bottlenecks and drift during range expansion. Multiple expansion axes along a broad front generate little reduction in total genetic diversity because different regions maintain different alleles. However, individual edge populations become more differentiated from each other as drift operates independently in each expanding lineage. Range expansion dynamics have important implications for evolution in changing environments. Climate change forces many species to shift ranges poleward or upward in elevation. The populations at expanding range margins will be genetically distinct from core populations due to founder effects and genetic surfing. This edge population genetic structure may affect adaptive potential, with reduced genetic diversity limiting responses to novel environmental conditions encountered during expansion. Understanding these dynamics is essential for predicting how species will respond to ongoing rapid environmental changes. Sexual conflict and antagonistic coevolution. Sexual conflict arises when optimal trait values differ between males and females, creating antagonistic selection on shared genes or conflicting selection on traits involved in male-female interactions. Two forms exist: interlocus sexual conflict, where genes affecting both sexes experience opposing selection, and interlocus sexual conflict, where genes expressed in one sex affect the fitness of the opposite sex. Both forms drive rapid coevolution and may promote speciation. Interlocus sexual conflict occurs when male traits that increase male reproductive success reduce female fitness. Males may evolve traits that coerce females into mating or that increase male fertilization success at the cost of female survival or reproductive potential. Traumatic insemination in bedbugs exemplifies extreme conflict, with males piercing female abdomens with copulatory structures, causing tissue damage. Females evolve counter-adaptations, including thickened abdominal cuticle and immune responses to male seminal proteins. This creates antagonistic coevolution where male offense traits and female defense traits escalate. Experimental evolution demonstrates antagonistic coevolution. Dung fly populations evolved under enforced monogamy versus polyandry show divergent male and female adaptations. Males in polyandrous lines evolved larger testes, investing more in sperm production for sperm competition. When crossed with females from monogamous lines, polyandrous line males imposed greater costs on females. This demonstrates that sexual selection in polyandrous mating systems drives evolution of male traits harmful to females, confirming sexual conflict predictions. Plant-pollinator interactions also exhibit sexual conflict despite plants being hermaphroditic. Pollen donors can induce early stigma receptivity, advancing fertilization timing. Early fertilization benefits pollen donors by ensuring paternity, but imposes costs on recipients through reduced seed production. Crossing experiments show that pollen donors from the same population as recipients impose greater costs than donors from distant populations. This pattern is consistent with local antagonistic coevolution, where recipients evolve resistance to manipulation by local donors, while remaining susceptible to unfamiliar donors from other populations. Sexual conflict maintains genetic variation through multiple mechanisms. Antagonistic coevolution creates perpetual arms races where neither sex achieves permanent advantage. As males evolve more effective coercive traits, females evolve stronger resistance. As female resistance improves, selection intensifies on males to overcome resistance. This red queen dynamic prevents fixation, maintaining polymorphisms for offense and defense traits. Sex ratio selection additionally influences conflict dynamics, with female-biased populations favoring male coercion and male-biased populations favoring female resistance. The interaction between intralocus and interlocus sexual conflict creates complex evolutionary dynamics. Reproductive traits often experience both forms of conflict simultaneously. Males and females both benefit from successful reproduction but differ in optimal mating rates, creating interlocus conflict over mating frequency. The same traits also experience intralocus conflict because alleles beneficial in males may be detrimental in females. The combination draws sexes into perpetual cycles of escalation alternated by phases of conflict resolution. These complex dynamics help explain maintenance of sexually antagonistic genetic variation and rapid evolution of reproductive traits. Chapter 58: Evolutionary SCALES and Modern Challenges. Evolution operates across multiple temporal and organizational scales, while contemporary environmental changes create novel selective pressures with sometimes maladaptive outcomes. Microevolution describes small-scale changes within populations, while macroevolution describes large-scale changes producing new species and higher taxa, though both rely on identical evolutionary mechanisms. Evolutionary traps occur when rapid environmental change causes formerly adaptive behaviors to become maladaptive, potentially driving populations toward extinction. The genetic architecture of complex traits involves thousands of loci with small effects distributed across the genome, complicating prediction of evolutionary responses. Modularity and pleiotropy structure developmental systems with intermediate levels of integration, potentially maximizing evolvability. Circadian clocks coordinate physiology with daily environmental cycles through conserved molecular mechanisms involving transcription-translation feedback loops. These topics reveal that evolution spans scales from allele frequency changes to the origin of major groups, while organisms must navigate rapidly changing environments that can trigger maladaptive responses. Microevolution and macroevolution. Microevolution refers to evolutionary changes occurring within populations over relatively short timescales, including changes in allele frequencies, adaptation to local environments, and divergence among populations. Macroevolution refers to evolutionary changes at or above the species level, including speciation, extinction, and the origin of major morphological innovations. The distinction between micro and macro is primarily temporal and organizational scale rather than mechanistic, as both rely on mutation, selection, drift, and gene flow. The mechanisms driving microevolution are directly observable and experimentally testable. Natural selection changes allele frequencies as individuals with favorable traits produce more offspring. Genetic drift causes random fluctuations in small populations. Gene flow homogenizes populations, while reduced gene flow allows divergence. Mutation introduces new variation. These processes, operating over generations, produce measurable evolutionary changes in traits, including beak size in finches, antibiotic resistance in bacteria, and pesticide resistance in insects. Macroevolution emerges from accumulated microevolutionary changes combined with additional processes operating at higher organizational levels. Speciation occurs when populations diverge sufficiently to become reproductively isolated, transforming microevolutionary divergence into distinct species. Species selection operates when characteristics affecting speciation or extinction rates vary among species, causing some lineages to proliferate while others decline. Mass extinctions remove entire clades, fundamentally restructuring ecosystems and opening ecological opportunities for survivors. The relationship between microevolution and macroevolution has been debated. Some argue that macroevolution is simply microevolution extended over longer timescales, with no additional mechanisms required. Accumulation of small changes within lineages eventually produces morphological and genetic differences sufficient to recognize new species and higher taxa. Others argue that species-level properties, including geographic range, extinction risk, and evolvability, affect macroevolutionary patterns in ways not reducible to population-level processes. The debate centers on whether macroevolution requires explanatory principles beyond those sufficient for microevolution. Scientific organizations, including the American Association for the Advancement of Science, describe microevolution and macroevolution as quantitatively different in scale and time, but not qualitatively different in mechanism. Both involve the same fundamental processes of heredity, variation, and differential reproduction. The primary distinction is that microevolution occurs within species over short timescales, while macroevolution transcends species boundaries over longer timescales. Understanding evolution requires explaining patterns at both scales and how they connect. Evolutionary traps. Evolutionary traps occur when rapid environmental change causes organisms to prefer habitats or exhibit behaviors that were adaptive ancestrally but have become maladaptive. The mismatch between environmental cues that organisms evolved to use in decision-making and current fitness consequences of those decisions creates traps. Individuals attracted to cues indicating high-quality habitat in ancestral environments now experience lower fitness than in alternative habitats they avoid. The mechanism underlying evolutionary traps involves decoupling of habitat selection cues from habitat quality. Organisms evolve habitat preferences using cues reliably associated with fitness in ancestral environments. These evolved preferences guide individuals toward high-quality habitats and away from poor habitats. Anthropogenic environmental change can break these cue-quality relationships. Formerly reliable cues now lead organisms to poor habitats while ignoring better alternatives. The maladaptive preferences persist because evolution operates too slowly to track rapid environmental changes. Climate change may trigger evolutionary traps through multiple pathways. Rising temperatures might trigger maladaptive developmental pathways evolved for different thermal regimes. Phenological mismatches arise when organisms time reproduction based on temperature cues, but food availability now peaks earlier or later. Range shifts bring organisms into contact with novel trap habitats. Species moving poleward to track climate encounter human-modified landscapes with attractive low-fitness habitats. These interactions between climate change and evolutionary traps may selectively remove phenotypes and compromise population. The type of anthropogenic change determines extinction risk from evolutionary traps. Traps arising from degradation of existing preferred habitat are more likely to facilitate extinction than traps arising from addition of novel low-quality habitat. When existing habitat degrades, the entire population experiences reduced fitness with no escape. When novel trap habitat is added while ancestral habitat persists, some individuals avoid traps by remaining in ancestral habitat, maintaining population viability. This distinction reveals why habitat degradation poses greater extinction risk than habitat addition. Rapid evolution may buffer populations from extinction in evolutionary traps. If genetic variation exists for habitat preferences and selection against maladaptive preferences is strong enough, populations may evolve updated preferences matching current environments. The balance between selection strength, genetic variation, and generation time determines whether evolutionary rescue from traps is possible. Long-lived species with slow generation times are particularly vulnerable because evolution cannot proceed rapidly enough. Understanding when evolutionary rescue from traps is likely requires integrating population genetics with behavioral ecology. Genetic architecture of complex traits. Complex traits including height, disease susceptibility, and behavioral characteristics are influenced by thousands of genetic variants distributed across the genome. Each variant typically has small effects, with most individual variants explaining less than 1% of trait variance. This highly polygenic architecture contrasts with Mendelian traits controlled by single genes with large effects. Understanding complex trait genetics requires genome-wide approaches identifying numerous small-effect loci. Genome-wide association studies identify genetic variants associated with complex traits by testing millions of single nucleotide polymorphisms across the genome for correlation with phenotypes. GWAS of height in 5.4 million participants identified 12,111 significant variants, explaining 40% of phenotypic variation. Total SNP heritability was 45%, indicating that identified variants captured most heritable variation. This provides direct evidence that complex traits like height are extraordinarily polygenic. The evolutionary causes of high polygenicity continue to be debated. One model proposes natural selection, distributed causal variation across many loci to flatten heritability. This flattening distributes effects across functionally important genomic regions rather than concentrating effects in few genes. Because higher polygenicity reduces GWAS power, the most significant associations may not reside in the most functionally important regions. Detecting true causal variance requires increasingly large sample sizes as polygenicity increases. Quantitative trait locus mapping complements GWAS by identifying genomic regions affecting traits in crosses between divergent lines. Unlike GWAS, which examines common variation in outbred populations, QTL mapping examines segregating variation between selected strains. QTL studies often identify different loci than GWAS, suggesting that different variants segregate in different populations. Molecular QTLs, including expression QTLs, show surprisingly limited overlap with GWAS hits for complex traits, indicating complex relationships between gene expression and organismal phenotypes. Several theories explain limited overlap between molecular QTLs and GWAS. Genes affecting complex traits may have redundant enhancers buffering the impact of variants on expression, making trait-relevant EQTLs difficult to identify. Features of EQTL mapping may favor discovery of loci with lower selective constraint and functional importance, biasing results away from truly important genes. Variants affecting complex traits may act through mechanisms other than changing steady-state expression levels, including tissue-specific expression, developmental timing, or post-transcriptional regulation. Modularity and evolvability. Modularity describes organization of biological systems into semi-independent units that can vary and evolve relatively independently. Developmental modules are sets of traits that cover due to shared developmental processes. Genetic modules are sets of genes with coordinated expression or function. Modularity is often proposed as a prerequisite for evolvability because it allows evolution to modify some traits without disrupting others. However, the relationship between modularity and evolvability is more complex than simple intuition suggests. Pleiotropy, the phenomenon where single genes affect multiple traits, creates connections among traits that could constrain evolution. Mutations beneficial for one trait may be deleterious for other traits affected by the same gene, preventing independent optimization. Strong pleiotropy creates genetic correlations among traits, causing them to evolve together rather than independently. This could reduce evolvability by preventing exploration of optimal trait combinations that require independent variation in different traits. Surprisingly, pleiotropy does not necessarily reduce evolvability. Pleiotropic effects can be variable and compensatory, with different genes having different patterns of pleiotropic effects across traits. This variational pleiotropy increases the dimensionality of accessible variation, potentially enhancing evolvability. Intermediate levels of integration among characters may maximize evolvability, with some integration maintaining functional coordination while allowing sufficient independence for adaptive evolution. Complete modularity is neither necessary nor necessarily optimal for evolvability. The evolution of modularity itself is an active research area. Modularity can evolve through selection favoring genetic architectures that facilitate rapid adaptation. When environments vary such that different trait combinations are optimal in different conditions, selection favors modular architectures, allowing independent evolution of trait modules. Experimental evidence shows that selection can reorganize variational patterns, uncoupling previously associated traits when selection favors their independent evolution. However, covariation patterns can also be maintained due to internal selective pressures like allometric relationships. Empirical studies reveal complexity in the interaction between modularity and selection. Evolutionary restrictions imposed by genetic associations are rarely absolute. Selection privileging uncoupling of associated traits can reorganize variational patterns over evolutionary time. The extent to which modularity facilitates evolution depends on whether modular pleiotropy characterizes the genetic architecture and whether selection acts to modify pleiotropic relationships. Understanding evolvability requires examining not just whether modularity exists, but how genetic architecture interacts with selection to determine the accessibility of adaptive variation. The molecular circadian clock. Circadian clocks coordinate physiology and behavior with 24-hour environmental cycles through cell-autonomous molecular oscillators. The mammalian clock involves interlocking transcription-translation feedback loops generating robust daily rhythms. 4 integral clock proteins form the core. Clock and BMAL1 are activators, while PER and CRY are repressors. These proteins interact with kinases and phosphatases, regulating their localization and stability to produce approximately 24-hour oscillations. The core transcription-translation feedback loop operates through delayed negative feedback. Clock and BMAL1 heterodimerize and activate transcription of period and cryptochrome genes. PER and CRY proteins accumulate in cytoplasm, dimerize, and are phosphorylated by casein kinases. After reaching threshold concentrations, PER-CRY complexes translocate to the nucleus, where they inhibit clock BMAL1 activity, repressing their own transcription. As PER and CRY are degraded, repression is relieved and a new cycle begins. The delays inherent in transcription, translation, protein accumulation, and nuclear translocation produce the approximately 24-hour period. Circadian regulation extends beyond transcription to include chromatin remodeling and post-transcriptional mechanisms. Genome-wide surveys reveal circadian variation in chromatin modifications and RNA polymerase recruitment at nearly all actively expressed genes. Histone modifications, including H3K4 trimethylation and H3K9 acetylation, show daily rhythms, creating favorable chromatin environments for transcription. Even genes lacking robust circadian transcription show rhythmic chromatin remodeling, suggesting widespread clock influence on genome function. Non-transcriptional oscillators complement transcription-based clocks. Redox oscillations driven by peroxide-axin rhythms occur in organisms across all 3 domains of life, including bacteria and archaea lacking transcriptional clocks. These metabolic oscillations may represent an ancient timekeeping mechanism predating transcriptional clocks. The modern clock integrates both transcriptional circuits and non-transcriptional elements, including redox oscillations and protein phosphorylation cycles. The interaction between these systems produces robust timekeeping resistant to perturbations. Peripheral clocks in tissues throughout the body maintain local circadian control coordinated by the master clock in the suprachiasmatic nucleus. Genetic redundancy among clock genes and compensation by the coupled SCN network provide resiliency, maintaining clock function despite perturbations. Single knockouts of most clock genes do not completely disrupt rhythms. However, knocking out multiple paralogs or disrupting clock function in specific tissues reveals tissue-specific circadian control of physiology. This distributed clock system allows different tissues to maintain phase relationships optimized for their specific physiological functions while remaining coordinated with the external light-dark cycle. Chapter 59: Timing and Environmental Synchronization. The temporal dimension of life requires coordination with environmental cycles ranging from hours to years, while nutrient ratios constrain ecological interactions and dispersal determines species distributions. Phenology, the timing of seasonal biological events, including flowering, migration, and breeding, responds to climate change with species-specific shifts that can create mismatches with resources or mutualists. Biological stoichiometry examines how the elemental composition of organisms and their environment constrains ecological processes through nutrient ratios of carbon, nitrogen, and phosphorus. Dispersal limitation occurs when species cannot reach suitable habitats due to barriers or limited movement capacity, shaping biogeographic patterns and community assembly. Adaptive landscapes visualize fitness as topography, with peaks representing optimal genotypes and valleys representing low-fitness combinations, with evolution climbing peaks through selection or crossing valleys through drift. These concepts demonstrate how organisms must synchronize with environmental rhythms while navigating constraints imposed by elemental chemistry, spatial barriers, and genetic architecture. Understanding temporal, chemical, spatial, and genetic dimensions of ecology and evolution provides integrated perspectives on life's patterns. Phenology and climate change. Phenology describes the timing of recurring biological events, including plant flowering, insect emergence, bird migration, and animal breeding. These events evolve to synchronize with seasonal environmental changes, maximizing fitness through matching activity with resource availability. Climate change alters the seasonal template, causing phenological shifts that vary among species and potentially disrupting ecological interactions when interacting species shift at different rates. Climate warming causes earlier spring phenology across diverse taxa. Plants flower earlier in warmer years. Migratory birds arrive at breeding grounds earlier. Insects emerge from dormancy earlier. Analysis of citizen science data reveals that spring migration phenology of North American birds has advanced substantially in response to approximately half a degree Celsius of spring temperature warming between 1995 and 2014. The magnitude of phenological response varies across species and geographic regions, with less seasonal environments showing greater phenological sensitivity to temperature changes. Phenological shifts create temporal mismatches when consumers and resources change timing at different rates. If plants flower earlier, but pollinators do not advance emergence correspondingly, plants may lack pollinators, while pollinators may lack food. American robins in the Rocky Mountains now arrive 14 days earlier than 2 decades ago, but spring snowmelt has not advanced. The interval between robin arrival and snow melt has increased by 18 days, potentially creating food shortages if robins arrive before insects become available. The consequences of phenological shifts depend on life history characteristics, including voltinism, the number of reproductive cycles per year. Multivoltine species with multiple generations annually can capitalize on earlier spring emergence by fitting additional reproductive cycles into the extended growing season. Butterfly species with multiple annual generations show positive correlations between phenology advances and population growth, with early emergence facilitating range expansions. Univoltine species with single annual reproductive cycles show neutral or negative consequences of phenology advances, with habitat specialists showing abundance declines associated with earlier emergence. Mechanistically, phenology advances facilitate range expansion in flexible species, by increasing abundance through enhanced reproduction within and between years. Early emergence permits faster population growth in subsequent generations, generating positive abundance trends that enable range expansion. However, species lacking plasticity in volcanism cannot capitalize on extended growing seasons. For these less flexible species, phenology advances may inhibit range expansion by creating mismatches with resources or by exposing individuals to unfavorable conditions occurring earlier in the season. Biological stoichiometry and nutrient ratios. Biological stoichiometry examines how the balance of chemical elements, including carbon, nitrogen, and phosphorus, affects ecological interactions. Organisms require these elements in specific ratios determined by their biochemical composition. Heterotrophs consuming resources with elemental ratios differing from their body requirements must cope with elemental imbalances through selective feeding, compensatory physiology, or altered growth. These stoichiometric constraints shape food web dynamics, nutrient cycling, and ecosystem processes. The carbon to nitrogen and carbon to phosphorus ratios of organisms vary systematically across taxa. Autotrophic plants have highly variable C to N ratios ranging from 10 to 50 depending on growth conditions and tissue types. Plant leaves typically have C to N ratios between 20 and 40. Heterotrophic animals maintain more homeostatic elemental composition with narrower ranges of body C to N ratios. Herbivorous insects have C to N ratios near 10. This stoichiometric mismatch between plants with high C to N and herbivores with low C to N creates nutritional challenges for herbivores. Decomposition is strongly controlled by stoichiometric ratios of litter and decomposer organisms. When litter C to nutrient ratios exceed decomposer body ratios, decomposers face nitrogen or phosphorus limitation. They respond by immobilizing nutrients from the environment, temporarily reducing nutrient availability to plants. When litter ratios are lower than decomposer ratios, decomposers mineralize excess nutrients, releasing them to the environment. The critical elemental ratio, at which immobilization switches to mineralization, depends on decomposer growth efficiency and nutrient content. Mycorrhizal fungi mediate stoichiometric relationships between plants and soil. Approximately 90% of plant species form mycorrhizal symbioses, where fungi provide water and nutrients in exchange for plant carbon. It is estimated that roughly 80% of plant nitrogen and phosphorus comes from mycorrhizal fungi. This symbiosis allows plants to access nutrients that would otherwise be unavailable, fundamentally altering plant stoichiometry and nutrient cycling. The trophic mode of plants influences their elemental composition within the framework of mycorrhizal network functioning. Stoichiometry provides mechanistic understanding of nutrient limitation patterns. When consumer C to N ratio exceeds resource C to N ratio beyond a threshold, nitrogen limits consumer growth. Similarly, phosphorus limitation occurs when ratios exceed thresholds. These stoichiometric principles apply across organizational levels from individual organisms to ecosystems, providing a unified framework for understanding elemental cycling. Ecological stoichiometry thus bridges organismal physiology, population dynamics, and biogeochemistry. Dispersal and colonization. Dispersal, the movement of individuals from birth sites to breeding sites, profoundly influences population dynamics, gene flow, and species distributions. Limited dispersal creates spatial genetic structure, restricts range expansion, and determines which species can colonize habitat patches. Understanding dispersal mechanisms and constraints is essential for predicting species responses to habitat fragmentation and climate change. Animal movement drives variation in seed dispersal distances more than gut passage time variation. Frugivorous birds disperse seeds based on where they travel after consuming fruits. Models incorporating bird movement patterns and gut retention times predict that dispersal distances are largely driven by animal movement, with gut passage time playing minor roles. All bird species disperse some seeds at local scales under 50 meters, but saturating movement patterns restrict most dispersal to a few hundred meters around frugivorous locations. Habitat fragmentation imposes restrictions on animal movement, limiting seed dispersal. In fragmented landscapes, birds primarily move within forest patches, infrequently crossing forest boundaries. This confines seed dispersal to within fragment movements rather than among fragment dispersal. The saturating nature of animal movement in fragmented habitat explains limited seed dispersal distances. Fragments as dispersal barriers reduce connectivity between plant populations, potentially limiting gene flow and colonization of suitable habitat patches. Multiple types of barriers limit dispersal. Physical barriers, including mountain ranges, oceans, and deserts, impede organism movement based on geographic features. Rivers act as barriers for terrestrial species while facilitating aquatic dispersal. Climatic barriers emerge from temperature gradients limiting species distributions and precipitation patterns, creating barriers between arid and humid regions. Biological barriers include competitive exclusion, preventing establishment in occupied niches, lack of suitable symbionts or pollinators, limiting colonization success, and predation pressure, creating barriers for prey species. Dispersal barriers shape biogeographic patterns, including endemism and disjunct distributions. Barriers can be temporary or permanent, affecting dispersal on different timescales. Anthropogenic structures, including dams and roads, fragment habitats and disrupt natural dispersal. Climate change alters existing barriers and creates new dispersal opportunities or constraints. Understanding how barriers interact with species dispersal abilities is crucial for predicting range shifts and managing connectivity in fragmented landscapes. Adaptive landscapes. The adaptive landscape metaphor visualizes evolution as populations moving across topography where elevation represents fitness. Peaks represent high-fitness genotype combinations, while valleys represent low-fitness combinations. Evolution through natural selection moves populations uphill toward local fitness peaks. This framework, developed by Sewall Wright in the 1930s, provides intuitive understanding of how populations navigate genetic possibilities constrained by fitness consequences. Adaptive peaks are regions of high fitness in genotype or phenotype space. Populations on adaptive peaks are locally adapted, with most mutations reducing fitness and selection maintaining peak occupancy. Multiple peaks may exist if different genotype combinations produce similar high fitness. Adaptive valleys are low fitness regions between peaks. Populations must cross valleys to move between peaks, but selection opposes valley crossing because intermediate genotypes have low fitness. Genetic drift allows populations to cross adaptive valleys that selection alone cannot traverse. In small populations, drift can cause fixation of slightly deleterious alleles, moving populations downhill into valleys. If drift moves populations sufficiently far across valleys that selection toward a higher peak becomes stronger than selection back toward the original peak, populations may shift to new adaptive peaks. This shifting balance process involves three phases: drift allowing subpopulations to cross valleys, selection moving them up new peaks, and migration spreading superior adaptations to other subpopulations. The adaptive landscape changes over time as environments change. What was a fitness peak under one environmental condition may become a valley under different conditions. This dynamic landscape means populations must continuously adapt to maintain fitness as environments shift. The rate of environmental change relative to evolutionary rates determines whether populations can track moving peaks or become maladapted and decline toward extinction. Adaptive landscapes have been reconciled with quantitative genetics approaches. Fitness peaks are determined by environments and represent ecological niches or adaptive zones for populations. Phenotypically similar populations occupying clusters of nearby peaks can be viewed as higher taxonomic levels. Mathematical models combining adaptive landscapes with quantitative genetics provide testable predictions about evolutionary trajectories, rates of adaptation, and constraints on evolutionary change. These integrated frameworks help explain both microevolutionary dynamics within populations and macroevolutionary patterns across lineages. Chapter 60: RHYTHMS, Mismatches and Scaling. Biological organization spans scales from molecular clocks to ecosystem processes, with evolutionary mismatches emerging when organisms evolved for ancestral conditions encounter modern environments. Biological rhythms operate at multiple timescales, including ultradian cycles faster than 24 hours, circadian daily cycles, infradian cycles longer than a day, and circannual annual cycles. Maternal effects transmit environmental information across generations through non-genetic mechanisms, including provisioning, hormones, and behavior, representing transgenerational plasticity. Evolutionary mismatch occurs when traits adaptive in ancestral environments become maladaptive in modern environments, contributing to diseases including obesity and diabetes. Dispersal syndromes describe correlated suites of morphological, behavioral, and life history traits associated with dispersal tendency. Allometric scaling laws relate biological variables, including metabolic rate to body size through power functions, revealing fundamental constraints on organism design. These patterns demonstrate that life operates across vast scales with coordination mechanisms at each level, while evolutionary history sometimes constrains adaptation to novel conditions. Biological rhythms across timescales. Biological rhythms coordinate physiology and behavior, with environmental cycles operating at multiple timescales. Beyond the well-studied circadian 24-hour rhythms, organisms exhibit ultradian rhythms with periods shorter than 24 hours, infradian rhythms with periods longer than a day but less than a year, and circannual rhythms spanning annual cycles. Each rhythm type serves distinct functions, synchronizing different biological processes with appropriate environmental periodicity. Ultradian rhythms occur more frequently than daily cycles. The basic rest activity cycle operates on approximately 90-minute periods, alternating between high and low arousal states throughout the day. During sleep, this manifests as cycles through sleep stages. During waking, ultradian rhythms influence alertness and performance, with peaks approximately every 90 minutes. Hormone secretion shows ultradian pulsatility, with growth hormone, cortisol, and reproductive hormones exhibiting episodic release patterns. These rapid cycles allow fine-tuned regulation responsive to immediate physiological demands. Circadian rhythms coordinate daily patterns of activity, metabolism, and physiology with 24-hour light-dark cycles. These daily rhythms evolved to anticipate predictable environmental changes, including temperature fluctuations, predation risk variations, and food availability patterns. Circadian regulation extends beyond sleep-wake cycles to encompass virtually all physiological processes. Body temperature, hormone secretion, immune function, and metabolism all show robust circadian variation, orchestrated by molecular clocks in cells throughout the body. Infradian rhythms operate on timescales longer than circadian but shorter than annual. The menstrual cycle represents a prominent infradian rhythm with approximately 28-day periodicity, though normal ranges span 21 to 35 days. This reproductive cycle coordinates hormonal fluctuations, preparing the body for potential pregnancy. Environmental factors can influence menstrual timing, with synchronization occurring among women spending time together, possibly through pheromone-mediated hormonal activation. Infradian rhythms influence brain function, metabolism, immune responses, microbiome composition, and stress. Circannual rhythms span annual cycles coordinating seasonal behaviors, including hibernation, migration, and reproduction, with yearly environmental changes. These endogenous rhythms persist even in constant laboratory conditions, demonstrating internal timekeeping mechanisms. Photoperiod changes provide the primary entrainment cue, with changing day length signaling seasonal progression. Circannual rhythms allow organisms to prepare for seasonal changes before they occur, initiating physiological preparations for migration or reproduction weeks before environmental conditions necessitate these activities. The hierarchical organization of rhythms from ultradian to circannual creates nested temporal structure synchronizing biology across timescales. Maternal effects and transgenerational plasticity. Maternal effects occur when the maternal phenotype or environment influences offspring phenotype beyond genetic inheritance. These effects represent transgenerational plasticity spanning generations, allowing environmental information experienced by mothers to shape offspring development. Maternal effects evolve when maternal environments provide reliable cues about conditions offspring will encounter, allowing adaptive preparation. Mechanisms of maternal effects include differential provisioning, hormones transferred during development, and behavioral interactions. Egg size variation represents a common maternal effect in many taxa, with larger eggs producing larger offspring with enhanced survival. Maternal hormones including steroids and thyroid hormones transferred to eggs or through placental connections influence offspring development, metabolism, and behavior. In mammals, maternal care behaviors including nursing duration and grooming frequency affect offspring physiology and stress responses through effects on neuroendocrine development. Both maternal and paternal environments contribute to transgenerational plasticity. Studies separating sire and dam contributions to thermal transgenerational plasticity reveal that both parents influence offspring growth rates. The contributions are additive rather than multiplicative, with no three-way interaction between dam, sire, and offspring environments. This suggests mean parent environment may sufficiently predict transgenerational effects. Simplifying models of transgenerational plasticity. The contexts favoring maternal effects parallel those favoring within-generational plasticity. Maternal effects evolve when environments are heterogeneous, costs of plasticity are low, and environmental cues are informative about conditions offspring will experience. However, maternal effects face unique challenges. Maternal environments must predict offspring environments with sufficient accuracy that adaptive preparation outweighs costs of mismatches when predictions fail. Time lags between maternal experience and offspring responses create opportunities for environmental changes, rendering maternal effects maladaptive. Theoretical models predict when organisms should rely on maternal effects versus within-generational plasticity. When environmental predictability across generations is high, maternal effects allow offspring to match environments without costly sensing or developmental adjustments. When environments change rapidly between generations, within-generational plasticity provides more accurate matching. Future mothers who are maladapted at birth may use adaptive within-generational plasticity to produce adult phenotypes matching prevailing conditions, then transmit appropriate maternal effects to offspring. The optimal combination of maternal effects and within-generational plasticity depends on environmental predictability, plasticity costs, and information reliability. Evolutionary mismatch and modern disease. Evolutionary mismatch occurs when traits adaptive in ancestral environments become maladaptive in modern environments due to rapid environmental changes outpacing evolutionary adaptation. This framework explains rising prevalence of non-communicable diseases, including obesity, cardiovascular disease, and type 2 diabetes that were rare historically but are now common. Understanding mismatch provides insights into disease etiology and potential interventions. The thrifty genotype hypothesis proposes that genes promoting efficient energy storage were adaptive during human evolutionary history, characterized by food scarcity and unpredictable availability. Individuals who efficiently stored energy as fat during abundant periods survived famines better than those who did not. This created selection for genes promoting fat storage, insulin resistance during fasting to preserve glucose for the brain, and strong appetites for calorie-dense foods. These adaptations are now maladaptive given constant availability of energy-dense, processed foods and sedentary lifestyles. Two mechanisms generate evolutionary mismatch. First, Mismatch arises when environments change beyond the range experienced during lineage evolution. The high availability of appetite-rewarding energy-dense foods and inclusion of processed foods with high-fructose corn syrup as dietary staples represent environmental changes exceeding anything encountered during human evolution. Obesity and comorbidities, including type 2 diabetes, largely reflect physiology not having evolved to cope with radical changes in nutritional environments. Second, mismatch emerges when traits adaptive in one context become expressed in inappropriate contexts, such as stress responses evolved for acute physical threats being triggered by chronic psychosocial stresses. Genetic studies combining genomic tools with analysis of subsistence populations experiencing rapid lifestyle changes can identify loci associated with mismatch-related disease risk. Comparing populations maintaining traditional lifestyles with populations adopting Western lifestyles reveals genetic variants influencing susceptibility to obesity, diabetes, and cardiovascular disease under modern conditions. Variants protective in traditional contexts may become risk factors in modern environments, revealing gene-environment interactions underlying mismatch diseases. Evolutionary mismatch affects multiple physiological systems. Modern sedentary lifestyles mismatch with activity patterns that characterized most of human evolution. Reduced physical activity contributes to metabolic syndrome, cardiovascular disease, and musculoskeletal disorders. Artificial lighting disrupts circadian rhythms evolved to synchronize with natural light-dark cycles, contributing to sleep disorders, metabolic dysfunction, and mood disorders. Hygiene and antibiotic use alter microbiome composition relative to ancestral states, potentially contributing to autoimmune diseases and allergies through effects on immune system development. Dispersal syndromes. Dispersal syndromes describe correlated suites of traits associated with dispersal tendency. Dispersal is not a single trait, but rather involves multiple components including departure propensity, movement behavior during dispersal, and settlement decisions. Life history, morphological, and behavioral traits cover with dispersal, creating integrated phenotypic syndromes. Understanding dispersal syndromes is critical for predicting demographic and genetic consequences of movements. Dispersers and philopatric individuals exhibit different age-specific life history traits. Young dispersive female lizards show higher reproductive effort than young philopatric females, consistent with theoretical predictions. The early high investment in reproduction of dispersive females trades off with earlier onset of senescence compared to philopatric females. Young dispersive females also produce smaller offspring in lower body condition than young philopatric females. These patterns demonstrate that dispersal syndromes vary with age, with different trait associations in young versus old individuals. Life history traits predict dispersal better than morphological traits in many systems. Analysis of butterflies using 4 different dispersal measurements relating to individual movement rates, distances, and gene flow among populations reveals that life history traits strongly predict dispersal. Predictions from life history traits are up to 5 times more precise than predictions from wing size alone. Slopes of observed versus predicted dispersal range from 0.81 to 0.95 for life history trait models, far exceeding wing size-only models. Dispersal syndromes reflect both correlated selection and genetic correlations among traits. Traits facilitating successful dispersal, including enhanced mobility, exploratory behavior, and stress tolerance, are favored in dispersers. Traits favoring local competitive ability, including larger size, territoriality, and resource defense, are favored in philopatric individuals. If genes affecting dispersal also affect other traits through pleiotropy, genetic correlations create integrated dispersal syndromes. Understanding whether syndromes arise primarily through correlated selection or genetic constraints requires experimental genetic analyses. The existence of dispersal syndromes has important ecological and evolutionary consequences. Syndromes affect population dynamics by linking dispersal to demographic rates. High dispersal associated with high reproductive effort influences colonization dynamics and range expansion rates. Dispersal syndromes also affect evolution by creating genetic correlations that constrain independent evolution of dispersal and life history traits. These constraints may slow adaptation to fragmented habitats, where optimal dispersal strategies differ from ancestral conditions. Allometric scaling and body size. Allometric scaling describes how biological variables relate to organism mass through power laws of the form y equals y sub 0 times m to the power b, where y is the biological variable, m is mass, y sub 0 is a normalization constant, and b is the allometric exponent. These scaling relationships reveal fundamental constraints on organism design imposed by geometry, physics, and biology. Understanding allometry illuminates why organisms of different sizes exhibit systematically different physiology, ecology, and life histories. Geometric constraints create baseline expectations for scaling exponents. If organisms were geometrically similar at all sizes, surface area would scale with mass to the power 2/3 and volume would scale with mass to the power 1. Assuming constant density, linear dimensions scale with mass to the power 1/3. Biological processes depending on surface area, such as heat loss or resource uptake through surfaces, are expected to scale with exponents near 2/3. Processes depending on volume or mass scale with exponents near 1. Metabolic rate scaling deviates from simple geometric predictions. Kleber's law describes metabolic rate scaling with mass to the power 3/4 across diverse taxa, falling between the 2/3 predicted by surface area and the 1 predicted by mass. Various theories explain 3/4 power scaling, including resource distribution network models proposing that fractal-like circulatory and respiratory systems create 3/4 scaling. However, metabolic scaling shows substantial variation around 3/4, with exponents ranging from 2/3 to 1 depending on taxa, measurement conditions, and activity levels. Metabolic level boundaries hypothesis proposes that geometric properties of surface area and volume help explain why the scaling exponent b varies between 2/3 and 1 in isomorphic organisms. Variable metabolic scaling breaks from universal laws, with context-dependent exponents reflecting different limiting processes. Isometric organisms with similar body shapes across sizes may show 2/3 scaling when surface area-dependent processes limit metabolism. Organisms with allometric shape changes or variable resource-demanding processes show different exponents. This framework accommodates empirical diversity in scaling relationships. Scaling relationships extend beyond metabolism to life history traits. Larger organisms live longer, reproduce later, and have slower population growth rates than smaller organisms. These relationships emerge partly from metabolic constraints and partly from ecological factors. Size affects mortality risk through predation vulnerability, starvation resistance, and competitive ability. Allometric relationships create fundamental trade-offs structuring life history evolution, with body size representing a master trait influencing most fitness components through scaling relationships. Understanding allometry thus provides unified perspective on biological diversity across size scales spanning microbes to whales. Chapter 61: Networks and Optimization. Ecological systems and evolutionary processes form complex networks where structure determines dynamics and organisms optimize behavior within constraints. Ecological networks, including food webs, represent species interactions with network properties affecting stability and resilience to perturbations. Genome evolution through whole genome duplication creates redundant genetic material, enabling divergence and functional innovation. Behavioral ecology applies optimization theory to foraging decisions, predicting how animals balance energy gain against costs, including travel time and predation risk. Habitat selection theory examines how organisms distribute themselves across patches, with the ideal free distribution predicting individuals equalize fitness across habitats through density-dependent settling. These frameworks reveal that biological organization at multiple scales reflects optimization under constraints, with network architecture shaping ecosystem function and individual decision-making maximizing fitness within ecological and physical limitations. Food web structure and stability. Food webs represent networks of predator-prey interactions within communities. Each species is a node connected to others by directed links representing energy flow from prey to predators. The structure of these networks, including properties such as connectance, modularity, and the distribution of interaction strengths, determines community stability and responses to perturbations. Understanding food web architecture illuminates mechanisms maintaining biodiversity in complex ecosystems. Trophic coherence measures the degree to which species organize into discrete trophic levels. Perfectly coherent food webs have all species at integer trophic levels, with energy flowing smoothly from basal producers through consumers to top predators. Real food webs show intermediate coherence, with omnivory creating fractional trophic positions. Trophic coherence strongly determines stability, with more coherent webs exhibiting greater resilience to perturbations. The mechanism involves reduced feedback loops and cleaner separation of timescales at different trophic levels. Mathematical analysis proves that maximally coherent networks with constant interaction strengths are always linearly stable. This provides theoretical foundation for the observation that natural food webs tend toward coherent structures. Simple models capturing trophic coherence accurately reproduce stability and structural features of empirical food webs. Remarkably, these models show stability can increase with size and complexity, contradicting early theory predicting larger networks should be less stable. The distribution of interaction strengths is highly skewed in natural food webs with many weak and few strong links. This pattern promotes stability by allowing weak interactions to dampen oscillations that strong interactions might otherwise amplify. Experimental manipulations confirm that the specific pattern of strong and weak interactions observed in nature confers stability. When interaction strength distributions are randomized while maintaining network topology, stability decreases dramatically compared to natural patterns. Foundation species enhance food web complexity through non-trophic facilitation. Analysis of 58 food webs from terrestrial, freshwater, and coastal systems reveals that foundation species, including habitat-forming plants and sessile invertebrates, consistently increase species richness, link density, and mean trophic level. Foundation species facilitate associated species across the trophic network rather than randomly, with carnivores receiving disproportionate facilitation. This creates longer food chains and more complex web architecture than would exist without foundation species. Genome duplication and gene family evolution. Whole genome duplication provides raw genetic material enabling evolutionary innovation through divergence of duplicate gene copies. Polyploidy events, where entire genomes are duplicated, have occurred repeatedly across plant and animal lineages. Following duplication, most genes experience one of several fates: loss through non-functionalization, retention of redundant function, subfunctionalization, where each copy performs part of the ancestral function, or neofunctionalization, where one copy acquires novel function. Duplicate genes increase expression diversity between closely related species and within allopolyploids. Analysis comparing duplicate and single-copy genes reveals that duplicates show higher rates of expression divergence between species. Approximately 18% of duplicate genes are differentially expressed between closely related cotton species compared to only 13% of single-copy genes. This elevated divergence suggests duplicates experience relaxed constraint, allowing exploration of expression space. The mechanisms underlying rapid expression divergence of duplicates involve both regulatory sequence changes and epigenetic modifications. Duplicate genes tend to contain TATA boxes in promoter regions more frequently than single-copy genes, facilitating binding of transcription factors. Duplicates show less DNA methylation in promoters, allowing more dynamic transcriptional regulation. These features enable duplicates to respond more strongly to environmental cues and developmental signals than constrained single-copy genes. Diploidization following whole genome duplication returns genomes to disomic inheritance through chromosomal rearrangements, gene loss, and subgenome dominance. This process occurs relatively quickly in the first few million years after duplication. However, many duplicate pairs are retained long-term. Analysis of 141 plant genomes reveals that whole genome duplication genes show lower sequence divergence than tandem or proximal duplications, indicating stronger purifying selection on duplicates retained after ancient polyploidy. Gene duplication contributes to adaptive evolution by expanding regulatory networks and increasing morphological diversity. Duplicate genes allow populations to explore larger regions of phenotypic space because mutations affecting one copy do not compromise the function provided by the other copy. This genetic redundancy buffers against deleterious mutations while allowing evolutionary experimentation. Expression divergence between duplicates expands gene regulatory networks, facilitating organismal adaptation to changing environments. Optimal foraging theory. Optimal foraging theory applies optimization principles to animal foraging behavior, predicting decisions animals make to maximize energy intake per unit time. The theory assumes natural selection has shaped foraging strategies to maximize fitness-relevant currencies, including net energy gain. While real animals face numerous constraints and imperfect information, optimal foraging models successfully predict broad patterns of foraging behavior across diverse taxa. The optimal diet model predicts which prey types foragers should include in their diet. The model ranks prey by profitability, defined as energy gain divided by handling time. The optimal strategy always includes the highest-ranked prey type when encountered. Lower-ranked prey should be included only if their encounter rate is sufficiently high that searching for higher-ranked prey would yield lower overall intake rates than accepting lower-ranked prey opportunistically. Marginal value theorem addresses patch foraging where resources occur in discrete patches requiring travel between them. As foragers deplete a patch, their intake rate declines due to diminishing returns. The theorem predicts foragers should leave a patch when the instantaneous intake rate falls to the average intake rate achievable in the environment, including travel time. This maximizes long-term energy gain by balancing benefits of continued exploitation against costs of depleting patches. Optimal foraging time in a patch depends on travel time between patches and initial patch quality. When travel time is long, foragers should stay longer in patches to amortize travel costs, tolerating lower instantaneous rates before departing. When patches vary in initial quality, high-quality patches warrant longer residence times because they maintain higher instantaneous rates through more depletion. The graphical solution involves tangent lines from travel time intercepts to gain functions representing cumulative energy acquired in patches. Extensions of basic optimal foraging theory incorporate additional biological realities. Central place foraging models animals returning to fixed locations like nests between foraging bouts. These models predict selective foraging on high-quality items when far from the central place because transport costs make low-quality items unprofitable. Predation risk models incorporate survival costs alongside energy gains, predicting shifts from optimal energy-maximizing patches to safer but less profitable patches when predation risk is high. Resource renewal models address dynamic patches where resources regenerate, predicting revisitation patterns. Ideal free distribution and habitat selection. The ideal free distribution describes how organisms distribute themselves across habitats varying in quality. The model assumes individuals are ideal in accurately assessing habitat quality and predicting fitness consequences, and free to move without constraints between habitats. Under these assumptions, individuals settle in habitats to equalize fitness across the landscape despite different intrinsic habitat qualities. This occurs through negative density dependence, where increasing population density reduces per capita fitness. Habitat matching emerges as a key prediction of ideal free distribution. The ratio of individuals in different habitats should equal the ratio of resources in those habitats. When one habitat has twice the resources of another, it should support twice as many individuals at equilibrium. The mechanism involves density-dependent fitness. As high-quality habitat fills, competition reduces per capita resources until fitness equals that achievable in lower-quality habitat. At this point, no individual benefits from moving between habitats. Empirical tests of ideal free distribution using fitness data rather than assuming fitness differences provide strong tests. Studies of northern pike in connected lake basins reveal that dispersal patterns match ideal free predictions based on basin-specific intrinsic fitness estimates. Pike move preferentially from basins with lower intrinsic fitness to those with higher intrinsic fitness, with dispersal rates equalizing fitness between basins over time. These patterns persist across 50 years, demonstrating that ideal free distributions can characterize long-term population spatial structure. Deviations from simple ideal free distribution occur when assumptions are violated. Differences in competitive ability create ideal despotic distributions where dominant individuals monopolize high-quality habitat, forcing subordinates into poorer habitat. Travel costs between habitats create ideal preemptive distributions where early arrivals gain advantages. Imperfect information about habitat quality causes errors in habitat selection, particularly for long-lived species where habitat quality varies over lifespans. Understanding when and why real distributions deviate from idealized predictions illuminates constraints on habitat selection. Habitat selection operates over multiple spatial scales, from microhabitat within territories to landscape-level distribution across regions. At fine scales, individuals select territories or home ranges within habitats. At broad scales, populations distribute across habitat types. Hierarchical habitat selection models recognize that individuals first select regions, then habitats within regions, then specific sites within habitats. Understanding this hierarchy is essential for predicting species distributions and responses to habitat modification, including climate-driven range shifts. Chapter 62: Assembly, Constraints, and Coexistence. Ecological communities assemble through filtering processes, while evolutionary change faces constraints, yet diverse species coexist through niche partitioning. Punctuated equilibrium proposes that evolution proceeds through long periods of morphological stasis, interrupted by rapid change during speciation events rather than gradual continuous change. Population viability analysis uses demographic models to assess extinction risk and guide conservation by identifying critical population thresholds and management interventions. Community assembly occurs through environmental filtering, removing species lacking appropriate physiological tolerances, and biotic sorting through competition and facilitation. Evolutionary constraints, including pleiotropy and canalization, limit the directions evolution can take despite variation and selection. Resource partitioning allows competing species to coexist by differentiating niches and reducing direct competition. These concepts demonstrate that both ecological communities and evolutionary trajectories are constrained by history, genetics, and interactions, yet constraint and competition drive diversification, enabling coexistence. Punctuated equilibrium. Punctuated equilibrium challenges the traditional view of phyletic gradualism, where species evolve slowly and continuously over time. The model, proposed by Niles Eldredge and Stephen J. Good in 1972, describes evolution as long periods of morphological stasis interrupted by geologically rapid speciation events. This pattern better explains observations from the fossil record, where species often appear suddenly and remain unchanged for millions of years before disappearing. The mechanism underlying punctuated equilibrium involves allopatric speciation in small isolated populations. Geographic isolation of peripheral populations from main populations allows intense natural selection or genetic drift to cause rapid morphological change. Small population size amplifies drift effects and increases the probability that beneficial mutations sweep to fixation. These isolated populations may evolve into distinct species relatively quickly, then potentially expand their ranges. The fossil record captures this as sudden appearance of new forms. Stasis characterizes most species' existence, with morphology remaining essentially unchanged for millions of years despite environmental changes. This observation challenges the expectation that continuous selection should produce continuous evolutionary change. Multiple mechanisms may explain stasis, including stabilizing selection, maintaining optimal phenotypes, developmental constraints preventing morphological change, and ecological constraints where available niches are filled. Stasis may also reflect gene flow from large, stable populations, swamping local adaptation in peripheral populations. The fossil record supports punctuated equilibrium patterns in many lineages. Species frequently show little morphological change from their first appearance to their disappearance, spanning millions of years with minimal evolution. Transitional forms between species are rare, consistent with rapid change in small, isolated populations unlikely to leave fossils. However, examples of gradual evolution also exist in the fossil record, suggesting evolutionary tempo varies among lineages and contexts. Punctuated equilibrium has implications for understanding macroevolution. If most morphological change occurs during speciation events, then factors affecting speciation rates, including geographic structure and climate variability, become critical for understanding long-term evolutionary patterns. The model emphasizes that evolutionary pace may be intrinsic to certain groups rather than solely responding to environmental pressures. It also highlights that microevolutionary processes within populations may not directly predict macroevolutionary patterns if most change is concentrated in speciation. Population viability analysis. Population viability analysis uses demographic modeling to assess extinction risk and guide conservation decisions. PVA simulates population trajectories under various scenarios, incorporating biological parameters, including reproduction and survival rates, environmental stochasticity, catastrophes, and management interventions. The approach provides quantitative estimates of extinction probability over specified time horizons and identifies which parameters most strongly influence viability. Minimum viable population size represents a key PVA output, estimating the population size theoretically ensuring low long-term extinction risk. MVP thresholds vary depending on assumed catastrophe regimes, with populations requiring larger sizes to buffer against frequent severe catastrophes. For endangered Roanoke logperch, estimated MVP ranged from 200 to 4,200 individuals, depending on catastrophe assumptions. This uncertainty reflects challenges in parameterizing rare events, yet highlights that MVP is context-dependent rather than a fixed value. PVA for endangered species identifies populations with greatest extinction risk. Analysis of threatened bird species in New Zealand assessed viability of the national population and 3 management units. Results revealed that 1 management unit faced critical extinction risk, requiring urgent intervention. Such spatially explicit analyses guide resource allocation by identifying where conservation efforts provide greatest benefit. PVA also evaluates potential effectiveness of proposed conservation measures before implementation. Sensitivity analysis within PVA frameworks identifies which parameters most influence extinction risk. For Roanoke logperch, extinction risk was highly sensitive to population growth rate, carrying capacity, and catastrophe regime. In contrast, demographic augmentation through translocations did little to reduce risk. These findings suggest management should prioritize increasing carrying capacity through habitat restoration and reducing fish kills rather than moving individuals between populations. Understanding parameter sensitivity focuses research and management efforts. Limitations of PVA include data requirements and parameter uncertainty. Accurate projections require detailed demographic data, often unavailable for rare species. Uncertainty in key parameters like growth rates and catastrophe frequencies propagates through models, yielding uncertain extinction risk estimates. Small changes in assumed values can shift conclusions about viability. Despite limitations, PVA remains valuable for comparing relative extinction risks across populations, evaluating alternative management strategies, and identifying critical research needs to reduce uncertainty in factors most affecting viability. Community assembly rules. Community assembly describes processes determining which species from regional pools colonize and persist in local communities. Assembly occurs through hierarchical filtering, with abiotic environmental factors determining fundamental niche requirements and biotic interactions determining realized niche occupancy. Understanding assembly processes is crucial for predicting how communities respond to environmental change and how restoration efforts can facilitate desired community states. Environmental filtering removes species lacking physiological tolerances for local abiotic conditions. Temperature, moisture, pH, and other physical factors create fundamental niche filters. Species unable to tolerate local conditions cannot establish regardless of biotic interactions. Environmental filtering predicts trait convergence, where coexisting species share traits allowing them to tolerate local conditions. Harsh environments exert strong filtering, producing communities of species with similar stress tolerance traits. Biotic interactions including competition, predation, and facilitation impose realized niche filters. After passing environmental filters, species must persist in the interactive milieu. Competition may exclude species too similar to established residents, predicting trait divergence. Facilitation by foundation species or ecosystem engineers can enable species to occupy habitats they could not colonize independently. The relative importance of environmental versus biotic filtering varies across environmental gradients and successional stages. Neutral processes operate alongside niche-based filtering. Stochastic colonization, ecological drift in abundance, and random extinctions cause communities to diverge even under identical environmental and biotic conditions. The debate between neutral and niche-based assembly frameworks has evolved toward recognizing both contribute. Neutral processes may dominate in communities of functionally similar species, while niche processes dominate when species differ substantially in traits affecting fitness. Empirical tests of assembly rules compare observed community patterns to null models simulating random assembly. Meta-analyses of plant communities reveal mixed support for non-random assembly. Some studies find evidence for limiting similarity where coexisting species are more different than random expectations, supporting competition-based assembly rules. Others find trait convergence consistent with environmental filtering. Still others find patterns indistinguishable from random, suggesting individualistic responses. The heterogeneity of results may reflect methodological differences, scale dependence, or genuine variation in assembly processes across systems. Evolutionary constraints. Evolutionary constraints limit the directions and rates at which populations can evolve despite genetic variation and selection. Constraints arise from multiple sources, including genetic correlations among traits through pleiotropy, developmental programs channeling variation into limited phenotypic dimensions, and lack of genetic variation in particular directions. Understanding constraints explains why some evolutionary transitions are common while others never occur. Pleiotropy, where single genes affect multiple traits, creates genetic correlations constraining independent evolution. When traits are genetically correlated, selection on one trait causes correlated responses in others. If pleiotropic effects oppose selection, traits may fail to respond despite genetic variation and strong selection. Life history traits show extensive pleiotropy with trade-offs between reproduction and survival arising from shared genetic and physiological mechanisms. These correlations constrain life history evolution, maintaining variation despite strong directional selection. Canalization describes developmental robustness to genetic and environmental perturbations. Developmental processes buffer phenotypes against variation in genotype and environment, producing consistent outcomes despite underlying variation. Canalization evolves through long-term stabilizing selection, favoring optimal phenotypes. However, canalization also emerges as a byproduct of developmental network structure even without selection. Regulatory networks with negative feedback and redundancy automatically produce canalized phenotypes. The developmental process, modeled as networks of interacting transcriptional regulators, constrains genetic systems toward canalization. Network topology, including feedback loops and parallel pathways, creates attractors in developmental space toward which development flows despite perturbations. These network properties make certain phenotypes highly probable and others nearly impossible to produce. Developmental constraints thus limit phenotypic variation that selection can act upon, biasing evolutionary. Historical contingency creates constraints through path dependence, where current possibilities depend on past evolutionary decisions. Body plans established early in lineage history constrain subsequent evolution, with arthropods always having jointed exoskeletons and vertebrates always having internal skeletons. Developmental programs inherited from ancestors channel variation, making certain modifications easier than others. These phylogenetic constraints explain why lineages show characteristic patterns of variation despite occupying diverse environments. Resource partitioning and coexistence. Resource partitioning describes how competing species reduce niche overlap by differentiating resource use, allowing stable coexistence. The competitive exclusion principle states that species with identical niches cannot coexist indefinitely, with one eventually excluding the other. Resource partitioning evolves through character displacement, where competition drives divergence in traits affecting resource acquisition. Understanding partitioning mechanisms explains how diverse species coexist in communities. Multiple dimensions of niche space allow partitioning. Species may partition resources by type, consuming different food items or utilizing different nutrient sources. Spatial partitioning occurs when species forage in different microhabitats or vertical strata within habitats. Temporal partitioning involves species active at different times of day or utilizing resources during different seasons. Behavioral partitioning includes different foraging modes or activity patterns, reducing encounter rates between competitors. Competition and resource diversity interact to shape niche variation. The resource diversity hypothesis predicts that greater variety of available resources favors niche expansion and divergence among consumer species. Empirical tests reveal that interspecific competition causes niche contraction and divergence, with effects strongest when resource diversity is high. This occurs because greater ecological dimensionality provides more axes along which species can diverge, facilitating stable coexistence through multidimensional niche differentiation. Niche breadth responds dynamically to competitive environments. When strong competitors are present, species show narrower niches concentrated on resources where they have competitive advantages. When competition is weak, species expand niche breadth, exploiting broader resource spectra. This plasticity in niche use allows species to adjust to varying competitive regimes. Intraspecific niche variation also increases under low interspecific competition, as individual specialization diversifies resource use within populations. The balance between niche differentiation and similarity determines community structure. Too much similarity causes competitive exclusion, reducing diversity. Too much differentiation suggests weak interactions and potentially insufficient niche packing. Natural communities show intermediate levels of overlap, where species are similar enough to compete but different enough to coexist. This balance reflects evolutionary and ecological sorting processes that assemble communities from regional pools, while maintaining species diversity through niche partitioning. Chapter 63: Fitness and Population Dynamics. Evolutionary success depends on fitness components, while spatial heterogeneity in habitat quality creates source-sink dynamics, and coevolutionary interactions drive escalating adaptations. Fitness components including survival, mating success, and fecundity combine to determine lifetime reproductive success. Source-sink dynamics emerge when high-quality habitats produce demographic surpluses that disperse to low-quality habitats where populations cannot persist without immigration. Evolutionary arms races between predators and prey or hosts and parasites drive reciprocal adaptations in offense and defense traits. Honest signaling evolves when costs prevent low-quality individuals from producing exaggerated signals, maintaining signal reliability despite conflicts of interest. These processes demonstrate that fitness is a complex multidimensional trait. Spatial structure fundamentally affects population persistence, and coevolution can generate perpetual escalation or stable equilibria depending on genetic constraints and costs. Understanding fitness components reveals what selection acts upon, while source-sink theory explains population dynamics in heterogeneous landscapes. Fitness components and reproductive success. Fitness in evolutionary biology refers to an individual's ability to transmit alleles to subsequent generations. Despite being central to evolutionary theory, fitness remains challenging to define precisely and measure accurately. Researchers typically quantify proxies for fitness, including survival, growth, or reproductive success, but determining true lifetime fitness is difficult, especially for long-lived species. The abiotic and biotic environment strongly affects fitness expression, creating spatial and temporal heterogeneity that drives adaptation. Fitness can be decomposed into multiple components that contribute to total reproductive success. In a simple life cycle, zygotes either survive to adulthood or do not. Survivors attempt to court and mate. Successful maters produce offspring. Fitness differences arise from differences in performance at any stage. Viability, the probability of surviving to reproductive age, represents the first component. Mating success, the ability to acquire mates, represents the second component. Fecundity, the number of offspring produced, represents the third component. The interactions among fitness components vary depending on selective context. Sometimes components show positive covariation, where individuals that survive well also mate successfully and produce many offspring. Other times, components show antagonistic pleiotropy, where increases in one component reduce others. The classic life history trade-off between reproduction and survival exemplifies antagonistic relationships, where investing energy in current reproduction reduces survival or future reproduction. Understanding how selection shapes adaptations requires measuring all fitness components. Absolute fitness measures the expected number of offspring an individual produces. An individual producing 3 offspring, while the population average is 2, has absolute fitness of 3. However, evolution depends on relative fitness, the fitness of a genotype compared to other genotypes in the population. The same individual with absolute fitness 3 has relative fitness of 1.5 if the population mean is 2. Selection acts on relative rather than absolute fitness because evolutionary change depends on differential reproductive success. Measuring fitness in natural populations faces practical challenges. Long generation times prevent observing complete lifetimes for many species. Environmental variation causes fitness to fluctuate temporally, making single-year measurements unrepresentative. Spatial heterogeneity creates fitness differences across locations. Molecular markers allow tracking allele transmission, providing genetic measures of fitness that capture realized reproductive success. Integrating demographic and genetic approaches yields comprehensive fitness estimates, accounting for both offspring number and offspring quality. Source-sink dynamics. Source-sink dynamics describe metapopulation systems where demographic surpluses in high-quality habitats support populations in low-quality habitats through dispersal. Sources are habitats where births exceed deaths, producing net exporters of individuals. Sinks are habitats where deaths exceed births, requiring immigration for persistence. Understanding source sink structure is crucial for population management because protecting sources is essential for metapopulation viability, while sinks may act as ecological traps, attracting individuals without contributing to population growth. Spatial variation in habitat quality is the fundamental factor structuring source sink dynamics. Differences in resource availability, predation pressure, climate, or other ecological factors create heterogeneous landscapes. Some patches provide conditions supporting high survival and reproduction. Other patches impose high mortality or low reproduction. At steady state, high-quality patches become sources where positive population growth generates emigrants. Low-quality patches become sinks where negative intrinsic growth is offset by immigration. Multiple factors influence the strength of source sink dynamics. Population growth rates determine how rapidly sources generate surpluses and how severely sinks decline without immigration. Differential patch quality affects the magnitude of demographic imbalance between sources and sinks. Patch sizes interact with quality, with large low-quality patches potentially supporting substantial populations despite sink status. Dispersal distances determine connectivity, with short dispersal limiting rescue of distant sinks. Environmental variation affects temporal stability of source and sink status. Assessing source sink status requires separating mortality from permanent emigration. High apparent mortality could reflect true deaths or undetected emigration. Spatially explicit integrated population models combining capture data with movement data allow estimating habitat-specific survival and dispersal probabilities. These models reveal which habitats are demographic sources, contributing more than one individual per capita to the metapopulation, and which are sinks contributing less than one per capita. Management implications of source sink dynamics are substantial. Conservation efforts should prioritize protecting source habitats because metapopulation persistence depends on sources producing emigrants. Sinks may harbor substantial populations but contribute negatively to metapopulation growth. However, sinks can buffer temporal variation by absorbing surplus production during favorable years. Spatial planning must account for connectivity because isolated sources cannot rescue distant sinks. Habitat restoration should focus on increasing source productivity or converting sinks to sources through quality improvement. Evolutionary arms races. Evolutionary arms races occur when reciprocal selection between interacting species drives escalating adaptations in antagonistic traits. Predators evolve improved hunting abilities, while prey evolve improved defenses. Parasites evolve mechanisms to exploit hosts, while hosts evolve resistance. These coevolutionary dynamics can produce elaborate adaptations as each species responds to evolutionary changes in the other, creating red queen dynamics where species must continually evolve to maintain fitness. Plant-herbivore interactions exemplify arms race dynamics. Plants that evolve chemical defenses, repelling or poisoning herbivores gain fitness advantages. This defense spread creates selection pressure on herbivore populations. Herbivores that evolve tolerance or detoxification abilities overcome plant defenses, gaining access to protected resources. This herbivore adaptation creates renewed selection on plants for stronger or novel chemical defenses. The cycle continues with plants and herbivores trading evolutionary innovations in offense and defense. The Red Queen hypothesis proposes that coevolution with parasites maintains sexual reproduction despite its costs. Asexual reproduction is more efficient, producing twice as many offspring per capita as sexual reproduction. However, asexual lineages are genetically uniform, allowing parasites to specialize on common genotypes. Sexual reproduction continually generates novel genotype combinations, reducing parasite success. This parasite-mediated selection, maintaining sex, requires perpetual coevolution, preventing parasites from catching up. Not all coevolution produces endless escalation. Evolutionary trade-offs can stabilize arms races. Parasites face trade-offs between transmission and virulence because killing hosts too quickly prevents transmission to new hosts. This trade-off selects for intermediate virulence, maximizing lifetime transmission. Host-parasite systems may evolve towards stable coexistence rather than perpetual escalation if costs of resistance and virulence are high. Genetic constraints limit arms race escalation. Lack of genetic variation in key traits prevents evolutionary responses despite strong selection. Genetic correlations create trade-offs where improving one trait degrades others. Developmental constraints channel variation, limiting accessible phenotypes. These constraints may halt arms races at equilibria where neither species can improve further given existing genetic variation and constraints. Understanding when arms races escalate versus stabilize requires examining both selection pressures and genetic architecture. Honest signaling and costly displays. Animal communication often involves conflicts of interest where senders benefit from manipulating receiver behavior in ways reducing receiver fitness. Males signaling quality to females benefit from exaggerating if females mate with higher quality males. This creates selection for dishonest signaling. Yet many signals appear honest, with low-quality individuals producing less elaborate signals than high-quality individuals. Costly signaling theory explains honesty by proposing that signal costs prevent cheating. The handicap principle states that for signals to be honest, they must be costly and differentially costly, such that low-quality individuals cannot afford elaborate signals. The peacock's tail exemplifies this principle. Growing and maintaining elaborate tails requires substantial resources and imposes predation and locomotion costs. High-quality males withstand these costs better than low-quality males because they have greater resource acquisition ability or physiological robustness. Low-quality males producing large tails suffer greater proportional fitness costs, preventing them from dishonestly signaling. Multiple types of costs can maintain signal honesty. Production costs involve resources and energy required to produce signals, including pigment synthesis or ornament growth. Maintenance costs involve ongoing expenditures sustaining signals. Social costs arise from receiver aggression toward signalers or increased conspicuousness to predators. Physiological costs result from signals interfering with other functions or requiring physiological trade-offs. For honesty, these costs must scale such that marginal costs increase more steeply for low-quality signalers. Empirical tests of costly signaling examine whether signal elaboration predicts male quality and whether costs differentially affect individuals of varying quality. Experimental manipulations increasing signal costs should reduce signaling more in low quality than high quality individuals if differential costs maintain honesty. Testosterone implants increasing plumage brightness impose greater survival costs on males in poor condition, supporting differential cost predictions. However, not all ornaments show predicted patterns, suggesting multiple mechanisms maintain honesty. Alternative mechanisms beyond cost-based handicaps may maintain signal honesty. Receiver retaliation punishes dishonest signalers, creating social costs discouraging cheating. Indices are signals physically constrained to reflect quality, making dishonesty impossible. Large body size cannot be faked because size directly reflects growth and condition. Condition-dependent signals reliably indicate quality if signal production depends on physiological condition that itself depends on quality. Understanding which mechanisms operate in specific systems requires detailed studies of costs, constraints, and receiver. Chapter 64: Speciation and Viability. Divergent selection promotes reproductive isolation, while multiple threats interact to determine extinction risk in changing environments. Ecological speciation occurs when reproductive isolation evolves as a byproduct of divergent selection in different environments. Carrying capacity limits population growth through density-dependent processes captured by logistic growth models. Extinction risk increases through synergistic interactions among multiple threats, including habitat loss, climate change, and small population size. Morphological evolution involves changes in regulatory genes, including Hox genes, that specify body plan organization. Genetic load accumulates in small populations through drift-overwhelming selection against deleterious mutations, potentially causing mutational meltdown. These processes demonstrate that speciation can occur rapidly when divergent selection is strong, while extinction risk depends on complex interactions among threats. Understanding these dynamics is essential for predicting evolutionary responses and extinction probabilities under environmental. Ecological speciation. Ecological speciation describes the evolution of reproductive isolation as a consequence of divergent natural selection between environments. When populations occupy different environments imposing different selective pressures, adaptation to local conditions causes phenotypic and genetic divergence. If divergence affects traits involved in mate recognition, habitat preference, or breeding phenology, reproductive isolation emerges as a byproduct. This contrasts with genetic drift-driven speciation, where isolation evolves without divergent selection. Meta-analysis of 34 experimental speciation studies spanning arthropods, yeast, and vertebrates reveals that divergent selection promotes reproductive isolation. Populations subjected to different selection regimes evolved significantly stronger reproductive isolation compared to populations evolving in similar environments. This pattern is consistent across diverse taxa and selection types, providing broad support for ecological speciation theory. Divergent selection explained approximately 20% of variation in reproductive isolation strength. Both phenotypic plasticity and genetic divergence contribute to reproductive isolation during early speciation. Plasticity allows rapid phenotypic responses to environmental differences, potentially creating behavioral or habitat use differences that reduce gene flow. Populations with greater phenotypic plasticity showed faster evolution of reproductive isolation. Genetic changes accumulate as populations adapt, fixing alleles conferring local adaptation. The combination of plasticity enabling immediate divergence and genetic change, causing heritable divergence, accelerates speciation. Premating isolation barriers evolve more rapidly than post-mating barriers during ecological speciation. Premating barriers, including behavioral isolation, temporal isolation, and habitat isolation, prevent mating between divergent populations. Post-mating barriers, including hybrid inviability or sterility, reduce fitness of hybrids that do form. The earlier evolution of pre-mating barriers suggests that divergent selection acts most strongly on traits affecting mate choice and reproductive timing, consistent with ecological speciation predictions. Multifarious selection, acting on multiple environmental axes, simultaneously may accelerate speciation. Selection on single environmental dimensions can promote reproductive isolation, but selection on multiple dimensions, including temperature, resource availability, predation, and parasitism, may drive faster divergence. However, empirical evidence for accelerated speciation under multifarious selection remains limited. Future experimental studies manipulating multiple selection axes are needed to test whether multidimensional divergence accelerates reproductive isolation beyond single-dimension effects. Carrying capacity and population regulation. Carrying capacity represents the maximum population size that an environment can sustain indefinitely given available resources. Population growth slows as density approaches carrying capacity due to intensifying competition for limiting resources. The logistic growth model captures this density dependence mathematically, providing a foundation for understanding population regulation and predicting dynamics under changing environmental conditions. The logistic equation modifies exponential growth by incorporating carrying capacity as a limiting factor. The growth rate equals the intrinsic rate of increase multiplied by the fraction of carrying capacity remaining unutilized. Mathematically, the per capita growth rate equals R times the quantity K minus N divided by K, where R is the intrinsic growth rate, K is carrying capacity, and n is current population size. This formulation makes growth rate decline linearly with population size. When population size is small relative to carrying capacity, the term k minus n divided by k approaches 1, producing nearly exponential growth. As population size increases, k minus n divided by k decreases, slowing growth. When population equals carrying capacity, k minus n equals 0, halting growth. If population exceeds carrying capacity through immigration or environmental change reducing k, the term becomes negative, producing population decline. This negative feedback stabilizes populations near carrying capacity. Carrying capacity depends on multiple environmental factors, including food availability, water, shelter, and space. In aquatic systems, dissolved oxygen and nutrient concentrations often limit carrying capacity. In terrestrial systems, territory availability or nest site availability may limit populations of territorial species. Carrying capacity is not constant, but varies seasonally and annually with environmental conditions. Climate change, habitat modification, and resource management alter carrying capacity, causing population tracking of changing K values. The concept of carrying capacity has important conservation applications. Threatened populations may be limited by low carrying capacity rather than demographics. Habitat restoration can increase K, allowing population growth without additional demographic interventions. Conversely, populations near carrying capacity cannot grow further without increasing K through habitat improvement. Understanding whether populations are below or at carrying capacity guides management priorities between addressing demographics versus habitat quality. Synergistic extinction risks. Species face multiple simultaneous threats that interact to determine overall extinction risk. Habitat loss, climate change, invasive species, pollution, and overexploitation rarely act in isolation. Instead, threats combine synergistically where total extinction risk exceeds the sum of individual threat effects. Understanding these interactions is essential for predicting extinctions and designing effective conservation strategies addressing multiple threats simultaneously. Climate change interacts with habitat fragmentation to elevate extinction risk beyond either threat alone. As climates shift, species must track suitable conditions by dispersing to new areas. Habitat fragmentation creates barriers preventing dispersal, trapping populations in areas becoming climatically unsuitable. The interaction produces higher extinction risk than climate change in unfragmented landscapes or habitat loss without climate change. Species with limited dispersal abilities face especially high risk from this threat combination. Multiple small threats can cumulatively produce substantial extinction risk. 10 individual threats, each posing 1% extinction risk, combine to produce approximately 9.7% total extinction risk. This multiplicative effect means that addressing only the largest single threat may not substantially reduce total risk if many smaller threats remain. Species facing numerous modest threats may have higher extinction probability than species facing one severe threat. This underscores the importance of comprehensive conservation, addressing all threats rather than just the most obvious. Habitat fragmentation dramatically increases extinction risk beyond simple habitat loss. When contiguous habitat is divided into multiple isolated fragments, each fragment supports a small population with elevated extinction risk. The combined extinction risk across all fragments greatly exceeds the risk for an equivalent population in unfragmented habitat. This occurs because small isolated populations suffer from demographic stochasticity, inbreeding, and limited rescue from immigration. Maintaining connectivity between fragments substantially reduces this synergistic effect. Predicting extinction risk under climate change requires integrating spatial and demographic processes. Population models capture demographic dynamics, including reproduction and mortality. Habitat models project how suitable habitat shifts spatially with climate change. Integrating these approaches allows assessing whether populations can persist through in situ adaptation versus requiring range shifts, and whether dispersal abilities and landscape permeability hermit tracking shifting climates. Complex interactions between life history, disturbance regime, and distribution pattern mediate whether species face increased extinction risk. Regulatory, evolution, and body plans. Morphological evolution often results from changes in gene regulation rather than protein coding sequences. Mutations affecting when, where, or how much genes are expressed can produce substantial phenotypic changes without altering protein functions. Regulatory evolution is especially important for body plan evolution because developmental gene regulatory networks control the formation of major morphological features. Understanding how regulatory changes produce morphological innovation illuminates mechanisms underlying evolutionary transitions. Hox genes encode transcription factors that pattern the body axis by specifying regional identities. These genes are expressed in overlapping domains along the anterior-posterior axis, with each Hox gene conferring specific segmental identities. Changes in Hox expression patterns can transform segment identities, producing morphological evolution. However, Hox genes themselves are highly conserved across animals. Body plan evolution primarily involves changes in Hox expression regulation rather than changes in Hox protein sequences. Snake body evolution involved regulatory changes allowing ribs to form throughout the trunk. Vertebrates typically restrict rib development to thoracic vertebrae, with lumbar vertebrae lacking ribs due to HOX10 expression suppressing rib formation. Snakes evolved extremely long rib cages extending from neck to tail. This required overcoming HOX10 suppression of ribs in posterior segments. A cis-regulatory polymorphism in the MIF5 gene enables differential interaction with HOX proteins, permitting rib development despite HOX10 expression. The MIF5 enhancer in snakes contains polymorphisms affecting HOX protein binding. Different HOX proteins bind the same regulatory site, but through different mechanisms producing opposite outcomes. In typical vertebrates, HOX10 binding suppresses MIF5 expression and rib development. In snakes, regulatory sequence changes allow different HOX proteins to bind productively, maintaining MIF5 expression and rib development even in HOX10 expressing segments. This cis-regulatory change enabled the elongated rib cage characteristic of snake body plans. Developmental gene regulatory networks constitute deeper control elements underlying body plan organization. While HOX genes are important for regional specification within established body plans, the initial body plan architecture is determined by regulatory networks acting earlier in development. These networks involve numerous transcription factors, signaling pathways, and regulatory elements interacting in complex hierarchies. Understanding major morphological transitions requires examining how entire regulatory networks evolve, not just individual genes like HOX. Genetic load and mutational meltdown. Genetic load refers to the reduction in mean population fitness due to deleterious mutations. All populations carry deleterious alleles at numerous loci, creating a mutation load that reduces average fitness below the theoretical maximum if all individuals had optimal genotypes. In large populations, selection efficiently removes deleterious mutations, maintaining relatively low loads. In small populations, genetic drift overwhelms weak selection, allowing deleterious mutations to accumulate, potentially driving populations toward extinction through mutational meltdown. Small populations accumulate deleterious mutations because drift is more powerful than selection when population size is small. The effectiveness of selection depends on the product of effective population size and selection coefficient. When this product is much less than 1, drift dominates, and even deleterious mutations can fix by chance. As mutations accumulate, mean fitness declines. Declining fitness reduces population size further. Smaller population size makes drift even stronger, accelerating mutation accumulation. This positive feedback creates a mutational meltdown driving populations toward extinction. The relationship between population size and mutation load creates complex dynamics. As mutation load increases, populations shrink due to reduced reproduction and increased mortality. Smaller populations experience stronger drift, making future mutations easier to fix. The interaction between demographic effects of load and genetic effects of drift can create tipping points. Above critical population sizes, selection prevents excessive load accumulation. Below critical sizes, populations spiral toward extinction as load accumulates faster than it can be purged. Inbreeding exacerbates genetic load effects by exposing recessive deleterious alleles. In outcrossing populations, recessive deleterious alleles are mostly found in heterozygotes where they are masked by functional dominant alleles. Inbreeding increases homozygosity, exposing recessive alleles and causing inbreeding depression. The combination of drift, load accumulating new mutations, and inbreeding depression, unmasking existing mutations, creates severe fitness declines in small inbred populations. These populations face elevated extinction risk from genetic factors alone. Conservation implications of genetic load are substantial. Small endangered populations may face genetic extinction threats beyond demographic and environmental threats. Genetic rescue through immigration of unrelated individuals can alleviate inbreeding depression and introduce genetic variation, enabling purging of load. However, if populations remain small, genetic load will accumulate again over time. Maintaining sufficiently large effective population sizes prevents genetic load accumulation, requiring conservation strategies ensuring demographic targets account for genetic as well as ecological considerations. Chapter 65: The Past, Present, and Future of Evolution. Evolution continues shaping life across all scales, from molecules to ecosystems, with our understanding expanding beyond the modern synthesis, while applications transform medicine, agriculture, and conservation. The modern synthesis of the early 20th century integrated Darwin's natural selection with Mendelian genetics and population thinking, establishing the conceptual framework that guided evolutionary biology for decades. The extended evolutionary synthesis incorporates developmental biology, epigenetics, and niche construction, expanding explanatory scope beyond gene-centered perspectives. Evolutionary medicine applies evolutionary principles to understanding disease, including antibiotic resistance and cancer evolution. CRISPR and genetic engineering technologies enable precise genome editing with profound implications for human evolution and agricultural improvement. The Anthropocene epoch represents unprecedented human influence on evolutionary trajectories globally. Astrobiology explores whether evolution represents a universal process operating on other worlds through convergent pathways. Conservation genetics guides management of endangered species through breeding programs, maintaining genetic diversity. The fossil record provides deep-time perspectives on biodiversity patterns and extinction dynamics, informing current conservation priorities. These developments demonstrate that evolutionary biology is a dynamic and expanding field, with critical applications addressing contemporary challenges. The modern synthesis and its legacy. The modern synthesis emerged in the early 20th century by integrating Darwin's theory of evolution through natural selection with Mendelian genetics and mathematical population genetics. Before the synthesis, evolution and genetics appeared incompatible. Darwin lacked a mechanism explaining how traits were inherited and how variation was maintained. Mendelian genetics provided particulate inheritance through discrete factors, but early Mendelians thought mutation alone drove evolution without selection. The synthesis reconciled these views, showing that Mendelian genetics provides the mechanism for Darwinian evolution. Key architects of the modern synthesis included Theodosius Dobzhansky, Ernst Mayr, George Gaylord Simpson, and George Ledyard Stebbins. These scientists integrated genetics, systematics, paleontology, and botany into a unified evolutionary framework. Dobzhansky's Genetics and the Origin of Species demonstrated that genetic variation within populations provides raw material for evolution. Mayr emphasized reproductive isolation, and biological species concepts. Simpson connected paleontological patterns to population genetic processes. Stebbins extended synthesis principles to plant evolution. The modern synthesis emphasized several core principles. Natural selection is the predominant mechanism of evolutionary change, with even slight selective advantages becoming important when sustained over time. The object of selection is the phenotype in its environmental context, but genetic variation underlying phenotypes determines evolutionary responses. Population thinking recognizes that genetic diversity within populations is fundamental to evolution. The strength of natural selection in nature exceeds earlier expectations. Ecological factors, including niche occupation and barriers to gene flow, profoundly influence evolutionary dynamics. The synthesis successfully unified microevolution and macroevolution, showing that large-scale patterns arise from small-scale processes. Population genetic changes accumulating over time produce speciation and morphological divergence observed in the fossil record. No special macroevolutionary mechanisms are required beyond those operating within populations. This reductionist perspective powerfully explained diverse evolutionary phenomena through common principles, establishing evolutionary biology as a mature quantitative science. Despite its success, the modern synthesis has been criticized for emphasizing gene-centered views while downplaying developmental processes, organismal agency, and non-genetic inheritance. These critiques motivated the extended evolutionary synthesis, which incorporates phenomena including developmental bias, phenotypic plasticity, niche construction, and epigenetic inheritance. However, debate continues regarding whether these additions constitute fundamental expansions or refinements within existing frameworks. The extended evolutionary synthesis. The extended evolutionary synthesis proposes expanding evolutionary theory by integrating insights from evolutionary developmental biology, epigenetics, and niche construction theory. Proponents argue that the modern synthesis, while successful, provides an incomplete picture by focusing primarily on genetic inheritance and natural selection, while neglecting developmental processes that generate variation and organismal activities that modify selective environments. Developmental bias describes how developmental systems channel variation in non-random directions. Not all phenotypic variants are equally likely to arise because developmental processes constrain possible outcomes. These biases influence evolutionary trajectories by making certain evolutionary transitions more probable than others. For example, the repeated evolution of similar structures across lineages may reflect shared developmental constraints rather than only similar selection pressures. Recognizing developmental bias helps explain evolutionary repeatability and convergence. Phenotypic plasticity, the ability of single genotypes to produce different phenotypes in different environments, plays active roles in evolution. Plasticity can facilitate evolution by allowing populations to persist in novel environments while genetic adaptation proceeds. Genetic accommodation converts initially plastic responses into constitutive traits through selection on regulatory loci. Plasticity-led evolution may accelerate adaptation by providing immediate phenotypic responses that selection then refines genetically. These processes give organisms more active roles in their evolution than purely gene-centered views suggest. Niche construction, the modification of environments by organisms, creates ecological legacies affecting descendant evolution. Organisms are not merely passive recipients of selection from external environments, but actively shape the selective pressures they experience. Earthworms modifying soil structure, beavers creating ponds, and plants altering nutrient cycling all construct niches that feed back to influence their own evolution and that of other species. Integrating niche construction with evo-devo reveals how developmental systems enabling niche construction co-evolve with the constructed niches. Inclusive inheritance recognizes multiple inheritance systems beyond DNA sequences. Epigenetic marks, symbionts, learned behaviors, and culturally transmitted information all contribute to transgenerational transmission of phenotypes. These non-genetic inheritance systems may respond to selection and drive adaptation, expanding the mechanisms through which evolutionary change occurs. The extended synthesis argues that incorporating these diverse inheritance systems provides more complete understanding of evolutionary dynamics. Whether the extended synthesis represents a paradigm shift or incremental refinement remains debated. Critics argue that phenomena emphasized by the extended synthesis can be accommodated within existing population genetic frameworks without requiring fundamental theoretical restructuring. Proponents counter that truly integrating development, plasticity, and niche construction requires reconceptualizing evolution beyond gene-centered perspectives. Regardless of resolution, the extended synthesis has productively stimulated research on previously neglected aspects of evolutionary biology. Evolutionary medicine and cancer. Evolutionary medicine applies evolutionary principles to understanding health and disease, revealing why humans are vulnerable to specific ailments and how pathogens evolve resistance. This perspective recognizes that natural selection shaped human biology for ancestral rather than modern environments, creating mismatches underlying many contemporary diseases. Additionally, infectious agents and cancers evolve within human bodies, requiring evolutionary frameworks to understand and combat them. Antibiotic resistance exemplifies evolution occurring in real time with profound medical consequences. When bacterial populations are exposed to antibiotics, selection favors resistant individuals. These multiply while susceptible bacteria are killed, causing resistance frequency to increase. Horizontal gene transfer spreads resistance genes among bacteria, accelerating resistance evolution. Understanding resistance as an evolutionary process informs strategies to slow its spread, including combination therapies, cycling antibiotics, and reducing unnecessary antibiotic use. Cancer represents an evolutionary process occurring within individual bodies. Normal cells acquire mutations affecting growth regulation. Cells with mutations conferring proliferative advantages undergo clonal expansion. Additional mutations in descendant cells create further advantages, including invasion, metastasis, and therapy resistance. This stepwise accumulation of advantageous mutations mirrors evolutionary adaptation, with tumor progression driven by natural selection among cell lineages within tissues. Genetic heterogeneity within tumors profoundly affects treatment outcomes. Tumors contain diverse cell populations with different mutations. When therapy is applied, it acts as selection pressure. Resistant subclones present at low frequency before treatment expand after treatment eliminates sensitive cells, causing relapse. This evolutionary dynamic explains why initial treatment responses are often followed by resistance. Understanding intratumoral heterogeneity as substrate for evolutionary adaptation suggests strategies targeting heterogeneity or applying adaptive therapy that maintains sensitive cell populations. Darwinian medicine also examines why disease vulnerability exists despite millions of years of selection. Some vulnerabilities reflect evolutionary trade-offs, where genes beneficial in some contexts are harmful in others. Sickle cell anemia results from alleles protecting against malaria despite causing disease when homozygous. Other vulnerabilities arise from rapid environmental change outpacing adaptation. Modern diets rich in processed foods create metabolic diseases because human physiology evolved for different nutritional environments. Recognizing these evolutionary explanations complements proximate medical approaches. Genetic engineering and human-directed evolution. CRISPR-Cas9 genome editing enables precise modification of DNA sequences in living organisms, revolutionizing biology and medicine. The technology derives from bacterial immune systems that use RNA-guided nucleases to cleave foreign DNA. Scientists repurposed this system to target specific genomic locations in any organism, allowing gene knockouts, insertions, or precise sequence changes. CRISPR's simplicity, efficiency, and versatility have democratized genome editing, enabling applications from basic research to agriculture and medicine. In biomedicine, CRISPR allows modeling genetic diseases in animals and cells by introducing disease-causing mutations. This accelerates understanding of disease mechanisms and testing potential therapies. Therapeutic applications include correcting disease-causing mutations in patients' cells, either ex vivo by editing cells outside the body then returning them, or in vivo by delivering editing machinery directly to tissues. Clinical trials are underway for treating genetic disorders, including sickle cell disease, beta thalassemia, and inherited blindness. Agricultural applications of CRISPR enable crop improvement by introducing beneficial traits. Breeders can now directly edit genes controlling yield, nutritional content, stress tolerance, and disease resistance rather than relying on lengthy traditional breeding. This accelerates development of improved varieties and enables introduction of traits difficult to achieve through conventional breeding. Edited crops that lack foreign DNA may face fewer regulatory hurdles than transgenic crops, facilitating deployment. The evolution of agricultural practices illustrates human-directed evolution spanning millennia. Early farmers unknowingly applied artificial selection by saving seeds from best-performing plants and breeding most productive animals. This created dramatic changes including larger grains, higher yields, and docile livestock. Modern breeding programs employ sophisticated quantitative genetics and genomic selection, predicting breeding values from genetic markers. These approaches have increased crop yields substantially, feeding growing human populations. Genomic technologies, including genome-wide association studies, identify genetic variants underlying complex traits. This enables genomic selection where individuals are selected based on predicted genetic merit rather than observed phenotypes. Phenomics platforms enable high-throughput measurement of traits, strengthening selection efficiency. The integration of genomics and phenomics represents precision breeding, dramatically accelerating genetic improvement of crops and livestock while maintaining genetic diversity. Evolution in the Anthropocene. The Anthropocene represents a proposed geological epoch defined by substantial human impacts on Earth's geology and ecosystems. Human activities now rival geological forces in shaping the planet through climate change, habitat transformation, species extinctions, and introduction of novel organisms. These unprecedented changes are driving evolutionary responses across the tree of life, creating what has been termed the bioevolutionary Anthropocene, where human activities fundamentally reshape evolutionary. Climate change caused by greenhouse gas emissions imposes novel selective pressures on species globally. Rising temperatures favor heat-tolerant genotypes while eliminating cold-adapted populations. Changing precipitation patterns select for drought or flood tolerance. Phenology shifts represent evolutionary responses to warming, with flowering, migration, and breeding advancing. These evolutionary changes occur rapidly, with measurable genetic changes detected over decades. However, whether evolution can track the pace of climate change remains uncertain for many species. Biodiversity loss in the Anthropocene rivals mass extinctions in Earth's history. Human activities, including habitat destruction, overexploitation, pollution, and invasive species introductions, drive extinction rates hundreds to thousands of times above background. Current extinction rates match or exceed those during historical mass extinctions. Unlike past extinctions caused by asteroid impacts or volcanism, the Anthropocene extinction is driven by a single species transforming the planet. This fundamentally alters community composition, reduces local diversity, and eliminates unique evolutionary lineages. The bioevolutionary Anthropocene hypothesis proposes that human activities favor organisms capable of rapid adaptation to modified environments. Invasive species, hybrids, genetically modified organisms, and anthropogenically favored species, including crops and livestock, will increasingly dominate, while native species lacking adaptive capacity decline. This predicts homogenization of biotas globally as human-adapted species spread. The hypothesis emphasizes bidirectional interactions where humans drive environmental changes that favor certain organisms, which then reshape ecosystems affecting humans in feedback loops. Novel ecosystems assembled from species never coexisting historically characterize the Anthropocene. Climate change causes species range shifts, bringing together previously allopatric species. Invasions introduce species to new continents. These novel communities experience unique selection pressures, driving evolutionary changes, including character displacement, rapid local adaptation, and evolutionary rescue. Understanding evolution in novel ecosystems requires integrating community ecology with evolutionary genetics to predict outcomes when previously isolated lineages interact. Astrobiology and universal evolution. Astrobiology investigates the possibility of life beyond Earth by integrating astronomy, planetary science, and biology. Central to astrobiological thinking is whether evolution represents a universal process operating wherever life arises or whether life on Earth reflects unique historical contingencies unlikely to repeat elsewhere. The concept of convergent evolution suggests that similar environmental pressures produce similar adaptations, potentially making extraterrestrial life recognizable despite independent origins. Cosmic convergent evolution proposes that natural selection operates as a universal force, producing similarly adapted life forms on planets with comparable environments. On Earth, convergent evolution repeatedly produces similar structures, including eyes, wings, and streamlined bodies in distantly related lineages facing similar selection. If this repeatability extends to extraterrestrial evolution, alien life on planets resembling Earth might exhibit familiar forms. This hypothesis makes SETI and astrobiology efforts more tractable by suggesting biosignatures and technosignatures may follow predictable patterns. The search for biosignatures on other worlds focuses on detecting chemical or physical indicators of life. Atmospheric gases including oxygen, methane, and phosphine in disequilibrium ratios suggest biological production. Surface features including seasonal color changes might indicate photosynthetic organisms. Convergent evolution informs biosignature selection by identifying which signatures are likely universal versus contingent. If photosynthesis is a convergent solution to energy harvesting, then oxygen signatures might indicate life on diverse worlds. Europa, Enceladus, and Mars represent priority targets for detecting extraterrestrial life within our solar system. Europa and Enceladus harbor subsurface oceans beneath ice shells, potentially providing habitats for microbial life. Mars once had liquid water and may retain subsurface aquifers. If life originated independently on these worlds, comparing their biochemistry with Earth life would reveal which features are universal versus contingent. Independent origins would demonstrate that life arises readily given suitable conditions. Advanced extraterrestrial intelligence might be post-biological, having transitioned from biological to technological or artificial forms. If intelligence is subject to convergent evolution, advanced civilizations might follow similar developmental trajectories from biological origins through technological phases to post-biological forms better suited to extreme environments, including interstellar space. This expands SETI considerations beyond biological organisms to artificial intelligences. Whether such transitions are universal or rare depends on unknown factors, including the likelihood of intelligence evolving and technological trajectories post-intelligence. Conservation genetics and species management. Conservation genetics applies population genetics to managing endangered species and maintaining biodiversity. Genetic factors critically affect extinction risk through inbreeding depression, loss of adaptive potential, and accumulation of deleterious mutations. Understanding genetic status guides conservation strategies, including habitat protection, captive breeding, and genetic rescue. Maintaining genetic diversity ensures populations retain evolutionary potential to adapt to changing environments. Effective population size determines genetic drift strength and long-term genetic viability. Small effective populations lose genetic diversity rapidly through drift, fixing alleles randomly regardless of fitness effects. Maintaining Ni above critical thresholds prevents excessive drift and maintains variation, enabling adaptation. For endangered species, estimating Ni from genetic data reveals whether populations are genetically viable or require interventions. Management plans emphasize increasing Ni through habitat restoration, expanding populations, and genetic rescue, introducing unrelated individuals. Captive breeding programs prevent extinction of critically endangered species while maintaining genetic diversity. Programs carefully manage breeding to maximize retention of genetic variation from wild founders. Pedigree analysis tracks relatedness, allowing pairing decisions that minimize inbreeding. Genetic management plans balance short-term goals of population growth against long-term goals of preserving diversity. Successful programs, including California condors and Przeworski's horses, have brought species back from extinction's edge through careful genetic management. Gene flow between populations maintains diversity and reduces inbreeding depression through genetic rescue. Isolated populations suffer from lack of immigration, allowing drift to fix deleterious alleles and inbreeding to expose them. Introducing individuals from other populations provides genetic variation and masks recessive lethals through heterozygosity. Genetic rescue has successfully improved fitness in populations, including Florida panthers and bighorn sheep. However, excessive gene flow from divergent populations risks outbreeding depression, requiring careful evaluation. Conservation priorities benefit from understanding deep-time extinction patterns revealed by fossils. The fossil record documents 5 mass extinctions where over 75% of species disappeared over geologically brief intervals. Comparing historical extinction rates with current rates reveals that the modern biodiversity crisis equals or exceeds mass extinction magnitudes. Species with narrow geographic ranges consistently show elevated extinction risk across deep time, indicating that protecting wide-ranging species and maintaining connectivity reduces extinction probability. The road ahead. Evolutionary biology stands at a remarkable juncture where theoretical advances, technological capabilities, and pressing global challenges converge. The field has expanded far beyond Darwin's original insights while remaining grounded in natural selection's power to shape life. Integration of genomics, developmental biology, and ecology provides unprecedented ability to track evolutionary processes in real time from molecules to ecosystems. These tools reveal that evolution operates faster and more pervasively than earlier scientists imagined. Contemporary challenges demand evolutionary thinking. Climate change forces species to adapt, migrate, or face extinction. Antibiotic resistance threatens modern medicine. Agricultural intensification requires improved crops feeding growing populations while minimizing environmental impacts. Conservation biologists must maintain genetic diversity in fragmented populations. Each challenge has evolutionary dimensions that must be understood and addressed. Evolutionary biology thus transitions from purely academic pursuit to essential framework guiding responses to humanity's most pressing problems. Looking forward, several frontiers promise transformative advances. Integrating evolution with other disciplines, including neuroscience, immunology, and ecology, will yield holistic understanding of life. Applying evolutionary principles to technology, including evolutionary algorithms and directed evolution of proteins, expands evolution's reach beyond biology. Understanding evolution's role in structuring ecosystems and providing services informs conservation and restoration. Discovering whether life exists elsewhere in the universe would illuminate whether evolution is universal or unique to Earth. The science presented across these chapters demonstrates evolution's explanatory power, spanning all biological scales and timeframes. From genetic mutations to mass extinctions, from molecular structures to global biogeographic patterns, evolutionary processes shape the living world. Every organism carries evolutionary history in its genes and anatomy. Every ecosystem reflects coevolutionary interactions accumulated over millions of years. Every biological question ultimately connects to evolution. As we navigate the Anthropocene with its unprecedented challenges and opportunities, understanding evolution becomes more critical than ever. Human activities now drive evolutionary changes across the biosphere. We possess technologies enabling directed evolution of organisms and potentially ourselves. The decisions we make today about how to apply evolutionary knowledge will shape life on Earth for millennia to come. This responsibility demands deep understanding of evolutionary principles, careful consideration of consequences, and commitment to using knowledge wisely. Evolution is not merely history, but ongoing process. It continues in populations around the world, in laboratories experimenting with genetic engineering, in fields breeding improved crops, in hospitals battling resistant pathogens, and in conservation programs preserving endangered species. Every generation inherits the outcomes of past evolution and shapes future evolutionary trajectories through the selection pressures it creates. Understanding this continuity between past, present, and future emphasizes both the wonder of evolution and our responsibility as conscious participants in Earth's evolutionary story. If you found this exploration of evolution fascinating and want to dive deeper into the mechanisms shaping life across our planet and beyond, please hit that like button and subscribe to the channel. Your support helps us continue creating detailed, scientifically accurate content exploring the wonders of science and discovery. Share this video with anyone curious about how life evolves and adapts. Together, we can spread knowledge and appreciation for the incredible processes that created the diversity of life we see around us today. Thank you for watching, and until next time, keep exploring the universe of knowledge.